Geography is the study of the physical features of the Earth, including how humans affect the Earth and are affected by it. Geography deals with physical aspects of the Earth, the composition, the layers of the Earth, the atmosphere, the plants and animals, mountains, rivers, and other landforms. But it also analyzes how humans are affected those physical features, and how the arrangement of those physical features has affected humans. Why do humans settle where they do? How do humans impact the environment? How do the physical landscapes create human conflict? All of these things are covered by geography. Since geography is such a large subject with so many topics, it makes sense to split it into key themes. Today we're going to briefly discuss the 5 main themes of geography. There are 5 main themes of geography: location, place, human-environment interaction, movement, and region. Collectively, these 5 themes encompass the whole of the subject of geography. Location is kind of like the first step in understanding an aspect of the Earth, and involves providing a reference to describe where a particular place is on the Earth. This could be an absolute location, where a location is based on a definitive reference that rarely changes, such as latitude or longitude, or an address. Or it could be a relative location, where a place is described relative to its environment or its connection to other places. Place is a description of the physical and human characteristics of the location being studied. This could involve describing the mountains, valleys, rivers, beaches, and the living organisms that inhabit it. It also includes human features like land use, infrastructure, and communications. Human-environment interaction is the study of how humans affect the environment and how the environment affects humans. Humans can have positive impacts on the environment or negative ones, and we can even disagree about whether an impact is positive or negative. Human geography is a complex and varied topic in itself. Movement involves describing and discussing the effects of anything that moves across the Earth. Very often this is related to humans, movement of humans themselves, goods, services, immigration, and so forth. But migration of animals can also play a part, especially when looking at changes in a landscape over long periods of time. Region is about classifying the parts of the Earth. We humans love to draw borders and put names, labels, and categories on things, even when those borders and labels are mostly made up. Region considers how the land is split up into continents, regions, countries, counties, states, and cities. Geography is the study of the physical features of the Earth, including how humans affect the Earth and are affected by it. Geography deals with the physical aspects of the Earth, the composition, the layers of the Earth, the atmosphere, the plants and animals, the mountains, rivers, and other landforms. But it also analyzes how humans have affected those physical features and how the arrangement of those physical features has affected humans. There are 5 main themes of geography: location, place, human-environment interaction, movement, and region. Collectively, these 5 themes encompass the whole subject of geography. Location is kind of like the first step in understanding an aspect of the Earth, and involves providing a reference to describe where a particular place is on the Earth. Place is a description of the physical and human characteristics of the location being studied. Human-environment interaction is the study of how humans affect the environment and how the environment affects humans. Movement involves describing and discussing the effects of anything that moves across the Earth. And region is about classifying the parts of the world. Region considers how the land is split up into continents, regions, counties, countries, states, and cities. Each of the themes can be both physical and human, and we can talk about the past, present, and future. So geography really is a huge subject with a lot to talk about.
Marie is very interested in people. She's fascinated by how people's environments can affect so much of their lives. From food choices to religion to how long people live, it seems like where a person lives has a huge impact on them. Cultural geography is the study of how places differ and how people interact with the environment. Cultural geography links the social sciences like sociology and psychology with the natural sciences like biology and evolution. The subjects that Marie is interested in, like how the environment affects how long a person might live, are part of cultural geography. Let's look closer at how Marie can study cultural geography, including two common techniques, spatial analysis and systems analysis. Marie is interested in how geography can affect a person's life. For example, she was studying the way disease spreads and is interested in how where a person lives might affect how likely they are to contract a disease. Spatial analysis, which is also called area analysis and locational analysis, is the study of human trends in a specific place. Think of the words space, area, and location, and you can remember spatial analysis, area analysis, and locational analysis. When thinking about a place, many people imagine a map. If I say Texas, you might think of a map of the shape of Texas, for example. Or if I say Nile River, you might imagine what it looks like on a map. Likewise, spatial analysis often includes looking at human trends on a map to see how the geography of a land might influence a trend. For example, this map shows how the bubonic plague spread across Europe. Each color is a different time period. In this way, cultural geographers can see how the disease moved from one location to another across time. Remember that Marie is interested in how disease spreads. She might make a map to show an epidemic that is spreading across her state. When she does, she might notice that the disease is starting at cities along a certain river and then spreading out to the land outside of the cities. Her spatial analysis of the epidemic has allowed her to see a trend in the spread of the disease. Spatial analysis isn't the only thing that Marie can study in cultural geography. She can also look at statistics and trends in order to change the way things are. Analysis meant to solve social problems based on geographic trends is called geographic systems analysis. In systems analysis, as with spatial analysis, Marie will be looking at trends in society across geography. But systems analysis is looking for a way to create or change systems in order to solve a problem, whereas spatial analysis is just looking for trends. Remember that Marie has discovered that an epidemic is sweeping across her state, and that the disease starts in cities that are on a river. In spatial analysis, this is as far as Marie goes. She looks at the information and says, that's interesting. But in systems analysis, Marie asks the question, why is the disease spreading this way, and what can I do to help stop it? Marie knows that the river is used a lot by people to travel from place to place. Because the disease is likely spreading from city to city as people travel from place to place, Marie can warn people not to travel from city to city, but to stay near their homes. This way, the spread of the disease might slow. Systems analysis is often used by insurance companies. Imagine that an insurance company has a lot of people with life insurance policies in Florida. If those people die, the insurance company will have to pay a lot of money to their loved ones. There is a hurricane coming to Florida, and the insurance company is worried that there might be a lot of fatalities in the hurricane. They compare where their policyholders live and see that there are a lot of people in a few central areas. Then, they can look at the projected course of the hurricane. They notice that the hurricane is scheduled to hit two places where there are a lot of policyholders. The insurance company can then alert their customers that they might be in danger and encourage them to temporarily leave to a safer place. The policyholders' lives are saved, and the insurance company saves money. The systems analysis has helped solve both of those problems. Cultural geography is the study of how people and their environment interact. There are many ways to study cultural geography. Spatial analysis, also known as area analysis or locational analysis, looks at human trends in a specific place. This often involves looking at data on a map. Geographic systems analysis takes this one step further by attempting to solve social problems based on data about geographic trends.
The Earth is spherical, or to be more exact, it's a vertically squashed sphere. But humans often like things to be flat, and that can be a problem. If you want to really see what the Earth looks like, you need a globe. Whenever we create a flat map, it isn't really an exact depiction of the surface of the Earth, because the surface of the Earth isn't flat at all. A flat map is a projection. A map projection is a way of representing the surface of a celestial sphere on a flat surface. The problem with a map projection is that they are never entirely accurate. It's impossible to take the peel of an orange and flatten it out without first cutting it apart. So in the same way, you can't unwrap the surface of the Earth and put it on a piece of paper. And this means you have to make choices about what you'll sacrifice to make it flat. Maybe things at the top and bottom of the map will look bigger than they really are. Or maybe it won't be as accurate when measuring distances left to right. Some map projections are useful in some situations, while others are useful in others. Most modern world maps use a projection called the Mercator projection. The drawback of this projection is that things near the poles appear too big, and things near the equator appear too small. So, for example, Greenland and Antarctica aren't really as big as they appear, and Northern Africa and South America are much bigger than they appear. The issues in the different types of map projections are issues of scale. When you look at a map, there is a scale. A scale tells you the ratio of a distance on the map to the actual distance in real life. For example, a scale of 25,000 to 1 tells you that every 1 inch on the map will be 25,000 inches in real life, or every 1 centimeter on the map will be 25,000 centimeters in real life. On a map, a scale looks like this. The problem with a map projection is that the scale is not consistent. 1 centimeter on a map projection is different in different areas of the map, and this is what creates its limitations. Technically, all maps are projections, because the Earth is curved everywhere. But on small scales, like maps of towns or local areas, the scale is so similar across the map that you don't really need to worry about it. Only at larger scales does it produce the huge anomalies we've been talking about. Whenever you design a map, you have an unlimited number of possible projections and scales to use, so there are some important decisions to make. Generally, a map scale and projection are chosen based on how the map will be used. The right tool for the right job. The Earth is spherical, or to be more exact, it's a squash sphere. But we humans often like things to be flat, and that can be a problem. If you want to really see what the Earth looks like, you need a globe. Whenever we create a flat map, it isn't really an exact depiction of the surface of the Earth, because the surface of the Earth isn't flat at all. A flat map is a projection. A map projection is a way of representing the surface of a celestial sphere on a flat surface. The problem with the map projection is that they are never entirely accurate. There are always drawbacks. Most modern maps use a projection called the Mercator projection. The drawback of this projection is that things near the poles appear too big, and things near the equator appear too small. Other map projections have different drawbacks. Maps also have a scale. A scale tells you the ratio of the distance on the map to the actual distance in real life. For example, a scale of 25,000 to 1 tells you that every 1 centimeter on the map will be 25,000 centimeters in real life. The problem with a map projection is that the scale is not consistent everywhere on the map. Though this is only a problem with large-scale maps. Generally, a map scale and projection are chosen based on how the map will be used, using the right tool for the right job. Remote sensing is any method of collecting data about an object or location without making physical contact with it. For example, you can fly a satellite or aircraft over an area and use that to collect data. These days, there are so many satellites in space that it can be an extremely practical way of collecting data. It's also convenient because you can access areas, such as the rainforest for example, that would be extremely hard to get to otherwise. There are two main types of remote sensing. Passive sensing is where information is recorded just from the sunlight bouncing off objects. Active sensing is where the satellite or aircraft actually produces or beams a signal toward the object or land. Active sensing can involve laser beams or other electromagnetic waves. There are many ways that remote sensing can be used. It can help collect a huge variety of data. Passive sensors include cameras for photos, infrared imagery, and radiometers. Active sensors include sonar for underwater positioning and radar, which bounces a signal off objects and sees how long it takes to return, giving information about where an object is, how fast it's moving, and in what direction. In geography, remote sensing can be used for mapping, surveying land use, and measuring deforestation, the movement of glaciers, the depths of oceans, the movement of ocean currents, and the features of clouds. Through remote sensing, geographers can study phenomena in the Earth's lithosphere, biosphere, hydrosphere, and atmosphere, making it one of the most useful tools we have. Making sense of images produced by remote sensing can be hard. Viewing things from above doesn't always come naturally to humans, and when images are taken using things other than visible light, they can look nothing like we would expect. To make it possible to interpret these kinds of images, there are certain characteristics that are used to identify objects in images. Those characteristics are shape, size, image tone or color, pattern, shadow, and texture. For example, let's say you're looking at overhead images of a city in infrared. Maybe you can't tell which building is which just by looking at it, but measuring the size and the shape, you might be able to find a match in the area you're imaging. Remote sensing is any method of collecting data about an object or location without making physical contact with it. For example, you can fly a satellite or aircraft over an area and use that to collect data. There are two main types of remote sensing, active and passive. Passive sensing is where information is recorded just from the sunlight bouncing off objects. Active sensing is where the satellite or aircraft actually produces or beams a signal towards the object or land. Active sensing can involve laser beams or other electromagnetic waves. Passive sensors include cameras for photos, infrared imagery, and radiometers. Active sensors can include sonar for underwater positioning and radar, which bounces a signal off of objects and sees how long it takes to return, giving information about where an object is, how fast it's moving, and in what direction. In geography, remote sensing can be used for mapping, surveying land use, and measuring deforestation, the movement of glaciers, the depths of oceans, the movement of ocean currents, and features of clouds. Through remote sensing, geographers can study phenomena in the Earth's lithosphere, biosphere, hydrosphere, and atmosphere, making it one of the most useful tools we have. Making sense of images produced by remote sensing can be hard. To help with this, geographers look at characteristics like shape, size, image tone or color, pattern, shadow, and texture. An orbit is a curved path of a celestial object around another celestial object due to the force of gravity. Orbits are everywhere in our universe. The Moon orbits the Earth, and the Earth orbits the Sun, and the Sun orbits around the center of the galaxy. Put simply, an orbit happens because gravity is pulling the object towards the thing it's orbiting, but the object is also moving sideways. If that sideways motion is fast enough, it will stay at the same distance away, despite gravity trying to pull it down. There are many ways that an object can orbit another. It can orbit at different heights, at a constant speed or a varying speed, and an orbit can be circular or elliptical. There are particular orbits that are most commonly used because they serve useful functions. The two most common ones are geosynchronous orbits and sun-synchronous orbits. A geosynchronous orbit is an orbit around the Earth where the object orbits once per day. A common kind of geosynchronous orbit is called a geostationary orbit, where the object orbits above the same part of the Earth at all times. This is an extremely useful type of orbit, and is used for anything where a satellite needs to send and receive signals from the same part of the Earth all the time. It's used for cell phone satellites, television satellites, weather satellites, as well as some military satellites. A sun-synchronous orbit is an orbit around the Earth where the movement of the satellite always looks the same when viewed from the Sun. A satellite in a sun-synchronous orbit still orbits the Earth, but does so in a way that over the course of the day, its distance to the Sun will change in a consistent pattern no matter the time of year. Here's what a sun-synchronous orbit looks like at different times of year. Notice that its position relative to the Sun varies across each orbit of the Earth, but the way that the orbit appears from the point of view of the Sun is the same no matter where the Earth is in its yearly orbit. This kind of orbit also has many applications. The big advantage of sun-synchronous orbits is that the Earth will be illuminated in a similar way year-round. For this reason, it's often used for weather and spy satellites, since they create images of the Earth. They're also used in ocean or atmospheric remote sensing satellites, since they require sunlight to take their data. There are many types of orbits we haven't mentioned, including polar orbits, polar sun-synchronous orbits, super-synchronous orbits, and others, but most satellites we have orbiting the Earth are either geosynchronous or sun-synchronous. They continue to be incredibly useful for a whole host of human activities. An orbit is a curved path of a celestial object around another celestial object due to the force of gravity. Orbits are everywhere in the universe. Put simply, an orbit happens because gravity is pulling the object towards the thing it's orbiting, but the object is also moving sideways. If that sideways motion is fast enough, it will stay at the same distance away despite gravity trying to pull it down. There are many ways that an object can orbit another. It can orbit at different heights, at a constant or varying speed, and an orbit can be circular or elliptical. The two most common types of orbit are geosynchronous orbits and sun-synchronous orbits. A geosynchronous orbit is an orbit around the Earth where the object orbits once per day. A common kind of geosynchronous orbit is called a geostationary orbit, where the object orbits above the same part of the Earth at all times. It's used for communication satellites, television satellites, weather satellites, as well as some uses for defense and intelligence. A sun-synchronous orbit is an orbit around the Earth where the movement of the satellite always looks the same when viewed from the Sun. The big advantage of sun-synchronous orbits is that the Earth will be illuminated in a similar way year-round. For this reason, it's often used for weather and spy satellites, since they create images of the Earth.
If you have ever been to Hawaii, you may have had the opportunity to snorkel. People are attracted to this activity because it gives you a small glimpse of the interesting features of the Earth that we often miss out on by living above water. Identifying these features both underwater and on land can give us some clues as to how the lithosphere, or the Earth's crust, changes. Hawaii is a great place to observe these changes because, unlike many places, they all can occur there. Just like snorkeling gives us a glimpse of what happens under the waves, volcanoes and earthquakes can give us glimpses of what is happening under the lithosphere inside the Earth. Volcanoes and earthquakes are natural disasters that can radically transform the landscape of the Earth in just a few moments. This, along with the ongoing breakdown of the surface of the Earth by weather, produces profound changes over time over the world. Earthquakes occur when stress builds up in the Earth's crust and causes it to break in a line known as a fault. A fault is a crack in the Earth's crust caused by stress in the surrounding rocks. Stress builds up in the crust for several reasons. Most commonly, pieces of the Earth push and grind past each other, and stress builds up as the pieces get stuck on each other. Rocks store energy when the pressure changes as new sediment is deposited in layers on the Earth's crust. The Earth's surface also may store energy because of contraction and expansion as the crust heats and cools. As the stress builds, eventually the rock reaches its breaking point. When it fractures, energy is released in waves over the crust's surface and down into the Earth. These waves are what cause the shaking of the ground, much like the waves felt on a waterbed. Earthquakes show us how the surface of the Earth is moving. But did you know that measuring earthquake waves can give us information about the interior of the Earth? Seismologists, scientists who study earthquakes and related phenomenon, have discovered a way to use earthquake waves to deduce the structure of the Earth's interior. Geologists cannot directly study anything more than the outermost 5 to 8 miles of the crust, leaving a vast majority of the Earth unobserved. However, they have found that after an earthquake, waves of energy travel not only through the rocks of the Earth's surface, but also through the center of the Earth. The waves that pass through the Earth travel at different speeds depending on the rock type, its temperature, and its pressure. Following an earthquake, scientists at stations all around the Earth record the time and intensity of the waves that arrive at their location. Using information about the arrival and behavior of the waves, scientists can deduce a picture of the different layers of the Earth's interior. This is how scientists have developed a 5-layer model of the Earth consisting of a solid inner core, a liquid outer core, a liquid mantle, a taffy-like upper layer, all underneath the outer crust. Tidal waves, or tsunamis, as shown in this animation, are also the result of earthquakes, and they can affect land, including the islands of Hawaii. Tsunamis can form in a couple of ways. One, an earthquake could trigger a massive landslide near a body of water. This landslide entering the water could trigger a large wave similar to the waves made when someone jumps in the pool. The mass of the material entering the water triggers the wave. Underwater landslides or volcanic eruptions can also cause tsunamis. Tsunamis can also be created by earthquakes that happen underwater. Fault lines exist under the ocean just like on land. Sometimes earthquakes cause one of the plates to move violently upwards. This also causes all the water above that fault line to push up, triggering the start of a tsunami. You might think that it seems unlikely that this can cause a gigantic wave, but imagine a 100-mile-long piece of crust being suddenly forced up 10 feet. The amount of water displaced by this event is easily enough to begin the wave. Out in the open ocean, the tsunami may not look like much, usually having a long, low crest, but these waves can move quite fast, up to 500 miles per hour. As the wave reaches the shoreline, it begins to slow down and pile up on itself. Initially, the shoreline water of the ocean may recede from the shore as it gets pulled into the wave itself. Tsunamis also may occur in several ways, increasing the danger of the event. Tsunamis have so much energy that they push up on land like a bulldozer, causing massive destruction. Volcanoes are formed one of 3 ways. First, magma can ooze out of the ground when the lithosphere pulls apart. These are often non-explosive volcanoes that form where 2 pieces of the earth are pulling apart. Second, volcanoes can erupt explosively, usually the result of a piece of the Earth's crust being forced back into the mantle. The piece of crust remelts and moves to the surface to cause the eruption. The third way a volcano can be formed is called a hot spot. Deep inside the Earth, hot magma moves toward the surface of the Earth the way bubbles move in a pot of boiling water. These isolated columns of magma are known as mantle plumes, and when they reach the crust of the Earth, they break through in one spot, forming an area of volcanism. Yellowstone National Park and the Hawaiian Islands are hot spots, examples of volcanic activity caused by these rising mantle plumes. This activity can be seen in Yellowstone's hot springs, geysers, and leftover volcanic deposits. Over long periods of time, the hot spots are relatively stationary, so as the plates move over it, chains of islands can be produced. Hawaii is a prime example of this. The Hawaiian Islands were created one at a time over long periods. The furthest northwest island is the oldest, and the Big Island of Hawaii is directly over the hot spot. The Big Island is the site of Kilauea, where most of the volcanic activity is found. Off the Big Island's southeast coast, a new island is forming deep underwater, but it will be a long time before the new island of Loihi breaks the surface. Studying the types of lava that come out of volcanoes also gives scientists some clues about the Earth's interior. On the surface of Hawaii, 2 other processes are really evident. These processes are known as weathering and deposition. Weathering is the wearing away of rock by wind, water, or any other natural agent. This could include repeated heating by the sun or cracking of rocks by water that expands when frozen. This can be seen in this image, which shows drainage channels on either side of the main valley. These are formed from water running off from heavy rainfall. Deposition is where sediment and other broken down parts of rocks accumulate to create landforms. Weathering and deposition are opposites of each other and are part of a process that changes the Earth's landscape due to climatic factors. Evidence of weathering can be seen in these pictures. As the volcanic rocks of Hawaii are eroded and washed into the ocean, they often get deposited on the beaches by waves. This is what causes the famous black sand beaches found there. There are many processes and events that shape the Earth's surface and also give us clues about the Earth. Earthquakes show us the power that can be released through pieces of the Earth's crust moving, which create faults, cracks in the Earth's crust that show movement. Scientists can monitor the arrival of earthquake waves at different points on the Earth, allowing them to build a model of the Earth's interior and deduce how earthquakes are caused. Tsunamis are rapidly moving, destructive tidal waves that are most commonly caused by underwater earthquakes. The water piles up as it reaches the shore and acts like a flash flood, causing massive destruction. Oftentimes, volcanoes are the result of pieces of the Earth's crust moving around, but hotspots, formed by mantle plumes in the Earth's interior, push through the crust, creating a volcanic zone. The lava and detritus that volcanoes emit during an eruption give us a glimpse of the interior of the Earth. The surface processes that change the Earth include weathering, the wearing away of rock by natural processes, erosion, the movement of broken down rock, and deposition, where the pieces of broken rock end up being placed.
Earth is a very complex place. Although it looks like one large structure, it's actually got a lot going on that you may not see if you don't look closely. All of the processes on Earth are driven by 4 spheres, which we describe individually, but are really all connected. The names of each of these spheres come from Greek words that describe what they're made of: geo for ground, hydro for water, bio for life, and atmo for air. Let's look at each of the 4 spheres in a bit more detail to gain a better understanding of how they help make up the Earth. Since geo means ground, the geosphere describes all of the rocks, minerals, and ground that are found on and in Earth. This includes all of the mountains on the surface, as well as all of the liquid rock in the mantle below us, and the minerals and metals of the outer and inner cores. The continents, the ocean floor, and all of the rocks on the surface, and all of the sand in the deserts are all considered part of the geosphere. Basically, if it looks like solid ground, it's part of the ground sphere. Knowing that hydro means water, you may have guessed that the hydrosphere is made up of all the water on Earth. This includes all of the rivers, lakes, streams, oceans, groundwater, polar ice caps, glaciers, and moisture in the air like rain and snow. The hydrosphere is found on the surface of Earth, but also extends down several miles below, as well as several miles up into the atmosphere. Most of Earth's water is salty and in the oceans, about 97%. 2/3 of the remaining 3% is frozen in glaciers and polar ice caps. Only 1% of the hydrosphere is liquid freshwater, and even most of this exists as groundwater down in the soil. With the prefix life, this means that Earth's biosphere is composed of all of the living organisms on the planet. This includes all of the plants, animals, bacteria, fungi, and single-celled organisms found on Earth. Most of this life exists no deeper than about 10 feet into the ground or about 600 feet above it. Because each individual is so small in relation to the overall planet, organisms are often grouped into biomes, which are regional communities characterized by vegetation and climate. You are likely already familiar with some of these, like deserts, grasslands, and rainforests. The final sphere is one you've probably already heard of. This is the atmosphere, which is the air that surrounds Earth. This air sphere is made up of mostly nitrogen, some oxygen, and small amounts of many other molecules. Most of the atmosphere is densely packed near the surface, which is where all of our weather occurs, but it extends to over 300 miles above ground. However, exactly where it ends and space begins is difficult to say. The atmosphere acts like a giant blanket, protecting us from harmful UV radiation and keeping our planet warm. Earth is one large planet, but it can be divided into 4 main spheres, which get their names from Greek words. The geosphere is all of the rock, land, and minerals on Earth, and you can remember this because geo means ground. The hydrosphere is all of the water on Earth, which makes sense since hydro means water. Bio means life, so all of the living organisms on Earth make up the biosphere. And finally, the atmosphere above us is all of the air surrounding Earth because atmo means air. While these spheres are described individually, they often occur in the same location and interact to drive Earth's processes. In another lesson, we learned about Earth's 4 spheres. These are the geosphere, hydrosphere, biosphere, and atmosphere. Together, they make up all of the components of our planet, both living and non-living. And while we can describe each individually in terms of its properties and features, you'd have a difficult time finding an example where one sphere doesn't either touch or interact with at least one other. This is important because these interactions are what drive Earth's processes. Material on Earth doesn't stay how it is, it gets recycled into other phases and forms. Plants in the ground die, and as they're broken down by microorganisms, they become soil, which can then feed new plants. Water cycles through different phases and locations, like when it evaporates from the oceans and then rains down onto the ground or into a lake. Rock also gets recycled under Earth's surface, where it is melted down and then sent back up in volcanic eruptions. So now that you know why this is important, let's look at some examples of how these interactions occur between the four spheres of Earth. Pretty much any event on Earth is going to involve more than one sphere. Let's look at a fairly simple example to begin with, volcanoes. Volcano eruptions are events in the geosphere because this is both rock being pushed out from under the surface as well as a change in the surface land itself. Volcanoes also spew a lot of gas and particulate matter into the atmosphere as well as send hot lava flowing down mountainsides, disrupting the biosphere. Water will condense around that particulate matter in the atmosphere, so now we've involved the hydrosphere as well. You can see how this simple example quickly got quite complicated. Let's look at another event to see how the spheres interact. Humans use a variety of natural resources to generate power, such as plant material, oil, natural gas, wind, water, and sunlight. You can see right away that we've involved all of the spheres already, even before we started talking about how we harness these resources. We use corn for ethanol, the biosphere, oil and natural gas for heating homes and fueling cars, the geosphere, and the wind, the atmosphere, and water, the hydrosphere, for electricity. Now let's look at an example that's a bit trickier, clouds. Clouds form when water droplets condense around dust particles in the air. But wait, does this mean that clouds are part of the hydrosphere because they're water, or does it mean that they belong to the atmosphere because they're in the air? And what about groundwater? Is this part of the geosphere because it's in the ground, or considered part of the hydrosphere because it's still water no matter where it's found? Or is this part of the biosphere because the soil is also filled with living things of all shapes and sizes? The biosphere is a major contributor to the recycling of other material and earth through different spheres. Take plants, for example. They drink liquid water from the ground and breathe it back into the atmosphere as a gas. They also eat minerals from the soil and turn them into biological material. And in the geosphere, their roots help keep the ground in place, protecting it from wind and rain. As you can see, it's really difficult to tease apart where one sphere ends and another begins. Oceans are filled with water, the hydrosphere, and living organisms, the biosphere, but they also touch the sky, the atmosphere, and the ground deep below, the geosphere. Can you see how this makes each sphere important not only to each other, but to Earth as a whole? Earth depends on these interactions, and the balances among these interactions are what allow life to exist on our unique planet. Earth has four spheres called the geosphere, hydrosphere, biosphere, and atmosphere. These spheres each have unique properties and features, but they are not isolated on Earth, and they work together to drive the processes of the planet. Not only do each of the spheres constantly interact with the others, but it can often be difficult to tell exactly where one sphere ends and another begins. Sometimes multiple spheres can even occupy the same space, such as with clouds in the sky or plants on the ground. These interactions are essential to life on Earth. They are what recycle matter through different forms, phases, and locations. And because they are part of an overall connected system, a change in one sphere will certainly affect the other three in some way or another. You may have heard that ogres are like onions because they have many layers. Well, Earth is the same way. Earth is made up of several different layers, each of which has unique properties. Let's start from the inside and work our way out. Earth has a core, but this is really two distinct parts, the inner core and the outer core. Both parts of the core are made up of mostly iron and some nickel. The difference is that in the inner core, those minerals are solid, and in the outer core, they're liquid. The inner core of the Earth is incredibly hot, so hot that if you try to dig a hole to China, you'd burn up on your way through the Earth. What's amazing about the inner core is that even though it's about as hot as the surface of the sun, there's so much pressure from the weight of the world pushing down on it that it can't melt. This is the same reason that water in a pressure cooker doesn't boil, no matter how hot it gets. The outer core is also made up of iron and nickel, but it's quite different because it is a liquid. This is because there is much less pressure on this layer than the one below it. That outer core adds a lot of pressure to the inner core. Though the flow of this liquid layer is very slow moving, about a few kilometers a year, it is what produces Earth's magnetic field. Our north and south poles exist because of this liquid outer core, even though it's almost 2,000 miles below us. Sitting on top of the outer core, we find the mantle. This layer is by far the thickest layer of Earth, about 1,800 miles thick. It also makes up about 85% of Earth's volume. Like the core, the mantle contains mostly iron, but in the form of silicate rocks. You might be surprised to learn that this rock actually moves like a fluid, similar to how silly putty moves. If you poke silly putty hard, it acts like a solid, but if you slowly pull it apart, it acts like a liquid. We call this ability of rock to move without breaking plasticity. The mantle can also be divided into two portions, the upper mantle and the lower mantle. The lower mantle is completely solid because, like the solid inner core of Earth, the pressure is just too great for it to melt and flow. The upper mantle is also known as the asthenosphere, which flows as convection currents. Convection occurs in all fluids and is the rising of warm particles and sinking of cool particles. So as the material in the upper mantle warms, it rises straight up, and as it rises, it cools and then sinks back down. This convection flow of the asthenosphere has a large impact on Earth's lithosphere, the outermost layer of the planet. The lithosphere is only about 60 miles thick and contains both the crust and a small portion of the upper mantle. The lithosphere is very rigid. It does not flow like the asthenosphere, but instead floats on top of it like ice on a pond. This layer of Earth is broken up into several different pieces like a jigsaw puzzle called tectonic plates. The convection currents below in the mantle move these plates around on the surface of Earth. Though the flow of the asthenosphere is on par with a snail's pace, these enormous plates running into each other is what causes earthquakes, volcanoes, and mountain range formation. The crust itself, which is contained in the lithosphere, can also be divided into two parts. Have you noticed a pattern yet? We live on the continental crust, and the ocean floor is made up of the oceanic crust. The continental crust is thicker than the oceanic crust, but it's made up of rock that is less dense than the oceanic crust, so it sits on top of it above sea level. Still not a believer? It might help to think of the Earth's crust like a cargo ship in the ocean. An empty ship floats higher in the water than a ship that has been loaded up with goods to carry across the sea, right? Well, in this analogy, the continental crust is the empty ship sitting higher on top of the liquid mantle, and the oceanic crust is the fully loaded ship sinking down lower into this liquid layer. It's all because of gravity. Compared to the rest of the planet, the crust is really quite thin. If Earth were an apple, the crust would only be about as thick as the apple's skin. It's so relatively small, in fact, that if Earth were the size of a cue ball, it would be just as smooth. This is because all of those giant mountains on the surface are insignificant compared with Earth's overall radius. Earth can be divided into three main layers: the core, the mantle, and the crust. Each of these layers can be further divided into two parts: the inner and outer core, the upper and lower mantle, and the continental and oceanic crust. Both the inner and outer core are made up of mostly iron and a little bit of nickel. The inner core is solid, while the outer core is liquid. This liquid flowing deep down below us is what produces Earth's electromagnetic current. And it's pretty hot in the core, about as hot as the surface of the sun. The mantle is the thickest layer of Earth, making up about 85% of Earth's volume. The lower mantle is pretty solid stuff, while the upper mantle moves around like silly putty. This movement of rock without breaking is called plasticity, and the liquid part of the mantle is referred to as the asthenosphere. On top of the asthenosphere is the lithosphere, which also contains the entire crust. The slow-moving convection currents in the asthenosphere move the tectonic plates of the lithosphere around like ice on a pond, causing earthquakes and volcanoes on the surface. Though the continental crust is much thicker than the oceanic crust, it's made of material that is far less dense. This means that the continental crust floats higher on the liquid mantle below than does the heavier oceanic crust that sinks down like a loaded cargo ship. Have you ever thought about digging a hole to China? It seems like a logical way to get there instead of flying all the way around the globe. While this sounds like a great idea, it would take you much longer to dig through the Earth than to travel around it. Even if you could dig down that far, you would have a difficult time getting through all of the stuff that lies underneath the surface of the planet. So, if we can't dig that far, how do we know what makes up the interior of the Earth? Well, scientists are able to understand Earth's interior by studying seismic waves. These are waves of energy that travel through Earth, and they move similarly to other types of waves like sound waves, light waves, and water waves. Seismic waves are sent through the Earth during earthquakes, and those energy waves are what cause the ground to shake as they travel through it. Seismic waves are recorded by a machine called a seismograph, which tells us about the strength and speed of the seismic waves. These recordings made by a seismograph are called seismograms. Seismic waves travel at different speeds when they pass through different types of material, so by studying seismograms, scientists can learn a lot about Earth's internal structure. Let's first review the two types of seismic waves, which we learned about in another lesson. Body waves are seismic waves that travel through Earth's interior or its body. Surface waves are seismic waves that travel through Earth's surface. Makes sense, right? Surface waves are important, but they don't provide much information about what happens below the surface. For this, we need to study body waves so that we can see what Earth's body is like. There are two types of body waves called P waves and S waves. P stands for primary waves because these waves travel the fastest and are detected first. S stands for secondary wave because these are slower than P waves, arriving second on the seismogram. Since the information recorded on a seismogram tells us how fast body waves are moving when they travel through Earth, we can tell what type of material they're traveling through. As body waves travel through the Earth's internal layers, their speed changes, causing the wave to bend. This bending is similar to looking at a straw in a half-full glass of water. If you look at the straw from the side, it appears to bend where it hits the surface of the water. This is because the light waves are bending and slowing down as they hit the different material, in this case, the water. The same thing happens to body waves when they travel through the Earth. We know that the surface of the Earth is solid because we can easily see this, but we need body waves to tell us what lies below. What they tell us is that directly below the crust is a layer of rock with a different density. As we learned in another lesson, this layer is called the mantle, and we know that it's a different density than the crust because seismic waves bend and suddenly pick up speed where these two layers meet. P waves can travel through both liquid and solid material, but S waves can only travel through solids. Since both P waves and S waves travel through the mantle, this means that it must be a layer of solid material. The really interesting part about this solid layer is that even though it is rock, it flows like a very thick liquid. It's similar to the consistency of silly putty, which if you punch hard feels like a solid, but if you stretch slowly, moves like a liquid. Another pretty significant change occurs at about 1900 miles down. S waves suddenly stop as if they have hit a brick wall, and P waves bend and slow down so much that no waves are detected at the surface of Earth. What this tells us is that there is another distinct change in density and composition here. And in fact, this is the place where the mantle and the outer core meet. The mantle is made of mostly that liquid rock that moves like silly putty, but the outer core is an area of mostly liquid iron, which is much denser than the rock in the mantle. Since S waves can't travel through liquid, this is why they run into a wall and stop. P waves can travel through it, but they do so much more slowly than through solid material. As P waves continue through the outer core, they suddenly bend again and pick up speed at a little over 3,000 miles into Earth's interior. This is where the outer core meets the inner core, and we know that it's solid because the P waves pick up speed yet again. While studying seismic waves from earthquakes provided scientists with a lot of information about Earth's interior, much of what we know actually came from nuclear weapons testing during the Cold War. During the 1960s, both the US and Soviet Union tested nuclear weapons by exploding them underground. These underground explosions produced seismic waves similar to the ones produced by earthquakes. Both countries used very sensitive seismographic stations to monitor the testing activity of their opponent, and without intending to do so, produced seismograms that provided detailed information about Earth's mysterious interior. Just because we can't dig our way down into Earth to see what it's made of doesn't mean we can't learn about it in other ways. Seismograms, which are recordings produced by seismographs, are the main way that scientists know what Earth's interior is made of. We can see that the crust is solid material, but we require body waves to tell us about the rest of it. We know that the mantle is solid because both P and S waves travel through it. We also know it's a different density than the crust because both types of body waves pick up speed as they hit this layer. We also know that the outer core is liquid because S waves hit this layer of Earth like they would hit a brick wall. They can't travel through liquid, so this is where their journey ends. P waves can travel through liquid, but much more slowly than through a solid. When P waves hit the outer core, they slow considerably, telling us that they've reached a much denser material than in the mantle. Another significant change in wave speed occurs at the edge of the inner core. Here, P waves bend and pick up speed, telling us that the inner core must be solid material because P waves travel faster through solid than liquid.
Have the continents always been where they currently are? If the coastlines slowly erode, the continents must have been much bigger. How big were they? Why do some of the coastlines look like they could fit together? The answer to these questions are all found in something called Pangaea. Pangaea, its definition, and its relevance to the current continents are the subject of this lesson. As far back as the 1600s, people studying maps have noticed that the coastlines of the continents had some interesting similarities. In studying them, particularly the coastline of South America and Africa, it looked like the two continents could fit together, implying that they were joined at one time in the distant past. This was a revolutionary thought, because the accepted theory of the continents was that they were stationary and constant. There was no evidence other than the similarities of the coastlines to support such a radical theory. In 1911, a German meteorologist named Alfred Wegener began looking for additional evidence to support the idea that the continents might actually move around on the Earth's surface. He discovered many scientific papers that described puzzling data that did not seem to fit the accepted model of stationary continents. One observation was that geologists, scientists that study the Earth, noticed that rocks of similar type and formation existed in Canada and in Scandinavia as well as other locations. Other geologists found fossils, or evidence and remains of once living organisms, of the same plants and animals on widely separated continents, sometimes in locations where they never could have existed, such as tropical plant fossils in Antarctica. Still other scientists noted that similar deposits left behind by glaciers also appeared on different continents like Africa and South America. In the current model of stationary Earth's surface, this data did not make much sense because there was no theory that adequately explained how continents separated by great distances and vast oceans could produce these similarities. So, in 1915, Wegener published a new book called The Origin of Continents and Oceans, where he proposed a radical new theory that the continents were connected at one time in Earth's history and have drifted to their present location. His theory, known as continental drift, also stated that the continents were still moving today. Even though his ideas were not initially accepted by most geologists, even with the support of his observations and explanations, his theory was eventually accepted when a mechanism for plate movement was explained in the 1950s and 60s. In Wegener's model, he proposed that the continents were all joined at one time in Earth's history, making a supercontinent. A supercontinent is a giant landmass made up of many or all continents. He proposed this because if you assume the continents are moving, then continents would be colliding and pulling apart. In 1927, his proposed supercontinent was named Pangaea, which means whole Earth, and scientists still believe that Pangaea was the most recent supercontinent in the Earth's history, existing about 225 million years ago. As more information was discovered about the Earth, they realized that the continents are part of large pieces of the Earth's crust known as tectonic plates. These tectonic plates are the pieces of the crust that move around on the Earth, pushing together, pulling apart, and sliding past each other, and those movements are known as plate tectonics. Many scientists believe that there have been several supercontinents before Pangaea, and there probably will continue to be supercontinents in the far future. Some scientists consider the continents of Europe and Asia a supercontinent, because they currently exist as one landmass and are separated only by the Ural Mountains, which were formed by the two landmasses colliding. So how did we get from Pangaea to present day? And where were the continents originally located? Wegener believed that Pangaea looked something like this illustration. Superimposing the current continents onto this supercontinent makes it helpful to see its original orientation and location. Over time, continents drifted or broke apart slowly. Scientists believe that one of the first splits created a northern part and a southern part. The northern part was named Laurasia and contained the future continents of North America, Europe, and Asia. The southern part was named Gondwana and was made of land masses that became South America, Africa, India, Australia, and Antarctica. As they separated, the shorelines and boundaries were created, forming their telltale shape that led people to originally hypothesize their unity. As in this sequence of pictures, the continents split apart and moved to their current location. This, however, does not mean that the continents have stopped at their current location. Each landmass is still moving about the Earth's surface and will continue to do so, colliding, pulling apart, and sliding past other continents. Scientists had noticed that the coastlines of the continents had complementary shapes and could fit together. Alfred Wegener was the first person to propose that all the continents were once connected together in a supercontinent known as Pangaea. Pangaea was chosen for the name because it means whole Earth. All of our current continents and land masses, part of larger tectonic plates, were located in Pangaea, and through the splitting apart of the continents known as drifting, they separated and moved to their current location. The continents have not stopped moving, however, and continue to crash into, slide past, and pull away from each other in a process known as plate tectonics. Who knows? Pangaea, too, may be in our distant future.
Have you ever been babysitting and decided it would be fun to play Nerf gun wars with a child, only to have a misaimed dart hit a rare plate from Israel and fall on the brick fireplace hearth, breaking into many pieces? Not that I have ever done this or anything. The only good thing is that the pieces of the plate fit together nicely and allowed a stressed-out babysitter to glue it back together. But what does this have to do with the Earth? In the middle of the 20th century, just a few decades ago, a new theory about the Earth and how it changed was proposed, and the mystery of the drifting continents was solved. Geologists, scientists who study the Earth, now had an all-encompassing theory to tie all of its observations and data together. This new theory of large-scale change on the Earth is known as plate tectonics. Plate tectonics is the theory that the surface of the Earth is broken into larger pieces of crust called plates that ride along on a softer layer of the Earth, known as the asthenosphere, which is the upper part of the mantle. Each plate's thickness depends on the type of crust it is made of and the location of the plate. Continental plates can be up to 150 kilometers thick, whereas oceanic plates usually average about 5 to 10 kilometers thick. Also, plate boundaries are not the same as continental boundaries, as the edges of the plates can be underwater. For example, the North American plate extends from the middle of the Atlantic Ocean to the west coast of North America. So the big question that remains is, how do the continents move? The answer is related to the layers of the Earth and how they interact with each other. So, first we need to understand how the properties determine the layers of the Earth. Let's use an apple as an example. An apple has three main layers to it: the peel, the fruit, and the core. The crust, or lithosphere, is the hard outer layer of the Earth and would be the peel of our apple. This is the part where we reside and about which we have the most data. The mantle. The mantle is the middle layer of the Earth, consisting mostly of oxygen, silicon, magnesium, and iron. This would be represented by the fruit of the apple between the peel and the core. The core. The core is the center of the Earth that is represented by the core of the apple. The Earth's core consists of two parts: a solid center about 1,200 kilometers thick, surrounded by a liquid layer consisting of iron and nickel that is about 2,300 kilometers thick. The main theory of plate movement states that heat from the core causes convection cells in the mantle that move the plates as they ride on the mantle. The main source of heat that drives this process is thought to be the radioactive decay of uranium and other elements that give up their energy as heat as they break down. All this heat softens the rock enough that it will begin to flow. But how does this happen? When you put a pot of water on the stove to boil, the water nearest the stove heats up faster than the water on the surface of the pot. The hotter water tends to move toward cooler areas, and as it does this, a current of hot water rising and cooler water sinking begins to form. This is known as a convection current. Using this model, the stove is like the core and the water is the mantle that rotates. Geologists think that this same phenomenon is what is happening inside the Earth. The rock near the mantle is heated and rises toward the crust. The rock near the surface is cooler and sinks back down toward the core. This forms the same type of convection current which causes the plates to move. Scientists believe that this cycle takes thousands of years to complete. At the top of the mantle, the convection currents encounter the thin crust, causing it to move. As this movement occurs, the plates smash into each other, slide past each other, or are pushed under another plate. This may also produce secondary events that cause the plates to move. In ridge push, plates that are higher at the spreading center flow downhill and eventually flatten out to the ocean floor. Gravity causes this flowing down the ridge and may give the plate a slight push along as new crust is forced up at the fault, causing the rest to move out of the way. This is like those coin bulldozers at the fair where one new coin may push forward and knock others out of the way. As the plate is pushed along, it may run into another plate. Oceanic crust is easily forced under another plate and back into the mantle. These converging boundaries can be identified by deep ocean trenches that mark the location where one plate is sliding under another one. As it slides under the other plate and is forced back into the mantle, gravity again works to pull it along, giving the plate another force to keep it moving. Plate tectonics is the theory that unified all the puzzling data from early observations, accounted for the movement of the plates of the Earth, and gave a mechanism for how the plates actually moved around. The theory stated that the plates moved around on top of the mantle driven by convection currents caused by heat from the Earth's core. This theory has been supported since then by the advance of technologies that allow scientists to actually measure the movement of the plates in centimeters per year. Plate tectonics is the current accepted theory that describes how the face of the Earth can change over time.
Have you ever had the experience where you see a younger relative or friend after not seeing them for a few years, and you're taken aback at how much they have grown? We have an image in our minds as to what they looked like the last time we saw them, and they're much different. If the continents of the Earth move and grow, why don't we notice that? Well, for two reasons. One, we really don't see what whole continents look like in real time. And two, they move so slowly that people die before any noticeable changes can take place. As far back as 1620, people often noticed that the coastlines of North and South America looked like they fit together with Europe and Africa. These observers noticed these coastlines, but had no easy explanation for how that could have occurred, since everyone believed the continents were stationary. Solving this mystery would take the work of a geologic supersleuth. Alfred Wegener, a German meteorologist, was the first to begin to work out details to explain this interesting observation. To begin with, the current geologic theory was that the crust was all stationary and continents were relatively unchanging. They didn't move around. Alfred Wegener knew that other people had made observations of the fit of the coastlines. He accidentally became drawn into that topic by discovering evidence that might explain that phenomenon. In the fall of 1911, though, he came across a scientific paper that described the locations of identical plant and animal fossils on very different continents. These fossils included Mesosaurus, which was a freshwater reptile, Lystrosaurus, a land reptile, Cyagnathus, a land reptile, and Glossopteris, which was a tropical fern. These were on very different continents, and he wondered how could these same plants and animals be on such different land masses? How could they have migrated over such vast distances or survived in such harsh conditions? The current theories were that the continents were connected by land bridges that have since eroded away, or by stepping stone islands. Stepping stone islands would be a series of islands that traversed the ocean. Wegener developed a much simpler hypothesis that stated perhaps the continents were all together at one point, thereby also explaining the fit of the coastline. He then theorized a supercontinent he named Pangaea, which meant one Earth. He realized, though, that if this idea were to be accepted, he would need much more supporting data than he had, just fossils and fits of coastlines. Other clues came from more research. He discovered that in his Pangaea model, large geologic features such as mountain ranges on separate continents often lined up closely. Rock strata from Africa and South America also matched when placed together, South America and Africa lining up. Puzzling data of fossils of plants and animals found in climates where they could never have survived was also explained, similar to the Glossopteris tropical ferns growing in Antarctica. Coal was found in Antarctica and Britain, areas that could never support coal formation today. Putting all this data together, Wegener concluded that the continents were, at one time, all together in a giant supercontinent, and that somehow they broke apart and migrated to their present location. There was some trouble with this theory, though. He called his theory continental drift and talked to many other scientists and geologists about it. His theory overall was soundly rejected, and often in harsh and scathing language. The big problem was that Wegener had no convincing evidence for how the continents might actually move from place to place. He thought the continents broke through the ocean floor, much like an icebreaker plows its way through an ice sheet. There was some scattered support for his theory, but he passed away before the discoveries that would provide the mechanism for his theory and ultimate acceptance. As countries began to map the ocean floor after World War II, additional surprising clues from the geography of the ocean floor were brought to the surface, which would ultimately provide a mechanism for his theory and lead to ultimate vindication. These included underwater mountain ranges and the separation of the ocean floor at giant cracks. Many people had observed clues about the Earth's past and could not put them together to solve the puzzle about how the Earth operated or how continents moved. Based on the fit of the coastlines, fossil evidence, rock types, and mountain ranges found on separate continents, Alfred Wegener developed a new theory he called continental drift. Unfortunately, he failed convincing the jury of public opinion that he was on the right track, but ultimately this geologic supersleuth would be proven correct by future discoveries from the ocean floor.
Alfred Wegener was a developer of a new theory of the Earth's surface called continental drift, and he was an adept investigator. but passed away in 1930 with his theories generally dismissed. New evidence, though, would excite a whole new generation of geologic investigators and inject new credibility into his ideas. This evidence eventually led to a mechanism for how continental movement would work. It also was a great example of how new evidence from investigations can cause an existing theory to change, which is one of the strengths of science, and it led them to a solution for the mystery of the drifting continents. In 1948, a scientist was exploring some islands in the Atlantic Ocean, and he found that they actually were the highest points along a submerged mountain range made of surprisingly young volcanic rock. This was a key clue in solving the mystery. This became known as the Mid-Atlantic Ridge. After World War II, there also was a heightened interest in the mapping of the ocean floor due to the increase in submarines and their use in battle. There was a keen interest in this new field of battle where soldiers now traversed, and they sent ships across the ocean to create sonar maps of the ocean floor. Their findings contained more critical clues to help solve the mystery of the drifting continents. As they mapped the ocean, they discovered the Mid-Atlantic Ridge actually ran around the whole Earth through the ocean floor like the seams of a baseball. What did this clue mean? They also found that there was a steep valley at the center of the mid-ocean ridge. More questions for investigators. Deep ocean trenches were also found in specific locations on the ocean floor. They wondered if they had anything to do with solving the mystery. Cracks in the Earth's crust, or lithosphere as it is also known, were discovered. This was a whole new clue, since it was thought that the continental crust, or the crust that the continents are made up of, sat on top of the oceanic crust. That's crust under the ocean, and the surface was all one piece. This clue showed these investigators that both kinds of crust were often different parts of the same piece of crust that they named plates. Plates are giant pieces of the lithosphere that all fit together like a big jigsaw puzzle. As scientists researched the ocean floor more fully, there were several more clues that were found which finally unraveled the mystery of the drifting continents. The first was magnetic reversals. As magma cooled to form new lithosphere, the natural iron oxides in the rock act as tiny magnets and align themselves with the magnetic field of the Earth. Other scientists knew that the magnetic poles of the Earth shift, so the location of the pole can be discovered by examining the rock. In the 1950s, scientists started taking measurements of the ocean floor and discovered a pattern of stripes where magnetic orientation switched. They found this pattern on either side of the mid-ocean ridges. They concluded that the only way for these identical patterns to occur would be if they formed at the same time and moved in opposite directions. This led to the idea of seafloor spreading. The center of the steep valley on the mid-ocean ridges was extremely hot, and magma was found to be leaking out of the cracks in the ocean floor, pushing aside existing ocean crust and making it wider. This became known as seafloor spreading, and this was the first physical evidence that the lithosphere actually moved on the surface of the Earth. This was a critical discovery into solving the mystery. This can be seen in Iceland, where the spreading actually splits the island, making new land in a violent volcanic way. As scientists investigated further, they also discovered that all these ideas were confirmed by studying the age of volcanic rocks in the oceanic crust. Rocks nearer the mid-ocean ridge were much younger than similar rocks further away from the ridge. Further data in the case surrounding the mystery of the moving continents also came from accumulated earthquake data. As scientists mapped where earthquakes occurred, they found they were focused in specific locations and patterns. These patterns happened to coincide with the locations of cracks they discovered, or faults, as they're known, in the lithosphere. These discoveries also led to the realization that the continents didn't move through the ocean crust like other scientists thought, but that the continental crust was part of a larger piece of crust called a plate. These geologic investigators discovered that the plates were what was moving, and the continents rode along as part of the whole plate together. After the mystery was solved, this new data was combined together to form a new theory called plate tectonics. To recap the mystery of the drifting continents, scientists had accumulated a lot of data to make the case that the continents were at one time all together in a giant supercontinent called Pangaea. As people mapped the ocean floor after World War II, new evidence was discovered that led to a new understanding of how the Earth's crust was put together. This included the discovery of a mid-ocean ridge underwater volcanoes, magnetic stripes in volcanic rock, and seafloor spreading. This led scientists to understand the crust is a jigsaw puzzle of giant pieces of lithosphere, or crust, that move around, causing the continents to move with them. The only thing left to discover was the cause for the plate movement.
You are certainly familiar with the pictures of planet Earth showing its large land masses separated by brilliant blue oceans. In fact, if you were given a multiple choice quiz right now, I bet you'd be able to identify the major land masses based on their shapes and locations. If you are from America, you might start by labeling North America and South America. From there, you would probably be able to identify the big land mass to the east as Africa, and the land mass that it wears as a hat as Europe. From Europe, it's a short trip east to Asia, which snuggles up to India at its base. The big continent at the bottom of the globe is easily recognized as Antarctica, and by process of elimination, you would label the remaining area as Australia. But is this always the way planet Earth has looked? According to geologists, at one time, these major land masses were all bunched together as one big supercontinent. This supercontinent then broke apart, and over time the continents drifted into their current locations. How this drifting apart of major land masses occurred was a mystery for many years and hotly debated among scientists. But when the theory of plate tectonics was introduced, much of the debating quieted down. Plate tectonics is the theory that Earth's crust is broken up into plates. It is as if the planet's surface is cracked, much like the cracks that would form on the outside of a hard-boiled egg if you were to drop it. These large cracks in the Earth's surface form plate-like sections of Earth's crust referred to as tectonic plates. These plates are actually pieces of the planet's lithosphere, which is the outermost shell of the Earth made up of the Earth's crust and upper part of the mantle. And for this reason, tectonic plates are sometimes called lithospheric plates. These plates float on top of the hotter and more fluid asthenosphere, which is the layer below the lithosphere. Now there are 7 major tectonic plates that very slowly move around on the surface of our planet, along with a number of minor plates. Let's take a look at the 7 major plates of the lithosphere. Now at the start of this lesson, we identified some major land masses found on Earth. This gets us closer to understanding the location of major tectonic plates, but it doesn't share the whole story. This is because tectonic plates can contain both continental crust and oceanic crust. Therefore, some of the plates may contain land, but others may be located underwater or be a mix of both. Take the North American plate, for example. It is one of the major plates of the lithosphere and extends from the middle of the Atlantic Ocean to the west coast of North America. The same can be said for the South American plate, which is another of the 7 major plates and extends from the middle of the Atlantic Ocean to the west coast of South America. So you can see that the North and South American plates contain oceanic crust even though they are named for the main continent they encompass. In fact, 6 of the 7 major tectonic plates are named after the continents they contain. The one exception is the Pacific plate, which lies beneath the Pacific Ocean. Not only is this the only major tectonic plate that is mainly underwater, it is also the largest, spanning over 100 million square kilometers. Now you might be noticing that these major tectonic plates bump up against each other. When tectonic plates meet, they become a site for tectonic activity. Depending on whether the plates are moving toward each other, sliding past each other, or pulling apart, tectonic activity might include mountain building, earthquakes, tremors, or volcanoes. In the southern Atlantic Ocean, we see that the South American plate meets the African plate, which is the major plate that includes Africa and surrounding oceanic crust. They meet at the Mid-Atlantic Ridge, which is a large underwater mountain range on the floor of the Atlantic Ocean caused by diverging tectonic plates. As the two major plates slowly move away from each other, they allow magma from the deeper layers of the Earth to seep up onto the ocean floor, producing new layers of oceanic crust. This ridge runs up through the northern Atlantic Ocean, where it also separates the North American plate from the Eurasian plate. As we mentioned, 6 of the major plates are named after the continents they include, and this plate holds to that rule. The Eurasian plate includes most of Europe and Asia and nearby oceanic crust. The name is simply a blending of the 2 continents it contains, giving us the name Eurasian. Interestingly, the Indian subcontinent is not part of the Eurasian plate, even though it looks like it should be when you look at the map. Instead, India is considered to be part of the Indo-Australian plate, which is a major tectonic plate that includes the Indian subcontinent, Australia, and surrounding oceanic crust. So again, we see a major plate whose name is a blending of the 2 main landforms it contains. In this case, India and Australia are blended into the name Indo-Australian. This leaves us with the final remaining major plate of the lithosphere, which is the Antarctic plate. By this point in the lesson, I'm sure you are able to guess that this plate includes the continent of Antarctica and surrounding oceanic crust. Because it is at the bottom of the world, we see that it shares boundaries with the southern plates we discussed in this lesson. Let's review. The theory of plate tectonics tells us that Earth's crust is broken up into plates. These plate-like sections of the Earth's crust are known as tectonic plates, or lithospheric plates, and they very slowly float around on top of the hotter and more fluid asthenosphere. There are 7 major tectonic plates. 6 of the 7 are named for the continent they contain. The largest plate, called the Pacific Plate, is the only exception as it lies beneath the Pacific Ocean. The North American plate extends from the middle of the Atlantic Ocean to the west coast of North America, and the South American plate extends from the middle of the Atlantic Ocean to the west coast of South America. Where plates come together, they form boundaries that are prone to tectonic activity. For example, the North and South American plates butt up against the Eurasian plate, which includes most of Europe and Asia and nearby oceanic crust, and the African plate, which includes Africa and surrounding oceanic crust. At their boundaries, they form the tectonically active Mid-Atlantic Ridge. The 2 remaining major plates of the lithosphere are the Indo-Australian plate, which includes the Indian subcontinent, Australia, and surrounding oceanic crust, and the Antarctic plate, which includes the continent of Antarctica and surrounding oceanic crust.
Do you ever wonder if the crazy thing someone just told you is true? For instance, you may have heard that person declare that at some point in the near future, California is going to break off and fall into the ocean. My older brother told me that the Golden State is hanging off the end of the continent and will fall into the Pacific Ocean during the next big earthquake. Do the tectonic plates, or giant pieces of the Earth's crust that fit together and move around on the Earth's surface, really move? If so, what causes them to move? The best stories are often based on fact, so it is helpful to know what is real versus what is not. Yes, tectonic plates move, and the mechanism that causes them to move is the subject of this lesson. The part of my brother's story that is true is the western part of California, west of the San Andreas Fault, is moving in a different direction than the rest of the continent. The western part of California is moving northwest at the rate of several centimeters per year. Looking to the future, California will indeed one day separate from the rest of North America and become an island. Where I think my brother got confused is the mechanism that will cause this to occur. First of all, it is important to know that the Earth's crust is broken up into large pieces called tectonic plates. Remember, tectonic plates are giant pieces of the Earth's crust that fit together and move around on the Earth's surface. This movement can be observed and measured using GPS systems, and the edges of the plates can be detected as their edges can be seen. We also know that these plates move around with respect to one another. Earthquakes and volcanoes are the results of such plate movement. One question geologists have been trying to answer is, what is causing the plates of the Earth to move? This can be a challenging question because we are not able to get into the Earth's interior to observe it. There are several mechanisms that scientists have developed based on the observations of the plates and a deeper understanding of the inner layers of the Earth. These mechanisms operate at different points in the Earth and very well could complement each other, each assisting in moving the plate in its own fashion. Scientists believe that one of the primary forces behind plate movement is thermal convection. Thermal convection is when heat from the core of the Earth is transferred to the surface of the Earth by the mantle. The mantle is the thick, mostly solid layer of the Earth between the crust and the core. Thermal convection works a lot like a pot of boiling water, which can be seen in this animation. In convection, heat from the stove warms up the water closest to the stove, causing the water to expand and rise. Cooler water near the surface of the pot sinks to take the place of the rising water. In doing so, a current of water is set up flowing toward the surface and back down again. Using this model, the stove is like the core and the water is the liquid mantle that rotates. The plates on the Earth's surface would be floating on top of the water. These currents push the plates along according to the direction of the flow. Geologists think that this same phenomenon is what is happening inside the Earth. Liquid rock near the mantle is heated and rises toward the crust. The rock near the surface is cooler and sinks back down toward the core. This forms the same type of convection current which causes the plates to move. Scientists believe that this cycle of magma rising from the core to the crust and back again takes thousands of years to complete. At the top of the mantle, the rock encounters the thin crust, and as it pushes it aside, lava flows out from the mantle to form new oceanic crust. As this happens, the plates smash into each other, slide past each other, or are pushed under another plate. This movement of the plate, along with the upwelling of the mantle by the convection currents, may also cause secondary actions that assist in plate movement. In ridge push, the mantle wells upward because of the convection and elevates the edges of spreading oceanic plates. Because these plates are higher at the spreading center, they are forced downhill due to gravity and eventually flatten out to the ocean floor. The gravity causes this movement down the ridge, and it gives the plate a push along as new crust forms behind the plate at the spreading center. This is like those coin bulldozers at the fair where one new coin may push forward and knock others out of the way. Another mechanism that forms as a result of plate movement is slab pull. As the plate is pushed along, it may run into another plate. Oceanic crust is easily forced under another plate and back into the mantle. These converging boundaries can be identified by deep ocean trenches that mark the location where one plate is sliding under another one. As it slides under the other plate and is forced back into the mantle, gravity again works to pull it along, giving the plate another force to keep it moving. These two mechanisms are different. In slab pull, gravity is pulling on the front part of the plate. In ridge push, it is forcing movement from the back end. A third force that forms as a result of plate movement is known as trench suction. As a plate gets pushed back into the mantle, as we saw in slab pull, it is forced down at an angle. Not only does gravity pull it down in the slab pull model, but another force can act on it as well. Underneath and behind the plate, a small convection current caused by the diving crust can form and help pull the plate into the earth. It is very similar to the force that keeps a raft trapped in suction under a waterfall. This force aids in pulling the plate back to the Earth's interior to remelt. This also differs from ridge push and slab pull because it is not the result of gravitational pull. So, to recap, there are several mechanisms that scientists use to help explain the movement of the giant pieces of the Earth's crust, called tectonic plates. The force that causes most of the plate movement is thermal convection, where heat from the Earth's interior causes currents of hot rising magma and cooler sinking magma to flow, moving the plates of the crust along with them. Additional mechanisms that may aid in plates moving involve ridge push, slab pull, and trench suction. In ridge push and slab pull, gravity is acting on the plate to cause the movement. Areas where the crust is pushed upward by magma welling up are also pulled downward by gravity, forcing edges of plates back into the Earth's interior. These processes pull the whole plate along. In trench suction, a small convection current is formed by the remelting plate as it pushes back into the interior, and the current creates a force that pulls the plate downward. I hope you have never been in a car accident, but I know we all have seen one in our lives. If you have watched many movies, you almost certainly have. Have you noticed how even when the car is no longer at the accident site, you can tell what happened to it, like where it was impacted, how fast it was going, or the other car was going, and what part was hit first? Even without impacts, perhaps you can piece together what happened when a scratch shows up on the side of the car. As tectonic plates of the Earth, or giant pieces of the Earth's crust, move and crash into each other, similar telltale signs show up to give us some ideas about how they move with relation to each other. The theory of plate tectonics states that the crust of the Earth is broken up into large pieces, or plates, that move around by floating on top of the layer of the Earth known as the mantle. This process is driven by convection currents within the mantle. Convection currents are formed by hot magma near the core rising towards the surface, while cooler magma near the crust sinks, setting up a current that causes the plates to move. These currents are the primary driving force behind plate movement. This theory was the result of decades of work and observations made of the Earth's surface. It is still the first model to neatly explain all the pieces of data scientists couldn't explain when they thought the surface of the Earth was stationary. The map may seem confusing at first, but the main thing is that the colored lines show the lines where the crust is broken up into many different plates. Most are named after the continents that are contained on them. Some plates are entirely oceanic crust, or crust under the ocean, while others are a combination of oceanic and continental crust, which is crust of the continents. The boundary where two separate plates meet is where all the action occurs and is called a fault. A fault is a crack in the Earth's crust resulting from the movement of the two plates. Getting back to the example of cars, when two cars are next to each other, there are three possible ways for the cars to move with relation to each other. Plates act in a similar manner. The first way two cars can move relative to each other is in divergent directions, like passing a car going the other way. Plates also can pull apart from each other. This is known as a divergent boundary. A divergent boundary is a fault where the two plates are moving away from each other. Now, as plates pull apart, several things may occur. First of all, volcanic activity is common in these areas, since mantle easily moves to the surface through the thin fractured rock as it separates. Volcanoes are a sign of a divergent boundary. This happens all along the mid-ocean ridge, where magma is constantly streaming to the surface, creating new ocean floor as the plates separate. If a continent happens to be a place where a divergent boundary occurs, then the continent will begin to be torn apart as the sides of the plates separate, creating a rift valley. The African Rift Valley in East Africa is an example of this occurrence. Eventually, the ocean will separate East Africa from the rest, making a large island. A second way cars interact, unfortunately, is by colliding. When cars impact each other or another solid object, the energy is transferred to the cars themselves, showing up as dents, ripples, or cracks. Plates also show telltale signs of colliding too, depending on the kind of crust colliding. Remember that at divergent boundaries, new crust is being made, but the Earth is not getting larger. Why not? Well, at the opposite ends, crust is being pushed into the Earth's interior by colliding plates, and being remelted at the same rate, new crust is formed. This happens at a convergent boundary. A convergent boundary is a boundary where two separate plates are pushing into each other. There are two kinds of surface features that are associated with a convergent boundary. The first is a deep ocean trench that forms a line of the two colliding plates. One plate made of oceanic crust can slide down underneath another plate, forming this narrow, deep trench. This happens because oceanic crust is more dense than continental crust, making it more likely to be pushed back into the mantle. These trenches are the deepest places on the face of the Earth, extending over 30,000 feet below the ocean's surface. You could take Mount Everest and sink it in the Mariana Trench, the deepest point in the ocean, and still have a mile to the surface of the ocean. That's deep. As one plate is forced under the other one, it begins to melt and a line of volcanoes forms in a parallel line to the trench. If the other plate is oceanic crust, the line of volcanoes will become islands like the Philippines, and if it is continental crust, then it will become a line of volcanic mountains, like the Cascade Range in the western U.S. or the Andes Mountains in South America. If both plates are continental crust, the plates will crumple up as they collide, forming a high mountain range, much like the Himalayas. Continental crust is less dense than oceanic crust, and does not get forced into the mantle. The crumpling of the continental crust is similar to two cars colliding as in the example from earlier. No matter which type of crust is colliding, you will see volcanic activity if one is oceanic crust, because the more dense oceanic crust is pushed down into the mantle. As it is forced down, it begins to remelt, and the magma forces its way to the surface to form the volcanoes. All types will form strong earthquakes, forming from the plates grinding together as they slide under.
A third way that plates can interact is by sliding past each other. This would be like cars sideswiping each other. One car is moving one way and scrapes by one going the other way. Tectonic plates do this as well, grinding past each other as they move in opposite directions. This third type of plate boundary is called a transform boundary. The most famous example of a transform boundary is the San Andreas Fault in California. The San Andreas Fault is the edges of the Pacific Plate and the North American Plate. The fault line runs through the Gulf of California and through the western part of California before running back under the ocean. The Pacific Plate is moving northwest with respect to the rest of North America at the rate of several centimeters per year. This means that thousands of years in the future, San Francisco and Los Angeles will be on a piece of land that will break off from the rest of North America and move out into the Pacific Ocean as an island. Remember that this piece of North America is on a different plate, which the whole thing is moving. This part of California is not drifting around like a boat in the ocean. It's moving as a part of the whole plate, which is moving northwest. At this type of boundary, the only effects are earthquakes. The sliding process is not smooth and moves in fits and starts. The pressure for the plate to move builds over time, and the rocks compress and strain. At some point, the stored energy is released as the plates move, which can be several feet at one time. When it does, an earthquake occurs. There is no mountains or volcanoes forming from this boundary, no matter how many Hollywood movies are made that portray volcanoes erupting in Los Angeles. To recap, there are three types of plate boundaries that are formed by the interactions of different plates. Divergent boundaries are boundaries where plates pull away from each other, forming mild earthquakes and volcanoes as magma comes to the surface. Convergent boundaries are boundaries where two plates are pushing into each other, and are formed when two plates collide, either crumpling up forming mountains, or pushing one of the plates under the other and back into the mantle to melt. Convergent boundaries form strong earthquakes as well as volcanic mountains, or islands, when the sinking oceanic plate melts. The third type is transform boundaries, or a boundary where plates slide past each other, forming strong earthquakes. All of this crashing, banging, and erupting are one reason why the surface of the Earth has such a variety of landforms and features.
Some of the most classic stories in history are about journeys at sea. From Homer's Odyssey to Gilligan's Island, it seems that we can't get enough of them. The story of plate tectonics is no different. Plate tectonics is the theory that the Earth's crust is broken up into plates, and these plates, which go by the name tectonic plates, float around on the hotter and more fluid layer of the Earth below them. As these plates move, they might push together, pull apart, or slide past each other. In this lesson, we will look at the evidence in support of the plate tectonics theory that was uncovered through analysis of samples drilled from the ocean floor. Our tale begins in the 1960s. That's the decade that introduced the deep sea drilling project. which was an ocean drilling project designed to analyze the ocean floor. The task was to drill down into the ocean floor and extract samples of the ocean sediments and underlying oceanic crust. This task was accomplished aboard a ship called the Glomar Challenger. This was a research vessel equipped with a drilling platform that traveled across the Atlantic Ocean drilling core samples into the sea floor along the way. Now, an important feature found on the Atlantic Ocean basin is the Mid-Atlantic Ridge, which is an underwater mountain range that runs from Iceland to Antarctica. This ridge system was an important area to drill because at the time it was not fully understood how this large underwater ridge had formed. It had been theorized that the creation of the oceanic ridge system was caused by sea floor spreading, which states that new oceanic crust is constantly being formed due to the upwelling of magma through diverging tectonic plates. However, this was a lot for some scientists to believe. The scientific community was perplexed over the idea that the Mid-Atlantic Ridge may actually be a tectonic plate boundary that was separating and allowing magma from deep within the Earth to ooze up through the crack, and that this magma then cooled and was responsible for creating the new layers of oceanic crust that spread out from that area. You can imagine that this whole idea sounded pretty far-fetched to many scientists. Yet when samples were taken from this ridge system, they showed two important things. First, the rocks found at or near the seam or crest of the ridge were very young, and they got older farther away from the crest. Second, there were very thin layers of sediment found near the ridge crest, but the sediment thickness increased in samples taken farther distances from the crest, as if those areas had been there longer and had time to collect dust. This showed that new oceanic crust was being formed along the plate boundary and then spreading out laterally, just like the seafloor spreading theory proposed. And if that were true, then it also provided strong evidence that the Earth's crust was made up of moving tectonic plates, giving credence to the theory of plate tectonics. Let's review. The Deep Sea Drilling Project was an ocean drilling project designed to analyze the ocean floor. The Glomar Challenger was the research vessel equipped with a drilling platform that extracted the samples. Samples were taken of the Mid-Atlantic Ridge, which is an underwater mountain range that runs from Iceland to Antarctica. This ridge system was thought to be created by seafloor spreading, which hypothesized that new oceanic crust is constantly being formed due to the upwelling of magma through diverging tectonic plates. The idea that the Earth's crust is broken up into plates that can move is the basis of plate tectonics theory. These samples showed that rocks found near the crest of the ridge were very young, and they got older farther away from the crest. They also showed that layers of sediment were thinner at the crest and thickened farther out from that area. This showed that new oceanic crust was being formed along the plate boundary, and then spreading out laterally, providing evidence to support the theory of seafloor spreading and plate tectonics. Have you ever had what you thought was a great idea, yet when you shared your idea with others, they all thought you were crazy? We've all been there, and I think you would agree that it is not a good feeling to be told that your ideas are silly. So you can sympathize with how the German meteorologist Alfred Wegener must have felt when he proposed his theory called continental drift, in which he hypothesized that at one time all of the continents were joined and then slowly drifted apart. You can imagine how such a radical theory would have been met with much ridicule from the scientific community, especially at the time of its proposal back in the early part of the 20th century. In fact, Wegener's ideas continued to be debated for decades following his death in 1930. But then new evidence began to surface that supported a related theory called plate tectonics, which states that the Earth's crust is broken up into plates that float on top of a hotter and more fluid layer below. If this were true, then these plates, known as tectonic plates, could carry the continents away from each other as Wegener had proposed. In this lesson, we will look at the study of paleomagnetism as well as research on hot spots and show how they provide strong evidence for plate tectonics and therefore support for Wegener's earlier ideas about continental drift. Paleomagnetism is the study of the Earth's past magnetic field. It may help you to recall this term if you remember that it is a combination of two words, paleo, which means ancient, and magnetism, which means exhibiting a magnetic field. So paleomagnetism can really be thought of as the study of an ancient magnetic field. Some of the strongest evidence in support of the theory of plate tectonics comes from studying the magnetic field surrounding oceanic ridges. Oceanic ridges are underwater mountain ranges that contain a rift down their center where magma seeps up, forming new oceanic crust. You can think of them as mountains created by underwater volcanoes. In the middle of the 20th century, scientists started to recognize some interesting magnetic variations detected from the ocean floor surrounding these ridges. Now, they already knew that the rocks formed from this underwater volcanic activity were mainly basalt, which is an iron-rich volcanic rock that makes up most of the ocean floor. Basalt contains magnetic minerals, and as the rock is solidifying, these minerals align themselves in the direction of the magnetic field. This basically locks in a record of which way the magnetic field was positioned at the time that part of the ocean floor was created. The interesting thing is that when paleomagnetists, who are scientists who study past magnetic fields, took a look at the ocean floor going out away from oceanic ridges, they found magnetic stripes that were flipped so that one stripe would be normal polarity and the next reversed. How could this be? Well, there was only one good explanation, and that was that these oceanic ridges were actually boundaries with tectonic plates pulling apart, which we remember is the main gist of plate tectonics. This movement of the plates allowed the magma to rise up and harden into new rock. As the new rock was formed near the ridge, older rock, which formed millions of years ago when the magnetic field was reversed, got pushed farther away, resulting in this magnetic striping. Another source of evidence that the Earth's crust is made up of plates that move comes from studying hot spots. Hot spots are fixed locations where magma wells up from deep within the Earth's mantle to form a volcano. Hot spots occur within tectonic plates, not at their boundaries. It's like forcing a pencil, which represents a hot spot, up through the middle of a flat sheet of paper, which represents a tectonic plate. After the pencil is removed, the raised fragments of paper around the puncture remain, much like a volcanic mountain remains. Hot spots prove that tectonic plates move because hot spots leave behind a chain of extinct volcanoes that show up in a line. This demonstrates that a tectonic plate travels over top of a stationary hotspot. The Hawaiian Islands are a great example of this phenomenon. The islands are a chain of extinct volcanoes that have formed over millions of years. There are still active volcanoes at the end of the chain, indicating that the tectonic plate that Hawaii sits on is moving away from the hotspot. Plate tectonics is the theory that the Earth's crust is broken up into plates that float on top of a hotter and more fluid layer below. Evidence to support this theory has been uncovered through the study of the Earth's past magnetic field, known as paleomagnetism. It was found that stripes of the ocean floor going out from the oceanic ridges alternated in polarity. This variation was explained by noting that oceanic ridges are actually boundaries where tectonic plates were pulling apart and allowing magma to rise up and harden into new rock. The new rock pushed older rock, which formed millions of years ago when the magnetic field was reversed, farther away, resulting in the magnetic striping. Another source of evidence to support plate tectonics comes from studying hotspots, which are fixed locations where magma wells up from deep within the Earth's mantle to form a volcano. Hotspots occur within tectonic plates and leave behind a chain of extinct volcanoes. This demonstrates that a tectonic plate travels over top of a stationary hotspot. The Hawaiian Islands are an example of this phenomenon. Imagine you are a scientist living in the 1800s. The first somewhat useful submarines were starting to appear, yet these early vessels were not well suited for exploring the tremendous depths of the ocean. So you would have been left with little more than speculation as to what the ocean floor looked like. And you would have likely shared the opinion of many in the scientific community at the time who considered the ocean floor to be a relatively flat surface with few distinct features. But then along comes World War I, and with it new technology, such as echo sounding devices that bounce sound signals off of the ocean floor to measure the sea floor depths. What this technology revealed was a surface that was far from flat and featureless. In fact, it demonstrated the existence of an underwater mountain range, which would later be called the mid-ocean ridge. Little was it known at the time, but this discovery held the clues that would soon unlock two mysteries of planet Earth: sea floor spreading and polar reversal. As ocean exploration continued into the middle of the 20th century, scientists started to detect some peculiar magnetic readings coming from the ocean floor. The fact that the ocean floor could give off a measurable magnetic reading was not surprising, because by this time in history scientists understood that the main component of the ocean floor was an iron-rich volcanic rock called basalt. Basalt contains magnetic minerals that give the rock its magnetic properties. The surprising finding was that the ocean floor contained stripes of rock with different polarities. So some of the stripes of the ocean floor would have normal polarity, meaning that the minerals in those rocks produced a magnetic field aligned in the same direction as the Earth's present-day magnetic field. Meanwhile, other stripes demonstrated reversed polarity, or a magnetic field aligned in the opposite direction as the Earth's present-day magnetic field. What was going on? Scientists were baffled as to what could cause the magnetic variation. Then they discovered a pattern of alternating stripes leading away from the center of the mid-ocean ridge, and pieces of the puzzle started to take shape. What they noticed was that the stripe of ocean floor closest to the ridge had normal polarity, but the next stripe out revealed reverse polarity. This alternating pattern continued the farther the investigators got from the ridge. This revelation led scientists to hypothesize that the method by which ocean ridges formed could explain this polar reversal phenomenon. And they were right. What they discovered was the mid-ocean ridge was actually a site where tectonic plates, which are large pieces of the Earth's crust, were pulling apart from each other. These diverging tectonic plates created a gap in the ocean floor where magma, which is hot molten rock, from the hotter and deeper layers of the Earth could escape. This hot molten rock would cool when it came in contact with the ocean waters to form new rock on the ocean floor. This creation of new oceanic crust due to the upwelling of magma came to be known as sea floor spreading, and it has been going on for millions of years. By understanding sea floor spreading, scientists could now understand polar reversal. As new magma reaches the surface and solidifies into rock, the magnetic minerals within the rock get locked in place, essentially recording the Earth's magnetic orientation at the time. The creation of new rock at the ridge crest pushes older stripes of rock farther away from the ridge. Because stripes of rock leading away from the crest show polarities that alternate between normal and reversed, scientists could conclude that the Earth's magnetic field must have flip-flopped a number of times since its formation 4.6 billion years ago. Let's review. The underwater mountain range known as the mid-ocean ridge is continually forming due to sea floor spreading, which is the creation of new oceanic crust due to the upwelling of magma. As new oceanic crust is formed at the crest of the ocean ridge, older rocks are pushed farther away from the ridge crest. It was found that the younger stripes of ocean floor closest to the ridge are always of normal polarity, which means they have a magnetic field aligned in the same direction as the Earth's present-day magnetic field. However, as you move away from the ridge, the polarity alternates between stripes of normal polarity and stripes of reversed polarity that show a magnetic field aligned in the opposite direction as the Earth's present-day magnetic field. This led scientists to the conclusion that the Earth's magnetic field has flip-flopped over the years.
We use minerals in our everyday lives. Most of us are well aware of common uses of minerals, such as copper in electric wiring, gold and silver in jewelry, and even salt or halite in food seasoning. Not all mineral use is well known. For example, graphite is a material used to make pencils, talc is used to make cosmetics, and gypsum is used to make wallboard. And then there's silicon that is derived from quartz and used to make computer chips. The wide variety of minerals begs the question, what is a mineral? And what properties distinguish one mineral from another? Have you ever played the game 20 Questions? My family plays the game when we travel. The game begins with the simple question, is it an animal, is it a vegetable, or a mineral? In this game, anything not alive is considered to be a mineral. But what is a mineral? The term mineral has different meanings for different people. Let's take a look. My wife is a health nut, and she is concerned with getting her daily vitamins and minerals. For example, calcium, magnesium, and potassium. The mining industry refers to minerals as anything taken from the ground. For example, coal, iron ore, sand, and even gravel. Let's focus on the meaning that geologists apply to minerals as they make a living studying the Earth's minerals. These scientists will define a mineral as any naturally occurring inorganic solid that has a particular crystalline structure and can be represented by a chemical formula. Now, these crystalline structures and chemical properties give minerals unique sets of physical and chemical properties shared by all samples of that particular mineral. As the chemical composition of a mineral is difficult to determine, more easily recognized physical properties are commonly used in identification of a mineral. This lesson will identify the different optical properties of minerals used in identification. Let's take a look at mineral luster. The appearance or quality of light reflected from the surface of a mineral is luster. This is a description of the overall sheen on the surface of the sample. Let me quickly note that luster should not be confused with color. For example, quartz has a glassy luster, but comes in different colors, including purple, rose, and yellow. Therefore, the apparent color of a mineral is generally not used to identify a mineral. Have you ever wondered why pennies dull over time? Well, a penny contains copper, which has a shiny or metallic luster. Weathering and corrosion over time can give some minerals, such as copper and galena, a dull appearance, referred to as a submetallic luster. Now, most minerals don't look like metals at all, and they exhibit a non-metallic luster. Pollucite, for example, has a glassy or vitreous luster, as it looks like glass. Cesium can be extracted from pollucite and used to make capacitors for electronics. Other non-metallic minerals, such as kaolinite, have an earthy luster. Kaolinite has a dull or clay-like appearance and is used to produce ceramics, cosmetics, and even paper. Stellarite has a pearly luster, as it has the appearance of mother of pearl, which is found on the inside of a clamshell. Stellarite can be used as a chemical filter or sieve, as it contains microscopic channels allowing water to pass but not larger molecules. Gypsum has a silky luster, like satin cloth, and is used to make wallboard from construction. Other minerals, such as nepheline, have a greasy luster, or like oil. The ability to transmit light is another convenient property used in the identification of minerals. Opaque minerals, such as graphite and jasper, cannot transmit light. Now, if both light and an image can be transmitted through a mineral, such as mica, it is said to be transparent. If light, but not an image, can be transmitted through a mineral, such as citrine, it is said to be translucent. A mineral streak is its appearance in a powdered form, and can be seen by rubbing it across a piece of porcelain. Unlike the color of the mineral itself, which varies considerably for most minerals, the color of the streak is more consistent of a mineral and is more helpful in its identification. It is important to note that some minerals, such as quartz, don't leave streaks as they are harder than the porcelain. Other minerals, such as cinnabar and pyrite, are similar in apparent color but leave different colored streaks. Therefore, the streak is helpful. In summary, a mineral is any naturally occurring inorganic solid that has a particular crystalline structure and can be represented by a chemical formula. Minerals can be identified based on physical properties. Luster is appearance or quality of light reflected from the surface of the mineral. Some minerals have metallic or submetallic luster. However, most minerals have a non-metallic luster, such as glassy, earthy, pearly, silky, or even greasy. The ability of a mineral to transmit light is another useful property used in identification of minerals. Opaque minerals cannot transmit light. Transparent minerals transmit both light and image, while translucent minerals transmit light but not image. Finally, a mineral's streak is its appearance in a powdered form, and it can be used in identification of some minerals that otherwise might appear similar on the surface. Crystals have amazed us throughout history. For example, the crystal structure of a diamond reflects light in such a way to mesmerize even the harshest critic. But what is a crystal? Well, the term crystal is used to convey different meanings at the microscopic or macroscopic level. At the microscopic level, a crystal is a solid formed by regularly repeating patterns of molecules that are connected together. Now, not all solids are crystals. In a non-crystal solid, the arrangement of the molecules is random throughout the material. It's not regular. Still at the microscopic level, the crystal is characterized by what we call the unit cell, which is a collection of molecules repeated in exactly the same arrangement throughout the entire material. Now, at the macroscopic level, geologists use the term crystal shape or crystal habit to refer to the visible external shape of a sample of a material. The shape or habit results from the common or characteristic shape of either a single crystal or aggregate of crystals. Now, in this lesson, we will discuss two general types of crystal habits. The first exists as regular polygons and are thus termed euhedral, where U means true. The second don't exist in regular geometric forms. Let's look first at the euhedral crystals. Euhedral crystals have flat surfaces or facets with sharp angles. Now, this is rare in nature, as most crystals don't form with sharp edges and smooth, flat facets. For example, diamonds have an octahedral habit as they have 8 facets, octa meaning 8. Magnetite is another mineral with an octahedral habit. As the name suggests, this mineral is magnetic. Now, ancient humans discovered the property of magnetism through this mineral. Garnets are most commonly dodecahedrons, as they are 12-sided. Many gemstones are garnet minerals, and some are quite valuable rubies. Some minerals form a cubic or a cube-shaped habit, such as halite, galena, and pyrite. Halite is nothing more than common rock salt. Galena is the natural mineral form of lead, and pyrite or iron pyrite is also known as fool's gold, as it has a shiny metallic luster, much like gold. Now, it's important to note that while most minerals have one common crystal habit or crystal shape, some can form different habits depending on the conditions in which they are formed. Now let's move on to the crystal habits that don't have a regular geometric shape. Some minerals rarely develop perfect geometric forms at the surface. However, other characteristics can be helpful in identification of these minerals. For example, kyanite has a bladed habit as its crystals are elongated and flattened in one direction, much like the blade of a knife. Tourmaline has a prismatic or prism-like habit as the crystals are prism-like, that is, elongated but not flattened. Still other minerals are banded as they have stripes or bands of different colors or different textures. Rhodochrosite is a banded mineral as it has characteristic layered texture and color. Hematite forms an interesting botryoidal habit that resembles a cluster of grapes. In summary, the habit or visible shape of a crystal is a physical property that can be used to help identify the mineral. Some crystals are euhedral as they have a regular polygonal structure. Euhedral habits include octahedral, such as diamonds, dodecahedral, such as garnets, and cubic, such as halite and galena. Non-geometric habits include bladed, such as kyanite, prismatic, such as tourmaline, banded, such as rhodochrosite, and botryoidal, such as hematite. It should be noted that some minerals can exist in different crystal habits depending on the conditions under which they are formed. I used to work construction, and I still enjoy a do-it-yourself project every now and then. I remember being excited to get a carbide tip blade for my electric saw. The blade would cut through wood like butter and not get dull even if I accidentally cut through a hard nail. Now how can this be? As it turns out, carbide can cut through steel without dulling because it is stronger than steel. This lesson will discuss the various ways by which mineral strength is measured and expressed, including tenacity, hardness, cleavage, and fracture. Tenacity refers to a mineral's toughness or resistance to breaking or being deformed. Minerals such as halite, calcite, and fluorite are brittle as their molecules are held together by weak ionic bonds. Therefore, these minerals shatter when they're struck. Metallic minerals such as copper and gold are said to be malleable as they are easily hammered into different forms. Minerals such as talc and gypsum can be cut into thin sheets or sections and are said to be sectile, like section. Mica is an example of a mineral that is elastic, as it reforms its original shape after a stress is released. Mica is used to make washers, as it is not only elastic, but heat resistant as well. Now let me quickly note that mica is not the same as formica, which is manufactured material commonly used on countertops. Interestingly, however, formica is used as a substitute for mica in industry, hence the name formica. You may have heard it said that diamonds are the hardest natural mineral known. While that may be true, what does it mean to say that one substance is harder than another? Hardness is the resistance of a mineral to scratching, and it is one of the more useful diagnostic properties. Relative hardness is easy to determine. All you have to do is rub one substance against the other. The substance that is not scratched is harder. Mohs is a relative ranking of the hardness of 10 different minerals, with talc being the softest and diamond being the hardest. Now let me emphasize, this is a relative scale, and it's not an absolute scale. For example, gypsum, which is number 2 on the scale, is not twice as hard as talc, number 1 on the scale. Rather, gypsum is simply the second softest mineral on the relative scale. Furthermore, while diamond is ranked only one number higher than corundum, it is 4 times as hard. This scale is very useful in determining the relative hardness of other substances. For example, a fingernail's hardness is between that of gypsum and calcite, and it's expressed as 2.5. That's between 2 and 3. I mentioned earlier that carbide-tipped blades are used to cut through construction materials. As carbide is harder than steel, it can cut through steel nails. Carbide is a synthetic material that is similar to diamond, but fortunately much cheaper. Even so, some drill bits are tipped with diamonds themselves, which are harder even than carbide. Indeed, these are real diamonds, but they're of the industrial grade rather than the gem grade that we use to make expensive jewelry. These diamond-tipped drill bits are used in oil drilling to cut through rock, and lots of it. Minerals can be composed of different molecules, and different molecules bound to each other with different strength. Cleavage is the tendency of a mineral to cleave or break along flat planes of weak bonding. Cleavage results in formation of sheets of material. Let's look at the micas, for example. Micas can be cleaved to form thin, flat sheets. It's important to note that not all materials exhibit cleavage. As discussed previously, mica is used to make durable washers, as it can be cleaved into flat sheets and retain its elastic property. While some minerals exhibit cleavage, all minerals exhibit fracture. Fracture is the shape and texture of the surface formed when a mineral is broken or fractured. Fracture is an important diagnostic property, as minerals fracture the same way regardless of how they are broken. It is important to note that fracture differs from cleavage in that cleavage results in the formation of smooth, flat sheets all the time. Most minerals, such as pyrite and magnetite, exhibit irregular fracture, as they break into pieces with rough surfaces and random edges. Quartz exhibits what we call conchoidal fracture, as it breaks into pieces with curved and smooth surfaces. Limonite exhibits an earthly fracture, as pieces resemble that of broken dirt clots, and if you look at the images, that's exactly what it looks like. So in summary, mineral strength is diagnostic in identifying a material and can be measured in different ways. Tenacity is the resistance of a mineral to breaking, and tenacity can be characterized as brittle, malleable, sectile, and elastic. Hardness is the ability of a mineral to resist scratching, and the Mohs scale provides a relative ranking of hardness for 10 different minerals. Cleavage is the tendency of a mineral to break along planes and form flat sheets of material. Finally, all minerals exhibit some form of fracture, that is, the shape and texture of the surface of the broken pieces. While most minerals fracture in irregular forms, other fractures include conchoidal and earthy. Have you ever been fooled by the question, which weighs more, a pound of feathers or a pound of bricks? Well, obviously they have the same weight. Well, how about this question? Which weighs more, a liter of water or a liter of bricks? The answer to this question is not so obvious. It requires understanding of density, the amount of mass in a certain volume of material. As brick has more mass per unit volume, it has a greater density. As the brick is more dense, it will sink in water. Mineralogists have often used a similar property called specific gravity to describe the density of a mineral. Specific gravity is simply a ratio of the mineral's mass to the mass of an equal volume of water. Different minerals have different densities and thus different specific gravities. This lesson will describe how density and specific gravity are used to differentiate between minerals. Let's pretend you find an unknown specimen in your backyard. It's a heavy specimen and you want to know what it is. As a novice mineralogist, you head to the laboratory to measure its density. Well, what to do first? You need to determine the mass of the sample. So you weigh it on a scale and find its mass to be 150 grams. Now that you've identified the mass, you need to determine how much water the sample displaces. Fortunately, your sample is small enough to put in a beaker of water that's calibrated on the side. Before you place the sample in the water, you note the level at 100 milliliters or 100 cubic centimeters. After you place the sample in the water, you notice the level rises to 120 cubic centimeters. Therefore, 20 cc's of water is displaced. This displaced volume of water is equal to the volume of the sample. Therefore, your sample has a volume of 20 cubic centimeters. Now you're ready to calculate density. Simply divide the mass of the sample by the volume of the water displaced. Remember, the volume of the water displaced is equal to the volume of the sample. So, density equals mass divided by volume of water displaced. In our case, density equals 150 grams divided by 20 cc's of water. Density equals 7.5 grams per cubic centimeter. Checking your mineral density handbook, you see that galena, the common form of lead, has a mineral density that ranges from 7.2 to 7.6. While the density does not provide definitive identification, you can use other properties to determine its identity definitely. For example, the sample has a metallic luster, which is characteristic of galena. Now that we have determined the density of our sample, it is a piece of cake to determine its specific gravity. Recall that specific gravity is simply the ratio of the sample mass to the mass of an equal volume of water. The density of our sample is 7.5 grams per cc. Our sample has a specific gravity of 7.5. Well, how do we know this? Recall that 20 cubic centimeters of water was displaced by the sample. Now, as we've learned in previous lessons, each cubic centimeter or milliliter of water has a density of 1 gram per cubic centimeter. Therefore, 20 cubic centimeters of water has a mass of 20 grams. To determine the specific gravity of our sample, we simply divide the mass of the sample, that is 150 grams, by the mass of the same volume of water, which would be 20 grams. So specific gravity equals 150 grams of the sample divided by 20 grams of water. Specific gravity equals 7.5. Now, as the units are the same in the numerator and the denominator, that is grams, they cancel each other out, and this gives us a value with no units. As it turns out, most common rock-forming minerals have a specific gravity between 2 and 3. For example, quartz has a specific gravity of 2.65. Our sample in this discussion, along with other metallic minerals, are more than twice as dense. Gold is more dense, with 24-karat gold coming in around 20. Platinum has a specific gravity of about 22. Now that's dense. Graphite, used to make pencil lead, and gypsum, used to make wallboard, are less dense minerals with a specific gravity just over 2. In summary, density and specific gravity are properties used to help identify minerals. Density is a measure of the mass of a certain volume of the sample. Specific gravity is a unitless measure, and it is the ratio of the mass of a substance to the mass of an equal volume of water. Most rock-forming minerals have a specific gravity between 2 and 3. For example, quartz has a specific gravity of 2.65. Metallic minerals are far more dense. For example, galena, as we've talked about in our discussion, has a specific gravity of 7.5, and platinum has a specific gravity around 22. Scientists have discovered over 4,000 different minerals, and more are discovered every year. However, only a few dozen minerals are relatively abundant in the earth. That's a lot easier to wrap your mind around. Furthermore, only 8 elements make up the bulk of these minerals. The percent of these elements in the Earth's crust is illustrated on the screen. As you can see, oxygen, and silicon are the most abundant elements in the Earth's crust. These two elements combine to form the most common mineral group, the silicates, accounting for more than 90% of the Earth's crust. This lesson will describe the major silicate minerals, including feldspars and quartz. So, we've established that silicate minerals are the most abundant, and they contain silicon and oxygen. What else do we need to know about the silicates? Well, all silicates have the same fundamental building block, and that is the silicon-oxygen tetrahedron. That's a mouthful. The silicon-oxygen tetrahedron forms a negative ion containing 4 oxygen atoms surrounding a smaller silicon atom, as shown on the screen. It has a molecular formula of SiO4, all of that with a negative 4 charge. Silicate minerals are composed of millions of these building blocks held together in various ways. Some tetrahedra are arranged independently within the mineral, such as the olivine group of silicates. Amphiboles and pyroxenes are arranged as long chains of tetrahedra. Micas are arranged in sheets of tetrahedra. Now last and certainly not least, feldspars and quartz are formed by 3-dimensional arrangements of the tetrahedra. The groups of tetrahedra are held together by positively charged ions, that is, cations, such as iron, magnesium, potassium, sodium, and calcium. As we will discuss briefly, silicates can be identified by the arrangement of the tetrahedra and the cation present within the mineral. Most silicates are formed as molten rock cools and crystallizes. The conditions and the environment during which the cooling occurs will determine the type of silicate formed. Some silicates, for example quartz, are formed near the surface of the Earth where there is low temperature and low pressure. Other silicates, such as olivine, form deeper under conditions of higher temperature and higher pressure. The chemical composition of the molten rock helps to determine the formed mineral as well. That is, the environment. For example, molten rock containing magnesium and iron can form minerals of the olivine group, while quartz is formed from molten rock composed of only silicon and oxygen, the silicon-oxygen tetrahedra, that is. Feldspars are by far the most common silicate mineral, making up more than half of the Earth's crust. Feldspars are distinguished by their 3-dimensional arrangement of the tetrahedra held together by various different cations. They are named for the cation present. For example, potassium feldspar contains, well, potassium. Quartz is the second most abundant mineral in the Earth's crust, and it is the only common mineral made completely of silicon and oxygen. Now, like feldspar, quartz is comprised of a 3-dimensional arrangement of the tetrahedra, but it lacks cations. While feldspars and quartz comprise the bulk of the silicates, and thus the bulk of the Earth's crusts, other less common silicates are important. For example, micas, such as muscovite, are characterized by an arrangement of the tetrahedra in sheets. Therefore, micas can be cleaved into thin sheets of material, as the bonds holding the groups of tetrahedra together are not as strong as the bonds holding the silicon and the oxygen together within a tetrahedron. Amphiboles, such as hornblende, found in granite, are formed from chains of tetrahedra. Now, the olivine group, as previously mentioned, is composed of millions of independent tetrahedra. In summary, most minerals making up the surface of the Earth are silicates, and they're composed of the building block we refer to as the silicon-oxygen tetrahedron. The environment and conditions under which molten rock crystallizes will determine the type of silicate formed. Silicates can form as independent tetrahedra, chain tetrahedra, sheeted tetrahedra, and finally, three-dimensional tetrahedra. The arrangements of the tetrahedra are held together by cations such as potassium, iron, calcium, and magnesium. Your feldspars and quartz are the most abundant silicates, comprising 75% of the Earth's crust. Finally, less abundant silicates of importance include our micas, amphiboles, and the olivine group. Minerals can be classified as either silicate, that is, containing silicon and oxygen, or non-silicate, that is, lacking silicon. While most of the Earth's crust is composed of silicate minerals, several non-silicate minerals are of great importance. Now, this makes sense when you consider the relative composition of the Earth's crust. As you can see on the screen, silicon and oxygen comprise well over half of the Earth's crust by weight. That's a lot of weight. This lesson will provide examples of and describe the major non-silicate minerals, including our carbonates, our sulfates, and our halides. I live in central Kansas, which is a pretty dry climate. At one time, however, Kansas was covered by a great sea. Among other formations, vast amounts of limestone were formed from sediments in this marine environment. The limestone was mined by settlers to build homes and even fence posts. You might wonder why settlers would go through all that work to make a fence post out of limestone. Well, back in the day, there were very little, if any, trees around in central Kansas to harvest for lumber. Limestone is formed from a carbonate mineral. Carbonates are composed of the carbonate anion, that is CO3 with -2 charges, and one or more cations, for example, calcium or magnesium. The most abundant carbonate is calcite, also known as calcium carbonate. Calcite is the major constituent in two well-known rocks, limestone and marble. Stalagmites and stalactites are limestone structures that are formed in caves, and they're formed as the water evaporates, leaving the minerals behind. Stony coral is formed from calcium carbonate produced by resident organisms of the coral reef. Gypsum, Colorado is known for mining gypsum. That's a mineral used to make wallboard for construction. Gypsum is an example of what we call a sulfate, a mineral composed of the sulfate anion, SO4 with -2 charges, and a cation. Like Kansas, much of Colorado was once covered by seawater. As the water evaporated, gypsum formed from the sediments. Halite, or common table salt, is mined in Kansas along with limestone. As the Great Sea evaporated, sediments formed vast deposits of halite. Halite is an example of a halide, a mineral formed with a halide anion, that is fluoride, bromide, chloride, or iodide. The molecular formula for halite is sodium chloride. Here's an interesting fact. Huge beds of halite and gypsum exist on the floor of the Mediterranean Sea. This is evidence that this sea has been relatively dry in the past. Well, how do we know this? Well, here's what happens. When 65% of seawater evaporates, gypsum forms and settles out of solution. That is, it becomes a sediment. When 90% of seawater evaporates, halite forms and settles out of solution as a sediment. Now, given this information, which mineral would you expect to encounter first when drilling into the seabed of the Mediterranean Sea? That's correct. You would hit halite first as it precipitates out of solution after gypsum. In summary, most minerals making up the surface of the Earth are silicates. However, several non-silicates are important as well. Carbonates, such as calcium carbonate that makes up the bulk of the limestone, are non-silicate minerals composed of carbonate with one or more cations. Sulfates, such as calcium sulfate we find in gypsum, are non-silicate minerals composed of the sulfate anion and a cation. Now finally, halides, such as halite or sodium chloride, are also non-silicate minerals, but here formed with a halide ion.
They say that a diamond is a girl's best friend. Rubies, sapphires, and other precious gemstones are also popular ways to impress a lady. Mankind has always been infatuated with rare crystals. Diamonds in particular have become a symbol of love and commitment. Young ladies can't wait to show off when they get a big shiny rock from the groom-to-be. But should we really be using the word rock to describe a diamond? You may have heard the phrase rocks and minerals at some point in your science schooling. The reason we say rocks and minerals is because they are two different things. Rocks are not minerals, and minerals are not rocks. As we'll soon discover, diamonds are actually minerals. Some people are under the false impression that minerals are things we eat, as in the phrase essential vitamins and minerals. But really, minerals encompass a broad range of natural substances, some of which you eat, some of which you forge into tools, and some of which you give to your future spouse. Let's talk about the differences between rocks and minerals so we can get all our facts straight. We'll start right now with minerals. A mineral is a solid, inorganic, naturally formed substance that has a crystalline structure and specific chemical composition. I know that's a lot to take in, so let's break down this definition piece by piece. First of all, minerals are solid and formed naturally in the earth. Natural solids can be familiar things like sand, granite, salt, and wood. Our definition says that minerals are inorganic, which means that they do not consist of tissues from living things. So that means that wood is not a mineral. It also says that minerals have a crystalline structure. That means that the component atoms of the substance have a repeating three-dimensional arrangement. This is a picture showing how the atoms of salt are arranged. Salt is also called sodium chloride because it's made of two types of atoms, sodium and chlorine. The sodium and chlorine atoms are put together in a very specific three-dimensional lattice that repeats over and over until you get to the end of the salt crystal. Yes, it's a crystal. I know you typically don't think of salt as being a crystal, but it is, and so is sand. Sand is just tiny chunks of quartz crystal made by a pattern of silicon and oxygen atoms. What about our last substance, granite? It's solid, it's formed naturally in the earth, it's inorganic, but does it have a specific chemical composition? Does it have a regular, repeating atomic arrangement? No. Granite may be made up of minerals, but it's not a mineral itself. It's a rock. A rock is a solid, inorganic, naturally formed substance without a particular atomic structure or chemical composition. It's probably easier to just remember that rocks are made up of two or more minerals. Examples of rocks include granite, limestone, marble, pumice, obsidian, sandstone, shale, and slate. Each of these rocks consists of several different minerals, which are mixed up inside the rock through a variety of geologic processes. Let's take granite for example. Granite is mostly composed of three minerals, quartz, feldspar, and mica. Each of these minerals can be found alone in nature, but here they are mixed up inside of the rock. Sometimes you see large chunks of one of these minerals inside of the granite, but when you take the stone as a whole, you have to call it a rock. Other rocks are much finer grained than granite, so it's not easy to spot the different minerals. Slate is a rock that was made from clay, and clay is composed of tiny, tiny particles. Those particles can be minerals like quartz, pyrite, apatite, muscovite, feldspar, kaolinite, biotite, tourmaline, the list goes on. But you can't see these minerals inside of a slate rock. The slate looks all the same color and texture. Still, it's not a mineral because it has no regular atomic structure or chemical composition. Rocks are made of minerals, and minerals stand alone. Another way to distinguish between rocks and minerals is by their classification systems. It makes sense that they would be classified differently since they're different things, but many students get confused. They try to describe a rock as though it were a mineral, or describe a mineral as though it were a rock. At the most basic level, rocks are classified by the geologic processes that form them. The three main groups are igneous, metamorphic, and sedimentary rocks. Minerals are not classified this way. You can't say that quartz is igneous because it's not even a rock. Minerals are classified by their properties and chemical classes. Chemical classes of minerals include groups like silicates, sulfates, and carbonates. We group the minerals based on the atoms and chemical bonds that make them up. Silicates include minerals like mica and feldspar. Carbonates include calcite and dolomite. Some minerals, called the native elements, have only one type of atom. These include copper, gold, and silver minerals. Scientists also classify minerals by their properties, like density, hardness, color, fracture, luster, cleavage, and crystal habit. Crystal habit describes the way minerals form three-dimensional shapes based on their atomic structure. You may know that carbon atoms make up the fragile mineral graphite. Graphite is used in pencils because it is so soft it makes an excellent substance for marking on paper. Graphite can shed off pieces of itself because its carbon atoms are arranged in parallel sheets. These sheets of connected atoms slide off from each other and allow us to mark our paper with the mineral graphite. But carbon atoms can be arranged in a completely different way, a sturdy, three-dimensional lattice that is nearly impossible to cut or break. This form of the carbon mineral is called diamond. It's composed of exactly the same atoms as graphite, but because of its crystal structure, it's the most durable and indestructible gemstone of all. It is this durability that inspires us to use diamonds as a symbol of love and commitment. So next time you're admiring diamonds at the jewelry store, be careful not to call them rocks. Instead, you should call them carbon-based minerals with a 3D atomic lattice. That will really impress your husband or wife-to-be. Rocks and minerals are both solid, naturally formed substances that are found in or on the earth. They are both inorganic, meaning they are not made from tissues of living things. Rocks are made of minerals, and minerals are not made of rocks. Minerals stand alone because they have a specific chemical composition and a crystalline structure. Crystalline simply means that the atoms in a mineral are arranged in a repeating 3D pattern. Rocks and minerals also differ in the ways they are classified. While rocks are grouped by their geological origin, minerals are grouped by their chemical classes and properties.
Welcome to Earth Science TV. We are back once again with everyone's favorite show, What a Great Life. I am your host, Geology. We have an all-new participant this week, Miss Crystal Rakenna. Crystal, you have had an eventful life, working your way through the rock cycle. You have met some interesting formations and been in some exotic places. Can you start by filling our viewers in on what the rock cycle is? Sure, I'd be happy to. When the Earth first formed, the materials that formed it were so hot from the contraction that formed the planet, and from the heat generated by the core, that the outer layers were mostly liquid. Over time, it slowly cooled, and a hard crust formed on the outer surface. This was much like the thin layer of ice that will first form over a pond when the temperature dips below freezing. And just as there is liquid under the layer of ice, there still is liquid magma flowing under the crust. As this happened, a cycle of events began to be put into place that causes changes in the rocks that exist on the Earth. This cycle is known as the rock cycle. The rock cycle is a model used to describe the creation, alteration, and destruction of the rocks that form from magma. It's important to note that new matter is never created on the Earth. All the matter that the Earth contains was present when the Earth formed, and still is here today. It may be in different forms, but it still is present. The rock cycle is the Earth's way of recycling the matter used to make up rocks from formation to destruction and back to formation. And you participate in that cycle, isn't that right, Crystal? Yes, Geo. All rocks, whether solid or liquid, are located at some point on that cycle. How long does the whole cycle take? It can take a long time, sometimes thousands of years. Well, we won't ask you your age or anything, but you still look great. So, Crystal, do you remember this voice? Hi, Crystal. Remember when we both came up and were formed and spent the beginning of the cycle together? Those were some of the best times. Wow, it's my good friend Igneous. We started the cycle at the same time. We were igneous rocks then, because we were rocks that formed directly from magma or lava. That's right, Crystal. To begin the process, magma cools and hardens, either under the ground or on the Earth's surface. As the rock cools, the minerals that make up the rock take shape. All magma that solidifies becomes one of two types of igneous rock, either extrusive rocks, rocks that form on the Earth's surface, or intrusive rocks, rocks that form under the Earth's surface. Hawaii is made up mostly of an extrusive rock called basalt that came from the volcanic activity common to that area. The most common type of intrusive rock is granite, recognized by its pink or gray color, flecked with light and dark mineral specks. Igneous rocks are constantly being formed on the Earth whenever magma leaks to the surface through cracks or erupts in volcanoes. Ah, those were good times. That is where I got my name, because the flecks of color you often see in igneous rocks are crystals of minerals. That's lovely. After growing up in the relative safety of a boulder of granite, your life was headed for a big change, wasn't it, Crystal? It sure was, Geo. It was a very difficult time. My home was broken down by the constant exposure to the elements. And then, one day, it happened. I was broken apart from my family and friends in a small bit of rock. How traumatic. Yes, it was. But then I was on to the next phase of my life, learning to be sediment. But don't forget about me. My good friend Sandy Grain. If it wasn't for you, I never would have found my home. Yes, we were all a bit gritty, but we learned how to stick together, right? Absolutely. Yes, Crystal, rocks that are exposed to the weathering nature of the elements can be broken apart. Small grains of exposed rock can be broken off by the action of wind and water, or broken apart as water freezes in cracks. This can affect any type of rock, not just igneous. As time passes, these grains of rock accumulate in slow currents, in rivers or river mouths, low areas, or other quiet spots. As sediment piles up, the first sediments get buried deeper and are subjected to increased heat and pressure. Sometimes water will flow through the sediment, dissolving and redepositing glue-like substances to bind the grains together into layers. Rock made from eroded material, broken off other rocks and cemented together, is called sedimentary rock. One of the best examples of sedimentary rock are the layers that are seen in the Grand Canyon. There are many kinds and types of sedimentary rock. Sandstone forms mostly from quartz, or silica dioxide, the most common mineral found in sand. Limestone is another very common type of sedimentary rock, often used to make gravel, and it forms from the calcium carbonate substances from dead sea animals, or from ocean water. Fossils often can be found in sedimentary rock as they get buried and trapped. Geo, those were some challenging decades, but we stuck together through thick and thin. Eventually, those weathering processes uncovered us and tore us apart again. This time, I was deposited, but I was covered up very deeply. I knew it was time to change. I had been the same type of crystal for my entire life. I needed to be transformed into something new. Yes, and change you did. What happened next? Well, as a rock, you never know when you will be forced back into the earth to be remelted and start all over. But I wasn't ready for that yet. From all the heat and pressure in the situation I was placed in, I gradually felt all my physical properties changing. I was being remade. I became the third type of rock, called metamorphic rock. The word metamorphic can be broken down into roots, meta, meaning change, and morphos, meaning shape. Metamorphic rocks are rocks that are transformed into new substances under intense heat and pressure. In certain conditions, igneous or sedimentary rocks can be changed into different rocks under intense heat and pressure. These rocks literally change into new substances, very different from their old ones. This usually happens as rocks are buried deep within the crust. One of the most common metamorphic rocks is marble. Marble begins as the sedimentary rock known as limestone, and then, because of intense heat and pressure, it's changed into marble, known for its many uses in sculpture and architecture. And this is where you currently are now, in a beautiful piece of marble, correct? Yes, Geo. But rather than being in a work of art on display, I am in a kitchen countertop, scuffed with knives and covered with chicken juice. At least I clean up nicely, right? You are lovely, Crystal. One day I will make my way back to the Earth's interior and be remelted. I will be all young again, but I always have great patience. Because the process is quite slow, I'm content to stay put right now. Well, let me see if I have this all straight. All three rock types, igneous, sedimentary, and metamorphic, make up a portion of the rock cycle. Igneous rocks are rocks that formed directly from magma and can form either in the earth or on its surface. Igneous rocks can weather and be compressed to form sedimentary rocks. Rock made up of eroded material, broken off of other rocks, and cemented together, and both of these can be transformed into metamorphic rock. Metamorphic rock is rock that is transformed into new substances under intense heat and pressure. Any one of these rock types can be forced back into the mantle and remelted to emerge again and cool as igneous rock. The process starts over again. You have it down, Geo. Well, thank you so much for sharing the cycle with us, and you certainly can say, "What a great life," about crystal's progress through the rock cycle.
Scientists are always looking for ways to put things into categories, and rocks are no exception. Rocks are solid masses occurring naturally as part of our planet. As it turns out, rocks can be put into three fundamentally different types: igneous, sedimentary, and metamorphic rock. This lesson will identify and describe these three types of rocks. Let's start with the igneous rock. Igneous rocks, for example basalt and granite, are crystalline solids that form directly from cooling magma. All right, that's fine, but what is magma and what is its source? Magma is molten rock made by the partial melting of rocks in the Earth's interior under conditions of high temperature and high pressure. As rock melts, it becomes less dense and rises towards the Earth's surface. Magma that reaches the Earth's surface is called lava. Most lava flows are quiet, but some can be violent, such as the eruption of Mount St. Helens back in 1980. Igneous rock that forms at the surface of the Earth is referred to as extrusive or volcanic rock. These are named after the fire god Vulcan. Basalt is a good example of extrusive igneous rock. Igneous rock formed before it reaches the Earth's surface is named intrusive or plutonic, after the god of the lower world, Pluto. These rocks cool over long periods of time and thus develop large crystal structures, as we see in granite. Some intrusive rocks are subsequently exposed to the surface, but only after uplifting or erosion of the Earth's surface. Otherwise, they would remain buried. While igneous rocks make up the bulk of the Earth's crust, they're often covered by relatively thin sheets of sedimentary rock. As the name suggests, sedimentary rock is formed from sediments or debris transported by liquid, water, ice, or wind and become compacted and cemented together. Sedimentary rocks are secondary rocks as they are formed from the accumulation of small pieces of pre-existing rock, that is parent rock. Now there's two main types of sedimentary rocks based on the source of the sediment. Sedimentary rock can form as solid particles from weathered rocks. These particles are called detritus. And detrital sedimentary rocks are accumulations of detritus. Therefore, the source of sediment for detrital sedimentary rocks is weathered rock from another form. For example, particles of sand from other rocks can form sandstone, and mud can form shale, which is the most common form of sedimentary rock. Chemical sedimentary rocks are derived from material carried in solution to lakes and oceans. Under certain conditions, the dissolved material precipitates out of solution and thus settles to the bottom. Precipitation may occur due to physical processes such as evaporation or through living organisms. For example, limestone is the most abundant chemical sedimentary rock, and it's typically formed when calcite precipitates due to evaporation. Calcite is produced by living organisms to form shells which can, in turn, form sedimentary rocks. Now, interestingly, 90% of limestone is of this biological origin. Much like a caterpillar can morph into a beautiful butterfly, rocks can morph into different rocks. Now, in this context, metamorphism is the transformation of one rock into another. Like sedimentary rock, Metamorphic rock is a secondary rock. Metamorphic rocks are formed from pre-existing igneous, sedimentary, and even other metamorphic rocks. In short, any rock can become a metamorphic rock. How does this happen? Everything on Earth, including rocks, tends towards what we call a stable state, that is, its lowest energy. Environmental change can cause rock to become unstable. Well, for example, rocks that become buried deep under the earth are under tons of earth and exposed to increased temperature and pressure. And common metamorphic rocks include slate and marble. In summary, rocks are solid masses occurring naturally as part of our planet. Rocks can be put into three fundamentally different types: igneous, sedimentary, and metamorphic rock. Igneous rocks are crystalline solids that form directly from cooling magma, where magma is molten rock made by partial melting of rocks in the Earth's interior. Lava is nothing more than magma that reaches the Earth's surface. Extrusive or volcanic rock is igneous rock that forms at the surface of the Earth, while intrusive or plutonic rock is igneous rock formed beneath the Earth's surface. Sedimentary rocks form from sediments or debris that settle out of water and become cemented together. Detrital sedimentary rocks form from solid particles of weathered rock. Chemical sedimentary rocks form from material carried in solution to lakes and oceans. Finally, metamorphic rock is formed from pre-existing rock, and as such, both sedimentary and metamorphic rock are secondary rocks, as they are formed from other rocks.
Let's say you're a big rock living in a national park. For the most part, life is good as you spend your days living outside in the natural environment. You get warmed by the sun on a daily basis and get cleaned by the gentle rains that occasionally fall on you. However, over time, the constant exposure to forces such as wind, water, cold, and heat take their toll on your rocky structure. These forces lead to mechanical weathering, which is defined as the physical breakdown of rock by environmental factors. In this lesson, we will take a look at how this process works and see examples of the different types of mechanical weathering. Mechanical weathering is a physical process that is constantly happening in nature because nature is always active, even if this activity is happening slower than our senses can detect. For example, we feel when temperatures fluctuate from daytime to nighttime, but we can't see a rock expanding and contracting due to this temperature fluctuation. However, this unperceivable movement does occur, and it weakens the rock, eventually causing it to fracture and break down. This is just one example of how mechanical weathering happens. Let's take a closer look at the different types of mechanical weathering. We have been discussing how temperature fluctuations affect rocks. The process is known as thermal expansion, which is the tendency for minerals to expand and contract based on temperature. Rocks contain various minerals, and these minerals expand and contract at different rates when exposed to rapid temperature fluctuations such as day-night cycles. This causes stress and small cracks within the rocks and the gradual breakdown of the rock. Gruce is an example of thermal expansion at work. Gruce is the accumulation of coarse-grained and loose fragments left behind by weathering. So we see that gruce is the direct result of the physical breakdown and weakening of rock over time. Therefore, if you were a rock climber and you saw a pile of small rocks gathered at the base of a rocky structure, you would be smarter and safer to move to a different location for climbing. Now, we learned that rocks expand and contract as a direct result of temperature. We see that water acts in the same way. Frost shattering is a type of mechanical weathering where we see the breakdown of rock due to the expansion of ice. It may help you to recall this term if you remember that frost is the formation of tiny ice crystals. For example, if you look out your window on a cold autumn morning, you might see the glistening of small ice crystals that formed on your lawn overnight. This is a frost, and it does not just form on grass. It can also happen in the crevices between rocks. During the day, when temperatures are warm, water trickles into cracks and pores within rocks. At night, when the temperature drops, the water freezes and expands. As this frost continues, the cracks within the rocks widen and eventually shatter portions of the rock. In areas where temperatures often hover around the freezing point, road crews worry about frost shattering. If water seeps into cracks within a road surface, which is basically rock, it can freeze and expand. This ice will force small cracks to widen, making for a bumpy road. It is also worth noting that in some areas, especially coastal areas, water that seeps into rocks may contain salt. If the water evaporates, the salt crystals are left behind in the cracks. Like water, the salt crystals expand when they are exposed to heat and can widen the cracks. This can lead to some very interesting weathering patterns on rocky coastal structures. As we are seeing, the nooks and crannies found in rocks expose them to elements that can expand and cause weathering. These little crevices can provide just enough room for living organisms to enter and grow, so we see that plant activity is another way rocks can mechanically weather. The roots of plants and trees grow into cracks within rocks. As the roots grow in size, they widen the cracks. In the end, the roots often win the battle and push the rock, causing pieces of the rock to fall away. Now, to this point, we have looked at types of mechanical weathering that have to do with pressure building within rocks. However, rocks can also be worn away by a process called abrasion. Abrasion is the breakdown of rock by friction. With abrasion, we see that stationary rocks are literally scraped away by other loose rock and mineral fragments. These small fragments are carried by the air or water and come in direct contact with the stationary rocks. And you may have seen this process at work in rivers where the stones within the riverbed are nice and smooth. The stones are smooth due to the constant weathering force of water running over their surfaces. We also see the effects of abrasion in deserts, where sand is picked up and carried by the wind. This flying sand acts like natural sandpaper, smoothing off the surface layer of rocks. Let's review. Mechanical weathering is the physical breakdown of rock by environmental factors. This process is always at work, and there are a number of different types of mechanical weathering. Thermal expansion is a tendency for minerals to expand and contract based on temperature. Rapid temperature fluctuations, such as day-night cycles, cause rocks to expand and contract. This causes stress within the rocks and small cracks form. Gruce is an example of thermal expansion at work. Gruce is the accumulation of coarse-grained and loose fragments left behind by weathering. If water seeps into cracks within rocks, it can freeze and expand. Frost shattering is a type of mechanical weathering where we see the breakdown of rock due to the expansion of ice. If that water contains salt, the salt crystals left behind in the cracks can expand when exposed to heat and cause additional weathering. Plant activity, where the roots of plants and trees grow into cracks within rocks, is another way rocks can break down under pressure. However, pressure is not the only way rock mechanically weathers. It is also prone to abrasion, which is the breakdown of rock by friction. This process may be seen in rivers due to the friction of running water over rocks, or in deserts due to the friction of wind-blown sand on the surface layer of rocks. You have probably noticed that no two rocks look exactly the same. Some look like they have been carved by a sculptor, some look like they have been painted red, and others have been hollowed out to form caves. One of the reasons rocks look so varied in their appearance is because they are subjected to chemical weathering, which is the process by which rocks are broken down by chemical reactions. In this lesson, you will learn about the different types of chemical weathering and how exposure to things such as water, oxygen, carbon dioxide, and acids can alter the minerals found in rocks. Now, we mentioned that chemical weathering is a way in which rocks get broken down. But it is important to emphasize that because there is an actual chemical change taking place, rocks are not just crumbled into smaller rocks. They are actually being chemically altered. In other words, after chemical weathering, we end up with a different substance than the one we started with. There are different types of chemical weathering. Let's start with a discussion of hydrolysis, which is the chemical breakdown of a substance when combined with water. You can recall this term by remembering that the prefix hydro means water and the suffix lysis means to break down. With chemical weathering of rock, we see a chemical reaction happening between the minerals found in the rock and rainwater. The most common example of hydrolysis is feldspar, which can be found in granite changing to clay. When it rains, water seeps down into the ground and comes in contact with granite rocks. The feldspar crystals within the granite react with the water and are chemically altered to form clay minerals, which weaken the rock. An easy way to remember hydrolysis is to think of it as the same process you go through each morning when you make a cup of coffee. When the water you add to your coffee maker heats up, it filters down through the coffee grains. The water chemically reacts with the coffee grains, giving you a chemically different substance called coffee. Another type of chemical weathering is oxidation. Oxidation is a reaction of a substance with oxygen. You are probably familiar with oxidation because it is the process that causes rust. So just like your car turns to rust through oxidation, rocks can get rusty if they contain iron. You may have noticed that rusted metal on your car is somewhat fragile. You could even poke your finger through a rust patch if it's big enough. This is because when iron reacts with oxygen, it forms iron oxide, which is not very strong. So when a rock gets oxidized, it is weakened and crumbles easily, allowing the rock to break down. Iron oxide is a kind of brownish red in color, and this explains why some rocks look red. Carbonation is another type of chemical weathering. Carbonation is the mixing of water with carbon dioxide to make carbonic acid. This type of weathering is important in the formation of caves. Dissolved carbon dioxide in rainwater or in moist air forms carbonic acid, and this acid reacts with minerals in rocks. The mineral calcite, which is common in limestone, is particularly vulnerable to carbonation. This mineral dissolves in the carbonic acid and gets washed away. This can hollow out the rock and leave behind a cave. Another type of chemical weathering involves lichens. Lichens are a combination of fungi and algae and grow on rocks and produce acids that break down the minerals within the rocks. When water mixes with the lichens, they produce a weak acid. This is a very slow process because lichens are slow growing and the acid they produce is very weak. However, this is a common type of chemical weathering near rivers and streams. So we see that lichens break down rock by producing acid, and we see a similar phenomenon with acid rain. The EPA defines acid rain as rain that has been made acidic by certain pollutants in the air. When pollutants such as sulfur dioxide, carbon dioxide, and nitrogen oxide are produced by activities such as burning fossil fuels, these pollutants are put into the air where they mix with moisture. This process produces acids such as sulfuric acid, carbonic acid, and nitric acid, which falls to the ground as acid rain and chemically weathers rocks. Let's review. Chemical weathering is the process by which rocks are broken down by chemical reactions. There are different types of chemical weathering. Hydrolysis is the chemical breakdown of a substance when combined with water. The most common example of hydrolysis is feldspar in granite rocks changing to clay. Oxidation is the reaction of a substance with oxygen. This is the process that causes rust. When iron in rocks reacts with oxygen, it forms iron oxide, which weakens the rock. Carbonation is the mixing of water with carbon dioxide to make carbonic acid. This type of weathering is important in the formation of caves. Lichens are a combination of fungi and algae that grow on rocks and produce acids that break down the minerals within the rocks. Acid rain is defined by the EPA as rain that has been made acidic by certain pollutants in the air. Acid rain falls to the earth and chemically weathers rocks. Weathering is the mechanical or chemical process by which rocks are broken down. The weathering that happens to rocks can be understood by relating it to the digestion of a chocolate chip cookie. When you bite into and chew a chocolate chip cookie, your teeth mechanically break the cookie down into smaller pieces. Your mouth also produces saliva, which contains enzymes that chemically mix with the cookie pieces, breaking them down even further. The physical elements in nature, such as wind, water, cold, and heat, physically chip away at rocks, just like your teeth chipped away at your cookie. Chemical reactions involving water, acids, and certain atmospheric gases mix with the minerals within rocks and break them down, much like saliva acting on your cookie. Now that you have a better understanding of what weathering means, let's take a look at factors that affect the rate at which weathering happens. One factor that influences the rate at which rocks will weather is their degree of exposure to the atmosphere. Rocks that are covered by ground are relatively protected from the environmental elements that tend to mechanically weather rocks, such as wind, water, and day-night temperature fluctuations. As rocks get uncovered and become more exposed to the atmosphere, cracks within the rocks widen due to the expansion of ice that freezes within the cracks and plant roots that grow into the cracks and break apart the rocks. These widened cracks provide more surface area where chemical weathering can occur, further accelerating the weathering rate. Another factor that affects the rate of weathering is the composition of rock. Rocks seem like a pretty basic structure, but in reality we see that most rocks are composed of a variety of minerals. Minerals are solid substances found within rocks that have their own distinct chemical composition. Minerals that are most reactive when mixed with water, oxygen, or other elements will weather more rapidly. For example, some rocks contain the mineral iron. Iron reacts with oxygen to form iron oxide, which you know as rust. If you have ever had a rusty car, you know that rust is not very strong. In fact, with very little pressure, you could poke your finger through a patch of rust. We see the same thing happens in rocks. The presence of iron in rocks causes them to weather more quickly and break apart more easily. Some minerals are softer than others, and therefore rocks that contain these minerals will weather more rapidly. For example, the mineral calcite, which is commonly found in limestone, is soft and particularly vulnerable to chemical weathering. When exposed to carbonic acid, which can form when carbon dioxide mixes with rainwater, calcite dissolves. This type of chemical weathering is often seen with cave formation. On the other hand, the mineral quartz is very hard and is slow to weather. We also see some rocks are more porous than other rocks, meaning the rocks have more pores or holes throughout their structure. If a rock is very porous, the amount of surface area exposed to atmospheric elements is increased and weathering is accelerated. Climate is another factor that plays a significant role in the rate of weathering. Climate is mostly based on the temperature and rainfall of a region. Water is an important element in weathering, so we see that wetter climates are prone to faster weathering. Temperature is also important. In a lab, chemists will often use heat to speed the rate of a chemical reaction. Just as in the lab, we see that warmer climates accelerate chemical weathering. Therefore, warm, humid environments, such as the tropics, tend to experience higher rates of weathering than cold, dry climates. For example, if you built a wall of limestone in the middle of a dry desert, it would stay there for a long time. But if you put the same size limestone wall on a tropical island, the stone would be worn away relatively quickly due to the accelerating rate of weathering. Let's review. Weathering is a mechanical or chemical process by which rocks are broken down. One of the factors that affects the rate of weathering is exposure to the atmosphere. Rocks that are fully exposed to the atmosphere and environmental elements, such as wind, water, and temperature fluctuations, will weather more rapidly than those covered by ground. Another factor that affects the rate of weathering is the composition of rock. Rocks are composed of minerals, which are solid substances found within rocks that have their own distinct chemical composition. Minerals that are most reactive when mixed with water, oxygen, and other elements will weather more rapidly, as seen in rocks that contain iron. Rocks that contain softer minerals, such as calcite, and those that are more porous will also weather more rapidly. Climate is also a factor that plays a significant role in the rate of weathering. Warm, humid climates, such as the tropics, tend to experience higher rates of weathering than cold, dry climates. Chances are that you haven't thought a lot about the soil under your feet, but you may be surprised at the complexity of soil. Soil varies in its composition and the structure of its particles, and these factors are closely examined by farmers, who need appropriate soil for planting crops, as well as engineers, who may need to understand how soil is going to hold up under different demands. Soil is also vitally important to the sustainability of an ecosystem, because it serves as the natural medium for the growth of vegetation. In this lesson, you will discover just what soil is and which factors are looked at when determining the structure and the types of soil. So what exactly is soil? Soil can be defined as the organic and inorganic materials on the surface of the earth that provides the medium for plant growth. Soil develops slowly over time and is composed of many different materials. Inorganic materials, or those materials that are not living, include weathered rocks and minerals. Weathering is the mechanical or chemical process by which rocks are broken down into smaller pieces. As rocks are broken down, they mix with organic materials, which are those materials that originate from living organisms. For example, plants and animals die and decompose, releasing nutrients back into the soil. Now, if you look down at the soil under your feet, you cannot tell very much about that soil. So when you study soil, it's helpful to grab a shovel and dig a hole that's big enough to reveal a vertical section of soil that ranges from the surface to the underlying rock, referred to as a soil profile. The soil profile is somewhat like the soil's fingerprint, and it will differ from other soil samples based on factors like its color, texture, structure, and thickness, as well as its chemical composition. Each layer of a soil profile is referred to as a soil horizon. These horizons are identified by letters. Horizon A is the upper layer, closest to the surface. You can think of this horizon as the topsoil. In fact, you can use this as a memory jogger to help remember the order of the horizons. The letter A is at the top of the alphabet and refers to the topsoil layer. As you move deeper into the layers of the soil profile, you have Horizon B and C, giving us the three main horizons. There are three basic types of soil: sand, silt, and clay. But most soils are composed of a combination of the different types. How they mix will determine the texture of the soil, or in other words, how the soil looks and feels. One type of soil is sand. Sand within soil is actually small particles of weathered rock. Sand is fairly coarse and loose, so water is able to drain through it easily. While this is good for drainage, it is not good for growing plants because sandy soil will not hold water or nutrients. Silt is another type of soil. Silt can be thought of as fine sand, and it will hold water better than sand. If you were to hold a handful of dry silt in your hand, it would feel almost like flour. If you were to add water to the silt in your hand, it would do a fair job of holding the water and feel slick and smooth. Clay is very fine-grained soil. Its particles are even smaller than silt, so there is very little space between the fine grains for air or water to circulate. Therefore, clay does not drain well or provide space for plant roots to flourish. If you were a farmer, you would not want your field to be mostly clay. However, if you were a potter, you would think clay was the best type of soil. When moisture is added to clay, it can be molded into shapes, such as a pottery bowl or a building brick. Now we can consider loam as our fourth type of soil, even though it is really a combination of sand, silt, and clay. Loam will vary depending on how much of each component is present, but generally, if you are a gardener, this is the type of soil you want because it holds moisture but also allows for good drainage. If you were to hold loam in your hand, you could mold it into a ball, but the ball would easily crumble when disturbed. So we learned about the types of soil. This told us about the texture, which really comes down to the size of the particles and how much of each particle was present. Now we can turn our attention to soil structure. The soil structure is based on the arrangement of individual particles of sand, silt, and clay. When we have these individual soil particles bound together, they form soil aggregates. These aggregates form distinct shapes, and we want to know about these shapes because they tell us how easily water will penetrate down through soil. For example, if the soil structure is granular, then it is made up of small crumbs of soil. Water will easily drain down past these small structures, and therefore granular structure is a good medium for drainage and aeration. However, if the soil structure is platy, then we see a horizontal plate-like structure to the soil particles. This makes water, draining down from the surface, take a windy, slow path around the plates, making for poor water and air circulation. Platy structure is common in highly compacted soil, such as forest soil and lake sedimentation. We also have columnar or prismatic structures, which have long vertical dimensions that look like columns of soil. These structures are very dense, and penetrating water has to work fairly hard to travel through this structure. Blocky structure is, as you might have guessed, a block-like structure. If the blocks are large, then water penetration and movement of water will not be good due to the fact that the water must flow around the blocks as opposed to taking a more direct route downward. Let's review. Soil is the organic and inorganic material on the surface of the earth that provides the medium for plant growth. A soil profile is a vertical section of soil that ranges from the surface to the underlying rock. The soil profile is somewhat like the soil's fingerprint and contains distinct layers. A layer of a soil profile is referred to as a soil horizon. And we see that there are three main horizons named using the capital letters A, B, and C. There are different types of soil based on the size of the particles and how much of each particle is present. One type of soil is sand, which is small particles of weathered rock. Sand is fairly coarse and loose, so water is able to drain through it easily. Silt is fine sand, and the particle size is in between sand and the next type of soil called clay. Clay is very fine-grained soil with particles that are even smaller than silt. Clay does not drain well. Loam is a combination of sand, silt, and clay. Loam is the best soil for gardening because it holds moisture but also allows for good drainage. Soil structure is based on the arrangement of individual particles of sand, silt, and clay. Soil aggregates is the term used to describe the individual soil particles bound together. These aggregates form distinctive shapes and tell us how easily water will penetrate down through the soil. A granular structure is made up of small crumbs of soil that are easy for water to penetrate, whereas a platy structure is a horizontal plate-like structure that requires water to take a windy, slow path. Other soil structures include columnar and prismatic structures, which have long vertical dimensions, and blocky, which has a block-like structure. Water has to work fairly hard to travel through these structures. Did you ever stop to think about how important soil is to your daily life? If all of the soil, or even just the top layer of soil in your area was suddenly washed away, there would be no medium for crops to grow. And think about the areas that would receive the washed away soil. These areas would be clogged up with the sediment that could block drainage canals and cause flooding. These areas could also experience a disruption to their ecosystems and diminished water quality. So it's important to hold soil in its place. Yet soil erosion, which is the wearing away of topsoil, does happen. In this lesson, you will learn about the specific effects of soil erosion and measures that can be taken to prevent it. Soil erosion occurs when natural forces, such as wind and water, act on the soil. Man can also cause soil erosion by such practices as tilling a farmer's field or the clearing of vegetation. Clearing vegetation removes the protection of plants and roots needed to lock soil in place. Basically, the more exposed or heavily tilled soil is, the more likely it is to erode during rain or windstorms. Soil erosion impacts the agricultural industry as well as the natural environment. The effects of soil erosion can be felt both on-site, meaning at the site of soil disruption, or off-site, meaning the location where the eroded soil deposits. Let's start by building our understanding of the impact of soil erosion on-site. When the topsoil is eroded from an area, that area loses its most nutrient-rich layer, and therefore soil quality is reduced. Poor soil quality means smaller crop yields and may even wash away seeds and small plants. This may call for more of a need for artificial fertilizers and pesticides, which can run off of fields and contaminate waterways. Also, when the organic matter that is found within the top layer of soil is removed, it can weaken the soil's ability to hold water, leaving the field susceptible to weather conditions such as droughts. The soil that is carried away has to go somewhere, and this leads to off-site problems. As mentioned, when soil is carried away from a farmer's field by water, it carries with it contaminants such as fertilizers and pesticides. This runoff can cause water pollution that contaminates drinking water and disrupts ecosystems of lakes and wetlands. This negatively impacts the fish and wildlife that depend on these downstream waters for food and habitat. Sediments that accumulate downslope of the erosion can obstruct the flow of water in streams and drainage canals, leading to flooding. Now, as we see, much of the effects of soil erosion are the result of water erosion, but wind erosion can also transport topsoil and weaken soil quality. Wind can also damage young seedlings by blasting them with sand and other small particles that damage the plants. Wind also distributes topsoil, which might uncover and expose some seedlings, while at the same time burying other seedlings too deep. Also, when farmers' fields undergo excessive tillage, meaning that the field is worked too hard in preparation for planting, the soil structure can be lost, making it more susceptible to erosion. Now, there are ways to avoid and manage soil erosion. One of the best ways to prevent soil erosion is to increase vegetation. Plants and trees grow above the surface, protecting soil from erosion, and their roots meander down through the soil and become like bars in a prison, locking the soil particles in place, making it hard for them to escape and be carried away by water. Embankments and sloped land are most vulnerable to erosion due to gravity. So adding plants, shrubs, and other vegetation to these areas is important. Vegetation not only locks in water, it can keep wind away. For example, if an area is vulnerable to damaging winds, a natural windbreaker created by trees planted across the wind's direction acts like a wall, cutting down on wind erosion. Because soil erosion is such an important issue to farmers, any practice that will help prevent water runoff or helps to maintain the strength of the soil structure will be beneficial. Terracing is an option for controlling erosion on sloped land by cutting in flat surfaces. When land is sloped, water runs down the slope, so by cutting steps or terraces into a slope, a farmer's field will have an easier time holding water. A field that contains terraces looks like a stairway for a giant. Crop rotation, which is the practice of growing different crops on the same plot of land in sequential seasons, can help control erosion of fields. In other words, crops are rotated from one planting season to the next. So this year a farmer might grow corn in his field, and next year he might grow soybeans in the same field. This helps by keeping vegetation on the land and strengthens the soil to retain nutrients that could be depleted by successive planting of the same crop. Strip cropping, which is the practice of growing crops in strips that follow the contour of the land, can be used to help control soil erosion. Strip cropping is typically done by alternating bands of crops. For example, you might drive by a field and see low-growing alfalfa planted right next to strips of cornfield. This alternating pattern helps the soil absorb more water, which leaves less water to run off on the surface. It also makes the soil stronger so it can resist erosion. Soil erosion is the wearing away of topsoil. It is caused by factors such as water, wind, and tillage of farm fields. The effects of soil erosion can be felt on-site, meaning at the site of soil disruption, because soil quality is reduced. The effects can also be felt off-site, meaning the location where the eroded soil deposits. When soil is carried away from a farmer's field by water, it carries with it contaminants such as fertilizers and pesticides. This runoff can cause water pollution that contaminates drinking water or disrupts ecosystems of lakes and wetlands. Sediments that accumulate downslope of the erosion can obstruct drainage channels, leading to flooding. One of the best ways to prevent soil erosion is to increase vegetation, which locks in the soil particles and breaks up damaging winds. Terracing is an option for controlling erosion on sloped land by cutting in flat surfaces. Crop rotation is the practice of growing different crops on the same plot of land in sequential seasons. So one year a field might be planted with corn and the next year soybeans. Rotating crops helps strengthen the soil. Strip cropping, which is the practice of growing crops in strips that follow the contour of the land, helps reduce water runoff. With strip cropping, rows of corn might be planted next to rows of alfalfa in the same field. If a rock slides off of a mountain and no one is around to hear it, does it make a sound? Well, I don't know about the noise this activity would create, but I do know that mountains erode and that rocks and debris can slide and fall down mountain slopes in massive amounts. In this lesson, you will learn about a process called mass wasting and the factors that cause this movement of material. Mass wasting, which is sometimes called mass movement or slope movement, is defined as the large movement of rock, soil, and debris downward due to the force of gravity. In other words, the Earth's outer crust is being wasted away on a massive scale and falling to lower elevations. Mass wasting is a type of erosion, and it is capable of making big changes to the side of a mountain. These changes can happen suddenly, as in 1 minute the rock is there and the next it is gone, or it can happen more slowly over time. You might think of this process as a landslide, and this term is sometimes used interchangeably with mass wasting. However, the term landslide is a bit limiting and does not allow for a description of the many different triggers and types of erosion that can happen on this large of a scale. Now, we mentioned that mass wasting is mainly due to gravity, so we see that mountains have an ongoing tug-of-war with gravity. Gravity is constantly trying to pull rock and debris down the slope of a mountain. At the same time, the resistive forces of the mountain, including the cohesive strength and internal friction between the materials, referred to as the mountain's shear strength, constantly pulls back against gravity. The shear strength works to maintain the slope's stability and keep the materials in place. This is a lot like a mountain climber gripping onto the side of a mountain and resisting gravity. The climber uses his grip strength to resist gravity, like the mountain uses its shear strength. With this understanding, we see that the causes of mass wasting occur when gravitational force overcomes the resistive forces of the mountain. And since gravitational pull is always constant, then we see that mass wasting occurs when something changes the mountain's ability to resist gravity. For instance, an increased slope steepness increases mass wasting simply because the gravitational force acting on a steep slope is greater than the force acting on a gentle slope. Increasing the steepness of a slope is one way man can increase mass wasting. For example, if a road crew cuts away a slope to make room for a new road, but makes the angle of the slope too steep, the slope will be prone to mass wasting, and you will want to cross your fingers when you drive past this steep slope so no rocks or debris fall on your car. Increased water is another factor that plays an important role in mass wasting. Water can wash away small particles that help keep the mountainside intact. This is similar to what happens when a wave comes ashore and washes away a sandcastle. The abundant water breaks apart the small sand particles and destroys the structural stability of the castle you spent the afternoon building. If an area has decreased vegetation, it will be more prone to mass wasting. Vegetation stabilizes soil particles on the surface and anchors soil under the surface through its root system. This is much like comparing two sand dunes on a beach. If one sand dune has grasses growing on it, it will resist the erosion of water and wind better than a sand dune without vegetation. Another factor that plays a role in mass wasting is earthquakes. The violent shaking that occurs in a region where an earthquake takes place has the ability to break off sections of mountains or hills, causing them to slide down the slope. Because there are different factors that cause mass wasting, not all wasting happens in the same way. In some cases, we may see a large portion of a slope fail and slide or roll downhill. In other cases, large collections of debris may flow like a river down the side of a mountain mixed with water or air. One of the types of mass wasting that is an example of the slope failing is a slump. This is the sliding of coherent rock material along a curved surface. It's almost as if the section of the mountain or hillside slumps its shoulders and shrinks in height. This is easy to imagine happening if you consider that a slump often results due to an undercutting of the mountain's base. For example, water might erode the base of a cliff. Without the base, the outer sections of the mountain slumps down as a unit or multiple units. A rock slide is another example of mass wasting of a slope. A rock slide is the sliding of rock material down a mountain. It is similar to a slump, but a rock slide does not move along a curved surface like a slump. Therefore, in a rock slide, we see rocks sliding down a pre-existing surface, such as an underlying layer of rock. In a way, it is as if the rocks are moving down a slide on a playground. As a result, we will see a collection of fallen rocks at the base of a rock slide. Other types of mass wasting involve the downward movement of unconsolidated materials. These are collectively referred to as flows because the materials flow like a fluid down a slope, much like cement flows out of a cement truck. One example is a debris flow. A debris flow is the movement of a water-laden mass of loose mud, sand, soil, rock, and debris down a slope. Some debris flows move slowly, while others can pick up momentum on steep slopes and reach speeds of 100 miles per hour or greater, sweeping away anything in their path, including trees, bridges, houses, or roads. Therefore, since a debris flow can pick up debris along the way, you might use this fact as a memory jogger. An earth flow is a flow of fine-grained material that typically develops at the lower end of a slope. When fine-grained materials such as clay, silt, and fine-grained volcanic material become saturated with water, they become susceptible to earth flows. The speed with which an earth flow travels will depend on the amount of water it contains. With more water comes more speed. Let's review. Mass wasting, which is sometimes called mass movement or slope movement, is defined as the large movement of rock, soil, and debris downward due to the force of gravity. Mass wasting is a constant tug-of-war match between gravity and the mountain's shear strength, which is the resistive forces of the mountain, including the cohesive strength and internal friction between the materials. The causes of mass wasting include an increased slope steepness, increased water, decreased vegetation, and earthquakes. One of the types of mass wasting that is an example of the slope failing is a slump. This is the sliding of coherent rock material along a curved surface. This often occurs due to the undercutting of a mountain's base. A rock slide is the sliding of rock material down a mountain. It is similar to a slump, but a rock slide does not move along a curved surface. Instead, rocks slide down a pre-existing surface, such as an underlying layer of rock. Other types of mass wasting involve the downward movement of unconsolidated materials that flow like a fluid. One example is a debris flow, which is the movement of a water-laden mass of loose mud, sand, soil, rock, and debris down a slope. An earth flow is a flow of fine-grained material that typically develops at the lower end of a slope. If you were to wager on a tug-of-war match between Team Gravity and Team Mountain Slope, which team would you put your money on? Well, if you chose gravity, you would be a winner. This is because the pull of gravity never stops. Yet the resistive forces that hold rock, soil, and debris on the slope of a mountain eventually gets worn down. This wearing down or erosion is due to factors such as water, the steepness of the slope, the removal of vegetation, and disruptive events such as earthquakes. These factors trigger a process known as mass wasting, and in this lesson you will learn more about this process and the triggers that put it in motion. Mass wasting is defined as the large movement of rock, soil, and debris downward due to the force of gravity. It happens when the gravitational force acting on a mountain overcomes the resistive forces of the mountain that work to keep rocks and soil in their places. These resistive forces, including the cohesive strength and internal friction between materials, are referred to as the mountain slope's shear strength. Any factor that weakens the shear strength of the mountain slope could lead to mass wasting. Of all of the factors that play a role in erosion and therefore trigger mass wasting, water may be the most important. Water can both increase the risk of mass wasting and decrease the risk, depending on how much water is present. This can be related to building a sandcastle at the beach. In order to make sand stick together, you need a little bit of water. The same goes for soil particles on a mountain slope. A small amount of water helps them bond and stick together. However, if you add too much water to the sand, you will have a hard time getting the sandcastle to stand up, and your sandcastle walls will collapse under the influence of gravity. This is also seen with mass wasting on the slope of a mountain. If too much rain falls or soil becomes saturated by increased water, then the soil particles and other materials will wash away down the mountain. Now, as mentioned earlier, mass wasting happens when the gravitational force acting on the mountain overcomes the resistive forces that hold the mountain in place. Sometimes man gives gravity an edge by cutting a slope too steep during road construction along the side of a mountain. When there is increased slope steepness, gravity has an easier time pulling rock, soil, and debris down. This is similar to how you would ski down a sharply sloped black diamond ski run faster than you would down the gently sloped bunny hill. Man is not the only culprit that can lead to mass wasting due to slope steepness. Nature can also play a role, especially along streams and coastlines where water or waves can erode rock and soil and steepen the slopes. We also see that vegetation removal can trigger mass wasting. Plants, trees, and other forms of vegetation stabilize soil on the surface and protect it from the impact of raindrops, which can detach the bonds holding the soil together. The roots that grow beneath the surface anchor sediment to underlying structures, which further decreases the risk of mass wasting. You may have noticed the protective function of vegetation when you visited the beach. Older and better established sand dunes that are formed farther inland often contain vegetation that prevents sand from blowing away and eroding the dunes, whereas newly formed dunes closer to the water's edge are constantly shifting under the influence of water and wind. When vegetation is removed from a slope, protection against water and wind is lost. This loss of vegetation may be due to the human influences, such as wildfires, cutting, or harvesting. Earthquakes are another factor that can play a role in mass wasting. Earthquakes cause violent shaking over a large area. If this agitation affects an area with already unstable mountain slopes, the vigorous shaking may cause the slope to fail, sending rock, soil, and debris down the slope. This was seen in the Northridge, California earthquake of 1994. Let's review. Mass wasting is defined as the large movement of rock, soil, and debris downward due to the force of gravity. It happens when the gravitational force acting on a mountain overcomes the resistive forces, including the cohesive strength and internal friction between materials of the mountain slope, known as shear strength. Increased water is one of the triggers of mass wasting. If too much rain falls or soil becomes saturated by too much water, then the soil particles and other materials will wash away down the mountain, much like a sandcastle washes away. Increased slope steepness will also cause mass wasting because gravity has an easier time pulling rock, soil, and debris down. This is similar to a skier moving faster down a steep-sloped black diamond ski run than a gently sloped bunny hill. Vegetation removal can trigger mass wasting. Vegetation stabilizes soil. When it is removed from a slope, the slope is vulnerable to water and wind erosion. Earthquakes can also play a role in mass wasting due to the violent shaking they cause. They say all good things must come to an end, and I guess this adage can apply to mountains. Eventually, even the best and mightiest mountain will wear away due to the natural eroding effects of the environment that eat away at rocks and soil holding the mountain together. When these resistive forces are overcome by gravity, we see mass wasting occur, which is the large movement of rock, soil, and debris downward due to the force of gravity. Mass wasting happens in different ways. On some mountains, we see portions of the mountain slope fail and slide down in defined units, while other mountains simply drop their rocks or have rocky debris mixed with water flow like a fluid down their slope. In this lesson, you will learn about types of mass wasting and how they differ from one another. So we see that mass wasting occurs when the gravitational pull acting on a mountain becomes too much for the mountain to resist. Therefore, anything that erodes or impedes the mountain's ability to resist this force may become one of the causes of mass wasting. For example, increased slope steepness will make a mountain or hill more prone to mass wasting simply because gravity has an easier time pulling materials down a steep slope as compared to a gentle slope. Too much water or rainfall will also weaken a mountain or hillside's ability to resist gravity. This is an example of too much of a good thing. A little bit of water actually makes it easier for soil particles to bond together and keep the mountain intact. However, if there is too much rain or water, then the soil particles lose this bond and break apart. If a mountain slope has decreased vegetation, then it will be more prone to mass wasting because it does not have the protective plant covering above ground or the soil anchoring root system below ground. Also, disruptive events such as earthquakes can cause sections of mountains to detach due to the violent shaking that occurs. A slump is a type of mass wasting that results in the sliding of coherent rock materials along a curved surface. In a slump, a portion of the mountain moves down a short distance. It's almost like when you stand up straight and tall and then slump your shoulders forward as if you're too tired to hold up your shoulders. In fact, if you were to look at an actual slump, it might appear to you as if the mountain just got tired of holding up that section of the mountain and let it drop down. A slump is sometimes referred to as a rotational slide because a portion or block of the slope slides down as it rotates around an axis parallel to the slope. A slump can occur as a single unit or as a number of slumps grouped together, and they form when the base of the mountain slope or hillside is eroded or cut away. For instance, water or waves may undercut a mountain slope, removing the physical foundation holding up the rocky material. Without a base, the block of mountain goes kerplunk and slumps down. Slumps can also be blamed on human activities. For example, if a road crew cuts away the base of a mountain slope to make room for a road, the structural stability of the slope could be weakened, resulting in a slump. Another type of mass wasting is a rock slide, which is the sliding of rock material down a mountain. It is similar to a slump in that there is a mass failure of the slope, but a rock slide does not rotate as a block around an axis like a slump. Therefore, a rock slide is more of a translational slide because it moves in a more uniform direction along a pre-existing plane such as an underlying layer of rock. It is as if the rocks were skiing down the slope and nothing is going to stop them until they reach the bottom. And they often do reach the bottom of the slope, so in an area that experienced a rock slide, it's common to see a pile of rocks at the base of the slope. With slumps and rock slides, we see the slope fails as a mass of rock and sediment falling together as somewhat large coherent blocks of material. However, there are other types of mass wasting that happen when loose materials mix with water and air and flow down the slope like a fluid. This type of mass wasting is referred to as a flow. A debris flow is the movement of a water-laden mass of loose mud, sand, soil, rock, and debris down a slope. A debris flow can dash down the slope, reaching speeds of 100 miles per hour or greater. That's as fast as a Major League Baseball pitcher's best fastball. So as you can imagine, debris flows can be very destructive and dangerous. As the flow moves down slope, it picks up debris in its path, including trees, bridges, and buildings. Every year, people are caught off guard and killed by debris flows. An earth flow is a flow of fine-grained material that typically develops at the lower end of a slope. With an earth flow, we don't see as much large rock as we see fine-grained particles such as clay, silt, and even fine pyroclastic material from volcanic eruptions. When these materials combine with moisture, they begin to flow, and while earth flows can move with a fair amount of speed if mixed with enough water, earth flows often move no faster than an earthworm trying to make its way over a patch of ground. In fact, the slowest earth flows move at a pace of only a few inches per year. Maybe we should refer to them as an earth ooze rather than an earth flow. If you were to fly over an earth flow, you might think its shape resembled an hourglass. The typical hourglass shape of an earth flow results because the initial material at the head of the flow liquefies and spreads before running down the slope in a more elongated path. At the bottom of the slope, the fine-grained material collects and spreads out. An earth flow can form at the base of a slope or form at the lower end of a slump. Mass wasting is the large movement of rock, soil, and debris downward due to the force of gravity. The causes of mass wasting include increased slope steepness, too much water, decreased vegetation, and disruptive events such as earthquakes. A slump is a type of mass wasting that results in the sliding of coherent rock material along a curved surface. A slump is sometimes referred to as a rotational slide because a portion or block of the slope slides down as it rotates around an axis parallel to the slope. A slump can form when the base of a mountain slope or hillside is eroded away by water or cut away during construction. A rock slide is a sliding of rock material down a mountain. It is similar to a slump, but it is more of a translational slide because it moves in a more uniform direction along a pre-existing plane, such as an underlying layer of rock. A debris flow is the movement of a water-laden mass of loose mud, sand, soil, rock, and debris down a slope. A debris flow can dash down the slope, reaching speeds of 100 miles per hour or greater. An earth flow is a flow of fine-grained material that typically develops at the lower end of a slope. Earth flows often ooze down a mountain at a pace of a slow-moving earthworm. Earth flows often take a characteristic hourglass shape and may form at the bottom of a slump.
Did you know that rocks experience stress? While not the same kind of stress that you might experience on a bad day, the stress rocks are subjected to still has quite an impact. Stress causes rocks to deform, meaning the rocks change size or shape. There are different kinds of stress that rocks experience, and these determine how the rocks deform. Tensional stress is when rock is stretched apart. This is similar to pulling on a string from both ends after the string has already been fully extended. Compressional stress is when rock is pressed together. Here, rocks are squeezed together like a car caught in the middle of a long pileup on the highway. Shear stress is when rock slips in a horizontal direction. With shear stress, the rock is being pulled in opposite directions, but on different ends. To understand this, try putting your palms together and then rubbing them back and forth. Now imagine that there's a rock in the middle, and you can see how one end goes forward while the other end gets pulled backward. As rocks are stressed, they go through stages of deformation. At first, the rock is strained enough that its shape or size may change, but the change is reversible. This is the first stage, called elastic deformation. Think of this elastic change like the elastic in your waistband. If you pull it and then let it go, the stretch is reversible because it can go back to its original shape. Rocks may also become so deformed that the change is not reversible, which we call ductile deformation. Ductile means that something can be changed into a new shape, but once this happens, it stays that way. This is like the copper wiring in your house. Copper is ductile, meaning you can stretch it into long, thin wires. However, once you've made this change, you can't unstretch it, and the same is true for rocks in this stage of deformation. Finally, if rocks are stressed enough, they fracture, which is when the change is irreversible and the rock breaks. If you fall down hard enough, you may fracture a bone in your body, and rocks experience the same thing when the stress is great enough. Some people handle stress better than others, and rocks are the same way. So just like there are various types of rock stress, there are also different responses to the stress for different types of rock material. The ability of a rock to handle stress depends on its elasticity, or the flexibility of the rock. You might be surprised to learn that rocks are flexible. Under the right conditions, they can flow very slowly. This movement is similar to silly putty. Push on silly putty very hard and it feels like a solid, but pull it apart and it moves like a liquid. Rocks are not quite as fluid as silly putty, but sometimes they can act similarly. Do you remember from before that ductile materials like copper can be reshaped? The same is true for rocks. Ductile rock is rock that flows in response to stress. These rocks are more flexible than not. Things like clay and mica minerals are ductile materials, which you've experienced if you've ever played with clay to mold it into different shapes. Alternately, there is also brittle rock, which breaks or fractures in response to stress. This type of rock is less flexible and therefore cracks under pressure more easily than ductile rock. Examples of this type of material are quartz and feldspar minerals, which would break very easily if you drop them on the ground. The material of the rock is just one factor in how it deforms. Temperature also plays a role because at high temperatures, material can flow more easily, so it's more ductile. The opposite is true for low temperatures, so materials are more brittle and break more easily. Water is also important, and the less water present in a rock, the more brittle it is. Let's use clay as an example again. Wet clay is easy to mold and shape because it still has a lot of water in it. But when you bake it in the kiln, this removes the water and you can no longer change its shape without breaking it apart. Cement is the same way. When you add water, you can pour and shape the material almost any way you like. But as soon as it dries, you have to break it apart with a jackhammer to get it to change at all. If you think you're having a bad day, try being a rock. Rocks experience so much stress that sometimes they deform or change size and shape. There are a few different types of stress that rocks may experience. Tensional stress is when rock is stretched apart, similar to stretching a string as far as possible from both ends. Compressional stress is when rock is pushed together, similar to a car being smashed from both ends in a long pileup. Shear stress is when rock slips horizontally, like how it would if you put it between your hands and then move them in opposite directions. As rocks are stressed, they go through 3 phases of deformation. First is elastic deformation, which is when the deformation is reversible. If the change is not reversible, then this is ductile deformation. If the stress is so much that the change is not reversible and the rock breaks, we call this fracture. Many factors determine how a rock reacts to stress. Ductile rock will flow in response to stress because ductile materials are flexible enough to be reshaped without breaking. On the other hand, brittle rock will simply break in response to stress because it's not very flexible material. In addition to the material, things like temperature and water also play a role. Heat and water tend to increase the rock's elasticity or flexibility. But in cool temperatures and dry conditions, rock becomes more brittle, breaking more easily. We often think of rock as hard, brittle material. Throw a rock hard enough on the ground and it will likely break into pieces. But under the right conditions, rock can actually flow in a way that keeps it from breaking. When rock deforms in such a way that it bends instead of breaking, we call this a fold. Folds come from pressure on rocks that occur over very long periods of time, think millions of years. So instead of a quick action like throwing the rock on the ground, it's more like standing on it for millions of years until the pressure is finally enough that it changes shape. Folds are created in rock when they experience compressional stress. This is when the rock is being pushed inward from both sides. This is like if you put a spring between your hands and push them together. As you push, you're compressing the spring, and rock can be compressed in the same way over long periods of time. There are different types of folds created by compressional stress depending on which way the rock bends. An anticline is a fold that arches up as both sides of the rock are pushed inward. You can remember that the anticline creates this type of fold because the arch looks like an A for anticline. A syncline is a fold that sinks down as both sides of the rock are pushed inward. You can remember that a syncline creates this type of fold because the fold sinks downward, which sounds like syncline. A monocline is a fold where the rock layers form an S shape as the sides of the rock are compressed. You can remember this type of fold because all the layers of rock are still horizontal, going in one direction instead of bending vertically upward or downward like anticlines and synclines. And since mono means one, monoclines are layers in only one direction. We also have domes, which are like anticlines, but instead of an arch, the fold is in a dome shape, like an inverted bowl. Similarly, there are also basins, which are like synclines, but again, instead of a sinking arch, the fold is in a shape of a bowl, sinking down into the ground. Not only do folds come in different shapes, but they also form at different angles. Symmetrical folds are folds with the same angle. This makes sense, since symmetry means the same on both sides. We can also have the reverse of symmetrical, which occur in asymmetrical folds, or folds with different angles. Isoclinal folds are similar to symmetrical folds, but these folds both have the same angle and are parallel to each other. Iso means the same, symmetrical, and cline means angle, so this name literally means same angle. So isoclinal folds are both symmetrical and aligned in a parallel fashion. Overturned folds occur when the folding is so intense that the fold appears to have turned over on itself. Similarly, we can have recumbent folds, which are even more extreme than overturned folds. These are folds that are nearly horizontal. Recumbent means lying down, so you could think of this fold as lying down sideways. Finally, we have chevron folds, which are folds in a zigzag pattern. The angles of the folds are shaped like chevrons, and instead of slowly curving, the edges are sharp and straight. Folds, which occur when rock deforms in such a way that it bends instead of breaking, come in all shapes and sizes. An anticline is a fold that creates an arch. This arch looks like an A, which is the same letter that anticline begins with. The reverse, a syncline, is a fold that sinks down. Syncline and sync both start with sync to help you remember this one. A monocline is a fold that creates an S shape. Mono means one, and this type of fold lives up to its name since all the rock layers stay layered in one horizontal direction. A dome is a fold that creates a dome shape in the ground, similar to an anticline, but sort of circular instead of an arch. A basin, the reverse of a dome, is a fold that creates a bowl shape in the ground, similar to a syncline, but again circular instead of an upside-down arch. Folds can also be classified based on their angle. Symmetrical folds are folds that have the same angle, and asymmetrical folds are folds that do not have the same angle. This makes sense since symmetrical means same and asymmetrical means not the same. Isoclinal folds are folds that are both symmetrical and parallel. These folds not only have the same angle, but are vertically aligned in a parallel orientation. An overturned fold is a fold that appears to have turned over on itself, just as the name implies. A recumbent fold takes this one step further and is a fold that is nearly horizontal. Recumbent means lying down. And finally, we have chevron folds, which are folds in a zigzag pattern. These folds are shaped just like chevrons, which is how they got their name. Instead of being rounded, these unique features have sharp edges and straight lines. The surface of Earth is like a giant puzzle, and all the pieces that make up this puzzle are called tectonic plates. Although these giant rock puzzle pieces fit together very nicely, they don't stay in place because they're floating on the layer below us, the mantle. This layer is like the consistency of silly putty, sort of like a liquid and yet sort of solid too. The plates float around on the mantle like ice floats on a pond. The movement of the plates is incredibly slow, but since the plates are so big, When they bump into and rub against each other, we get massive events like volcanoes and earthquakes. And along these plate boundaries we find faults. Faults are cracks in the Earth's crust where movement occurs on at least one side. So in order for a crack in the ground to be a fault, one side or the other has to move, but sometimes both sides move too. Faults are classified by how they move, and there are three main types of stress that cause movement along faults. The stress occurs because, as mentioned before, the plates fit together really well, but also float around on the mantle and rub against each other. Tensional stress is when slabs of rock are pulled apart. Imagine stretching a rope out all the way and then continuing to pull on it from both ends. You're putting tension on the rope because it's being pulled in opposite directions. The same is true for tensional stress in rocks. Compressional stress is when slabs of rock are pushed together. They are literally being compressed into one another. This is like when two cars crash into each other. They're compressed into smaller, crumpled versions of what they were before. Shear stress is when slabs of rock slide past each other horizontally in opposite directions. The rocks are not smashed into each other or pulled apart, but their edges slide along each other with a lot of friction. This is like when you rub your hands together to warm them up. One hand goes forward and the other goes backward, rubbing against each other. The type of fault we get depends on the type of stress that caused it, which also tells us about how the fault moves. Faults have two sides, the hanging wall and the footwall. These terms were coined by miners because you can stand with your feet on the footwall and hang a lamp on the hanging wall on the opposite side, and the reverse situation would be impossible. Tensional stress, meaning rocks pulling apart from each other, creates a normal fault. With normal faults, the hanging wall and footwall are pulled apart from each other, and the hanging wall drops down relative to the footwall. Most of the area just west of the Rocky Mountains is affected by normal faults. Places like southern Oregon, southwestern Idaho, eastern California, western Utah, and the entire state of Nevada. Compressional stress, meaning rocks pushing into each other, creates a reverse fault. In this type of fault, the hanging wall and footwall are pushed together, and the hanging wall moves upward along the fault relative to the footwall. This is literally the reverse of a normal fault. The Rocky Mountains, the Canadian Rockies, and the Appalachian Mountains are all examples of the types of features created by reverse faults. Shear stress, meaning rocks moving horizontally against each other, creates strike-slip faults. There's no vertical movement of either the hanging wall or footwall, just horizontal movement of each side of the fault. You can think of this like striking a match. You have to strike it horizontally along the strip to get it to light, and once it does that slip, you get a sudden flame. Strike-slip faults are very similar. They slide past each other, and at the right moment, if there's enough friction that they get stuck, they suddenly slip apart, causing very powerful earthquakes. The San Andreas Fault that runs through California is one of the most famous strike-slip faults in the world because it's so large and causes so many earthquakes. Earth's crust is broken up into tectonic plates, which are like giant puzzle pieces made of large slabs of rock. The places where movement occurs along the plate boundaries are called faults. Faults are the large cracks between plates, but not just any crack can be a fault. There has to be movement along at least one side of it. Three types of faults are caused by three types of stress. Tensional stress is when rock slabs are pulled apart from each other, causing normal faults. With normal faults, the hanging wall slips downward relative to the footwall. Compressional stress is when rock slabs are pushed into each other, like cars in a head-on collision. This causes reverse faults, which are the reverse of normal faults because in this case, the hanging wall slides upward relative to the footwall. Shear stress is when rock slabs slide past each other horizontally. There's no vertical movement of either the hanging wall or footwall, and we get a strike-slip fault. These rocks move like your hands do when you rub them together to warm up. The movement along faults is what causes earthquakes. Some faults are more active than others, like the strike-slip San Andreas Fault that runs the length of California. Others are known for their mountainous masterpieces, like the reverse fault activity that created the Rocky Mountains in North America. Mountains are magnificent and inspiring features. Just thinking of mountains conjures up beautiful images of places like the Rockies, the Andes, Hawaii, and the Alps. But not all mountains are the same. Though they all take a very long time to form, mountains are created in different ways depending on where they are on Earth. Some mountains are created by land pushing together, while others are formed over hot spots on Earth. Let's take a closer look at the mountain building process to better understand how these incredible structures come to be. The most common type of mountain is a fold mountain. Fold mountains form when continental tectonic plates are pushed together, like the Himalayas in South Asia. Tectonic plates make up the Earth's crust, both the continents and the ocean floor, and are like puzzle pieces floating around on the mantle below. They move around very slowly, but sometimes push into each other along their edges. When this happens, the intense pressure of the edges pushing together forces the plate material upward since there's nowhere else for it to go. This would be like you taking two pieces of bread and sliding them across a surface into each other from opposite directions. As the edges of the bread are compressed together, they rise upward, forming a sort of bread mountain. Sometimes oceanic plates run into continental plates, and when this happens we also get mountain formation, but it's a bit different because the oceanic crust is much denser than the continental crust. Because of this, the oceanic crust sinks down below the continental crust, a process known as subduction. The crust material gets heated and then rises to the surface as magma, pushing upward and forming a volcano. As volcanic eruptions spew their material out, the material builds up around the ground, forming the mountain itself. This is why we find many of the world's volcanoes along oceanic continental boundaries, like the area known as the Ring of Fire. Oceanic plates may also collide with other oceanic plates, and when this happens, the older one is subducted under the younger one because the older one is denser. This type of plate compression results in a volcanic island arc. As the name implies, these are mountainous islands made of volcanoes. Japan is one such set of mountainous islands along oceanic plate boundaries in the Pacific Ocean. Not all volcanoes and mountains are along plate boundaries. Some mountains form when magma pushes upward on Earth's crust from underneath. Like with fold mountains, the land has nowhere to go but up, so upward as a mountain it goes. If the magma makes it through to the surface, this creates a volcano. But sometimes the magma never reaches the surface, in which case we get a dome mountain. Both the Black Hills in South Dakota and the Adirondacks in New York are examples of dome mountains. Other mountains are formed in the middle of ocean plates, and a great example of this is Hawaii. The islands of Hawaii were formed over a hot spot on Earth. This is a place where magma pushes upward through the crust as the surface moves over it. It's like a conveyor belt of mountain building. Imagine you had a large flame under a moving belt, and on the belt you had objects like pieces of chocolate. Each piece would be heated, and probably pretty melted, as it moved over the flame, but it would cool and harden as it moved away from it. Hotspots work the same way. They build volcanic mountains as the land moves over it, forming a long chain of islands. So the northwest islands of Hawaii are actually much smaller and older than the ones nearer to the hotspot. We can also get mountain formation due to large-scale erosion. These erosional mountains, sometimes called plateau mountains, are large areas of land that are already higher than the surrounding ground, but don't start out in the shape of a typical mountain. Over many, many years, wind and water wear down parts of the land, leaving behind large mountain peaks. Pikes Peak in the Rockies is an example of a mountain created by erosional forces. Finally, we have fault block mountains. These are formed when large blocks of earth are forced upward along faults. Faults are just large cracks in the surface of Earth, and sometimes they tilt upward, creating large areas of elevated land. Because of this, one side of the fault block mountain is quite steep, while the other side slopes downward more gently. The part of the land that is raised during the process is called a horst, and the valley below it is called a graben. The Sierra Nevada mountain range in the western U.S. is an example of fault block mountain formation. Mountains are some of the most awe-inspiring features on Earth and are found on every continent and even in the oceans. They come in many different shapes and sizes and are formed in a variety of ways. The mountain building process takes a very, very long time because it takes a lot of work to move that much land. Fold mountains form when continental plates are pushed together. The land gets forced upward as a mountain because it simply has nowhere else to go. If an oceanic plate is involved in the plate compression, volcanoes tend to form because the denser plate is subducted under the plate that is less dense. As the volcano spews out ash, rock, and hot lava, this material builds up around the opening, creating a mountain on the surface. Volcanic mountains can also be formed over hot spots, which is where magma pushes up through Earth's surface as the land moves over it. Dome mountains are similar to volcanoes, but this time the magma does not reach Earth's surface. In this case, the land is forced upward from below, but the magma doesn't come up like it does with a volcano. Erosion also helps create mountains, and erosional mountains are formed when wind and water wear away elevated land over long periods of time. Finally, fault block mountains form when large blocks of Earth are forced upward along faults. Faults are just large cracks in the surface of Earth, and sometimes the land around them gets tilted upward, creating a stretch of mountains along the fault. Believe it or not, groundwater, or water below the surface, makes up most of Earth's liquid freshwater. All of the streams, lakes, rivers, and ponds, so all of the Great Lakes, the Mississippi, the Amazon, the Nile, and all of the other fresh surface water, only make up 1% of Earth's liquid freshwater. Water gets underground because when it precipitates, like with rain or snow, the ground soaks up the falling water like a sponge. Some soils are better at absorbing groundwater than others. Sand, for example, is really good at soaking up water, and you've seen this if you've ever been to the beach. Clay, however, is not very good at taking in water, and rocks are even worse. Where groundwater completely fills any open spaces underground is called the saturated zone. It's literally saturated with water. There is space above this in the soil where moisture exists, but it doesn't completely fill all of the open spaces. The water here is called soil moisture, and this region where the soil is not saturated is called the unsaturated zone. You can tell where these two meet if you dig a hole. Once the hole hits the saturated zone, you'll see the bottom fill with water, and this boundary where the saturated and unsaturated zones meet is called the water table. Groundwater is an important component of the water cycle, which is the natural cycling of water through phases and locations on Earth. The water that soaks into the ground sometimes comes back out above ground in other locations, feeding the world's rivers, lakes, streams, and oceans. Much of the world's groundwater is stored in aquifers, which are underground water reservoirs, usually made of rock like limestone. The limestone acts like a giant rock sponge, soaking up the water and holding it for thousands of years. One of the world's largest aquifers is the Ogallala Aquifer in the Great Plains of the U.S. This aquifer is one large connected system, stretching from South Dakota to Texas and from Colorado to Arkansas. Because aquifers hold so much water, they take a very long time to fill, sometimes thousands or even millions of years. Groundwater also acts like a cementing agent, helping sedimentary rocks form. As it moves, it carries sediments along with it, and then over millions of years, the water glues those sediments together into rocks. Geysers are the result of groundwater. If the water underground is above a near-surface magma source, this magma underneath heats the water. As the water heats, the pressure builds up, sometimes escaping at the surface. When this happens, the result is the same as heating a kettle of water on the stove. Steam escapes through a small opening in the surface, and we get a geyser like Old Faithful. Natural ecosystems depend on groundwater because, as mentioned before, it's a source of fresh water for surface water systems like wetlands and rivers. Both plants and animals depend on groundwater because plants take it up through their roots in the soil, and animals, like us, use it as a source of drinking water. We pump groundwater not only for drinking, but also for things like agricultural irrigation. The problem is that, as mentioned before, it takes a long time to fill or refill an aquifer. So if we pump too much groundwater out, the land can be affected in various ways. Sinkholes are funnel-shaped cavities in the ground. They are literally holes that occur from the ground sinking. Groundwater holds the land underground in place, and when it's removed, that ground just sinks downward to fill the empty space. Sinkholes can be small or can be very large, like Lake Eola in downtown Orlando. Once a sinkhole, Lake Eola has since been turned into a park in the middle of the city, and this open-air ground hole is an incredible 23 acres in size. Groundwater also dissolves rock underground, creating caves. Caves are large open spaces underground, so similar to a sinkhole but without the sinking of the ground above. Caverns are very large caves, and these are especially amazing because they sometimes connect to other underground caves and caverns through underground tunnel systems that are many miles long. There is a lot of water below the surface, which we call groundwater. In fact, most of Earth's liquid freshwater is underground, so if you add up all of the Great Lakes, all of the large rivers like the Mississippi and the Amazon, and all of the other lakes, rivers, and streams, you wouldn't even come close to the amount of water below us. There are two regions underground called the saturated and the unsaturated zone. The saturated zone is saturated with water. The unsaturated zone sits on top of the saturated zone and contains soil moisture. Like its name, this part of the ground is not completely saturated with water. Where these two zones meet is called the water table. If you dug a hole deep enough to reach the water table, you'd have a hole filled with water at the bottom. Groundwater plays an important role in the water cycle, in natural ecosystems, and in land formations on Earth. It's stored underground in aquifers, which are underground water reservoirs. Like giant rock sponges underground, these are often made of limestone and take thousands or millions of years to fill. As groundwater moves underground, it carries sediment with it, which acts like a cement, gluing these sediments together and forming sedimentary rock. It may also get heated up underground by near-surface magma, pushing out steam like a tea kettle on the stove when the pressure finally becomes too much. If groundwater is removed, which happens when we pump it out for things like drinking water and agriculture, it leaves behind an empty space. Sometimes the ground sinks down to fill this open space, creating a sinkhole. These funnel-shaped holes in the surface can be large or small, depending on the amount of water removed. Groundwater can also dissolve rock underground, which is what forms caves and caverns. These are large open spaces underground. Some cave systems are connected over many miles, like a large underground highway extending from one cave to the other. When you think of moving water, you likely think of babbling brooks, flowing streams, or raging rivers. Water moves on the surface quite easily, but it also moves underground as well. Groundwater, which is water below Earth's surface, doesn't flow in quite the same way as it does on the surface, but it still gets around. How water moves underground depends on several factors. One factor that influences how groundwater moves is the porosity of the soil. This is the amount of water the soil can hold. You can think of porosity as the spaces between particles, much like the spaces in a jar of jelly beans. All of those nooks and crannies in between the pieces of candy are the pores. The larger the open spaces, the more porous it is. The size and shape of the soil particles determine porosity in this same way. When particles are about the same size and shape, there tend to be larger open spaces since the particles don't fit together very well. Clay and sand are both very porous materials for this reason. On the other hand, sediment like limestone is less porous because the particles fit together like puzzle pieces, closing up those pores. What does this have to do with groundwater? Well, the more porous the sediment, the more water it can hold. The more water it can hold, the more water can move down into the ground. Porosity tells us how much water the soil can take in, but not how fast it does so. We call the rate of water infiltration into the ground permeability. To better understand this, think of a sponge and a rock. A sponge is very permeable because it absorbs water very quickly. A rock, on the other hand, is not very permeable because it really doesn't absorb water very well at all. Soil is the same way. Some sediments easily absorb water while others do not. Remember how clay was very porous? Turns out that even though it can hold a lot of water, it's not very permeable, so it takes a long time to absorb it. Sand, on the other hand, is both porous and permeable. It can hold a lot of water and is happy to take it in. Limestone is a tricky one though, because it is very permeable but not very porous. So it will absorb water very well, but its capacity is not as large as something like clay or sand until it starts absorbing water. Water dissolves limestone easily, so as it is absorbed, it creates new holes inside, making it more porous as time goes on. In fact, most of the world's aquifers are made of limestone for this very reason. There's one more important factor in groundwater movement, and that's gravity. Gravity doesn't just pull objects down to the surface of Earth, it also pulls some things down through the ground. All water flows downhill because gravity causes it to do so, so both surface and groundwater flow from high to low. However, with groundwater, it moves depending on the elevation of the water table. This is where the ground is saturated with groundwater, sort of like the surface of a lake or stream, but underground. Groundwater moves from where the water table is high to where it's low, and this downward slope of the water table is called the hydraulic gradient. The other difference between surface water and groundwater is that surface water has to travel through channels. It's like the bumper lanes at the bowling alley. Your ball is confined to that lane and that lane only. There aren't channels underground though, so groundwater moves through open pores in the soil. Groundwater also doesn't move as fast as surface water. It's like the difference between skiing downhill with no trees versus skiing through a thick forest. However, that doesn't mean that groundwater is any less powerful as it makes its way through the ground. Groundwater gets around. It moves underground, trickling through soils and sediments. Unlike surface water, it doesn't flow through open channels, rather it flows through spaces in the ground called pores. The size of the pores underground is called porosity. Soils and sediments that have similar sized particles like clay and sand are very porous because those sediment pieces don't pack together very tightly and leave a lot of open space. Groundwater flow also depends on the permeability of soil, which is the rate of water infiltration into the ground. It's like the difference between pouring water onto a sponge versus a rock. The sponge is very permeable because it quickly absorbs the water. The rock, however, is not very permeable because it doesn't absorb the water at all. Gravity also plays a major role in groundwater movement because it pulls water down the hydraulic gradient. This is the downward slope of the water table underground, much like surface water gets pulled downhill from high to low elevations. So you can see that all three factors are important to the movement of groundwater. Porosity is where groundwater can flow, and permeability and gravity, the hydraulic gradient, determine how fast it can get there. I'll bet that if you look at a bottle of water, it claims to be natural spring water. While this may or may not be true, what exactly do they mean by spring? Well, spring is a place where water naturally flows out of the ground. This comes from the German word Springer, which means to leap from the ground. One reason you may want to be skeptical about that natural spring source is that springs are not common enough on Earth to support the enormous bottled water industry. In fact, while they are an important part of both the water cycle and the ecosystems they're found in, they're actually somewhat rare. In another lesson we learned about groundwater, which is water below Earth's surface. Groundwater is stored in aquifers, which are underground water reservoirs. Aquifers hold billions of gallons of water and feed water bodies on the surface like lakes and rivers. However, because they're so large and can hold so much water, it can also take thousands of years for aquifers to recharge if the water is removed in large quantities. There are two types of aquifers, confined and unconfined. Confined aquifers are sandwiched between two layers of low permeability soil. This means that the water coming into the ground does not flow directly into or out of the aquifer since the soil around it doesn't allow much water to pass through. All aquifers are at least partially unconfined aquifers because they wouldn't be filled with water if they didn't have a source feeding them. These aquifers are underneath permeable soil layers, so water easily trickles through the ground into the aquifer. A spring is formed when the pressure in an aquifer causes some of the water to flow out at the surface. This usually happens at low elevations, along hillsides, or at the bottom of slopes. Some springs are just tiny trickles of water seeping from the ground, while others are large enough that they create rivers or lakes. Springs are named for how they flow, and there are 5 main types. The first type of spring is a gravity spring. This is just what it sounds like. These form from the pull of gravity. The water gets pulled down through the ground until it reaches a layer it can't penetrate. Because it has nowhere else to go, it starts flowing horizontally until it reaches an opening and water comes out as a spring. These are usually found along hillsides and cliffs. Next, we have artesian springs, which come from pressure in confined aquifers forcing the water to the surface. The pressure inside the confined aquifer, from being smushed between those impermeable layers, is less than the pressure outside the aquifer, so the water moves in that direction. Any cracks or holes in the land will easily let the water escape. Our next type of spring is a seepage spring, which, as you may have guessed, is groundwater seeping out at the surface. Seepage springs slowly let water out through loose soil or rock and are often found in land depressions or low in valleys. The fourth type of spring is a tubular spring. These springs occur in underground cave systems, which resemble underground highways. These tubes or channels are made of limestone, and as water moves through this type of rock, it dissolves some of it away. Tubular springs are some of the largest springs on Earth, and the tubes themselves can be so small that you can't see them or large enough to walk through. Finally, we have fissure springs. Fissures are just large cracks, so you can probably figure out that fissure springs occur along large cracks in the ground like fault lines. Fissure springs are often used as a source of drinking water, and sometimes scientists go looking for fissure springs when they want to find a fault on Earth. Not only do springs come in different forms, but they also come in different sizes. They are classified based on how much water they discharge, called the magnitude. There are 8 magnitudes used to classify springs, 1 being the largest and 8 being the smallest. First magnitude springs put out an incredible amount of water, more than 100 cubic feet per second. That means that every second that spring is pumping out more than 100 1-foot by 1-foot by 1-foot cubes of water, or 64.6 million gallons of water per day. That's a lot. Fourth magnitude springs, which are mid-sized in terms of water discharge, still pump a lot of water. These springs discharge anywhere from 144,000 to 646,000 gallons per day. Even 8th magnitude springs are impressive, discharging up to 1 pint of water per minute, or about 200 gallons per day. You can see why springs are so important to our surface waters. Without them, they'd run dry. Springs are areas where water naturally flows from the ground. They come in many different forms and sizes, but they all have the same source, aquifers. These underground water reservoirs come in 2 types, confined and unconfined aquifers. Confined aquifers are just what they sound like. They're confined. They're sandwiched between 2 layers of soil that doesn't let much water through, which puts a lot of pressure on the water in the aquifer. All aquifers are at least partially unconfined, otherwise they wouldn't be full of water. The unconfined portion of an aquifer is where it sits below permeable soil, which allows water to filter through the ground into this special type of holding area. Based on how they flow, springs are categorized into 5 different types, and the name tells you how or where the water is flowing. Gravity springs are formed by gravity. The water is pulled down through the ground until it can't go any farther, so it moves horizontally until it reaches an opening, usually on the side of a hill or cliff. Artesian springs come from the pressure in a confined aquifer. The weight of the world is sitting on its shoulders, and sometimes that's just too much pressure for the aquifer, and the water comes out of the ground. Seepage springs slowly seep water from the ground, usually in low areas like depressions and valleys. Tubular springs are made of limestone and occur in underground cave systems. These tubes connect the cave systems underground like a giant highway, though some of the tubes are so small you can't see them with your eyes. Fissure springs occur when groundwater comes out through large cracks in the ground, known as fissures. Faults are a great example of fissures, and sometimes these springs can even help scientists identify fault lines on Earth. Springs are also classified by their size. Their magnitude, or how much water they discharge, helps us understand how important springs are to surface water bodies. The largest, a first magnitude spring, discharges an incredible 64.6 million gallons of water per day. Even the smallest spring, an 8th magnitude spring, can discharge up to 200 gallons of water per day. While this may not sound like a lot, think about this. In order to drink 200 gallons of water, you would need to drink 8 glasses of water each day for 400 days straight. That is no small feat. Have you ever tried to dig a hole at the beach just to have it keep filling up with water? Or maybe you thought you could dig a hole to China through your backyard, again, just to find that at some point your hole started filling with water. In both instances, you couldn't get too far because you had reached the water table. This is the level underground that is saturated with water. As we learned in another lesson, this water is called groundwater, and it makes up almost all of the liquid fresh water on Earth's surface, 98.5% of it. Access to the water table has always provided an important source of drinking water, most often through wells. A well is a human-made hole in the ground specifically used for accessing groundwater. Wells come in different shapes and sizes, but their use is generally the same. In fact, for many people in both developed and developing countries, well water is still the main supply of water for home uses, irrigation, and drinking water. Groundwater is even more important in areas that lack surface water, such as deserts. There are 3 main ways that wells are created. Originally, all wells were dug wells. These are wells that are created by digging it out by hand. Wells are rarely made this way anymore because, let's face it, who wants to spend all day digging a hole in the ground with a shovel? Dug wells are dug down below the water table and lined with a material like stone or brick. This helps support the well and keep it from collapsing. Driven wells are much more common in today's society than dug wells because they are wells that are created with a small pipe driven into the ground. The pipe has a filter over the bottom to keep out as much sediment as possible, and that pipe is driven down into the ground until it reaches the water table. Once the well is deep enough, all of the dirt is washed out of the inside of the pipe and a pump is installed so that water can be removed from the well. Finally, we have drilled wells. These are how most modern wells are created because these wells are created by digging a hole in the ground with machinery and can reach deeper into the ground than both dug and driven wells. A large bit drills into the ground, much like your drill creates a hole in your wall for hanging a picture. These wells can be drilled more than 1,000 feet deep. Pumps are used with drilled wells too, since it would take a really long rope to reach a bucket down that far. There is one more type of well, but this one is special. Groundwater is usually held underground in a reservoir called an aquifer. Normally, an aquifer gets filled with water when rainwater soaks into the ground and collects in these underground locations. This is called an unconfined aquifer because it is not confined as it is open to receiving water through the soil above. All the wells you have learned about in this lesson are wells that tap into unconfined aquifers in the ground. Sometimes, though, an aquifer is below an area of ground that doesn't let water soak through. When this happens, we call this a confined aquifer because it is confined under an impermeable layer of soil. All aquifers are unconfined in some location, otherwise they wouldn't be able to fill with water. The water in a confined aquifer is under a lot of pressure. This is because it is below the water table, so the weight of the ground and water above create pressure underneath. This pressure causes the water to flow out through openings at lower elevations. When this opening into the confined aquifer is natural, this is an artesian spring. However, when the opening is human-made, this type of well is known as an artesian well. Sometimes the water in an artesian well flows out at the surface, and when this happens, we call it a flowing artesian well. The word well likely brings certain images to mind, even if you have never used one. A well is a human-made hole in the ground specifically used for accessing groundwater, and though they generally have the same purpose, there are different ways that wells can be created. Dug wells are just what they sound like, wells that are dug by hand. Because they take so much work, these types of wells are fairly rare anymore. Driven wells are wells that are created by driving a pipe into the ground. The pipe is hollow so that once the sediment is cleared from it, the water can be pumped from the ground down below. Drilled wells should bring to mind an image of drilling a hole in your wall for a shelf or painting, because these are wells that are created by drilling a hole deep into the ground with large machinery. These are the most common types of wells because they can reach very deep, sometimes more than 1,000 feet into the ground. Artesian wells are a special kind of well because these are wells that are dug into a confined aquifer. The water in a confined aquifer is under a lot of pressure from the ground and water table above it and is looking for a way to escape. If it escapes enough that it flows out at the surface of the ground, we call this a flowing artesian well. Groundwater is one of our most important natural resources. It provides us with much of the water that we use for drinking water, household uses, crop irrigation, and many other things. In fact, over 1/3 of Earth's population relies on groundwater for its needs, including 99% of the rural population in the U.S. But just because it's underground doesn't mean that groundwater is safe from many of the same environmental issues that surface water faces. In fact, being underground makes it more vulnerable to environmental issues because we can't easily access it for testing, regulating, and cleaning. Groundwater also moves around a lot, not only underground, but also as a source of discharge into Earth's streams, rivers, lakes, and oceans. Pollution is one of the main environmental issues that groundwater faces. Groundwater pollution comes from many sources, and this happens when harmful substances get into the soil. When it rains, water washes over the substances in the ground and carries them down into aquifers below, much like hot water does when you pour it over a filter full of coffee. Agriculture pollutes groundwater as fertilizers, pesticides, and herbicides soak into the ground. Nitrates from the fertilizers are especially dangerous in drinking water because they've been linked to various cancers, miscarriages, and birth defects. Manufacturing industries are also major culprits. There are often many different toxic chemicals involved in manufacturing the products that we use, and if not properly disposed of, they may leach into the ground, soaking down into the groundwater below. Underground storage tanks like septic tanks can also leak sewage waste, oil, and toxic chemicals into the ground. Groundwater can be depleted much faster than surface water because aquifers take a very long time to refill. Groundwater is pumped from wells for drinking water, but is also pumped for large-scale uses like agricultural irrigation. This water is removed from the ground at a very fast rate and then moved to another location to water large areas of crops. The water doesn't get returned to the ground in the same place, so even as it slowly sinks back down into the soil, it doesn't go directly back into the aquifer it came from. You can think of the world's aquifers like a bank account. You can take out as much as you like as long as you're making deposits that cover your withdrawals. Unfortunately, we're not depositing nearly as much water as we're withdrawing, so our account is quickly dwindling down to a dangerously low balance. Overdrawing groundwater not only means that we may run out of water to pump, but it also allows salt water to intrude into aquifers along coastal areas. Have you ever accidentally swallowed some seawater? Imagine that your aquifer has become salty from ocean water intruding. Still want to use it for your drinking water? Probably not. Overdrawing groundwater also leads to another problem called subsidence. This is when the ground sinks down to fill the space below. You can think of groundwater like an inflated balloon below ground. This balloon is filling up some space below the surface, and then you quickly let the air out of it. Everything around where that balloon was will sink in to fill the newly opened space. The same thing happens with the land around groundwater when water is removed too quickly. Subsidence can occur as sudden small holes, like the sinkholes we learned about in another lesson, or it can occur over a large area like an entire city. In fact, Mexico City, one of the largest cities in the world, has slowly sunk more than 33 feet because of subsidence. In this city, you'll find buckled streets, buildings that tilt and lean, much like the Leaning Tower of Pisa, and broken underground pipes. Groundwater is very important to us, but it faces several environmental problems that put both us and the environment at risk. Because groundwater is out of sight, problems often go unseen, unmonitored, and untreated. Groundwater pollution is a serious problem because many people get their drinking water from wells. Agriculture, manufacturing, and underground storage tanks are just a few of the harmful substances that enter the ground and percolate down to aquifers below. Overdrawing groundwater is much like overdrawing your bank account. Unless you put in more than you spend, you'll quickly find that you've got nothing left. Aquifers take a very long time to refill, and we're pumping groundwater out much faster than it is going back in. Overdrawing aquifers along coastal regions also allows seawater to intrude, making that water unavailable for drinking. Subsidence, which is when the land sinks down due to overdrawing groundwater, can come suddenly as sinkholes or can slowly wreak havoc on large areas. Like deflating the space below, pumping too much groundwater leaves a void that gets filled by the ground above, slowly sinking into it. Many cities are facing this problem, which can destroy buildings, roads, and underground pipe systems as the land falls in. As we learned in another lesson, groundwater is water below Earth's surface. Groundwater is an important part of the water cycle because it is where rainwater and snow end up after they hit the ground, soaking down into the soil. Once in the ground, this water either stays there for a very long time or it discharges into streams and rivers, keeping them flowing smoothly. Though water may look simple, do not be fooled. Water is a very powerful substance. When water moves underground, it can drastically change the landscape, like when it creates sinkholes and caverns. Sinkholes are funnel-shaped holes in the ground, and caverns are large open spaces underground. Groundwater is important not only to the water cycle, but also to us. We pump groundwater for a variety of uses, like crop irrigation and drinking water. However, groundwater also acts like a support system for the ground, similar to how the bones in your body provide you with support. If you suddenly removed all of your bones, you'd fall to the ground like a big pile of mush. The same happens when too much groundwater is removed too quickly. The ground collapses into the open space below, and the result is a sinkhole. Sinkholes come in all shapes and sizes. Some are small and simply look like dips in the land, while others are so large that entire city blocks collapse into the ground. Water is not the only important structure underground, though. The soil and sediment also play an important role. Sometimes groundwater dissolves these sediments, leaving little left to support the ground above. Just like with removing too much groundwater, the ground sinks down into the empty space, which is exactly why they're called sinkholes, and fills the void left where the sediment stood before. When the land surface lowers into the ground like this, we say that the land has subsided. Subsidence not only creates quickly falling sinkholes, but can also cause large-scale land sinking over long periods of time. For example, the Leaning Tower of Pisa leans because it was built on unstable land, and as the soil underneath it compacted and sank into the ground, the tower began to tilt. In the U.S., extreme groundwater pumping in the San Joaquin Valley of California caused the water table, or the area below ground where it's saturated with groundwater, to sink 245 feet over 50 years. The land on top simply couldn't help but sink with it, and over that same period of time dropped 30 feet. Caverns form in much the same way that sinkholes do. Sometimes when groundwater dissolves sediment underground, it simply leaves a big hole, and the ground above doesn't fall in. These holes are caverns. Groundwater is stored in underground reservoirs called aquifers, which get dissolved by rainwater as it soaks into the ground. Cracks develop in the aquifer, and as time goes on, those cracks get larger and larger, forming channels underground. Eventually, they may get so large that they form underground rivers, connecting caves and caverns like a giant highway beneath the surface of the earth. Caverns are not only cool because they are underground, they're about 55 degrees Fahrenheit most of the time, but they also have some really unique features. Since water is soaking in from the ground above, some of it drips from the ceiling and leaves behind stalactites, which are icicle-shaped structures made of precipitates. The water that filters through the ground is filled with tiny sediment particles, the precipitates, and as the water evaporates into the cavern, it leaves behind these particles, forming the stalactite. Just like water may drip off the end of an icicle, water also drips off the end of stalactites and collects on the ground below, forming cone-shaped stalagmites. You can remember which is which because stalactites have to hold on tight to the ceiling, while stalagmites are mighty secure on the ground. Groundwater is powerful stuff, providing support underground for the land above. If too much groundwater is removed, it leaves behind empty space under the surface, sometimes causing the ground to collapse in on itself. This land sinking down is called subsidence, and if it leaves a funnel-shaped hole open to the sky and the surface, we get a sinkhole. Sinkholes may also be caused by groundwater dissolving the sediment underground, which is also how caverns are formed. Caverns are large open spaces underground. If the sediment is dissolved so much that it creates channels underground, caverns may become connected through underground rivers, much like a highway connects different cities. We find some very unique features in caves called stalactites and stalagmites. These form when water drips through the cave ceiling and either collects like an icicle on the top or drips to the bottom, forming a cone. How can you tell which is which? It's all in the name. Stalactites have to hold on tight to the ceiling, while stalagmites have it good. They are mighty secure on the ground.
A stream is a continuous flow of liquid through a channel, for example a creek or river. Streams and rivers in the real world are constantly changing. They wear away or erode at the banks and start to wind left to right. They erode at their beds and get deeper, or even deposit soil from other parts of the landscape and get shallower. A stream can change direction, change size, and even change how steep the land is. But theoretically, there could be a point where all these factors balance out, where a river stays pretty much the same because everything is perfectly in balance, or in equilibrium. A river that is perfectly balanced in this way, where its profile isn't changing, is called a graded stream. There are many factors that affect how much erosion happens around the flow of a river. The speed of the current is a factor. Faster currents erode more of the soil and rock and can carry larger particles with them. The size of the stream is also a factor. Larger streams can carry more material at any one time. Both these factors are then, in turn, affected by how steep the land is. As the river winds back and forth, the water may get pushed against a particular bank of the river more heavily than another, and this causes that side of the river to get worn away and more materials to be deposited on the opposite side. This is what makes a river change direction. Some parts of the river are erosion dominant, meaning that more material is being eroded than deposited. This part of the river is gradually getting larger. Other parts of the river are deposition dominant, meaning that more material is being deposited than eroded. In that case, the river is getting smaller. All these factors combine together to affect how the river is changing at any given moment. Over time, the river becomes increasingly balanced. The factors that make a river larger and the factors that make it smaller balance out. This is when it becomes a graded stream. Though no river in the real world is really graded, rivers are always changing. If the conditions stay the same for long enough, a river may eventually be stable enough that changes happen slowly. One of the ways this happens naturally is related to how the river flows. A river passes a certain amount of water every second, a certain number of gallons. This amount of water must be consistent along the river, otherwise you would get gaps in the river. Because of this, the fastest parts of the river tend to be the smallest, thinnest areas, and the slowest parts of the river are the larger, wider areas. Water flows faster down steeper slopes, and water flows slower down shallow slopes. So when we look at rivers, we notice that the fast, thin parts of the river tend to be over steep land, and the wider, slower parts over flatter land. But why is it like this? Well, the faster, thinner, and steeper parts of the stream erode a lot of material, but the slower, wider, and shallower parts of the stream deposit more material than they erode. The steeper areas will tend to get worn away, making them larger, and the shallow areas will tend to build up, making them smaller. But as they change in size, so does the amount of erosion or deposition. These factors balance out with each other, leading to an optimum size for the river at each point. Eventually, you end up with a gradual change from steep streams at the start of the river's path in the mountains to wider, flatter streams towards the end of its path. Once this theoretical balance is reached, the river will not change. If more material is deposited in the wider part, erosion will become dominant and wear it away again. If more material is eroded in the steep part, deposition will become dominant and build it back up. It has become a graded stream. A stream is a continuous flow of liquid through a channel, for example a creek or river. Streams and rivers in the real world are constantly changing. They wear away or erode at the banks and start to wind left to right. They erode at their beds and get deeper, or even deposit soil from other parts of the landscape and get shallower. A stream can change direction, change size, and even change how steep the land is. But theoretically, there could be a point where all these factors balance out, where a river stays pretty much the same, because everything is perfectly in balance, or in equilibrium. A river that is perfectly balanced in this way, where its profile isn't changing, is called a graded stream. There are many factors that affect how much erosion happens: the speed of the current, the size of the stream, and how steep the land is. Some parts of the river will be erosion dominant, meaning that more material is being eroded than deposited. This part of the river is gradually getting larger. Other parts of the river are deposition dominant, meaning that more material is being deposited than eroded. In that case, the river is getting smaller. Over time, the river becomes increasingly balanced. The factors that make a river larger and the factors that make a river smaller balance out. This is when it becomes a graded stream. Though no river in the real world is really graded, rivers are always changing. If the conditions stay the same for long enough, a river may eventually be stable enough that it approaches this ideal. A river that is graded will start out steep and small, and gradually get wider and less steep as it runs its course, in a nice smooth pattern. This creates a balance, where the steep parts can't get less steep, and the flatter parts can't get less flat. And this is what we call a graded stream.
The Earth's surface is constantly being broken down and reshaped. This can be accomplished by many factors, most notably the elements. This includes all factors of the climate, like wind, ice, rain, and snow. The Earth also can be shaped by the action of waves, floods, and storms. Humans also can affect the rate of weathering by contributing to the pollution that may cause landforms to break down, like acid rain. Over time, these changes can vastly change the landscape of the Earth. This topic became a field trip for a boy and his father, and, inadvertently, his mother. At home, the boy named Jonah heard his dad talking about how he was upset at how the recent freeze had broken part of their cement driveway. His dad said that this was something they called weathering. Dad said that weathering was where rocks and minerals are broken down by the elements of nature into smaller pieces. Jonah thought that his dad was mistaken, and he was talking about erosion, since he had been learning about landforms at school. His dad asked him to come outside and see for himself. His dad asked him to share what he was learning in science class at school, and Jonah stated that a landform is a term that refers to any natural surface feature of the Earth. Landforms include things like mountains and hills, or valleys and canyons. That's right, said his dad, and he told him that like anything in nature, they are formed and change over time. Jonah wondered how things changed over time. Since he was such a young boy, he wondered if he had lived long enough to see changes in the Earth. As they went outside to look at the driveway, they talked about what kinds of things could weather rocks. They found that things like heat, cold, rain, climate, pollution, acid rain, water, ice, and waves all were elements that could break down rocks over time. Over time, water can get into a rock, and as it freezes, it can break the rock into pieces. "Did you know that there are two kinds of weathering?" stated Dad as he picked up the piece of cement from the driveway. "Mechanical weathering and chemical weathering. Mechanical weathering is when rocks are broken down by physical agents like ice, wind, or water. And chemical weathering is when rocks are broken down by chemical reactions." Jonah asked, "So let me get this straight. I understand that other things in nature can break down rocks, but how do chemicals cause rocks to break down too?" His dad told him about pollution and the production of acid rain. He said that outer layers of rocks can get worn away by acids, and statues sometimes even are destroyed too. As time passes, mechanical and chemical forces can begin to break down landforms and cause them to change. Take the Grand Canyon, for example. All the layers that form the rock formations were deposited over many years, with the oldest layers near the bottom and the younger layers deposited on top of them. If viewed long ago, no one could see the different layers because they were all underground. Through the years, forces of nature like water and wind broke down and then wore a channel through the rock, exposing the layers underneath. Over time, more and more area was weathered by these physical agents, enlarging the canyon into what we see today. Another one is Devil's Tower, which is thought to be the plug of an ancient volcano. It is all that is remaining of the volcano that weathered from around it. Jonah also learned that there were two other forces that also affect and form landforms. The first one is called erosion. He found that erosion is the movement of broken down, weathered rock from place to place. His dad took him to the garden where there were channels made in the soft earth. During erosion, the weathered rocks are carried from one place to another by wind, water, or gravity. The other word he learned from his reading was deposition. Like making a deposit in his piggy bank, deposition means the laying down or depositing of broken rock, which reminded him of the time he got in trouble for burying his sister at the beach. That made him smile. Dad said, "There are several agents of erosion that occur. Water can be one of the most effective and efficient modes of erosion. Waves, for instance, can cause changes in landforms by weathering the surrounding rocks and forming a beach by eroding the debris and depositing it on the shore. As the waves slowly wear down the rocks, the bits of rock turn into sand, which is a size of a rock piece. As these sand grains pile up on the shore, the beach gets formed by deposition. The waves can form many other landforms too, like sea arches, sea caves, or sea stacks, which are piles of rock that were once connected to the mainland. As mentioned, most of this rock that gets broken down ends up on the shore as a beach." Jonah also said that his teacher told him about water erosion, and his favorite was floods. Flooding can cause massive changes in a short amount of time. If you have seen a dam break, the effects of a tsunami or even small local flooding, water can carry away massive amounts of rock and soil in a very short time. Landforms can be changed extremely rapidly by the power of water. "Yes," Dad said, "and wind is another agent of erosion, as it breaks down exposed landforms and then transports the debris away. Deserts and coastlines are prime areas to be shaped by wind erosion." A third way that erosion and deposition can take place is through snow and ice. As snow piles build up, they can form glaciers, which are large masses of ice that can move. Glaciers are so large and heavy that they can pick up giant rocks and boulders and transport them long distances. Jonah stated they saw a picture of a huge boulder left behind from a glacier. As the temperature of the ice increases and begins to melt it, the rock debris that is left behind from a glacier is called a moraine. Also, as the glacier forms, more and more ice builds up, and the weight of the glacier can become immense. As it slides forward, the glacier can act as a giant piece of sandpaper, scouring the land behind into U-shaped valleys and making a variety of interesting landforms in its wake. After the day, Jonah felt he had a good idea of weathering, erosion, and deposition. Weathering is where rocks and minerals are broken down by the elements of nature into smaller pieces. Erosion is the movement of broken down, weathered rock from place to place, and deposition means the laying down or depositing of broken rock. After being out and about all day, he realized he was covered from head to toe with the debris of his day. As he walked in, his mother shouted, "How could you bring that mess into my house?" He replied, "It's erosion, Mom, science." She retorted, "Deposit it and yourself in the shower and let it erode down the drain." Jonah thought his mom was pretty clever and did as he was told. He had a lot to talk about at school on Monday.
A rill is a shallow channel in some soil created by the erosion of flowing water. Rills can generally be easily removed by tilling the soil. When rills get large enough that they cannot be easily removed, they're known as gullies. Sometimes humans will create artificial rills to move water to where it's needed, or as a water feature in a garden because it looks nice. Rills happen most often in soft soil and areas with a lot of rainfall. Rills form when water flows over bare soil. When soil isn't protected by vegetation, water can flow unhindered and fall on the surface directly as rain. Water has powerful erosive capabilities. It erodes away soil and rock. Erosion is the gradual destruction or breaking down of a material by an agent like water, wind, or harsh chemicals. As the water flows over the land, it picks up pieces of soil, moving or eroding the soil away inside the flow of water. This moving of soil is what creates the rill and eventually a gully. Generally, for a rill to form, the water has to be flowing downhill. Gravity is the reason that the water flows in the first place, giving it the chance to create a rill. The steeper the slope, the more likely it is that one will be created. It shouldn't be a surprise that they also form more often in rainier months, where there's more water flowing through and across the land. Rills and gullies are more common after human activities than they are in the natural world. That's because humans tend to leave the land bare. Humans cut down trees, which is called deforestation, and plant crops. We also leave land bare while constructing buildings. Farming in particular often involves leaving areas bare, either for short periods of time or sometimes for whole seasons. Farming also removes nutrients from the soil. These factors make the soil susceptible to the effects of rainwater, creating rills and ultimately gullies. Rills can be the first sign that the land has an erosion problem. Erosion can be a problem both from a natural perspective and a human perspective. Erosion carries the soil down the gully, downhill and away from the land. This can make the quality of crops grown on a piece of land go down over time. A rill is a shallow channel in some soil created by the erosion of flowing water. Rills can generally be easily removed by tilling the soil. When rills get large enough that they can't easily be removed, they're known as gullies. Rills happen most often in soft soil and areas or times of year with a lot of rainfall. Rills form when water flows over bare soil. When soil isn't protected by vegetation, water can flow unhindered and fall on the surface directly as rain. Water has powerful erosive capabilities. It erodes away soil and rock. Erosion is the gradual destruction or breaking down of a material by an agent like water, wind, or harsh chemicals. As the water flows over the land, it picks up pieces of soil, moving or eroding the soil away inside the flow of the water. This moving of soil is what creates the rill, and eventually a gully. Since gravity makes the water flow, the steeper the slope, the more likely it is that a rill will be created. Rills and gullies are more common after human activities than they are in the natural world. That's because humans tend to leave the land bare. Humans cut down trees, which is called deforestation, and plant crops. This makes the soil susceptible to the effects of rainwater. Erosion can be a problem because it carries the nutrients of the soil away. This can make the quality of crops grown on a piece of land go down over time.
Most of the Earth is covered with water, and most of that is salty and in the oceans. In fact, about 97% of Earth's water is ocean water. The remaining 3% is freshwater, and 2/3 of that is frozen in glaciers. Glaciers are large masses of ice that can take many forms, from huge sheets to jagged blocks of slow-moving ice and rock. For billions of years, glaciers have carved the Earth's surface and fed rivers and oceans with water. Their presence is still felt even millions of years after melting away to create valleys, lakes, and even mountains. Glaciers are formed from the accumulation of ice and snow, but in order for this to become a glacier, it has to move under its own weight. An accumulation of ice isn't considered a glacier until it starts moving. Once it does start moving, though, it acts like a giant plow that scrapes and scours the earth. As glaciers move across the land, they loosen and pick up rocks along the way, dragging them across the Earth's surface and creating striations, which are just large scratches that are formed in the direction of glacial movement. A glacier may move in two ways. Internal flow is when the pressure and gravity on the ice in a glacier cause it to move downhill. This movement is like pushing a deck of cards from one side. As you push the deck of cards, the base of the deck moves very little because it is in contact with the table and there's more friction here. Conversely, the cards at the top of the deck move faster because there's less friction. Basal sliding is when an entire glacier moves because its base is slightly melted. Instead of mostly internal movement, the bottom of the glacier slides downhill as well. This makes the glacier able to move, much like an ice cube is able to glide across a table if it is pushed. Even though glaciers are moving, trying to watch this movement would be like trying to watch grass grow. Most move only a few feet or inches each day, though some glaciers have been known to move as fast as 50 meters in a single day, this is about 160 feet, or about the equivalent in length of 16 minivans. Continental glaciers are also known as ice sheets because they envelop everything in sight with a layer of, you guessed it, ice. These are the kind of massive, all-consuming glaciers that might bring to mind images of ice ages and polar bears, and they currently cover the Earth's poles and very cold places like Greenland. Because they are so massive, continental glaciers smooth the Earth's surface as they move. The markings they leave behind are not very obvious, but since continental glaciers cover such large pieces of land, scientists can use the striations left behind to study how continents used to be linked together. Alpine glaciers are created from the densely packed snow and ice found on top of mountains as well as in the valleys between them. Once alpine glaciers begin their downhill descent, they start their slow-moving havoc on the terrain around them. Hanging valleys are also caused by alpine glaciers and are formed when a glacier carves out a deep valley and then melts, leaving the valley suspended in the mountain range. The valley usually ends with a waterfall, and Yosemite National Park is famous for having many of these. Tidewater glaciers are alpine glaciers that move downhill and meet the ocean. Chunks of the glacier can break off in a violent process called calving, which causes large ice chunks to fall into the ocean and form icebergs. As a glacier moves downhill, it picks up and moves lots of sediment and debris. The debris left behind is called drift, and it creates some very unique landforms. Moraines are like small, perpendicular mountains that occur along the edge of where the glacier stopped moving forward. Drumlins are elongated hills that look like a whale's back. Bunker Hill in Massachusetts is probably the most famous drumlin. As glaciers carve out holes in the landscape, they fill with water and create kettle lakes. Once the glacier is gone, the water is left behind in these pockets, leaving behind lakes of a variety of shapes and sizes. Minnesota is known as the land of 1,000 lakes because all of the kettle lakes left behind from glacial activity. Glaciers are large ice masses that definitely leave their mark on the world. Glaciers move slowly through internal flow and basal sliding, but along the way create some stunning features and landscapes such as hanging valleys and kettle lakes. Many of the world's lakes, such as the Great Lakes surrounding Michigan, were formed by glaciers millions of years ago. We use these lakes as sources of fresh water in addition to the glacier water which feeds our rivers and oceans. Glaciers act as a frozen reservoir for most of our fresh water on Earth and are greatly affected by climate change. As the Earth becomes warmer, glaciers melt and become more mobile. We know how drastic the effects of slow-moving glaciers can be, but we do not know how these effects will change if this process is sped up.
Did you ever wonder what life would be like without glaciers? Well, for starters, if all of the world's glaciers melted at once, sea level would rise about 215 feet. That means if you currently live on the beach, you would have to move to the 22nd floor of the nearest hotel just to stay afloat. Glaciers are masses of ice that form in areas of the world where snow falls more often than it melts. This builds layers of snow that compress due to the increasing weight, eventually turning the mass into glacier ice. Glaciers are impressive to see, but they're not just stagnant blocks of ice. They are actually dynamic structures that move, grow, and recede under different conditions. When a glacier is growing, we use the term accumulation, which means the addition of snow and ice to a glacier. There are different processes that factor into accumulation, with a common factor being snowfall directly onto the glacier. But we also see that accumulation occurs when other forms of precipitation hit the ice mass, such as freezing rain. Snow does not have to fall directly onto the glacier. In fact, significant accumulation can be attributed to wind-blown snow that settles onto the glacier or snow that flows onto the glacier via an avalanche. The opposite of accumulation is ablation, or wastage, which means the removal of snow or ice from a glacier. Most ablation occurs due to melting during the warmer months of the year, but it can also be the result of wind erosion that blows snow from the glacier, or sublimation, which is the direct change from a solid to a gas. In other words, with sublimation, ice can directly change into vapor, bypassing the liquid water phase. Calving is another form of ablation, in which large chunks of ice break off the glacier and fall into the water. This can be a dramatic sight and can be accompanied by a loud crack. Calving gives birth to floating masses of ice called icebergs. You can recall this term by remembering that cows give birth to calves, and glaciers calve icebergs. As we mentioned, glaciers are dynamic structures, and they change throughout their lifetime. They are said to be retreating if the leading edge of the glacier does not travel as far as it previously did because ablation exceeded accumulation. On the other hand, a glacier is said to be advancing if the leading edge of the glacier moves forward faster than the rate of ablation. Scientists determine if a glacier is retreating or advancing by measuring where the terminus or leading edge of the glacier is located. The terminus is sometimes called the snout of the glacier, as if the glacier is being led by its nose. Knowing the location of the terminus helps scientists determine the glacier mass balance, which is simply the balance between accumulation and ablation. If there is equal balance between these two factors, then a glacier is said to be in equilibrium, and it does not change in size. It might help you to think of the mass balance as the health of the glacier. For example, if there is more growth than melting, then the glacier is gaining mass and looking healthy. These growing glaciers are said to have a positive mass balance, and they will advance. Consequently, if there is a loss of mass due to faster wasting than growth, the glacier will be sick. There is a negative mass balance, and the glacier will retreat. Let's review. When a glacier is growing, we use the term accumulation, which means the addition of snow and ice to a glacier. This happens due to different processes, including snowfall or freezing rain directly hitting the glacier. Accumulation can also be attributed to wind-blown snow or avalanche snow that settles onto the glacier. The opposite of accumulation is ablation or wastage, which means the removal of snow or ice from a glacier. Ablation occurs due to melting, wind erosion, and calving, which is when large chunks of ice break off the glacier and fall into the water. The floating masses of ice are called icebergs. Sublimation is a direct change from a solid to a gas. The glacier's terminus, or snout, is defined as the leading edge of the glacier. By knowing the location of the terminus, scientists can determine if a glacier is retreating or advancing. Retreating means the leading edge of the glacier does not travel as far as it previously did because ablation exceeded accumulation. Advancing means the leading edge of the glacier moves forward faster than the rate of ablation. The glacier mass balance is the balance between accumulation and ablation. If there is equal balance, then a glacier is said to be in equilibrium, and it does not change in size. If there is more growth than melting, then there is a positive mass balance and the glacier will advance. If there is a loss of mass due to faster wasting than growth, then there is a negative mass balance and the glacier will retreat. Glaciers are basically ice mountains, but unlike typical mountains that are made of rock, these mountains can move. As they move across the Earth's surface, they act like a sculptor's tool, scraping against rocks and carving out basins. In fact, many of the most beautiful and rugged landscapes, as well as many of our lakes, have been shaped by moving glaciers. Glaciers move because they either get top-heavy or they slip on their base. We will discuss the processes by which glaciers move in this lesson. Now, all glaciers start with snowfall that accumulates faster than it melts. As the years pass, layers of snow pile up, compressing the layers below into dense ice. This process continues until the mountain of ice becomes very heavy. It starts to move when the weight becomes too heavy to maintain the glacier's shape. Of course, if you stand next to a glacier, you probably would not see this movement, because most glaciers only move a couple of centimeters to a couple of meters per day. The movements they do make are typically a combination of processes, but the most common process is internal plastic deformation, or internal flow, in which the glacier's weight becomes too much to support itself. This results in the slippage of ice layers within the glacier. So the glacier moves downhill, as if it is being spread like a deck of cards, with the top layers flowing more quickly than the bottom layers. This spreading happens because the lower layers are subjected to friction due to contact with the land, which slows their movement. Another process by which glaciers move is basal sliding. With basal sliding, we see the entire glacier moves as a single unit due to melting at its base. Pressure at the base of the glacier causes a thin layer of ice to melt. This reduces friction, allowing the entire glacier to slide downslope as a single mass, kind of like it's on a water slide. Basal sliding is greatest on steep slopes, where the reduction in friction allows the glacier to succumb to the pull of gravity. The lowest levels of a glacier are under a lot of pressure due to the weight above. However, the upper layers are not subjected to the same forces and are therefore more brittle. This can cause the upper layers to split as the glacier below moves, forming huge crevasses or ice cracks on the surface of the glacier. Crevasses are what make walking on glaciers very dangerous because they get covered with fresh snowfall, making them invisible to hikers and mountain climbers. Glaciers move at varying rates. We mentioned earlier that the slowest glaciers move only a couple of centimeters a day. The fastest can move upwards of 30 meters a day, which is a little more than the distance between bases on a baseball field. There are factors that increase glacial flow rates. These include a steeper slope, which accelerates the movement thanks to the added pull of gravity. The rate also increases with increased size and thickness of a glacier due to the added weight and pressure. Warmer temperatures allow for more melting of ice at the base of the glaciers, which acts as a lubricant to speed flow. And glaciers that sit on smoother rock surfaces will flow with more ease because there are not as many rocky structures to impede their movement. Let's review. Glaciers are basically ice mountains that move. Their movement is typically a combination of processes, but the most common process is internal plastic deformation, or internal flow, which involves the slippage of ice layers within the glacier. With this action, the glacier moves as if it is being spread like a deck of cards. Another process by which glaciers move is basal sliding, where the entire glacier moves as a single unit due to melting at its base, kind of like the glacier is slipping down a water slide. The lowest levels of a glacier are tightly packed, but the upper layers are somewhat brittle. This can lead to the creation of dangerous crevasses or ice cracks on the surface of the glacier. Glaciers move at varying rates, from a couple of centimeters a day up to about 30 meters a day. There are factors that increase glacial flow rates, such as a steeper slope, increased size and thickness, warmer temperatures, and smoother rock surfaces below the glacier. If a block of ice the size of a mountain is moving towards you, what should you do? Well, if it were me, I would get out of the way. These moving mountains of ice do exist, and we call them glaciers. They tend to move very slowly, often only a few centimeters per day, so it would be a rare occasion for a human to get struck by a glacier. This is not true, however, for the landscape that lies in the path of a moving glacier. Land and rock cannot move out of the path of a glacier, so they are subjected to glacial erosion, which is simply the carving and shaping of the land beneath a moving glacier. Glacial erosion and the interesting landforms that result from this process are the subjects of this lesson. There are two main processes of glacial erosion. The first that we will talk about is plucking, which is defined as the erosion and transport of large chunks of rocks. As a glacier moves over the landscape, water melts below the glacier and seeps into cracks within the underlying bedrock. This water freezes and melts, weakening the bonds holding pieces of bedrock in place. These pieces of rock can now be picked up or plucked from their rocky base and carried along with the moving glacier. If you ever put an ice cube on your finger and felt the skin of your finger stick to the ice cube, then you have a fairly good idea of how plucking works. Plucking removes rocks and by itself creates changes in the landscape, but plucking also contributes to the second process of glacial erosion, known as abrasion. Abrasion is defined as the erosion that occurs when particles scrape against each other. The enormous weight of the glacier, along with the rocks and sediment plucked up and clinging to its belly, scratch and carve the rock surface below. It's almost as if the moving glacier is sanding the rocks with abrasive sandpaper. As the glacier sands the rock, it leaves behind long scratches that form in the direction of the glacial movement, called glacial striations. Seeing these scratch marks is a sure sign that a glacier once covered the land. The scraping and plucking of glacial erosion creates a number of distinct landforms and features. If the glacier erodes into a mountain, it can create a cirque, which is a round hollow with steep sides. It's as if the glacier scoops out the side of the mountain like an ice cream scooper. If you look at a cirque, you might think it resembles an amphitheater. In fact, with a bit of imagination, you could imagine circus animals and clowns putting on a circus at the base of a cirque. When the glacier melts and moves on, it often leaves behind water that gets trapped in the cirque. A small mountain lake of trapped water is called a tarn. It might help you remember this term if you think of the two T's, tarn and trapped. When we look at cirques and tarns, our eyes are drawn to the bowl-like inner structures that were carved out. But the peaks left behind from glacial erosion are just as impressive. If a mountain is eroded by several glaciers, we see the formation of a glacial horn, which is a good name because it looks like a horn jutting up from the earth. A glacial horn is defined as a sharp, angular peak formed when several glaciers erode a mountain in different directions. It's almost as if the glaciers sharpen the mountain into a point, just like ancient civilizations sharpened rocks into spears. The Matterhorn in Switzerland is a perfect example of a glacial horn. In a somewhat similar fashion, if two glaciers slide down opposite sides of a mountain, we end up with a sharp, narrow mountain ridge called an arete. If you're an adventurous hiker, you would find walking along the ridge of an arete exhilarating, as it would provide a high-altitude scenic view. In fact, you would likely give an arete an A rating. We mentioned earlier that as ice moves over bedrock, it can smooth the rock, cut striations into the rock, and also pluck rocks from the foundation. The erosion can lead to the formation of a roche moutonné, which is a mass of rock carved by a passing glacier. The rock formation is distinctive because it has a smooth, rounded side, where the ice abrasively slid over it, followed by a steep, ragged side, where rocks were plucked from the surface. These formations can be small, with some measuring only a meter in height, and we see that the term roche-moutonné means sheep back in French. Perhaps the person who coined the name thought that the rock structures looked like the backs of sheep grazing in a field. Knowing this might help you recall the term, but I think if you say the term roche-moutonné fast enough, it sounds a bit like Rock Mountain, and this might be the best memory jogger. Let's review. Glaciers can be thought of as moving mountains of ice. As they move over the landscape, they cause glacial erosion, which is defined as the carving and shaping of the land beneath a moving glacier. There are two main processes of glacial erosion. Plucking is the erosion and transport of large chunks of rocks that stick to and get picked up by the glacier. Abrasion is the erosion that occurs when particles scrape against each other. It works in a similar fashion to sandpaper. There are a number of features and landforms that result from glacial erosion. Glacial striations are long scratches that form in the direction of glacial movement. A cirque is a round hollow with steep sides that resembles an amphitheater, maybe one that could hold a circus. If a cirque traps water, it can result in a small mountain lake of trapped water called a tarn. A glacial horn is conveniently named because it looks like a horn jutting up from the earth. It is actually a sharp, angular peak formed when several glaciers erode a mountain in different directions. If two glaciers erode opposite sides of a mountain, we end up with a sharp, narrow mountain ridge called an A rate, which provides an A rating when it comes to scenic views. Glacial erosion can also create a roche-moutonné, which is a mass of rocks carved by a passing glacier. The rock formation has a smooth, rounded side caused by abrasion and a steep, ragged side where rocks were plucked from the surface. I have a little quiz for you. Which area of the United States was at one time covered by a glacier? Was it A, Long Island, New York, B, the state of Wisconsin, or C, the Yosemite Valley located in the mountains of California? Or is the correct answer D, all of the above? Well, if you picked D, then you got it right. In fact, at different times over the long history of our planet, glaciers covered much of North America. We know this because as glaciers move out of an area, they leave behind clues in the form of glacial deposition. Glacial deposition is simply the settling of sediments left behind by a moving glacier. For example, Long Island was formed by rocks and sediment pushed there by a couple of glaciers. Wisconsin contains many interesting sediment deposits that were carried there by glaciers from Canada, and the Yosemite Valley was carved by a glacier. Glacial deposition and the landforms that result from this process are the subjects that we will cover in this lesson. Glaciers are kind of dirty. This is because as they move over the land surface, they pick up debris, sand, soil, and rocks. And these particles get stuck within the ice and travel with the glacier, often for long distances. When the ice melts, the mixture of unsorted sediment deposits carried by the glacier, known collectively as glacial till, is dropped or deposited. These sediments often get formed into piles known as moraines, which we can define as piles of till deposited along the edges of past glaciers. Because moraines form in lines, their locations give us important clues as to where the borders of a glacier were once found. Lateral moraines are deposits found along the sides of a past glacier, and terminal moraines are deposits found at the farthest point that a past glacier reached. It might help your understanding of moraines if you think of a glacier as a bulldozer pushing through a mound of dirt. As the bulldozer pushes forward, some dirt is left behind in piles along the sides of its path. These would be the lateral moraines. If the bulldozer backs up and leaves a pile of dirt at the farthest point it reaches, this pile would be the equivalent of a terminal moraine. This goes back to our discussion of how Long Island, New York was created. A couple of glaciers pushed rocks and soil south, forming a terminal moraine. Then the glacier retreated, meaning it melted, leaving behind Long Island. Glaciers are kind of like litter bugs because they drop materials wherever they please, and sometimes they leave behind boulders so large that they could never be moved there by human power. These are called glacial-erratics, and they are described as big rocks deposited in unusual places due to glacial movement. For example, you could find a huge limestone boulder sitting in an area where most of the bedrock is made up of granite. These misplaced boulders were aptly named because the term erratic is used to describe something that is unusual. In fact, you could say that erratics are big rocks deposited in erratic places. A drumlin is another example of a deposit left behind by a glacier. It's described as an elongated hill composed of glacial till. Unlike moraines, which form in rows of sediment, drumlins look like the backs of whales as they breach the surface of the ocean, and where there is one drumlin, you will likely find others. This is because they are usually found grouped together in drumlin fields. These fields do not only leave behind clues that the glacier once passed through the area, they also tell us which direction the glacier was moving. This is because all drumlins in a drumlin field align themselves in the direction of ice flow. Bunker Hill in Massachusetts is a famous drumlin. In fact, you might find it easier to recall this term if you picture a soldier in the Battle of Bunker Hill playing a drum as he walks up the drumlin. Let's review. Glacial deposition is the settling of sediments left behind by a moving glacier. As glaciers move over the land, they pick up sediments and rocks. The mixture of unsorted sediment deposits carried by the glacier is called glacial till. Piles of till deposited along the edges of past glaciers are called moraines. Lateral moraines are deposits found along the sides of a past glacier, and terminal moraines are deposits found at the farthest point that a past glacier reached. Glaciers are big enough to pick up boulders and move them to different locations. These big rocks deposited in unusual places due to glacial movement are called glacial-erratics. A drumlin is an elongated hill composed of glacial till. Drumlins are grouped together in drumlin fields and are found aligned in the direction the ice flowed through the area. Their appearance resembles the backs of whales. If you live in an area where winter roars its ugly head and plummets temperatures below zero, then you know the joy that comes with the arrival of spring and warm temperatures. But what if the weatherman said spring wasn't scheduled for another 10 million years? Well, if that were the case, then you would be living in an ice age and be able to look forward to nothing but a prolonged period of cold with glaciers blanketing much of the earth. Glaciers are huge moving mountains of ice that can directly affect the landscape in many ways. The carving and shaping of the land beneath a moving glacier is a process referred to as glacial erosion. As a glacier moves over the Earth's surface, it plucks up rocks and sediment, which then get stuck to its belly and go along for the ride. These particles act like sandpaper and scratch the bedrock below. The removal of rocks and grinding of bedrock create entirely new landscapes. Glacial erosion is responsible for some of the most stunning rock features in mountainous regions, such as glacial horns with their sharp angular peaks, and cirques that have round hollows with steep sides. Glaciers carved out basins within bedrock that later filled with water, forming millions of lakes that exist to this day. Glaciers were responsible for turning many of the typical V-shaped valleys between the mountains into U-shaped valleys with broad and wide valley floors. When the environment emerges from the freezing ice age temperatures, we see another direct effect of glaciers known as glacial deposition, which is the settling of sediments left behind by a moving glacier. This process occurs as the melting glaciers drop all of the rocks and sediment they previously picked up. It's almost as if the Ice Age glaciers were the original litter bugs of the environment because they spread debris over vast areas. The unsorted materials moved and deposited by a glacier is known as till. Till can be pushed or deposited into piles. Lines of till that form at the edges of past glaciers leave behind landforms known as moraines. Moraines form in lines and give a general idea of the boundaries and farthest points that the past glaciers reached. We also see drumlins, which are elongated hills composed of glacial till. A number of drumlins can form together in a field, and their unique shape makes them look almost like the backs of whales breaching the surface of the ocean. Glacial erosion and deposition are direct effects of Ice Age glaciers, but there are also indirect effects that impact the Earth. One indirect effect is the creation of pluvial lakes, which are lakes that were at one time very large due to excessive rainfall associated with glaciation. To recall this term, it might help you to understand that the word pluvial means rain in Latin. So pluvial lakes formed due to very heavy rainfall. But there's a catch. Pluvial lakes formed in desert areas. Are you wondering how so much rain fell in the desert? Well, it all had to do with the presence of Ice Age glaciers. Glaciers are huge, and during an ice age, they can cover about a third of the land. These huge ice cubes change airflows and weather patterns and turn previously dry areas into wet areas. This allowed basins in these previously dry areas to fill with water, giving us the pluvial lakes. After the Ice Age, the pluvial lakes began to shrink, but we still see some remaining today, such as the Great Salt Lake in Utah. Another indirect effect of Ice Age glaciers is a phenomenon referred to as isostatic depression. This is the sinking of the Earth's crust due to pressure from a heavy weight. During an ice age, this heavy weight is the glaciers. Isostatic depression is similar to what happens when you lay down on a mattress and it compresses or depresses under your weight. When the glacier eventually melts, the Earth's crust rebounds in the same way your mattress rebounds when you get out of bed in the morning. Of course, your mattress tends to spring back into shape quickly, whereas the rebounding of the Earth takes thousands of years. In fact, measurements on the shorelines around the Great Lakes shows that this area is still rebounding from the last ice age. One other indirect effect that is worth noting is the change in sea level that results with the growing and melting of Ice Age glaciers. We shouldn't forget that glaciers are frozen water. During the prolonged cold of the Ice Ages, water that once filled oceans was turned to ice. This resulted in a drop in sea level during the Ice Ages and the uncovering of large land bridges, such as the bridge that connects Alaska and Siberia. Some ice is still tied up in glaciers today, with modern-day glaciers covering about 10% of the world. If all of these remaining glaciers were to melt tomorrow, the sea level would rise 215 feet, which is more than 21 stories high. Let's review. An ice age is a prolonged period of cold with glaciers blanketing much of the Earth. These glaciers cause glacial erosion, which is the carving and shaping of the land beneath a moving glacier. Glacial erosion leaves behind glacial horns with their sharp angular peaks and cirques that have round hollows with steep sides. Glaciers also carved out millions of lakes and U-shaped valleys. When glaciers melt, we see another process called glacial deposition, which is the settling of sediments left behind by a moving glacier. The unsorted materials moved and deposited by a glacier is known as till. When till accumulates, it can result in moraines, which are lines of till that form at the edges of past glaciers, or drumlins, which are elongated hills composed of glacial till. One indirect effect of Ice Age glaciers is the creation of pluvial lakes, which are lakes that were at one time very large due to excessive rainfall associated with glaciation. The huge glaciers changed airflows and weather patterns and turned previously dry areas into wet areas, leading to the formation of the lakes. The glaciers were so heavy that they caused isostatic depression, which is the sinking of the Earth's crust due to pressure from a heavy weight. And they were so massive that they tied up much of the world's water, resulting in a change in sea level. Earth is a dynamic place, with major changes happening constantly. changes so big that we cannot perceive them. The Earth turns on its axis, continents shift their positions, and glaciers grow and recede, all beyond our conscious awareness. In this lesson, we will explore how the constant moving of the continents and cyclic changes in the Earth's orbit result in periods of glaciation, where we see the covering of large areas with glaciers. You have probably heard the term Ice Age, which simply put is a long period of cold temperatures. And when I say long, I mean long, as in millions of years. Yet within an ice age, there are episodes of fairly extensive glaciation where we see glaciers growing and advancing, broken up by episodes of relatively warm temperatures when glaciers retreat. Geologists believe Earth has survived through 5 major ice ages in the past 2.4 billion years. So what causes the Earth to periodically freeze up? Well, there are 2 main theories behind the cause of glaciation. One theory has to do with changing continental positions, which is based on the theory of plate tectonics, in which scientists believe that the Earth's surface is made up of large plates that move over top of a more fluid, deeper layer, somewhat like a puck glides over an air hockey table. The continents sit on top of these large plates, and therefore their positions are constantly changing. This movement of large land masses affects the circulation patterns of the oceans and atmosphere. When these circulation patterns change, the result is a change in climate. For example, if continents shift in such a way that they block warm water currents from the equator from making their way north to the poles, then ice can grow in those polar regions. Another theory to explain the cause of glaciation is the variations in the Earth's orbit that occur in cyclic fashions. This theory, known as the Milankovitch theory, after the man credited with its development, points to 3 orbital variations that result in the long-term climate change needed for glaciation. The first is eccentricity, which is defined as changes in the Earth's orbit around the Sun. The Earth can follow a nice even circular path around the Sun, or it can follow a more oblong path. When the Earth follows this oblong path, we could say that the orbit is a bit off, just like a person who is eccentric could be said to be a bit off. This change in the Earth's orbit does not happen suddenly. It takes about 100,000 years to go from circular to eccentric and back. But when the Earth is in the farthest position of the oblong orbit, the Earth and the Sun are far apart. This lessens the amount of warm sunlight hitting the Earth, which promotes glaciation. The second orbital variation to consider is obliquity, which is defined as shifts in the tilt of the Earth's axis. It might help you to recall this term if you remember that when something is oblique, it's slanted. So obliquity is describing how much the Earth is slanted. This slant, or tilt, varies only a couple of degrees, from 22.1 degrees to 24.5 degrees. Yet this small change takes about 41,000 years to complete and is enough to influence the intensity of the seasons. For example, less tilt means fewer extremes, so there is less cold in the winter and less heat in the summer. These cooler summer months allow the snow that falls over the winter to stick around. Over years, this snow builds up and glaciers are born. The third orbital variation is precession, which is the wobbling of the Earth's axis. This cycle takes about 23,000 years to complete and results in a change in the direction that the North Pole points, much like a spinning top will wobble when it's in motion. This changes the way the Sun hits the north and south hemispheres of the globe. What does this have to do with the amount of glaciers? Well, the northern hemisphere has more land masses positioned in high altitudes, and glaciers need land to start growing. Therefore, if less sun is hitting the northern hemisphere, then glaciers have an easier time growing. Let's review. An ice age is a long period of cold temperatures in which there are episodes of fairly extensive glaciation, where we see the covering of large areas with glaciers. There are 2 main theories behind the cause of glaciation. One theory has to do with changing continental positions, which is based on the theory of plate tectonics. The movement of continents affects the circulation patterns of the oceans and atmosphere. This changes the climate, which in turn affects the formation of glaciers. The Milankovitch theory, that deals with variations in the Earth's orbit, is another theory used to explain the cause of glaciation. This theory points to three orbital variations that result in the long-term climate change needed for glaciation. The first is eccentricity, which is defined as changes in the Earth's orbit around the Sun from a somewhat circular path to an oblong path. The second is obliquity, which is defined as shifts in the tilt of the Earth's axis. This slant varies only a couple of degrees, but is enough to influence the intensity of the seasons. The third is precession, which is the wobbling of the Earth's axis, much like a spinning top wobbles. This results in a change in the direction that the North Pole points.
Bad thoughts usually come to mind when you think of the word radiation, but solar radiation is actually a very beneficial thing. It's sunlight. Every living thing on Earth depends on sunlight for survival. It warms the planet, provides food for plants, and in general just makes us feel pretty darn good. I don't know about you, but being outside on a sunny day, soaking up all that energy, is a really nice feeling. Solar radiation is all of the light and energy that comes from the sun, and there are many different forms. The electromagnetic spectrum explains the different types of light waves that are emitted from the sun. Light waves are similar to waves you see on the ocean. They move up and down and travel from one place to another. The difference is that instead of the water vibrating up and down, light waves are vibrations of electromagnetic fields, hence the name the electromagnetic spectrum. You can think of the spectrum like a piano keyboard. One end of the keyboard has low notes while the other has high notes. The same is true for the electromagnetic spectrum. One end has low frequencies, the other high frequencies. Low frequency waves are low energy waves with a long wavelength. The length of the wave itself is very long for a given period of time. These are things like radar, TV, and radio waves. High frequency waves are high energy waves with a short wavelength. This means that the length of the wave itself is very short for a given period of time. These are things like gamma rays, X-rays, and ultraviolet rays. You can think of it like this. Low frequency waves are like going up a hill that slowly rises in elevation, while high frequency waves are like going up a steep hill very quickly. The height of each hill is the same, but the elevation either slopes gently over a longer incline or slopes up quickly over a shorter incline. The frequency of the electromagnetic wave determines how much energy it carries. Electromagnetic waves that have longer wavelengths and therefore lower frequencies carry much less energy than those with shorter wavelengths and higher frequencies. This is why X-rays and ultraviolet radiation can be dangerous. They carry so much energy that if they enter your body, they can damage your cells and cause problems like cancer and deformities in DNA. Things like radio and infrared waves, which carry much less energy, don't really affect us. This is good because you certainly don't want to put yourself at risk just by turning on your car stereo. Visible light, which is the sunlight we and other animals can see with our eyes, falls in almost the middle of the spectrum. We can't see any other waves on the spectrum, which are all just different forms of light, but that doesn't mean they aren't there. In fact, insects see ultraviolet light, but not our visible light. Flowers look very different to them than they do to us, and this helps them know which plants to visit and which ones to stay away from. Solar radiation also affects the overall temperature of each planet in our solar system. Our planet is hospitable partly because it is covered with water, but also because of where it lies in the solar system. Earth receives just enough solar energy, like Goldilocks' bowl of porridge, not too hot and not too cold. The angle of the sun's rays also determines our global weather patterns and seasons. It might help to think of a flashlight pointing at the wall. If you point the flashlight directly at the wall, you get a small area where all of the light is concentrated. Tilt that flashlight either up or down, and the same amount of light spreads out over a larger area on the wall, decreasing the amount of energy that hits one particular spot. On Earth, the sun's rays hit the equator at pretty much a 90-degree angle, which means all of that solar radiation is concentrated in a small area and keeps it warm all year round, like the straight-pointing flashlight. The polar regions, however, get the same amount of solar radiation as the equator, but it's spread out over a larger area because the angle is much less direct, like the tilted flashlight. So the same amount of warmth covers a greater area, making it much colder in these regions. As Earth rotates around the sun each year, it also tilts, so sometimes the sun's rays are more direct in certain places than others. This is what creates our seasons. It's like pointing the flashlight of the sun directly at some parts of Earth during certain times of the year. When the northern hemisphere is tilted toward the sun, receiving more direct solar radiation, it's their summer. At the same time, the southern hemisphere is tilted away from the sun, so it's their winter. The reverse is true during the opposite seasons. During the northern hemisphere's winter, that part of the Earth is tilted away from the sun, and the southern hemisphere is experiencing summer because they are tilted towards the sun, receiving more direct solar radiation. Believe it or not, during the northern hemisphere's winter, Earth is actually closer to the sun than during its summer. So while the distance certainly plays a role, the main factor that influences the temperature is how the sun's rays hit Earth, not how far they travel. All that stuff we call sunlight is actually solar radiation. Like waves on the ocean, light also travels in waves, but light waves are vibrations of electromagnetic fields. Because of this, they're classified along the electromagnetic spectrum, which categorizes different types of light waves, like notes on a piano keyboard. On one end of the spectrum, we find low-frequency waves, such as radio waves, infrared waves, and radar. On the other end, we find high-frequency waves such as gamma rays, X-rays, and ultraviolet light. Solar radiation plays a large role in Earth's climate. We receive just enough sunlight to make Earth a nice place to live, not too hot and not too cold. However, Earth is not warmed evenly, which is why even though the equator and polar regions both receive the same amount of solar radiation, they're different temperatures. The angle of the sun's rays is also what causes Earth to have seasons. As Earth orbits the sun, it's tilted at an angle. This means that throughout the year, the sun's rays hit different parts of Earth more directly than at other times. So even though the northern hemisphere is closer to the sun during its winter, it's still colder because it's tilted away from it.
The sun is constantly radiating energy. It has some cycles involving sunspots, flares, and other disturbances, which cause some minor fluctuations in radiation, but in general, the output of energy stays about the same. If it changed significantly, life on Earth would not be possible. We live on a fairly comfortable planet. The sun provides all of the energy that powers life on Earth's surface, and life as we know it is only possible because of Earth's distance from the sun. If Earth was any closer, it would be way too hot for life to thrive. If it were farther from the sun, it would be way too cold. Like in Goldilocks and the Three Bears, Earth's distance from the sun is just right. Our distance from the sun isn't the only factor. The amount of energy Earth is receiving from the sun also influences our weather and climate. So how exactly do we measure the amount of energy Earth receives from the sun? Let's say you want to get a deep brown tan and go to a tanning booth to do so. How tan you can get depends on how close you are to the UV bulbs in the bed, the number of bulbs or area over you, and how much time you spend under them. Intuitively, this makes sense. The closer you are to the source of energy, the larger its area, and the longer you spend there, the more radiation you will absorb. Distance, area, and time are important variables in understanding how much energy an object receives. All three variables are factored into the solar constant, a value that describes how much solar energy hits Earth's atmosphere. More specifically, this energy is defined as irradiance, the total amount of solar energy from the sun per unit of time per unit of area at Earth's distance from the sun measured outside of Earth's atmosphere. This number turns out to be about 1.366 kilowatts per square meter. The solar constant makes sense when we want to know how much radiation the Earth receives, but what if you were on the moon, or Mars, a different distance away from the sun? The solar constant formula would change since the distance has changed. Calculating how much of the sun's radiation you would feel at different distances depends upon the inverse square law, which shows us that the solar irradiance is inversely proportional to the square of the distance away from the sun. Think of a flashlight turned on in a dark room and the cone shape that the light makes. The farther away from the light source, the more the light spreads outward and decreases intensity, illustrating that inverse relationship between radiation intensity and distance. Because the sun is spherical, the irradiance spreads out evenly in all directions. The farther away you are from the sun, the less radiation you receive. We now know how solar energy can be a constant when measured outside of Earth's atmosphere, but what happens to that energy inside the atmosphere? Weather and climate patterns are greatly influenced by the amount of radiation that makes it through the atmosphere and down to the surface. Because of the speed of Earth's rotation, the thickness of the atmosphere is slightly greater at the equator than at the poles, trapping more incoming radiation. Just that alone means that more solar energy can be absorbed at the equator, but we also factor in how radiation hits the equatorial region at a high, direct angle and hits the poles at low, shallow angles. This is another reason why the equatorial region is warm year-round and why the poles have a cold climate. The angle at which radiation strikes an object affects its absorption, how much energy is taken in. Because of the inverse square law, the concentration of solar energy decreases through the atmosphere down to the surface. But due to the greenhouse effect, the insulating atmosphere traps incoming radiation, warming the surface and determining Earth's global climate. The amount of solar energy that Earth receives depends upon the surface area of the sun, the distance between the sun and Earth, and time. The solar constant relates these values to give the total amount of solar energy from the sun per unit of time per unit of area at Earth's distance from the sun, and is approximately 1.366 kilowatts per square meter. The inverse square law is what determines this constant, showing that the sun's energy output is inversely proportional to the square of the distance away from the sun. The farther away from the source of radiation you get, the weaker the intensity of the radiation. While the solar constant is measured outside of Earth's atmosphere, the radiation is absorbed and trapped within Earth's atmosphere due to the greenhouse effect. This is a major factor in climate and weather patterns across the planet.
Solar radiation. Nothing feels better than the sun's warmth shining down while you relax on the beach. Not only does solar radiation keep our planet's climate livable for its inhabitants, it also is the driving force behind photosynthesis, the water cycle, and many other processes that make Earth habitable to the living things that call it home. But not all of the radiation emitted by the sun makes it to the Earth's surface. Some of it is absorbed, but much of it is reflected off of the surface or scattered off of the atmosphere. This is actually a good thing, given that too much radiation would render the planet lifeless. Any object that can absorb radiation will also reflect some of that radiation. This is the reason why, from space, Earth appears bright and glowing, reflecting away some of the sun's light. Earth's albedo, the amount of radiation reflected, is about 30% of the total incoming radiation from the sun. The other 70% of the radiation is absorbed. The reflected radiation simply bounces off of Earth's atmosphere and is re-emitted into space. All objects have some degree of albedo, except for theoretical black-body objects, which absorb 100% of the radiation it receives and reflect none, hence appearing to be black. A black hole would be one such object, since its gravitation is so strong that no radiation can escape it, much less be reflected. Most of the radiation Earth receives is directly absorbed by land and water, but some of it is reflected off of clouds or ice, bouncing the radiation out of the atmosphere. Different materials absorb different amounts of radiation, as do different colors of materials. You'll likely have heard that it is better to wear light colors on a hot sunny day than it is to wear dark colors, as dark colors absorb more heat than the light colors. Snow caps, for example, reflect away more radiation than rock does. But not all of the reflected albedo is lost to space. Some of the longer wavelengths, infrared or heat radiation for example, stay in the atmosphere, providing a cozy, insulating layer of heat. The gases of Earth's atmosphere provide that insulation because some of them are greenhouse gases, gases that absorb and trap infrared radiation, which include water vapor and carbon dioxide. The more greenhouse gases are present in the atmosphere, the more heat is trapped, and the warmer the atmosphere tends to be. Not all of the gases in Earth's atmosphere are good at absorbing incoming radiation. Many of them are responsible for scattering incoming radiation, particularly light waves, causing them to bounce off the molecules in multiple directions. The size of the gas molecule can influence the size of the wavelengths those gases can scatter. For example, oxygen and nitrogen are two of the most abundant gases in the atmosphere, and are relatively small in size compared to some of the larger compounds in the atmosphere like water and carbon dioxide. Oxygen and nitrogen tend to scatter shorter wavelengths of light, blue and violet light. Our eyes don't see violet light as easily as they do blue, so this is why the sky is blue on a sunny day. But what about the spectacular oranges and reds of sunset? When the sun's relative position lowers on the horizon, the radiation it emits hits the atmosphere at a lower angle, causing the incoming light to have to pass through more of the atmosphere before it reaches your eyes. This causes more light to scatter, particularly on the yellow and orange range of the light wavelengths. Interestingly, the more aerosols, or atmospheric particles, are present in the atmosphere, the more reddish the sunsets will appear. Solar radiation, which includes infrared heat waves and visible light waves, is mostly absorbed by Earth's atmosphere. But, due to Earth's reflectivity, or albedo, some of that radiation bounces off of Earth's atmosphere. The rest is absorbed by the land and oceans, is reflected back up to be trapped by greenhouse gases which insulate the planet, or is scattered by other gases that make up the atmosphere. Scattering occurs when light waves bounce off of gas molecules, which can produce different colors depending on the aerosols, or atmospheric particles, involved, and result in colorful sunrises and sunsets when the sun's angle is lower on the horizon. These principles of absorption, reflection, and scattering allow the optimum amount of heat and light for surface-dwelling animals like ourselves to live comfortably on Earth.
Have you ever touched a hot pan and burned yourself? How about warmed yourself in front of a nice campfire on a cold night? Ever notice that most of the time air vents in houses in the north are on the floor, while in the south they're on the ceiling? These are all related to the movement of heat and how it gets transferred between substances and locations. Heat can move between objects or spaces, and there are three main ways it does this: conduction, convection, and radiation. Let's look at how each one works. If someone pours you a hot cup of coffee, you're likely going to pick it up from the handle instead of around the main part of the mug. This is because the coffee mug will conduct heat from the hot liquid inside to your hand. This direct transfer of heat from one object to another is called conduction. The coffee mug transfers heat well, as do many other substances, including metal. You certainly wouldn't touch a hot metal pan on the stove or hold a nail over a flame without some sort of protective glove, because you know that the heat from the metal will quickly transfer to your hand and burn you. It makes sense then that these substances that conduct heat well are called conductors. Some substances are very bad at transferring heat, and these are called insulators. Wood is a very good insulator, therefore a very poor conductor, which is why your metal pot on the stove may have a wooden handle. You can do a little experiment to see this in action. If you have an area in your house where wood floor meets some tile, put a bare foot on each one. You'll find that the tile floor feels cooler, but both floors are actually the same temperature. The tile is a much better conductor of heat than the wood, so it transfers the heat from the bottom of your feet better than the wood does, making your foot feel cold. Air is also a very poor conductor, which is why you can reach your hand inside an oven to grab a dish without burning yourself, unless you forget your oven mitts and grab the dish itself. Your house is insulated with something like rock wool or fiberglass because these substances are poor conductors of heat. Imagine how cold your house would be if there was no protection from the cold outside during winter, or how hot it would be if you weren't protected from the heat outside in the summer. Interestingly though, insulators don't actually stop the flow of heat, just slow the transfer considerably. That's why you still need to run your heat in the winter and AC in the summer, just not as much as if you had no insulation at all. Remember how I said houses in the north commonly have their air vents on the floor, while houses in the south have theirs on the ceiling? This is due to the way that heat flows in fluids, and both gases, like air, and liquids, like water, are considered fluids because of the way they move. When heat is transferred by currents in a fluid, this is called convection. Convection happens in all fluids, like the air in your home, water in a lake, and magma underground, just to name a few. Here's how it works. Imagine a room full of children who have just had a bunch of cookies. They become quite energetic and start running around the room. If you open the door and let them outside, they burst out and start running around the larger space, spreading out in the yard. The same thing happens when a fluid is heated. The molecules at the bottom gain energy and begin to move faster. As they move faster, they begin to spread apart, which makes the fluid less dense. But instead of being confined to a yard, the fluid's warmer molecules begin to move upward while the cooler, denser fluid begins to sink, just like the children start settling down as their cookie rush subsides. Once the cooler molecules reach the bottom where the heat is, it's like they ate another cookie and get an increase in energy again. They rise back up to the top while the cooler molecules sink back down to the bottom. The cycle continues as long as there is a heat source at the bottom. What does this have to do with air vents in a house? Well, if you live in a cold climate, you probably use your heat more often than your AC. And if you live in a warmer climate, you probably use your AC more than your heat. So if hot air rises and you use your heat more often, you'll want your vents on the floor so that hot air travels upward to fill the room as it comes out of the vents. The opposite is true for air conditioning. If cool air sinks, you wouldn't want it to start out on the floor because it wouldn't cool the room as effectively as if it starts from the ceiling, where it can cool the room as it falls. When you sit in front of a campfire, you're warmed by its heat. Hover your hand over a hot light bulb and you'll feel the heat coming off it, even without touching it. Stand out in the sunshine and you'll quickly get warmed by its rays. These examples illustrate our final mechanism of heat transfer, radiation. Radiation is when heat is transferred by electromagnetic waves like radio waves, infrared waves, X-rays, and even visible light. All objects both emit and absorb radiant energy, even you. Though, like everything else, some objects and substances are much better at this than others. Those that are good at emitting radiant energy, like the sun, are also very good at absorbing it. A radio antenna is designed to be a good absorber of radio waves, but that also means it's very good at emitting them. When it comes to radiant heat, much of what is produced on Earth comes from the Earth itself. It absorbs radiant energy from the sun and then emits it back toward space. This radiant energy emitted by the Earth is called terrestrial radiation, and it is what makes life possible. Like a big blanket, gases in the atmosphere trap terrestrial radiation on Earth and keep our planet nice and warm. What's really interesting is that unlike conduction and convection, radiation happens even when there is no material for the heat to travel through. The sun's rays travel through space to Earth, but since space is by definition empty, there's no point of contact, like conduction, or fluid, like convection, for the heat to travel through. The waves simply move heat through space just by, well, moving. Heat is very friendly. It likes to move, transfer, and travel. It does this by three main mechanisms: conduction, convection, and radiation. Conduction is the transfer of heat through direct contact between different objects or substances. Touching a hot pan on the stove, walking on hot sand along the beach, and putting a metal poker into the fire are all examples of conduction because heat is transferred from one object to the other as they touch. Some substances are better at transferring heat than others, and to make it easy, these are called conductors. Substances that do a poor job of transferring heat are called insulators. Metals are good conductors, but things like wood and air are poor conductors. If you put your hand in the oven, it doesn't burn, but grab the dish that's been heating in there, and I bet you'll wish you had your oven mitts on. And remember, you still have to use your heat in the winter and air conditioning in the summer because insulators don't stop the transfer of heat, They just slow it down considerably. When heat is transferred through the movement of fluids, this is called convection. Convection currents are like the result of giving children cookies. The molecules at the bottom have more energy and are warmer, so they move to the top of the fluid. Meanwhile, the molecules at the top are cooler, they're coming down from their sugar rush, and sink back to the bottom where the cycle starts all over again. Both gases and liquids are considered fluids, so you'll find convection currents in air as well as water. When heat is transferred by electromagnetic waves, this is called radiation. These waves come in all forms: X-rays, ultraviolet, radio waves, and even visible light. Like heat radiates from a fire or a radiator in a house sends heat out into a room, radiation is the movement of heat from one place to another simply by traveling along with the waves. All objects both absorb and emit radiation, though some are better than others. The Earth is very good at both absorbing and emitting the sun's radiant energy, and when it sends it back into space, this is known as terrestrial radiation. Terrestrial radiation is what makes life possible on Earth. This is because as heat is radiated back toward space, it gets trapped by the gases in the atmosphere, making Earth a nice, warm place to live.
We take sunlight for granted, but we really shouldn't, because essentially all energy on Earth comes from that big bright star in the center of our solar system. And while we're at it, we should also give a shout out to our atmosphere, because it absorbs some of that sunlight before it reaches us, as well as traps some of it for safekeeping on the planet. This is an important balance. Too much sunlight and Earth is too hot to live on. Too little sunlight and Earth is not warm enough. What does pass through the atmosphere provides energy in many different forms. But before we get ahead of ourselves, let's review the different ways that energy is transferred. When I was growing up, I listened to a band named CCR, which stands for Creedence Clearwater Revival. And when I think of CCR, I also think of energy transfer, because the three ways that energy is transferred between objects is also CCR: conduction, convection, and radiation. Even if you're not a classic rock fan, you've got to admit that's pretty catchy. Conduction is when energy is transferred between direct contact. When you burn your hand on a hot pan because you forgot to put on an oven mitt, that's conduction. The pan is transferring heat to your hand through direct contact. Likewise, when your feet touch the cold tile in the bathroom in the morning, your feet are transferring heat to the floor through direct contact. Conduction in action. Convection is when energy is transferred via currents in a fluid. This fluid could be a liquid or a gas, but the process is the same either way. When heat is applied to the fluid, the molecules near the heat become excited, spread apart, and become less dense, so they are buoyed upward. When they cool, they fall back down again, creating a cell-shaped current path. Radiation is when energy is transferred in the form of electromagnetic waves. Think about sitting next to a campfire and feeling the welcome heat radiate from it to you. That's radiation. Radio waves, light waves, and heat waves can all travel like this, moving from one place to another without the help of any materials. Let's put together what we know so far. First, we know that the energy comes from the sun, travels through space, then through our atmosphere, and finally reaches Earth's surface. We also know that this energy does not travel through any materials as it travels from the sun to Earth. If we put these two things together, we can deduce that it therefore must travel by radiation, and because of this, we call it solar radiation. Energy that is emitted from the Earth is called terrestrial radiation. Amazingly, every object or substance above absolute zero emits some energy via radiation. The amount of energy released is directly related to the temperature of the object or substance, and since the sun has a very high temperature, it makes sense that it emits so much energy. There is a flip side to this though, because all objects also absorb energy. The relationship here is the same as before. Objects that are good at emitting radiant energy are also good at absorbing radiant energy. The Earth is clearly not as good as the sun at emitting energy, which means it also can't absorb as much energy as it receives. And this is where the atmosphere becomes really important. The atmosphere does let in radiation, but also acts as a blanket to keep much of it trapped on Earth, which keeps the planet warm. However, if the gases in the atmosphere become too abundant, they may trap too much heat on Earth, These gases act like the walls of a greenhouse, which is why they're called greenhouse gases. But like a greenhouse, if there is no escape for the excess heat, then too much heat is trapped inside, and this can have detrimental effects on that temperature balance mentioned before. You're probably already aware that the Earth is not warmed in the same way across its entire surface. Otherwise, the North Pole would be a hot tourist spot, and Cancun would just be another city in Mexico. There's a few reasons for this unequal warming of Earth's surface. One reason is that the sun hits the Earth at different angles in different places. Along the equator, the sun's rays hit the Earth perpendicularly at a right angle, but at the poles, the sun's rays hit the Earth at a more indirect angle, spreading the light and energy over a larger area. You can do this at home with a flashlight. Point your flashlight directly at a wall, holding it at a right angle. There should be a nice bright circle concentrated right where you're pointing your light. Now tip the flashlight to different angles so that the light is not at a right angle. You'll notice that the light spreads out into an ellipse and covers a larger area of the wall. You're directing the same amount of light at the wall in both cases, but the amount of light that hits that same spot is very different. Another reason that temperatures vary across Earth is due to convection currents. Remember those from earlier? Heat is redistributed across Earth's surface through cell-like circulation currents of air. These currents are also responsible for the different types of environments we see across the planet. If you look on a map, you'll notice that rainy tropical areas tend to align across a specific region of Earth, as do the large deserts and polar regions. Solar radiation is the source of energy on Earth. This radiant energy comes from the sun, travels through space, then our atmosphere, and eventually reaches us here on the ground. We know this energy is transferred through radiation because it is transferred from one object to another without traveling through any type of material. If this energy was transferred via currents, we would call it convection, and if it was transferred through direct contact, we would call it conduction. All objects both emit and absorb radiant energy, but some are better than others. The Earth receives a lot of energy from the sun, but it can only absorb so much and requires a little help from the atmosphere to keep it here. However, when the gases in the atmosphere become too abundant, they help too much and trap more heat on Earth than is good for it. Solar radiation doesn't reach Earth the same in all places. When it hits the Earth at right angles, like it does along the equator, the energy is direct and much more concentrated than when it hits the Earth at less direct angles, like it does in the polar regions. The same amount of energy is spread over a larger area, so it is not warmed as much. Air currents also form cells around Earth, transferring energy from one place to another, and create unique regions like the tropics, the world's great deserts, and the poles.
At the start of every month, it's time for most responsible adults to complete a budget. You look at all the money you have coming in, everything you're paid for the jobs you do, and write down everything you'll have to pay for. Rent, electricity, water, gas, food. When you're done, you'll find out what, if any, money is left over. Maybe you want to go to a concert and see your favourite band with whatever's left. But you can't do that until you know that there's enough money in the budget. And if things aren't going so well, you might even be in the red. That's when it's hard to even pay the bills. The Earth also has a budget, a radiation budget. The Earth is a complex system, but we can look at the amount of radiation that goes into that system, like the pay from a job, and the amount of radiation that leaves the system, your expenses. The energy entering the system comes from solar incident energy. The solar incident energy is the amount of energy that reaches the Earth from the sun. Energy is measured in joules, but we usually measure incident energy in watts, which is joules per second, the amount of energy received from the sun every second. The energy leaving the Earth has two parts, the solar reflected energy and the Earth emitted energy. The solar reflected energy is the energy that, having arrived from the sun, just bounces back off into space. It might bounce off the upper atmosphere, or off the layers of clouds, or even off the surface of the Earth. And also leaving the Earth is the Earth emitted energy, which is the energy produced by the Earth itself. The Earth, and we humans, are constantly emitting infrared radiation. In fact, anything that contains heat energy will emit infrared radiation. We emit infrared radiation in all directions, but some of it leaves the Earth in the process. The global radiation budget is related to something called the greenhouse effect. The greenhouse effect is the trapping of the sun's heat in the atmosphere due to the fact that the sun's rays can enter the Earth, but infrared radiation has a harder time leaving. The sun's rays can enter the Earth's atmosphere, and most of them go straight through, arriving at the Earth's surface. But everything that contains any heat energy, like humans, animals, plants, the soil, all release infrared radiation too. While the atmosphere allows the sun's rays to go through it, infrared gets blocked and absorbed by greenhouse gases in the atmosphere. Those greenhouse gases then release that energy again, but they release that energy in every direction equally. Some of the infrared energy is released upwards and leaves the Earth into space, but some of it is released downwards and stays in the Earth. Because of this, some of the heat we receive from the sun gets trapped inside the Earth's atmosphere. It's as if the atmosphere is like a greenhouse, staying warm because the heat gets trapped, and that's called the greenhouse effect. Humans have been producing a lot of greenhouse gases in the last 100 years, and that's making the Earth warmer. But it's actually a good thing that the greenhouse effect exists at all. If it didn't, we would be freezing cold on the Earth. I'm not talking so cold you would have to wear thick sweaters. No, this is really cold, so cold that humans would never be able to survive. But with all the extra greenhouse gases humans are producing, the Earth's budget is no longer balanced. We've created a budget surplus of heat. But whereas a budget surplus in money terms is a good thing, when it comes to heat energy, it's not so good. At the start of every month, adults have to do a budget and see if they have any money left over. The Earth also has a budget, a radiation budget. The Earth is a complex system, but we can look at the amount of radiation that goes into that system and the amount of radiation that leaves the system. The energy entering the system comes from solar incident energy. The solar incident energy is the amount of energy that reaches the Earth from the Sun. Energy is measured in joules, but we usually measure incident energy in watts, the amount of energy received from the Sun per second. The energy leaving the Earth has two parts, the solar reflected energy and the Earth emitted energy. The solar reflected energy is the energy that, having arrived from the Sun, just bounces off back into space. It might bounce off the upper atmosphere, or off the layers of clouds, or even the surface of the Earth. Also leaving the Earth is the Earth emitted energy, which is the energy produced by the Earth itself. The Earth and we humans are constantly emitting infrared radiation. In fact, anything that contains heat energy will emit infrared. We emit infrared in all directions, but some of it leaves the Earth in the process. The global radiation budget is related to something called the greenhouse effect. The greenhouse effect is the trapping of the sun's heat in the atmosphere due to the fact that the sun's rays can enter the Earth, but infrared has a harder time leaving. This is the reason that we can survive on Earth without freezing to death, but it's also the cause of global warming, since humans are releasing more and more greenhouse gases every day. This gives us a budget surplus of heat, but whereas a budget surplus in money terms is good, when it comes to heat energy, it's not so good.
You may think that air is pretty simple, straightforward stuff, but this is far from true. Believe it or not, air is actually a mixture of different types of gas molecules. The components of air are important because they allow both plants and animals to breathe, trap heat on Earth, keeping it warm, and block harmful UV radiation from coming in through the atmosphere. However, these gases need to be present in just the right amount in order to do their jobs correctly. You may be surprised to learn that the most prominent gas in Earth's atmosphere is not oxygen. This is certainly an important component, but our atmosphere is in fact mostly nitrogen, about 78%. Oxygen is the second biggest player, making up about 21% of the atmosphere. Argon is next, but here we get another significant drop. Only 0.9% of the atmosphere, not even 1%. There are several other components, but they occur in such small quantities that they're all grouped together as other gases, and together they make up only 0.04% of the atmosphere. This other category contains components that you are likely familiar with: water vapor, carbon dioxide, helium, ozone, methane, hydrogen, neon, and carbon monoxide, just to name a few. There are also particles floating around the atmosphere like dust and pollen, and these are such a small fraction that they are less than 1/100,000th of a percent. These percentages may make it sound like there isn't much of anything but nitrogen and oxygen in the air, but it's important to remember that there is a whole lot of air up there. The atmosphere extends to over 300 miles above the ground and circles the entire planet. So while the other category makes up only 0.04%, that still covers a lot of space. You may have recognized some of the gases in the list of other components as greenhouse gases. This category as a whole makes up only a small fraction of the atmosphere, but just because they are small in numbers does not mean they do not play a large role. In fact, we should be glad that gases like water vapor, carbon dioxide, and methane occur in small amounts they do because they are such potent greenhouse gases. Like a thick blanket that covers Earth, they are especially good at trapping heat. And because their concentrations are increasing due to human activity, more heat than ever is being trapped underneath these gases, and Earth overall is warming. Ozone is also a small but very important component of the atmosphere. Ozone is made up of 3 oxygen molecules and is what protects us from harmful UV radiation coming from the sun. Ozone absorbs this radiation, blocking most of it from reaching us on the ground. This is why there is such a concern about the thinning of the ozone layer. If it can't do its job properly, then more UV radiation reaches us on Earth. This is a major issue because UV radiation makes us very sick. It causes skin cancer, cataracts, DNA mutation, and harms other plants and animals as well. Though you can't tell by looking at it, air is made up of many different components. About 78% of Earth's atmosphere is nitrogen, and only about 21% is oxygen. Argon makes up less than 1%, only 0.9% of the atmosphere is argon. Everything else occurs in such small amounts that they get grouped together as other components. These are gases such as water vapor, hydrogen, helium, neon, methane, carbon dioxide, and ozone. Particulate matter such as dust and pollen also contribute, but they make up less than 1/100,000th of a percent. Many of the components of the other category are greenhouse gases. These are small but mighty. Even though they make up a small percentage of the overall atmosphere, they are very potent gases, trapping heat underneath them like a giant blanket over Earth. To some degree, this is beneficial because we need Earth to be warm in order for us to survive. However, human activity is increasing their concentrations to dangerous levels, trapping too much heat on Earth and increasing global temperatures too much. Ozone is also found in the other category, but is no less significant. Ozone has the very important job of protecting us from harmful UV radiation, which causes cancer, cataracts, DNA mutation, and harms plants and other animals on Earth. It's important to remember that while the percentages of everything but nitrogen and oxygen sound small, there's a lot of air up there. Our atmosphere extends to over 300 miles above the ground and covers the entire Earth. So even small percentages of a lot are still, well, a lot.
Imagine that you're preparing for a rocket launch in which you and your crew will launch from the surface of the Earth in an attempt to repair the International Space Station. While it may be hard to believe, you actually won't be leaving the Earth's atmosphere for this mission. This is because the atmosphere of Earth actually extends hundreds of miles above the surface. In this lesson, we'll prep you for your mission by making sure that you're familiar with each layer of the Earth's atmosphere, starting at takeoff and ending with your rendezvous with the damaged satellite. The starting point for your mission is the troposphere, the lowest level of Earth's atmosphere. For the most part, this is where most of the aspects of the atmosphere that affect us on a daily basis occur. We breathe the air of the troposphere, which is a mix of mostly nitrogen with some oxygen and carbon dioxide, and we experience the weather that occurs in its highest reaches. In fact, the troposphere extends 14.5 kilometers above sea level, meaning that even while in a commercial airliner, we never leave the troposphere. At only 14.5 kilometers up, you're nowhere near close enough to be able to service the space station. However, considering that your rocket travels at 8 kilometers per second, which is a bit slow for a rocket to be honest, you'll be out of the troposphere in less than 2 seconds. In doing so, you'll be one of a small few to leave that layer of the atmosphere. Continuing upwards, you'll be in the stratosphere, the second of Earth's layers of the atmosphere. Here you'll find a few clouds, but the fact is that most of the weather takes place in the troposphere. Instead, you'll find only 2 real markers of human activity in the stratosphere. The first of these is the condition of the ozone layer, a blanket of air that helps to keep ultraviolet light out of the lower levels of the atmosphere. This is particularly helpful as ultraviolet light can cause some serious damage to much of the life on Earth. Second, you may see the distant jet trail of an airplane. Commercial airplanes often fly in the lower stratosphere. Most spy planes, such as the infamous U-2, fly even higher in the stratosphere to avoid being shot down by less capable planes. However, as rockets can still reach them, they're still in danger. Speaking of rockets in the stratosphere, as this layer of the atmosphere is only 40 kilometers from top to bottom, you'll be through it in 5 seconds from the time you entered it. I hope you remember to dress warmly for the next layer of the atmosphere. The mesosphere comes next, and it is the coldest of the 4 layers of the atmosphere. It's too far up to benefit from the warmth-catching abilities of the planet's clouds, but too far down to be warmed directly by the sun. In any event, it stretches from the top of the stratosphere, or around 55 kilometers above the Earth, for another 30 or 40 kilometers. This is also the start of the ionosphere, where trillions of charged atoms and molecules provide the network necessary for radio transmissions to work. Still, as the region is only a few kilometers from top to bottom, your rocket makes its way through in another 4 seconds. Less than 10 seconds into your trip, and you're already in the layer of the atmosphere that will serve as your final destination. The thermosphere is the highest of the 4 main layers of the Earth's atmosphere. It starts past the mesosphere, so about 100 kilometers or so above the Earth's surface, and then continues for 600 kilometers. Like the mesosphere, it is also home to the ionosphere. However, it is also home to some of Earth's satellites, as well as the International Space Station. As a result, it is your final destination. That said, if you were curious, if your rocket kept going the extra 2 minutes or so to get out of the thermosphere, you'd find yourself in the exosphere. Up here are more satellites, but mostly the atmosphere gives way to the depths of space. Let's review. In this lesson, we looked at the different layers of the Earth's atmosphere. There are 5 of them worth noting. The troposphere is the lowest level of Earth's atmosphere and extends from the surface to about 14.5 kilometers. The stratosphere is the second of Earth's layers of the atmosphere and extends for 40 kilometers past the troposphere. The mesosphere comes next, and while it's only 30 to 40 kilometers from one end to the other, it is the coldest of the 4 layers of the atmosphere. It is also home to the lower part of the ionosphere, where trillions of charged atoms and molecules provide the network necessary for radio transmission. The thermosphere is the highest, extending for more than 600 kilometers. It's where the International Space Station is. Beyond it is the exosphere.
Marley the meteorologist is back to teach you everything you want to know about temperature. Now, if you don't remember, Marley studies the weather and is going to take us around the world in order to investigate factors that influence the temperature, or how much heat energy is present on the Earth. So, pack your bags because we're about to head out. Let's start at the equator. Wow, it's nice and warm. The first thing that influences the temperature on Earth is the latitude, or how far north or south a place is from the equator. The equator is at a latitude of 0 degrees. Let's zoom in and check out a city that's pretty near the 0 degree latitude mark. Quito, Ecuador falls at 0.2333 degrees south latitude. The average monthly temperature only varies by about 1.8 degrees Fahrenheit throughout the year, and high temperatures hover around 70 degrees Fahrenheit. I don't know about you, but Marley seems to be enjoying herself in Quito. Why is it so warm at Quito? Because the Earth is round, the equator receives a lot of heat energy from the sun. The further north or south you go from the equator, the less heat energy the Earth receives. So, because of its location near the equator, Quito's temperature doesn't vary much and remains relatively warm. Now, let's head north to a latitude of 90 degrees. Brr, there's less heat energy up here, so the temperature is lower. The same holds true at 90 degrees south of the equator. Let's zoom in on a city that's near the North Pole, specifically 82 degrees north. Welcome to Alert, Nunavut in Canada. Unlike Quito at the equator, the average monthly temperatures vary by 66.6 degrees here in Alert. The average winter highs are in the -30s and summer highs are in the 40s. So, due to its location near the North Pole, Alert experiences huge variations in temperature as well as frigid temperatures. By comparing Quito to Alert, you can see what a big deal latitude plays in temperature. I can tell Marley is ready to get out of here. Next, let's look at altitude and elevation and how they influence the Earth's temperature. Now, before we climb any mountains, let's get our vocabulary straight because altitude and elevation are often interchanged. Altitude is the distance above a given point, whereas elevation is the distance above sea level. You often hear elevation used for geographical features like a mountain, and altitude used while traveling in a plane. So, why does the temperature change as you gain elevation? Grab your climbing gear, let's ascend a mountain and find out. As you climb, you may start to notice it's getting colder. Why? Well, as you ascend, the molecules in the air get further and further apart and are less likely to collide with one another. When molecules collide, heat is exchanged. So, with no collisions, there is less heat energy and the air cools. As we increase elevation, it gets colder. The same would hold true for altitude. As you gain altitude, say in a plane, the temperature decreases. If you check out mountain communities, you'll notice their average temperatures are quite a bit lower than areas at sea level. Let's get off this mountain and check out our next factor that influences the Earth's temperature. Atmospheric circulation patterns are due to uneven heating of the Earth as well as the Earth's rotation and causes cells of wind throughout the Earth. These winds redistribute heat. For example, warm air from the equator heads north where it cools, sinks, and heads back to the poles. Of course, it's a little more complicated and there are different cells, but you get the general idea. These cells cause wind like the polar easterlies, which can be found near the poles. The polar easterlies bring cold, frigid air into that region. Or, closer to the equator, you can find trade winds that blow warm, steady wind. Without these circulation patterns, heat would not be distributed, and the temperature ranges on Earth would vary even more dramatically than they already do. Okay, Marley can't wait to get to the next factor that influences the Earth's temperature. Let's head to the California coast to check out the difference in heating between land and water. It's a gorgeous day in San Francisco, and Marley is taking in the sights. But how will San Francisco teach us about the different heating and cooling of land and water? Excellent question. You might notice that during a hot, sunny day, a body of water feels chilly, but at night, the same body of water feels warm. This is because, compared to land, water takes a really long time to warm up. That's why the water feels cold compared to the sand when it's a hot, sunny day. But, on the flip side, the water takes a long time to cool down. So, at night, when the sand is cold, the water feels warm. In many coastal regions, like San Francisco, the ocean regulates the temperature on land. Remember, it takes water a long time to warm up. In the summer, when San Francisco gets warm, the ocean is a little cooler. This cold ocean water prevents the temperature from getting too high during those hot summer days. Now, fast forward to the winter. San Francisco gets colder, but the ocean takes a long time to cool down, so it still has some of the heat it obtained during the summer. As a result, the ocean keeps San Francisco relatively warm. If you were to compare the temperatures in San Francisco to a city a little further inland, like Bakersfield, you'd see the ocean prevents San Francisco's temperature from fluctuating too much. San Francisco's high temperatures range from about 57 degrees in January to the mid-60s in the summer. Compare that to Bakersfield, which has a January high of 56 degrees Fahrenheit and highs in the 90s throughout the summer months. Finally, let's check out how ocean currents impact the Earth's temperature. Like wind in the atmosphere, ocean currents move heat energy throughout the Earth. Also, like the atmospheric circulation, the ocean has patterns of circulation. Specifically, ocean currents are movements of water that redistributes heat energy and are made up of surface and deep ocean currents. Wind primarily influences surface currents, whereas differences in density results in deep ocean currents. Both of these types of currents are involved in a 1,000-year cycle that brings cold, dense, deep water from the poles to the equator and warm, less dense water from the equator to the poles. Let's check out a few examples. For the first example, we can stay on the west coast where the California current brings cold water from the poles to the west coast, thus cooling the west coast water. Now let's travel to the east coast of the United States where the Gulf Stream brings warm equatorial water to the North Atlantic Ocean, thus keeping the southeastern coast of the United States fairly warm. I don't know about you, but Marley's getting pretty tired. All of this travel sure takes a lot out of a person. Before we go, let's review the factors that influence the Earth's temperature. Starting with latitude. The further north or south you get from the equator, the colder the average temperature. Remember keto versus alert? Next, we climbed a mountain and looked at altitude and elevation and learned that the higher you get from sea level, the colder the average temperature. Then we looked at atmospheric circulation and saw how wind redistributes heat throughout the Earth from the trade winds to the polar easterlies. From there, we traveled to California, where we saw how the different heating of water and land results in mild climates along the California coast, like San Francisco. Finally, we examined ocean currents, where we saw cold ocean currents along the west coast and warm currents along the east coast. Wow, I can see why Marley's tired. Not only was that a lot of traveling, that was a lot of info. You've probably noticed temperature patterns. For example, it gets warmer during the day or cooler when it's cloudy. What if I were to tell you the same holds true on other planets as well? Although the focus of this lesson will be Earth, we're going to look at two extremes in order to examine why the temperature varies daily and annually on Earth. Think back to the fairy tale Goldilocks and the Three Bears, where things were too big, too hot, too small, or too cold. Earth, Mars, and Venus would have fit nicely into that fairy tale, with the Earth being just right and Mars and Venus having too little or too much of various temperature-altering properties. But more on that shortly. You might think that Earth's location in the solar system is what makes it the just right planet, but there's more to the story than proximity to the Sun. In fact, many things can affect daily and annual temperature patterns. It takes the Earth a little under 24 hours to rotate on its axis, and this is considered a day. As you know, during a day, there is a period of daylight and a period of darkness. Mars is similar to the Earth, with a day of a little over 24 hours. Venus, however, has an extraordinarily long day. In fact, one day on Venus is 243 Earth days. When the sun rises on Earth, Mars, or Venus, daytime heating takes place. Daytime heating, as the name implies, just means the rise in temperature that occurs during the day. This is caused by the sun's energy reaching the surface and then radiating back into the atmosphere. Some of that heat energy can radiate back into space, but much of it gets trapped due to greenhouse gases. Like their name suggests, greenhouse gases trap heat energy, like a greenhouse, which keeps the planet toasty warm. In our planetary Goldilocks story, the greenhouse gases on Earth are just right. This means that enough heat energy gets trapped so that, after the sun sets, the temperature doesn't cool off too much. Mars doesn't have as many greenhouse gases as Earth, so a lot of the heat energy from the sun radiates back into space. As a result, the temperature on Mars fluctuates dramatically when the sun sets, as much of the heat energy escapes. For example, during the summer near the equator, Mars can get to a comfortable 65 degrees Fahrenheit during the day. But at night, the temperature can drop to a frigid minus 130 degrees Fahrenheit. Venus, on the other hand, has a lot of greenhouse gases, so too much heat energy gets trapped, resulting in surface temperatures of nearly 900 degrees Fahrenheit. Yep, you don't have to worry about the temperature cooling off too much during the night on Venus. This leads us into nighttime cooling. As you've probably guessed, the flip side to daytime warming is nighttime cooling, or the cooling that occurs during the night due to heat energy radiating back into space. Remember, the greenhouse gases on Earth keep heat energy trapped, so, although the temperature does drop at night, a lot of the energy remains trapped and keeps it from getting too cold. Contrast this with Mars, whose temperature drops very quickly after the sun sets. Remember, 65 degrees Fahrenheit to minus 130 degrees Fahrenheit, and Venus, who has less temperature variation due to all the greenhouse gases. You might not realize it, but you are familiar with daytime heating and nighttime cooling on Earth. Just take a look at the weather forecast and you can see the daily highs are reached during the day due to daytime heating, and the daily lows are at night due to nighttime cooling. This heating and cooling pattern exists throughout the year, but due to seasons, the daily highs and nightly lows will vary throughout the year. Daytime heating and nighttime cooling are not the only factors that play into temperature patterns. Clouds reflect the sun energy that is coming to Earth. In fact, about 30% of the sunlight that reaches Earth is reflected back into space due to cloud cover. When weather forecasters predict the weather, they assume the temperature will be a little lower during the day if they suspect clouds, but a little warmer after the sun sets. This is because clouds act like a greenhouse, trapping heat energy, so it doesn't radiate away at night. Depending on where you live, you may notice a daily or annual pattern with clouds. Some regions, for example, experience more clouds during the afternoon. Other areas experience more clouds during the winter months. So if Earth has the just right cloud cover, what about Mars and Venus? Venus is almost 100% covered by clouds. This results in much of the sun's energy getting reflected away from the planet. But remember, the planet has a lot of greenhouse gases, so the heat that does enter the atmosphere gets trapped, causing sweltering temperatures. Mars, on the other hand, doesn't tend to have a lot of cloud cover, so the sun that reaches Mars is able to penetrate and reach the surface. That being said, remember also that Mars doesn't have much in the way of greenhouse gases, so even though the sun can reach the surface, a lot of the heat energy radiates back into space. Wind is another factor you must take into consideration. Wind distributes heat throughout the Earth, and it impacts the ocean, the atmosphere, and the land. Depending on where you live, wind can bring warm, cold, dry, or moist air into your region. For example, there are winds called the Chinook winds that bring warm air to the eastern parts of the Canadian Rockies during the frigid winters. In India, there are monsoonal winds that bring moist air from the ocean onto land. These winds often follow a pattern. The monsoonal winds, for example, bring rains to India during the summer and dry weather during the winter. For Earth, our winds are just right, even if you feel your area could experience a little more warm wind during the winter months. Before we check out planetary Goldilocks for wind, you need to know that, in order for wind to redistribute heat energy, there needs to be an atmosphere, and the thicker the better. So let's check out poor Mars, who has a thin atmosphere, which results in less heat energy being distributed. That's not to say Mars doesn't have wind. In fact, the winds on Mars can be quite strong, but because of the thin atmosphere, heat isn't distributed well. Venus, on the other hand, has an extremely thick atmosphere, in fact 100 times thicker than the Earth's, so temperatures do not vary as much on Venus because the winds distribute the heat energy throughout. But since temperatures are approaching 900 degrees Fahrenheit, the wind can't really cool down the planet enough to make it bearable. Although the focus of this lesson is daytime heating, nighttime cooling, clouds, and wind, we need to touch on other factors that impact daily and annual temperature patterns, like seasons, latitude, geography, and elevation. The tilt of the axis of the planet is what causes the seasons. The Earth's axis is tilted at about 23.5 degrees. When the North Pole is tilted towards the sun, that's summer solstice, and when the South Pole is tilted toward the sun, that's winter solstice. That not only applies to Earth, but other planets as well. Venus has a small tilt at 3 degrees, so there isn't much variation between seasons on Venus. Mars has a tilt similar to Earth at 25 degrees, but since Mars takes twice as long to orbit the sun, the seasons are longer. Other factors for the Earth, and elsewhere, include latitude, geography, and elevation. Generally, as you get further north or south of the equator, temperatures decrease. Geography impacts the temperature as well. Water and land have different heating and cooling rates, as do valleys and mountains. Finally, the higher you get from sea level, the cooler the temperature. Although Venus, Mars, and Earth are all rocky planets orbiting our sun, the Earth is the only one known to have life. Venus has a thick atmosphere which traps heat, causing temperatures to reach upwards of 900 degrees Fahrenheit on the surface. Mars has less of an atmosphere compared to Venus and Earth, which causes large temperature variations between night and day. Earth's ideal temperatures are due to its just right factors. For example, the Earth has the right amount of greenhouse gases to prevent too much of a variation between daytime heating and nighttime cooling. Mars has too little and Venus has too much. Next, the Earth has the right amount of clouds. Too few or too many alters the amount of sunlight that penetrates. Due to the thickness of the atmosphere, Earth is able to redistribute much of its heat energy through winds. If the atmosphere is too thin, like Mars, there is wind, but it isn't able to move heat energy around. There are other factors like seasons, elevation, geography, and latitude that impact the daily and annual temperature patterns in an area. So, as you might have gathered, there are a lot of factors that influence the daily and annual temperature patterns you witness, and, fortunately for us, the Earth is just right to provide a habitable living environment for us.
No two places on Earth will have exactly the same climate, which is the overall pattern of meteorological conditions, such as temperature, humidity, air pressure, wind, and precipitation. If this sounds a lot like weather, it's because climate is basically the long-term weather patterns of an area. While weather is a more day-to-day view of these variables, the climate of an area is these variables over a long period of time. Though no location on Earth will have exactly the same climate as another, many do have very similar climatic characteristics. In fact, these characteristics were first classified in 1884 by a Russian-German climatologist named Vladimir Köppen. Named after its founder, the Köppen climate classification system categorizes Earth's climates into 5 major groups based on the native vegetation present. He based his classification system on plants because he felt that they are the best representative of the local temperature, precipitation, and other variables that contribute to climate. Though vegetation helps us classify the major climate types on Earth, we tend to describe them in terms of temperature and humidity. The classifications start at the equator and work their way outward all the way to the polar regions. And to make it easy, the classifications are just letters of the alphabet. The first is A, which is along the equator, then B, C, D, and finally E at the polar regions. Group A, our first climate classification, is also known as humid tropical. This is what you would expect at the equator, a warm, wet climate. Temperatures here stay pretty warm all year round. Summer is the only season here. And we also find the world's rainforests in this region, like the Amazon. You could even think of Group A for Amazon. Group B is the next climate classification, one step away from the equator, both north and south. This is also known as the dry group because there is little moisture in the air here. Not surprisingly, we find the world's great deserts in this region, like the Sahara in Africa and the Great Victoria in Australia, so you could even think of Group B as the barren group. Like Group A, temperatures also stay fairly constant in this region, with little seasonal change throughout the year. Group C is our next classification, now 2 steps away from the equator. This group is also known as the humid middle latitude with mild winters region. So think of Group C for cold, since these regions do have winters, unlike Groups A and B. It's called humid because there's moisture in the air, middle latitude because it is about midway between the equator and the polar region, either north or south, and mild winters because while it may get cold and snowy, they are still fairly tolerable conditions. These areas have wonderful seasonal changes and occur in places like the central U.S., southern Europe, and central South America. Group D is our second to last classification, so we're getting pretty close to the poles now. You can think of these regions as Group D for darn cold, because the winters are much more severe than in Group C. This group is also known as the humid middle latitude with severe winters region. While closer to the poles, we're still in somewhat middle latitudes here, and the air is still moist, but man, these winters really are cold. Think of places like northern Canada and Siberia, and you'll likely understand why these get the severe winter classification. Our final group is Group E, the polar group. Think E for end of the line. You can't go any farther than the poles. Like Group A, there's no seasonal change here, but on quite the opposite end of the spectrum. As you might expect, this region is very cold all year round. Both the Arctic and the Antarctic regions of Earth are part of this climate classification. You can probably imagine that each of these major groups can be further broken down into more specific classifications. While the major classifications broadly describe the temperature and precipitation of a climatic region, the subdivisions get really specific about certain temperature ranges and the amounts of rainfall that occur during the year. In fact, there are 14 different subclassifications for Earth's various climates used to describe this information. Earth is a wonderfully dynamic place. Each location is unique in both its daily and long-term weather patterns. The long-term weather patterns of an area are known as its climate. Climates are determined by variables like temperature, humidity, air pressure, and wind. However, they are best expressed by the vegetation that grows here, since plants are fairly specific in the living conditions they can thrive in. From this school of thought, Vladimir Köppen created a climate classification system for Earth based on the native vegetation present, which we now call the Köppen climate classification. This system divides Earth's climatic regions into 5 groups named A, B, C, D, and E. We start with A at the equator and move through the alphabet until we reach E at the polar regions. The major groups are divided based on temperature and humidity. Group A is found at the equator, so it should not be surprising that this is also known as the humid tropical group. Here we find year-long summers and warm, wet areas like rainforests, like the Amazon. Group B is one step from the equator, both north and south, and is known as the dry group, think barren lands. This region contains the world's great deserts because even though the temperatures may be similar to Group A, the precipitation is quite the opposite. Group C is the group described as humid middle latitudes with mild winters because the air is much wetter than Group B, the region falls midway in latitude between the equator and the poles, and because winters are cold but certainly tolerable, so think C for cold region. It's in Group D that we have the humid middle latitudes with severe winters region. D stands for darn cold. Like Group C, the air is relatively moist, and we're still in a middle latitude range, but the winters are pretty unbearable. We find Siberia and northern Canada under this classification. Finally, we have Group E, the polar group. This is literally the end of the line. Just like its name suggests, this region contains both the north and south poles. Not only is the location of these regions opposite to Group A, but the climate is also dramatically different. Instead of endless summer, this area experiences endless winter. Bring your jacket if you plan to visit this region because it's about as cold as it gets on Earth.
Let's get started on our trip around the globe. Be sure to pack a large variety of clothing since the temperature will change drastically as we move from the equator to the poles. To begin with, take a look at this map so you can have a good understanding of where we will be going. We are going to start in that dark red area right along the equator. This is the area of the planet that receives the most direct sunlight, so it is nice and hot. You can leave your parkas and snow boots in your suitcase for now, but be sure to have your bug spray since we are going to the jungle. Right along the equator is where we find Category A, tropical moist climates. These are the tropical rainforests of the world. This climate zone is very hot and experiences high levels of rainfall year-round. The average temperature for all months throughout the year is greater than 64 degrees Fahrenheit. Traveling slightly north or south of the equator, we now find ourselves in B, dry climates. It is still really hot, but these are our deserts. So break out the sunscreen and sun hats. Summers are extremely hot and dry, and winters can get quite cold. Only very specialized plants are able to live in this environment, since it is possible for plants to lose more water through evaporation than they would receive through rainfall. As we continue to move away from the equator, we enter the yellow zone on our map. C, mid-latitude climates with mild winters. These are our temperate or comfortable climates. Here we have summers that are warm to hot with mild winters. The coldest month averages between 27 degrees and 64 degrees Fahrenheit. We are continuing on our trek and it's starting to get colder. We are entering Zone D, mid-latitude climates with cold winters. This is where we find the taiga, snow forests, or pine forests. Here, summers are warm. The hottest month averages above 50 degrees Fahrenheit. And winters are cold. The coldest month averages below 27 degrees Fahrenheit. All right, we've made it to Zone E, polar climates, or the Arctic. Here you must be very careful going outside. In the winter, if you are not dressed properly, you can get frostbite in under 10 minutes. In the Arctic, the average temperature for the warmest month is below 50 degrees Fahrenheit. As you probably noticed during our trip, you can see a lot of variability within each of the climate zones. For example, the steppe and the desert are both part of Zone B, dry climates. This is where the subcategories of the Köppen climate system come into play. These subcategories seem overwhelming at first, but they do follow a pattern. With a little bit of patience, you will be rattling them off in no time. Lowercase letters F, M, S, and W are used to differentiate patterns of rainfall and are only used for the moist climate categories, zones A, C, and D. F is for rainfall and indicates precipitation all year round with no dry season. Zone AF, for example, is tropical wet. This is a jungle that receives rainfall evenly dispersed throughout the year. The driest month still receives at least 2.4 inches of rain. S stands for a dry summer season, and W stands for a dry winter season. Zone AW is tropical wet and dry. In this climate, there are more than 2 months with less than 2.4 inches of rainfall. This will be considered the dry season, and as the category indicates, it occurs during the winter. M is for monsoon. Monsoon climates have a definite wet season and a short dry season. Dry months receive less than 2.4 inches of rain. This category is only found in Zone A as the classification AM, tropical monsoon. As we discussed earlier, Zone B, the dry climates, are further broken down into the uppercase letters S and W. S is for steppe, the semi-dry zones. W is for deserts, or dry zones. Though it is a bit dramatic, you can think of W as standing for wasteland. The polar climates, Zone E, also have 2 subtypes, indicated by the capital letters F and T. T is for tundra, and F is for frozen. Zone EF, for example, is the polar ice cap and is permanently covered in ice. Zone ET is the polar tundra, which thaws during the summer. Zones B, C, and D, which cover the majority of the planet, are even further divided into a third subcategory. Zone B, the dry climates, also use the lowercase letters H and K for hot and cold. In dry climates designated with an H, the coldest month stays above 32 degrees Fahrenheit. In dry climates designated with a K, the coldest month drops below 32 degrees Fahrenheit. Zone BWK, for example, indicates a cold desert. Finally, for zones C and D, the mid-latitude climates, the lowercase letters A, B, C, and D are used to signify seasonal differences in temperature. A is for hot summers, where the warmest month is over 72 degrees Fahrenheit. B is for warm summers, where the hottest month stays below 72 degrees Fahrenheit. C indicates cool, short summers, with the majority of the year under 50 degrees Fahrenheit. D indicates very cold winters, with the coldest month dropping below negative 36 degrees Fahrenheit. For example, Zone CFC is marine cool winter. This is a mild climate with no dry season and cool summers. The average temperature of all months is under 72 degrees Fahrenheit. Most months are under 50 degrees Fahrenheit. Here is a map that shows the entire breakdown of the Köppen climate classifications. I hope you enjoyed our trip. Before you go, let's review what we have learned. The hottest part of the globe is the equator, which receives the most direct sunlight. This is climate zone A, tropical moist climates, the tropical rainforests of the world. As we move away from the equator, either north or south, the temperatures start to cool down and the climates change. Category B, dry climates, are the deserts. Most of the world lives in zones C or D. Category C, mid-latitude climates with mild winters, are the temperate or comfortable climates. Category Zone D, mid-latitude climates with cold winters, is where we find the taiga, snow forests, or pine forests. Finally, Zone E, polar climates, is the Arctic. Since there is a lot of variability within the zones, subcategories help us further distinguish the global climates. The moist climate zones, A, C, and D, use the lowercase letters F, M, S, and W to differentiate patterns in rainfall. F stands for rainfall and indicates climates without an obvious dry season. M is used for tropical climates with a monsoon weather pattern. These areas have a short dry season of only a couple months. S and W indicate defined dry seasons. For category S, the dry season is in the summer, and for category W, the dry season is in the winter. Zone B, the dry climates, have subcategories indicated by the capital letters S and W. S is for steppe, which is semi-dry, and W is for the dry desert. You can think of W as standing for wasteland. Similarly, Zone E, the polar climates, also have subcategories. The uppercase F for frozen is permanently covered in ice. The uppercase T for tundra thaws during the summer months. Zones B, C, and D have a third subcategory. Zone B, the dry climates, use the lowercase letters H for hot and K for cold to indicate whether or not the climate freezes during the winter. Zones C and D use the lowercase letters A, B, C, and D to distinguish between seasonal differences in temperature. A represents the warmest seasonal averages, and D represents the coldest seasonal averages. Ah, California, home of beach weather in the summer and 60-degree days in the winter. Who wouldn't want to live there? But how exactly did Californians get so lucky? Why is their weather so wonderful? The answer to that has to do with the beautiful Pacific Ocean right next door. The California coast has what is called a maritime climate. In other words, its climate is influenced by oceanic air patterns. Maritime climates tend to have cool summers, warm winters, and a minimal change in temperature throughout the year. San Diego, famous for its year-round beautiful weather, has a high of 65 degrees Fahrenheit in January and a high of 75 degrees in July. That's a change of only 10 degrees from January to July. Compare this to continental climates. Continental climates do not have the stabilizing influence of a neighboring large body of water. Thus, their summers are hotter, winters are more severe, and temperatures change more drastically throughout the year. Omaha, Nebraska, for example, has a high of 33 degrees Fahrenheit in January and a high of 87 degrees in July, a 54-degree change. Okay, but this still does not really tell us why maritime climates are more temperate than continental climates. To understand this, we need to discuss heat capacity. An object's heat capacity is the amount of heat required to raise its temperature by 1 degree Celsius. Water has twice the heat capacity as land. This means it takes a lot more sunlight to raise the temperature of water than it does to raise the temperature of land. And, conversely, it takes a lot longer for the temperature of water to go back down. So, land heats up and cools down quickly, allowing for quick and extreme changes in temperature. If you live in an area that is near an ocean or a large lake, this difference in heat capacity works in your favor. The ocean tends to keep the surrounding air, and thus the surrounding environment, at a more stable temperature. Okay, but New York is also by an ocean. The high in January is 39 degrees Fahrenheit, and the high in July is 85 degrees. That is a change of 46 degrees from January to July. That's more mild than Omaha, but not nearly as nice in San Diego. Why is that? This is the result of prevailing wind patterns, or the primary direction of the wind in a certain area. If you look at the map, the prevailing winds across the United States are westerlies. Thus, the milder temperatures from the Pacific Ocean are being blown across California, while the more severe temperatures from the Midwest are being blown into New York. This results in a less temperate climate on the East Coast than on the West Coast. So let's summarize. Maritime climates, like those on the west coast of the United States, are influenced by oceanic air patterns. They tend to have cool summers, warm winters, and a minimal change in temperature throughout the year. Compare that to continental climates, which do not have the stabilizing influence of a nearby large body of water. These climates have hot summers, cold winters, and drastic changes in temperature during the year. The difference in these two climates is the result of water having twice the heat capacity as land. Heat capacity is the amount of heat required to raise the temperature of a substance 1 degree Celsius. It takes much longer for water to both warm up and cool down. Thus, the surrounding air stays at a more steady temperature. Prevailing winds, or the primary wind direction in an area, also have an effect on the climate. Even though the climate of New York is stabilized by the Atlantic Ocean, it is still not as mild as the climate in San Diego. This is because the prevailing winds of the United States blow the extreme temperatures of the Midwest into the city. Our Earth was born from a cloud of dust and space particles around 4.5 billion years ago. That's a really, really long time ago. During this long existence, the Earth's climate has changed many times. There have been periods when the Earth has been covered in ice over 1 kilometer thick, and there have been times when the Earth has been much warmer than it is today. Over the last 650,000 years, the Earth's global temperature has gone up and down in a regular pattern. Scientists have linked these cycles in our Earth's climate to several factors, including changes in solar radiation, changes in atmospheric turbidity, and changes in radiation-absorbing atmospheric gases. In addition to factors that change Earth's temperature globally, phenomena such as changes in the Earth's orbit and changes in the Earth's surface affect climates locally. Just as the Earth experiences periodic changes, so does the Sun, and these changes in the Sun can lead to climate changes on Earth. A sunspot is, just like it sounds, a dark spot that sometimes appears on the Sun's surface. Sunspots are the result of concentrations of the Sun's magnetic field. This results in cooler surface temperatures and thus a darker color. The increased magnetic activity of sunspots lead to greater solar radiation hitting the surface of our planet. Thus, high sunspot activity is associated with warmer climates on the surface of the Earth. As an example, the Maunder minimum was a period from about 1645 to 1715 where very few sunspots were seen. Scientists theorize that this lack of sunspot activity is linked to the coldest period of the Little Ice Age, which lasted from around 1300 to 1870. Atmospheric turbidity refers to the amount of tiny particles, such as water droplets, dust, and smog, suspended in the air. Increased turbidity scatters the sun's rays. This makes it harder to see, but it also means that less direct solar radiation is hitting the Earth. These tiny liquid or solid particles suspended in the atmosphere are also referred to as aerosols. Aerosols reflect incoming solar radiation, bouncing it back into space. As a result, less radiation makes it to the Earth's surface. So, an increase in atmospheric aerosols creates a cooling effect on the planet. If you look at this diagram, periods of high dust concentration in the atmosphere, that's the red graph at the bottom, coincide with lower global temperatures, the blue graph on top. Certain gases in our atmosphere allow the radiation from the sun to pass straight through to Earth's surface. Some of this radiation is then bounced back off the planet. However, this time, since the Earth is nowhere near as warm as the sun, the radiation is less intense with a longer wavelength. These same gases that just let the sun's radiation through now reflect the longer wavelength radiation back to Earth, trapping the warmth within the atmosphere. This is known as the natural greenhouse effect. the warming of the Earth's surface and atmosphere through the trapped energy of the sun. These natural greenhouse gases include water vapor, carbon dioxide, and methane. The gases in the atmosphere are serving the same purpose as greenhouse gas. They are letting in the sun's warmth and trapping it inside so the greenhouse, our planet, heats up. The greenhouse effect is a good thing. Without it, our planet would be a cold and inhospitable place. The greenhouse gases go through a natural cycle that coincide with the warming and cooling of our planet. We hear so much about greenhouse gases in the news lately because, through factories, cars, and the burning of fossil fuels, humans are dumping many more greenhouse gases into the atmosphere than can be considered natural. Because of this, our planet is heating up much quicker than would otherwise be expected. Other climate-changing factors do not necessarily affect the temperature of the entire planet. Nonetheless, these factors can cause significant changes in individual regions. As I'm sure you remember from grade school, the Earth rotates on its own axis. At the same time that it is rotating, it also orbits the sun. While you may expect Earth's rotation and orbit to always remain the same, it actually doesn't. Remember, the Earth is very, very old and has gone through many changes in its long life. The Earth's obliquity refers to the angle of Earth's tilt on its rotational axis. Currently, the Earth is tilted at 23.4 degrees from straight up and down. Over a time period of 41,000 years, this angle travels from 22 degrees to 24.5 degrees. This change in tilt affects the climates of particular regions on the planet. The areas that begin to receive more direct sunlight as the Earth tilts will become warmer. The areas that start receiving less direct sunlight will cool down. Eccentricity refers to the shape of the Earth's orbit around the sun. Over a period of approximately 100,000 years, our Earth's orbit changes from almost circular to highly elliptical. Currently, our orbit is quite circular. When the Earth's orbit is very elliptical, either the northern or southern hemisphere boils in extremely hot summers and freezes in severely cold winters. The opposite hemisphere basks in warm summers and mild winters. And finally, due to the gravitational pull of other bodies in the solar system, particularly the Sun, the Moon, and Jupiter, the Earth undergoes a phenomenon known as precession, or the wobbling of the Earth as it spins on its axis. Similar to a spinning top, the Earth appears to sway as it spins on its axis. Again, this wobbling effect does not alter the climate of the entire planet. It does, however, affect individual regions by making summers and winters in some areas longer and more severe. At the same time, other areas are blessed with summers and winters that are shorter and milder. Earth has developed since its birth 4.5 billion years ago, and it looks very different today. The outer surface of the planet, known as the lithosphere, is made up of the crust and upper section of the mantle. The lithosphere consists of 12 plates that are constantly shifting and moving past each other. As the land masses on top of these plates change positions, they interrupt surface ocean circulation, redirecting the circulation of warm and cold water as a result. Water temperature has a huge influence on the local climate. Florida is infamous for its hot, humid summers. These summers are caused, in part, by the warm waters from the equator flowing up and through the Gulf of Mexico. Thus, as the plates move and interrupt the warm and cold water currents, local climates will change in response. As the lithospheric plates collide into one another, they create mountain ranges. North-south oriented mountain ranges in particular interrupt atmospheric circulation, again redirecting the circulation of warm and cold air. Just as local water temperature affects regional climates, so does air temperature. As land masses shift and modify the warm and cool air currents, the nearby climates will adjust accordingly. So let's summarize. Our Earth has gone through many predictable periods of cooling and warming in its long history. Scientists have linked these climate cycles to various observable factors. Changes in solar radiation are caused by sunspot activity. An increase in sunspot activity leads to greater radiation hitting the Earth and is thus associated with warmer climates. Atmospheric turbidity refers to the amount of tiny particles, such as water droplets, dust, and smog, suspended in the air. These tiny particles, also referred to as aerosols, reflect the sun's radiation back into space and thus have a cooling effect on the planet's surface. The natural greenhouse effect is the warming of the Earth's surface and atmosphere through the trapped energy of the sun. The natural greenhouse gases include water vapor, carbon dioxide, and methane. Greenhouse gases go through a predictable cycle that coincides with the warming and cooling of our planet. Changes in Earth's orbit include obliquity, eccentricity, and precession. These changes do not alter the Earth's temperature overall. Rather, they create more localized climate changes, affecting only particular regions of the planet. Obliquity refers to the angle of Earth's tilt on its rotational axis. Eccentricity refers to the shape of the Earth's orbit around the sun. Precession is the wobbling of the Earth as it spins on our axis. Our planet's lithosphere is broken into 12 plates that are constantly moving past each other. As the physical characteristics of the Earth's surface change, the circulation of warm and cool air and water is shifted, and local climates are affected as a result.
Droughts, superstorms, melting glaciers, oh my! We hear about extreme weather events often and are told that they are the result of a changing climate. Global warming is changing our climate by heating the Earth's temperature. But isn't that weather? What is the difference between weather and climate? Just like weather, climate is affected by many factors that do not change rapidly, like ocean currents, gases in the atmosphere, and moving continents. In this lesson, we'll explore how these factors can have a big effect on what we see and the kinds of conditions we can expect. Weather and climate are terms that are related, but do not mean the same thing. Weather is the state of the atmosphere at a given time and place. For instance, this would be if it currently was sunny today and what the temperature is, or if we were expecting clouds and rain tomorrow. Weather is what is forecasted from day to day. Climate is the long-term average of the weather of an area. This would refer more to the type of weather you could expect at different times of the year. Normally, the northern U.S. can expect snow and below freezing temperatures in winter and warm summers with some humidity. These expected weather patterns, together with other factors, make up our climate, which generally remains unchanged over the span of a human lifetime. There are many factors that can influence the climate of a region. One of the main things that determines the climate of an area is the circulation of air in the atmosphere. The atmosphere is the blanket of air that surrounds the Earth. The atmosphere circles air in patterns or in a band caused by the heating of the Earth by the sun and the Earth's rotation. Air near the tropical regions rises as it gets heated, while cooler air near the poles sinks. Warmer air has more energy and is less dense than cooler air, which causes this rising and sinking action. However, the Earth's rotation also has an effect on this movement of air by breaking the rising and sinking action of air into 6 distinct sections. These bands alternate the direction of wind flow, much like the bands that are seen on Jupiter. For instance, near the equator, the prevailing winds move from east to west and are known as trade winds, shown in yellow and brown on the map. Next, the blue arrows show the bands of air that travel west to east, the dominant wind pattern for the United States, and are known as the prevailing westerlies. This difference can be seen anytime a hurricane gets close to us and we begin tracking it. As the storm forms in the Atlantic, it moves from east to west, caught up in the trade winds. As it moves north near North America, its direction will begin to shift back to the east, as it moves into a band of air moving in the opposite direction. Another effect on climate can come from the composition of the atmosphere itself. The greenhouse effect is when gases naturally trap heat in the atmosphere, moderating the Earth's temperature. These gases include carbon dioxide, methane, and water vapor. If the percentage of these gases changes over time due to natural or man-made effects, then the amount of heat held in can change also. This is the concern with global warming, that we're adding too much carbon dioxide to the atmosphere, warming the planet. Another factor that influences climate is how the Earth distributes heat. Large bodies of water along with ocean currents greatly influence a region's climate by holding and redistributing heat through the water, adding moisture to the air and influencing the strength and direction of the wind. Ocean currents move heat around from areas that are warmer to areas that are cooler, adding energy and moisture to new regions. An example of ocean temperature's effect on our weather and climate is the El Niño effect that occurs in the Pacific. In El Niño, a band of water near the equator becomes warmer than normal and transfers extra heat, disrupting normal weather patterns. In the United States, this can cause warmer, drier winters with less snow in the northern states and more rain and cooler temperatures in the southern states. The movement of air as wind accomplishes this task too because the amount of sunlight that is transformed into heat also plays an important part in our climate. Without the movement of heat through air, the temperature in areas that receive more sunlight would continue to rise, becoming extremely hot, and areas like the poles would be extremely cold since heat received would be much less than what is lost. Areas would cease to have changes in seasons, and a much more difficult time sustaining growing seasons and moderate temperatures. The continents and landforms also influence climate. Mountain ranges, for instance, force air masses to change elevation. As air approaches the mountains, it rises and cools, forms clouds, and releases much of its moisture as precipitation. This can be seen in clouds that are often surrounding the tops of mountains. Often, the higher the elevation, the more that precipitation occurs. This is known as the orographic effect. The orographic effect states that cooler air will hold less moisture than warmer air. On the opposite side, air can sink again, which allows it to warm and absorb moisture by producing less clouds, more sun, and less precipitation. This drier side of a mountain range is known as rain shadow, or the dry area on the leeward side or backward side of a mountain. The difference in precipitation can be quite dramatic. The driest desert in the world is the Atacama Desert in Chile, and receives less than 0.5 millimeters of rain each year, while the windward side might receive hundreds of centimeters. Another way that continents can determine climate on a much longer scale is by the movement of the continents themselves. For instance, there is fossil evidence of tropical plants that has been found on Antarctica. It is clear to scientists that Antarctica was at one time much warmer than it is now, and the discovery of mechanisms that cause the plates and continents of the Earth to move a few centimeters each year reinforce that idea. Climate is determined by the kinds of weather that a location experiences over a long period of time and does not change much over the span of a human's lifetime. The factors that determine climate include global wind patterns in the atmosphere, like the westerlies and the trade winds. Large bodies of water and circulation of air are also important for distributing heat around the globe. Landforms like mountain ranges can also affect climate. They can force air masses up, forming clouds and precipitation on the windward side, which is known as the orographic effect. And they can produce drier, clear air on the backside, known as rain shadow. Finally, continental movement can change the climate of a region over thousands of years as it migrates to a different latitude. Prediction of climate is very difficult and relies on complex computer models. However, scientists are working on accuracy to give us an idea of what our weather patterns will be like in the future. One thing is for certain, our climate changes over time and will continue to do so in the future.
You probably don't realize that every time you step outside, ozone, a gaseous molecule of 3 oxygens, makes it possible for you to do so without reaping the harmful effects of the sun's radiation. This helpful ozone is found in the stratosphere, which is the atmospheric layer just above where life exists and weather occurs. When that same gaseous ozone is found in our lower layer, called the troposphere, it is considered an air pollutant and is very harmful to human health. However, we need it in the stratosphere because even at the low concentration of 12 parts per million, ozone is so effective at absorbing the sun's UV radiation that this small amount is plenty enough to protect us on Earth. Just how harmful is UV radiation? In humans, UV radiation causes skin cancer and cataracts. UV radiation also affects the fertility of other animals, as well as the viability of their offspring. Plants are affected by UV radiation because it affects their ability to grow and develop correctly. As you'll see later, UV radiation also influences how chemicals break down and react, and this can lead to catastrophic changes in environments and ecosystems. You've likely heard about the ozone hole, or thinning of the ozone layer, but you may not know what causes these problems. These discoveries came about through many years of scientific research, so let's take a trip back in time to gain a better understanding of how the ozone layer has been affected by human activity. It all began in the 1960s when scientists noticed that their measurements of ozone in the atmosphere were lower than what their models predicted they should be. The scientists believed that either naturally or artificially created chemicals were somehow depleting the ozone. It turns out that these chemicals were something called chlorofluorocarbons, or CFCs. These are compounds used for refrigerants, fire extinguishers, and aerosol propellants. CFCs were invented in the 1920s and were originally thought to be environmentally friendly, but in fact they break down ozone in the presence of UV radiation. What happens is this: a chlorine molecule from the CFC is released from the compound by the UV radiation. It then reacts with the ozone molecule, O3, leaving a molecule of oxygen gas, O2, and a molecule of chlorine monoxide, ClO. The chlorine on this molecule is free to react with a single oxygen atom and then breaks away, leaving another O2 molecule and the free chlorine atom. This chlorine atom is now floating around the stratosphere, ready to break apart another ozone molecule into atmospheric oxygen, continuing the cycle until the chlorine atom breaks down. Unfortunately, the chlorine may not break down for 1,000 years or more. Okay, so now that we know how CFCs break apart ozone, let's go to the early 1970s, where CFCs are being mass-produced at an annual rate of 1 million metric tons and growing by 20% each year. In 1974, two scientists named Sherwood Rowland and Mario Molina were able to demonstrate how CFC molecules were splitting ozone molecules into atmospheric oxygen and chlorine monoxide molecules, and this work earned them the 1995 Nobel Prize in Chemistry. Their research helped put new policy into motion, and by 1979 the US and other countries had banned CFCs in aerosol sprays, but not for other uses. Fast forward to 1985, when a new and shocking discovery sparked action across the world. British scientists who had been measuring ozone concentration at a research station in Antarctica since the 1950s discovered that the ozone above this region had declined by as much as 60% in the previous 10 years. This extremely thin layer of ozone above the region became known as the ozone hole, and over the next several years it was confirmed that CFCs were the cause of so much thinning. Let's jump one more time, now to the Montreal Protocol of 1987. When it was originally drafted, 24 different nations signed this treaty agreeing to reduce CFC production by at least 50%. Since then, 5 more agreements have followed up this original one with more severe cuts to CFC production and other ozone-depleting chemicals. At present, it includes almost 200 different signatory nations from all over the world. Finally, we come to the present, where the use of ozone-depleting chemicals is down 95% from what it was in the 1980s. According to NASA, the hole in the ozone layer in 2019 was the smallest since 1982. The ozone is slowly beginning to recover and rebuild, but a major concern is that many of the ozone-depleting chemicals that were emitted years ago have yet to react with UV and split ozone molecules in the stratosphere. And as mentioned before, CFCs take a very long time to break down, so there are many chlorine molecules still floating around, continuing their destructive cycle. Ozone is quite the double-edged sword. When found at ground-level atmosphere, this gas serves as a dangerous, harmful pollutant. As a molecule in Earth's stratosphere, it protects us by absorbing harmful UV radiation from the sun that causes a variety of health problems in humans, plants, and other animals, as well as damages ecosystems. The ozone layer in the stratosphere is thin but powerful. However, because it occurs in such a low concentration, it is vulnerable to ozone-depleting chemicals such as CFCs. CFCs are compounds that react with ozone in the presence of UV light by splitting the 3 oxygen atoms into one O2 molecule and one ClO molecule. The ClO molecule may react with a single oxygen atom, creating more atmospheric oxygen and a single chlorine atom, which is then free to start the cycle anew. It took many decades and several dedicated scientists such as Rowland and Molina to describe the harmful effects of CFCs on the ozone layer. The Montreal Protocol was originally signed by 24 different countries in 1987, and now almost 200 nations have vowed to reduce their CFC production and use in order to curb this global problem. Because of this and other legislation that followed, the production and use of ozone-depleting chemicals has been reduced by 95%. However, because CFCs may take 1,000 years or more to break down, the recovery of the ozone layer may be a long, slow process.
"97% of climate scientists agree we are drastically altering life on Earth and creating global climate change. The cause of this change? Human activities that increase emissions of greenhouse gases such as carbon dioxide, methane, and ozone. Greenhouse gases are important because when present in the right amount, they trap heat under the atmosphere and keep Earth hospitable. However, in the last century, greenhouse gas emissions have risen to unprecedented levels in the atmosphere. The current concentrations are far too high and are trapping too much heat on Earth. This leads to an overall increase in the temperature of the planet, which affects many other components of our global climate system. Over the past 100 years, the temperature of Earth has increased by an average of 1.5 degrees Fahrenheit. This may not sound like a lot, but think about your body temperature. A healthy temperature is 98.6 degrees Fahrenheit. If you raise this by 1.5 degrees, you would then have a temperature of 100.1 degrees Fahrenheit. That's a fever and a pretty sick person. If you've ever had a fever like this, you know how awful it feels. You're hot and cold, you don't have an appetite, and you just want to lie in bed until you get better. Now take into account that this is the average temperature change on Earth. That means that some places are experiencing much greater changes than just that 1.5 degrees. People tend to associate global climate change with just increasing temperatures, but much like your body goes through cycles of extreme hot and cold during a fever, the Earth experiences something very similar. As mentioned before, temperatures on Earth have increased in the past 100 years like never before, and in that period, 10 of the warmest years on record have occurred since 1997. Not only do temperatures become more extreme, but storms and weather events also increase in severity as temperature rises on Earth. Hurricane Katrina and Superstorm Sandy are both examples of extraordinary hurricanes, while Oklahoma was recently devastated by a mile-wide tornado. Why are these storms so much more intense? They get their energy from warm water and wind, and since both of these are becoming warmer along with the Earth, this gives the storms more power and the ability to cause more damage. In addition to storms, other natural disasters are becoming more frequent and severe. This year, Colorado was shocked by a raging wildfire like never before. Dangerous forest fires have also taken their toll on the southwest U.S. and California, killing people and causing extensive damage. These fires are the result of drier conditions and extended summer seasons. And speaking of drier conditions, droughts have also become more prevalent as Earth heats up because warmer temperatures mean more moisture evaporates from land. These extreme droughts have caused economic hardships for farmers and ranchers worldwide. What happens when things heat up? They melt. Polar ice caps and glaciers are certainly no exception to this. Of all the fresh water on Earth, more than 2/3 is stored in frozen ice caps and glaciers. As they melt into the oceans, they increase the overall volume of liquid, which has to go somewhere. Unfortunately, that somewhere is the land that many people call home. Since the extreme warming of the Earth started 100 years ago, sea levels have risen almost 7 inches. Again, this may not sound like much, but think about this. Around the world, about 100 million people live within 3 feet of sea level. If the rate of increase were holding steady, 7 more inches in another 100 years might not be so bad. But considering the rate of sea level rise in the past 10 years was twice the rate of the past century, we are likely going to lose more than another 7 inches of land. Many plants and animals also make their homes along shorelines. These species are uniquely adapted to their environments, and with rising sea levels, they will be forced to move inland or may simply go extinct, meaning they will be gone from Earth forever. As the polar ice caps and glaciers melt, other animals such as polar bears and Arctic birds are also at risk of extinction. In tropical areas, coral reefs provide critical habitat for hundreds of species, but warmer ocean temperatures are killing the vegetation that helps corals survive. Bird migration routes are drastically changing as they search for cooler climates, and many species that are not able to migrate will simply die in the hotter weather. This all seems pretty doom and gloom, but there are people and organizations who are dedicated to understanding and mitigating global climate change. NASA is one organization that provides data to help researchers understand the impacts of climate change on Earth. NASA does this by studying Earth from space. Satellites and other spacecraft orbit Earth and collect information about Earth's land, oceans, and atmosphere. The Environmental Protection Agency, an organization created for the purpose of protecting human health and the environment, is also a key data collector. They focus much of their efforts on greenhouse gas emissions data. The data are provided to policymakers and organizations that need this information to impact decisions and policies regarding emission standards and renewable energy sources. Some companies are developing new technologies to make us more energy efficient, while others are interested in making renewable energy sources more affordable. Many cities are working to become more bike-friendly, provide better public transportation, and offer rebates to citizens who install energy-efficient appliances. Another important way we can slow climate change is by protecting natural resources. Forests and oceans are very good at absorbing carbon, which keeps it out of the atmosphere. Agriculture, a major producer of greenhouse gases, can also be more efficient through proper land use and modified irrigation systems. Public education is by far the best way to spread the word about global climate change. Becoming educated and sharing your knowledge with others will help people understand not only what is happening on Earth as temperatures increase, but also what steps they can take in their personal lives. Over the past 100 years, the temperature on Earth has increased at an alarming rate. On average, the Earth has become 1.5 degrees Fahrenheit warmer, which is similar to you going from a normal body temperature to a fever, but on a much larger scale. Like having a fever, the Earth experiences extreme temperature changes, which leads to other issues such as altered weather patterns, more intensive storms, and more severe and frequent droughts and forest fires. A warmer Earth also means that glaciers and polar ice caps will continue to melt. This melting water will add to the oceans and raise sea levels. Over the past 100 years, sea levels have already risen almost 7 inches and are continuing to rise more quickly as time passes. Sea level rise not only affects humans, but also the plants and animals along shorelines. Other habitats are also affected by global climate change, and the loss of natural habitat will force organisms to search for new habitat or possibly go extinct. In order to understand the effects of global climate change, scientists and organizations continue to collect data and share their findings with other organizations, companies, policymakers, and the public. Incentives for energy-efficient products and making renewable energy sources more affordable are current methods being used to try and offset the dangerous impacts of global climate change that we are already experiencing on Earth.
Just like you may occasionally update your wardrobe and hairstyle, our Earth's surface has gone through some pretty drastic overhauls during its lifespan. Approximately 600 million years ago, our planet was a giant ball of snow and ice, covered in frost over a kilometer thick from the poles to the equator. During the dinosaurs' time, around 120 million years ago, a multitude of erupting volcanoes dumped greenhouse gases into the atmosphere, creating a hot, humid rainforest. This was one of the warmest periods in Earth's history. Obviously, though, there were no humans around to see this. So how do we know that all these changes actually happened? Paleoclimatology is the study of the changes in Earth's climate throughout the history of our planet. Paleoclimatologists have several means of measuring the changes in climate, including taking ice core samples, observing remnant glacial landforms, surveying the sediment on the ocean floor, and studying the fossils of ancient vegetation. Ice core samples are cylinders of ice drilled out of a glacier. Yearly snowfall collects on the surface of the glacier, burying the layers below. As the snow turns into ice, air bubbles are trapped, preserving samples of the Earth's atmosphere within. Scientists drill deep into glaciers, removing portions for study. This allows them to take a peek at what our atmosphere was like many thousands of years ago. The oldest ice core samples we have taken so far contain ice that dates back 800,000 years. Ice core samples allow paleoclimatologists to measure the Earth's past climate in a couple of ways. First, trapped samples of atmosphere allow scientists to measure the concentration of greenhouse gases. Higher concentrations of greenhouse gases in the atmosphere lead to higher temperatures on the surface of the planet. Second, scientists can compare this information to another yardstick contained in the ice. Isotopes are variations of an atom that have a different atomic weight than the primary form. For example, 99% of oxygen atoms have an atomic weight of 16 atomic mass units, O16. This is the weight that you will see represented on the periodic table. However, we know of many other versions of oxygen, all the way from O12 to O24. The heavy oxygen isotope O18 is found in liquid water molecules at higher concentrations when the temperature is colder. Knowing this, scientists can estimate past temperatures based on the amount of O18 found in the glacier ice. As you may have noticed from the previous graph, Earth has gone through several glacial eras, also known as glaciations or ice ages. We can find evidence for these time periods in ice core samples. However, there are also indications of these ice ages visible to the naked eye. Remnant glacial landforms are geologic characteristics created by the movement of glaciers or large sheets of ice. Yosemite National Park in California is famous for its breathtaking vistas created by the ebb and flow of glaciers. As glaciers expand, the growing weight of the ice and snow erodes, crushes, and cuts at the surrounding mountains, hillside, and bedrocks. This action creates landforms such as plucked rocks, U-shaped valleys, and arates. This animation shows how, as a glacier moves, it abrades or cuts at the Earth's surface. It also plucks at loose bedrock, trapping the rocks and boulders and transporting them far from their point of origin. As glaciers recede, they leave behind their accumulated rocks and pebbles, creating landforms such as drumlins, moraines, and kames. Similar to how paleoclimatologists use samples of glaciers to look into the past, they also take cores drilled out of the ocean floor. Every day, dust, dirt, and the remains of plants and animals fall to the bottom of the ocean floor. The skeletons of the deceased plants and animals settle on the bottom of the ocean, only to be covered by more dust, dirt, and skeletons. Over time, these oceanic deposits build up, creating a record of the plants and animals that lived in the area. Digging down into these layers gives scientists a glimpse at the life and climate of a region dating back 170 million years. One of the most useful fossils found in these sediment cores are foraminifera, a microscopic plankton found in all marine ecosystems. One species of foraminifera is only found in Arctic environments. A discovery of this cold water species is an indication that the climate of that region was once much colder, even glacial. Scientists can then date these fossils, creating a timeline of when that ocean zone experienced glaciations. Further, oceanic deposits provide evidence of the biodiversity or the amount and type of life in a particular area at a certain time. Warmer tropical regions tend to have greater biodiversity than colder Arctic regions, as well as different types of plant and animal life. You would not, for example, find a polar bear living in a rainforest. Based on the degree of biodiversity found in a sample, as well as the adaptations represented in the fossils, scientists can deduce what the climate might have been. Paleoclimatologists also use fossils found on land to give them clues to the past climates. Modern-day plants living in a particular climate, no matter where they are found in the world, have remarkably similar adaptations to their surroundings. For example, in environments with plenty of moisture and sunlight, such as rainforests, plants have large leaves and thin cuticles. A plant's cuticle is a waxy layer on the outside of the leaf that helps prevent water loss. In dry environments, such as tundra or desert, vegetation tends to have small leaves or no leaves and thick cuticles to help the plant retain water. By comparing the leaf fossils of ancient vegetation with the leaves of plants alive today, paleoclimatologists can get an idea of what past climates were like in a particular region. This leaf from an extinct maple tree is very similar to the leaves of a current living species. Scientists will use this observation to deduce that the extinct maple leaf probably existed in a similar environment to the modern version. Tree rings, both living and fossilized, give clues to past climates too. Each year, a tree grows wider, adding new layers of cells around those already there. If you look at a cross-section of a tree's trunk, these layers appear as growth rings. Aside from an estimation of a tree's age, growth rings also provide a glimpse of yearly variations in climate. Years with lots of rainfall allow for lots of growth, so those years will show as wide rings. Years with little rainfall do not allow for growth, so those years will show as narrow rings. Missing rings or false rings indicate times of stress, such as drought or frost. Climates with lots of rainfall and sunlight, such as rainforests, will show steady, continuous growth. This is often reflected as a lack of any growth rings at all. By finding naturally old trees, such as Methuselah, a nearly 5,000-year-old bristlecone pine tree in California, and combining it with deceased and fossilized trees in the area, scientists have used data from tree rings to judge climate changes up to 10,000 years in the past. So let's summarize. Paleoclimatologists are scientists who use evidence found on the planet today to deduce changes in climate throughout the Earth's history. One way they do this is by taking ice core samples drilled from glaciers. Scientists can check these samples for the presence of trapped greenhouse gases and for quantities of the heavy oxygen isotope O18. Both of these measurements provide an indication of past atmospheric temperatures. Remnant glacial landforms provide telltale signs of the passage of glaciers. As glaciers expand, they cut at the mountains and landscape around them. As glaciers recede, they leave behind the accumulation of rocks and boulders absorbed during their expansion. Both of these processes offer distinct and recognizable evidence that an ice age had previously taken place. Similar to ice core samples, paleoclimatologists take core samples of the sediment on the ocean floor. Fossils of foraminifera, a microscopic plankton, found in these samples allow scientists to determine where and when past glaciations had occurred. Additionally, based on the biodiversity found in the sample, scientists can deduce which climates that region had previously experienced. Likewise, paleoclimatologists can compare the fossils of ancient vegetation to the leaves of modern plants to infer past climates. Scientists can surmise that plant fossils with similar characteristics to modern plants probably lived in the same relative environment. Finally, by using tree ring data of fossils and particularly old living trees, scientists have been able to judge yearly changes in climate going back 10,000 years. I can tell by those sunglasses, rain boots, weather vane, and barometer that you are a budding climatologist. Well, lucky for you, I am here to help. So, without wasting any time, let's get started on your first project. When you are studying climate, the very first decisions you need to make are what will be your spatial and temporal scales. In other words, where are you going to focus your study, and during what time period? When you are deciding on the spatial scale of a study, you are focusing on a geographic region of climate change. In other words, where are you going to concentrate your study? How large or small will your focus be? Will you be studying the entire planet? Climatologists do this when they use computer models to predict global temperatures into the future. How about using political boundaries like a country? Maybe you are interested in the effect of carbon emissions in China. This would be focusing on a single country. Or what about a state? Do you want to research whether or not climate change caused the California drought? This would be focusing on a single state. Obviously, though, ecosystems and climates don't follow political boundaries. Maybe you want to study the Sahara Desert, which crosses 12 countries. Or maybe, since this is your first study, you just want to focus on the creek ecosystem near your home. So now that you have decided on a location, you need to think about the temporal scale, or the time period of climate change. This would be the when of your study. How far into the past or future do you want to look? Do you just want to look at the climate right now? In that case, you are studying the present. Are you going to look into the future? Again, climatologists use computer programs to model future climates. But here is something to think about. How far into the future do you think you can reasonably predict? Tomorrow? That's easy. 100 years? That's a little harder. You can also look into the past. Again, the further back you go, the less accurate your information will be. A search on the internet will get you reliable weather data for the last 100 years. If you want to know what the climate around your creek looked like when dinosaurs walked there, you must rely on observations from the fossil record. To give you some ideas, here are time periods that have been studied by other climatologists. You can look at the past 100 years and see how human activities have changed the climate. You can look back 1,000 years and study how volcanic activity and solar radiation have affected our current climate. It takes around 100,000 years for Earth's shifting orbit to alter the climate. You could study what the area around your creek looked like 100,000 years ago. You can look back 1 million to 100 million years at the effects of continental drift and plate tectonics. Your creek would have been at a very different position on the globe and thus would have a very different climate than it does today. You can even look back 200 million years and study climate change caused by galactic dust as our solar system travels through the galaxy. How far back would you go? Let's go over what we have discussed so far. When you are studying Earth's climate, the first decision you need to make is what will be your spatial and temporal scales. The spatial scale refers to the geographic region of climate change. This can include the entire planet, it can follow political boundaries like countries or cities, or it can follow ecoregions such as a desert or watershed. Once you have decided where you are going to focus your study, you need to think about the when. This is the temporal scale, or the time period of climate change. You can concentrate only on the present, or you can look into the future or the past. Just remember, the further into the future or past you go, the less reliable your data will be. So have you decided what your first project will be? I can't wait to hear all about it.
Sometimes it seems like climate change is all we hear about these days. What does this actually mean? As of 2014, the average global temperature was roughly 60 degrees Fahrenheit, but actually even a slight change to this can have dramatic results. Over the last 4 billion years, there have been dramatic shifts in the average global temperature from periods so cold that the polar ice caps extended almost to the equator to warm periods with tropical plants growing in Antarctica. The study of ancient climates is called paleoclimatology, and it's demonstrated that Earth's climate is constantly changing as a result of gases in the atmosphere, cycles of the Earth in relation to the sun, and other factors. So what's the big deal if the climate is changing now? Well, let's take a quick trip through time and see what climate change is really all about. Now, like I said, the Earth's climate is always changing, so we can't cover 4 billion years in our 6-minute tour. So let's hit some highlights. From the beginning of Earth's history, we've got periods of extreme heat, some of extreme cold, but let's start here. Yep, that's a dinosaur. Welcome to the Cretaceous. It's about 70 million years ago, and the current global temperature is roughly 82 degrees Fahrenheit. Now, this doesn't mean that your average day will be a balmy 82. What this means is that the Earth itself is radiating this much heat on average. So it's hot, humid, and muggy. Good for dinosaurs, not as great for mammals. But fast forward a bit, and now we're in the Pleistocene, lasting from 2.5 million to 11.5 thousand years ago. This period is also called the Ice Age by many. An extreme drop in temperatures to a global average peaking at highs of 42 to 51 degrees Fahrenheit led to a period of repeated cycles of glaciation, during which having fur turned out to be pretty advantageous and mammals thrived. But no dinosaurs. Starting to see why climate change can be a big deal? And now we get to the real reason we're out here. We are entering the Holocene, a geological period dating from roughly 11,500 years ago to present. While humans evolved in the late Pleistocene, the Holocene saw the first rise of civilizations. So this is the period of human history. The Holocene has been an interesting period, marked by dramatic shifts in global temperature as a result mostly of our position in major cycles of solar radiation. Researchers estimate that there have been as many as 20 climatic cycles during the Holocene so far, but they can be summarized in 3 major events. We start with a cool period, roughly 11,500 to 10,000 years ago. New glaciers formed, trapping water as ice, and coastlines dropped, leading to massive migrations of animals and early people to places like Australia and North America. This wasn't the first major period of migration, or the last, but it was a big one. The next major period in the Holocene was the Altithermal, a warming period also called the Holocene climate optimum that lasted from roughly 9,000 to 5,000 years ago. The average global temperature increased by quite a bit, and while still cooler than today, was characterized by a major shift in rainfall and vegetation, helping lead to the rise of many ancient civilizations. After that, we can jump forward to the Little Ice Age, another rapid cooling off between 1450 and 1850 CE. This really hit the northern hemisphere most dramatically, and it's actually worth noting that paintings from the Northern European Renaissance show a huge focus on snow and ice during this time. The Little Ice Age changed the ways that people lived, but after 1850, the Earth steadily started warming up. Obviously, climate changes all the time, so what's the big deal about climate change in the last century or so? Well, it's not just a matter of the increase in temperature, it's a matter of the rate. You see, since the advent of major industrialization efforts across the 20th century, the average global temperature went from steadily rising at a normal rate to skyrocketing. The current average temperature is warmer than it's been in the last 11,000 years, and the startling thing is that roughly 2/3 of that increase has only occurred since 1975. That's a fast change. Now, when temperatures increase over thousands of years, nature can adapt. But this change is outpacing evolution. In the geologic record, we've seen major changes that come along with rapid warming trends, including droughts that kill off large amounts of plant life and massive tropical storms that completely reshape coastlines. And that's with global warming that occurs from natural causes. So the incredibly fast climate change of the last 50 years is cause for concern. It may not seem like a big deal now, but when we look back through the history of our ever-changing climate, we can see exactly what this could mean. Earth's climate is changing now, just as it's been doing for the last 4 billion years. The study of ancient climates, called paleoclimatology, has revealed some interesting trends. From the Cretaceous, 70 million years ago, and a global temperature of roughly 82 degrees Fahrenheit, to the Pleistocene, lasting from roughly 2.5 million to 11.5 thousand years ago, and global average temperatures of 42 to 51 degrees Fahrenheit, climate shifts dramatically. Even throughout the Holocene, the last 11,500 years, there have been 3 major changes, starting with a cool period, a warmer Altithermal, and then a Little Ice Age. However, in the last century, climate has started changing at a dramatic pace as a result of industrial technology, leading people to worry if we are outpacing nature. So climate change is real. Of course, that's been true for 4 billion years, but still.
Just like this rock formation, the Earth's climate represents a delicate balancing act. There is a precise equilibrium between the energy coming in from the sun and the energy being reflected back into space from the planet's surface. When an event occurs, such as humans adding greenhouse gases to the atmosphere, this equilibrium is disturbed. In response, the climate will either warm up or cool down to reset the balance. In this example, greenhouse gases prevent solar radiation from being reflected back into space. However, to keep the balance, energy must be reflected back into space from the planet. So, The climate warms up, allowing more energy to be released as heat until the original balance has been restored. The climate responds through what is referred to as feedback mechanisms. A feedback mechanism is a process that allows a system, such as climate, to self-regulate in response to a change, such as increasing greenhouse gases. A common example of a feedback mechanism is the thermostat in your home. When the temperature inside becomes too cold, the heater switches on, warming up the air. Once the air reaches the correct temperature, the heater switches off and the air starts to cool back down. This process repeats, allowing you to keep your room at a stable temperature. The Earth's climate has several feedback mechanisms, such as the ice-albedo feedback, the water-vapor-cloud feedback, the atmosphere-ocean interactions, and the atmosphere-biota interactions. Albedo is derived from the Latin term for whiteness and refers to how reflective a surface is. The more ice there is on the Earth's poles, the higher the Earth's albedo. When the Earth is very white, it becomes more reflective. You have likely noticed this effect if you have ever been skiing. When the Earth has a high albedo, more of the sun's radiation is reflected back into space and less is absorbed by the planet. This has the effect of keeping our planet cooler. Here is how the ice-albedo feedback loop operates. The amount of radiation that the Earth receives from the sun does not always stay the same. When the sun sends more radiation to the Earth's surface, the planet starts to heat up. This increase in temperature causes the ice at the poles to melt. Less ice means the planet's albedo decreases. Less radiation is reflected back into space and more is absorbed, causing the Earth to heat up even more. A warmer planet means more ice melting, less radiation reflected back and more absorbed, and so on. As you can see, the ice-albedo feedback loop causes the planet to continue to heat up. This is what is referred to as positive feedback. In positive feedback, the initial effect is enhanced or increased. In this case, the initial effect was warming caused by increased solar radiation. The positive feedback loop causes the warming to continually increase. Lucky for us, and everything else on our planet, the ice-albedo feedback loop does not continue unchecked. This is where the water-vapor-cloud feedback loop, an example of negative feedback, comes into play. In negative feedback, the initial effect is counteracted or decreased. The thermostat we discussed in the introduction is another example of negative feedback. As you have probably noticed, on a very foggy day, water droplets in the air make it hard to see. This is because they are scattering and reflecting the sun's rays. While this can make it hard to drive your car, it also helps keep the Earth cool as the sun's radiation is bounced back into space. As the planet warms up, the oceans begin to evaporate at a higher rate. This water vapor in the atmosphere leads to the formation of clouds or water droplets in the sky. The clouds, notice that they are white like snow, reflect the sun's radiation away from the planet, causing the Earth to cool back down. Thus, the water vapor cloud feedback loop keeps the planet from heating up forever. Another example of positive feedback can be found in the Earth's atmosphere-ocean interactions. The ocean serves as a giant storage vault for carbon dioxide, one of the primary greenhouse gases. Nearly half of the carbon dioxide that humans have added to the atmosphere in the last 100 years, through factories, cars, and the burning of fossil fuels, has been absorbed by the oceans. Here is where the feedback loop comes in. Colder water can hold more carbon dioxide than warmer water. As the atmosphere heats up, so do the oceans. The warming water allows carbon dioxide to escape into the atmosphere, enhancing the greenhouse effect and further warming the planet. We find an example of negative feedback in Earth's atmosphere-biota interactions. Biota simply refers to all of the living creatures, plant, animal, or otherwise, in a particular area. In this case, we are looking at all of the living creatures on the planet, particularly the plant life. Plants both on land and in the ocean play a very large role in the stability of our climate. They are essential in removing carbon dioxide from the atmosphere during the process of photosynthesis. Additionally, returning to the concept of albedo, as the temperature around plants increase, they lose more water through transpiration. Transpiration refers to the evaporation of water from plants' leaves. More water in the atmosphere means more cloud cover, which reflects solar radiation back into space. So, a warmer climate leads to more plant life. Increased plant life means that more carbon dioxide is removed from the atmosphere and more clouds are added. This leads to less greenhouse gases trapping heat and more of the sun's rays being reflected away from the planet. As a result, the climate cools down. You can see that plants are important in combating global warming. So let's review what we have learned. The Earth's climate is in a delicate equilibrium between the energy coming in from the sun and the energy reflected back into space from the planet's surface. Whenever there is a shift in this equilibrium, the climate responds through various feedback mechanisms. A feedback mechanism is a process that allows a system, such as climate, to self-regulate in response to a change, such as increasing greenhouse gases. Feedback can be either positive or negative. In positive feedback, the initial effect is enhanced or increased. In negative feedback, the initial effect is counteracted or decreased. Two examples of positive feedback in the climate are the ice albedo feedback and the atmosphere-ocean interactions. Albedo is derived from the Latin term for whiteness and refers to how reflective a surface is. Two examples of negative feedback in the climate are the water vapor cloud feedback and atmosphere biota interactions. Biota refers to all of the living creatures, plant, animal, or otherwise, in a particular area. Hi, my name is Kelly and I live at the Alaska Zoo. I'm an Arctic ambassador with Polar Bears International. This is all true. Look, I even have a hashtag. My job as an Arctic ambassador is to educate you about global warming and what will happen to my home if it doesn't stop. I'm sure you have heard about global warming. It has been all over the news for many years now. Maybe you are saying to yourself, sure, I have heard of global warming, but how do we know that it is actually happening? Well, I can help you answer that question. Scientists have developed what is called a general circulation model, which is a computer model that both identifies possible causes of climate change and predicts climate change into the future. General circulation models are also called global climate models, and, lucky for us, they both use the acronym GCM. A model is a smaller representation of a larger object or process. For example, a model train is an accurate but much smaller replica of an actual train. In this case, scientists are using computer programs to model past, present, and future climates. A general circulation model uses lots of intricate math and physics equations to model the circulation of the atmosphere and the oceans on planet Earth. More complex versions take many factors into account, such as living things, glacier ice, energy from the sun, landforms, and how all these factors interact. The math required to make all of these calculations is so elaborate that these models can only be run on supercomputers. The GCM at the National Center for Atmospheric Research, for example, is so sophisticated that it uses almost 3 trillion equations to simulate a single day. So let's take a look at a GCM in action. A scientist can program these models to predict a future climate under a particular scenario, such as continually increasing greenhouse gases. Obviously, future amounts of greenhouse gases are uncertain as global initiatives strive to reduce this number. Additionally, unforeseen events such as major volcanic eruptions cannot be calculated. For this reason, model descriptions are phrased as if current conditions continue. So, the application takes the scenario of increasing greenhouse gases as an input. It then takes into account current ocean, land, and atmospheric conditions, and voila! The program calculates an output. This animation predicts global temperatures into 2100 if current rates of population growth and carbon dioxide emissions continue. So let's review what we have covered. A general circulation model is a computer model that identifies possible causes of climate change and predicts climate change into the future. A GCM uses lots of complex math and physics equations to calculate the movements of the atmosphere, oceans, landforms, glacier ice, and living creatures, as well as how these factors interact with each other. The math for these calculations is so sophisticated that the climate models can only be run on supercomputers. Scientists program the models to calculate future climates based on inputs such as increasing greenhouse gases. Based on this information, as well as current ocean, land, and atmosphere conditions, the GCM will output a possible future.
Although it may seem like it sometimes, weather forecasters don't just make up their predictions. They use the best available science, as well as 3 key variables that are critical to understanding weather: air pressure, temperature, and air density. These variables are essential because, like a well-organized set of drill sergeants, they control how air behaves, and thus they control the weather. However, they're not mutually exclusive. Like a set of siblings, each variable is closely related to the others, whether they like it or not. Let's look at air pressure first. Though you can't see them, air is a cocktail of molecules that fly around and bump into each other. Think of the molecules as billiard balls. As they bump into each other, they push each other around. You aren't going to notice one molecule bumping into another one, but if you add up all of these tiny collisions and pushes, you might start to feel it. Those molecules also have weight, and between the weight of the air pushing down and the collisions between molecules, we get air pressure. So how does air pressure relate to temperature? Well, remember how I said the air molecules are moving around and bumping into each other? If they move faster, they bump into each other harder and more often. This happens when the temperature of the air is increased. Warm air molecules have more energy, so they move faster and create more pressure. Likewise, cold air has less energy and therefore exerts less pressure on its surroundings. Density also plays a role. The denser the air is, the more molecules there are in that given space. It's like the difference between having a large party packed into a tiny living room versus having that same large group of people in a big recreation hall. The denser the air, the more collisions there are between molecules because there is less room for them to avoid running into each other, so we get more air pressure. So you can see that density, temperature, and pressure work together to change the conditions of the air. When heat is added, air temperature and pressure both increase. And when the density of air changes, the pressure, and sometimes the temperature, does as well. Now that you know how the 3 variables work together, let's take a look at how they affect weather. Adiabatic processes come about when an air parcel changes temperature without any gain or loss of heat from outside the parcel of air. Huh? How on earth does that work? Well, this is where density comes into play. Remember our partygoers from before? If you put them in the tiny living room, they bump into each other more. The molecules in dense air do the same thing, and these collisions give off heat and create pressure. When there is more space to move around in, the molecules run into each other less, which means they give off less heat and pressure. And because air has weight, it is affected by gravity. So nearer to the ground, there is more pressure because there is more weight. As you rise in altitude, the weight is less, so there is less pressure and more space for the air to expand. This means fewer collisions, less pressure, and less heat. You can see this process along mountainsides. As warm, moist air rises up the side of the mountain, known as the windward side, it expands because there is less pressure and it therefore cools. As it blows over the mountain and comes back down on the leeward side, it gets compressed, which makes the molecules bump into each other more, and the air is then warmed by these more frequent collisions. This is why the windward side of a mountain has its name. This is where the wind first encounters the mountain. It's also why the windward side is rainy and the leeward side is dry. Cold air can't hold as much moisture as warm air, so as the warm air rises up the mountain and becomes cooler, the water it holds is squeezed out of the air as rain on the windward side, and the dry air continues on to the leeward side. Do you think that if air rising up a mountain creates rain on that side, that it also must create a cloud? If you said yes, you're right. Air pressure, temperature, and density all contribute to cloud formation. As warm, moist air rises up into the atmosphere, it cools, which, as you now know, means that it has to let go of any water it brought along with it. The water from the air condenses into tiny droplets, which is what clouds are made of. And the type of cloud that forms depends greatly on the surrounding air, its pressure, temperature, and density. Air masses are huge parcels of air that cover large portions of Earth's surface, much larger parcels of air than ones we've been talking about so far. As we learned in another lesson, each air mass has specific characteristics, and when they meet up, they can produce an interesting variety of weather conditions. Whether large or small, when air parcels meet, we get fronts. The differences in the temperature, pressure, density, and moisture content of the air masses makes one front slide over the other one, which can affect weather patterns by creating cloudy skies, thunderstorms, and gusty winds. Fronts are like fights between air masses. Since they are so different, it almost feels like they can't decide on the weather, and the storms that follow are their conflicting opinions. Our three variables also influence other weather patterns, such as thunderstorms, tornadoes, and hurricanes. Thunderstorms occur when warm, wet air rises quickly. This rising air is called an updraft. The updraft builds a large vertical cloud. The water inside the cloud falls back toward the ground, and as it does, it tries to convince all of its friends to come along with it. This collection of water droplets builds until the larger water droplets form that are heavy enough to push past the updraft and reach the ground as rain, creating a downdraft, or downward moving air. When the air inside a thunderstorm cloud begins to spin, we get tornadoes over land and hurricanes over water. The combination of low-pressure centers and high-pressure exteriors drive these dangerous storms along until they are stopped by opposing winds or run out of energy. Like a set of siblings, air pressure, temperature, and density are related to one another. Air pressure describes the collision of molecules and weight of air pressing on its surroundings. Temperature refers to how warm or cold air is, and the density of the air is how many molecules are packed into a certain space of air. Air pressure is influenced by temperature because as the air is warmed, the molecules start moving around more, so they bump into each other more often and create more pressure. But air pressure also affects temperature. The more those molecules bump into each other, the more heat they generate, so more collision means warmer air. Density is also important because, like our big party of people, if you pack more molecules into a given space, they are inevitably going to bump into each other more, creating more pressure and therefore more heat as well. This is how we can have air parcel temperature changes without adding or removing heat from outside the parcel of air, known as adiabatic processes. As air rises up the windward side of a mountain, it expands, which means our party-going molecules have a larger space to move around in. There are fewer collisions, so the air cools, but as air cools, it can't hold as much water, so that water gets pushed out as rain on this side of the mountain. Any air that continues over the mountain to the leeward side gets compressed as it sinks back to the ground, which means the party gets moved into a smaller room, and we get more collisions and therefore warmer air. However, most of the moisture was left on the windward side as rain, so the leeward side is dry. The family of air variables is also responsible for clouds, air masses, fronts, and storms. Fronts are like fights between differing air masses, and their storms are their disagreement. Clouds form when warm, moist air rises, just like over the mountain, which sometimes releases their water as rain. If the cloud grows tall enough, we get a thunderstorm cloud, which can lead to tornadoes and hurricanes if the air inside starts to spin.
Ever heard the phrase stuck in the doldrums? It means you're stagnant, stuck, not really going anywhere. And it comes from sailors who would get stuck in an area along the equator they called the doldrums. If you're sailing through this area, you better have some oars handy because there's very little wind and you won't get very far. The doldrums are also related to the rainforests along the tropics, the Sahara Desert in Africa, and Mojave Desert in the southwest U.S., as well as the frigid winds of the polar regions. These all come about because Earth spins on its axis, which, as we learned in another lesson, deflects straight-moving winds and creates multiple cells of air circulation across the globe. The northern and southern hemispheres each have 3 air circulation cells. These cells help distribute heat and air across Earth. Each cell is like a wide belt around that part of Earth, and in these belts we get wind, which is horizontally moving air. Where each cell meets is also like a belt, but these are opposite to our cells. They are thin, windless strips that girdle Earth. You can remember which is which because the windy cells are wide and both begin with W. Let's start along the equator. As you might expect, the air is very warm here, so it rises straight up. When warm air rises like this, it leaves behind an area of low pressure. You can remember this because the air is leaving, which creates an area of low pressure. Leaving and low both begin with L. This particular area of low pressure along the equator is where we find our doldrums, a long stretch of stagnant air, and our first windless strip between cells. The warm air rising from the equator also brings a lot of moisture with it, and as the air rises, it cools. The water in the air is pushed out and comes back down as rain. It's certainly no accident that we find the world's tropical rainforests along the equator. This is where all that moisture from the hot equatorial air gets released. The warm air rising from the equator eventually begins to spread horizontally, which creates those wide, windy circulation cells. On either side of the doldrums are the Hadley cells, one for each hemisphere. You can remember the Hadley cell borders the equator because the equator is hot, and hot and Hadley both begin with H. As the air spreads horizontally, we find that it begins to cool even more, around 30 degrees north and south latitudes. When the air is cool enough, it starts to fall back towards Earth's surface, but as it falls, it warms. So if hot air leaving creates low pressure, hot air coming in creates the opposite, high pressure. Because of this, the falling air creates our next thin, windless strip called the horse latitudes. They were named this because, like the doldrums, there is little wind to push ships along the ocean. Legend has it that when this happened, horses on board the ship were either eaten as food supplies went low or thrown overboard to reduce the load. The horse latitudes create areas of hot, dry surface air around Earth. You might not be surprised to learn that this is also where we find the world's great deserts like the Sahara in Africa, the Mojave in the U.S., and the Great Victoria in Australia. Some of the air heads back towards the equator as the warm, steady breezes of the trade winds, but much of it keeps heading towards the poles, creating our next cell, the ferrule cell. The winds that blow towards the poles and create the ferrule cells are the westerlies, which you can remember because they come from the west and blow to the east. When the warm, moist westerlies reach about 60 degrees north and south, twice the latitude as our other thin windless strip, they meet up with the cold, dry polar easterlies, which, as you have probably guessed, blow from the east. The polar easterlies make up our third and final circulation cell, the polar cell, and where the polar cell and the ferrule cell meet is called the polar front. Here, just like at the equator, air rises vertically, and that leaving air creates an area of low pressure. The other interesting thing that these two different temperature cells create when they come together is storms. As we learned in another lesson, fronts are contact areas between two different air masses. When these air masses meet, they're so different that it's almost like they're fighting about the weather, and the storm is like their conflict. The polar front is no exception, and these areas on Earth are well known for their unpredictable storms. Earth spins on its axis, which creates interesting wind patterns around Earth. Among these interesting patterns are global air circulation cells, 3 in the northern hemisphere and 3 in the southern hemisphere. These cells help distribute heat and air across Earth, as each cell is like a wide, windy belt around the globe. Where each cell meets another is also like a belt, but these are opposite to the windy cells, acting like thin, windless girdles. Warm air rises vertically along the equator, and when that air leaves, it creates an area of low pressure. This is our first windless strip, the doldrums. As the vertically rising air cools, it rains a lot of the ocean moisture it brought with it back down onto land, which is why we find the tropical rainforest in this area. At some point, the air starts traveling horizontally, creating the first cell, the Hadley cell. The Hadley cell is home to the warm, steady breezes of the trade winds. As the air of the Hadley cell begins to cool even more around 30 degrees north and south latitudes, it falls back towards Earth. Air coming back creates the opposite situation from air leaving, an area of high pressure, and our next windless strip, the horse latitudes. Similar to the doldrums, the horse latitudes are a terrible place to sail, and along the strip of warm, dry air we find the world's great deserts. Some of the air falling from the Hadley cell continues to travel to the poles, creating the second windy belt, the Ferrel cell. In the Ferrel cell we find the westerlies, so named because they blow from west to east. The Ferrel cell meets up with the third and final windy belt, the polar cell, around 60 degrees north and south latitudes. The polar cell is home to the cold, dry polar easterlies, which blow from east to west, and when these meet up with the warm, moist air of the Ferrel cell, they create the polar front. This is our final windless girdle on Earth, and along here we find many storms because when two different air masses meet, they have a difficult time agreeing on what the weather should be.
Johnny Dalton and his family have just arrived on Ideal Island, where all gas particles behave ideally. They move rapidly and randomly, they don't interact with each other, they have elastic collisions, meaning they don't lose energy when they collide, and they are point particles, meaning the individual particles don't have any volume. Just like when you travel to a foreign country and have to use a different currency or different units to measure things, Johnny must use different units on Ideal Island. Today we are going to discuss pressure and the pressure units that are used here on the island. I want you to think about the last time you measured the pressure of something. It may have been the pressure of the air in your car tires. You remember what it was? The air in my car's tires is 32 psi. PSI represents the pounds per square inch, which is a common unit for pressure. Let's look a little more closely at pounds per square inch. What does a pound measure? If you said weight, you are correct. Weight is just the force of gravity's pull on an object. We measure it in pounds. Now, the square inch is just an area. And if we put the two parts of PSI together, we get the definition for pressure, the force per unit area. So now we know what pressure is, but what causes it in our tires? To answer this, I want you to picture the gas particles flying around inside of your car's tires. They're in there, flying past each other, and hitting the walls of the tires. The pressure comes from each time they hit the inside walls of the container, or in this case it would be the tires. The more times they hit the inside walls, the higher the pressure in the tires. So if you keep adding air to the tires, you're going to increase the number of particles that hit the inside walls of the tires and increase the pressure. Let's go back to the unit that we use to represent pressure, PSI. This is one of many different units that can be used to measure pressure, and it's probably the one that you use most on a daily basis in the United States. But on Ideal Island, different units are used, so it's important to know what they are and how to convert among them. On the island, the most common units of pressure that are used are atmospheres and millimeters of mercury, or mmHg. 1 atmosphere is often abbreviated as ATM, and it's really just the weight of all of the air above you pressing down on you while you stand at sea level. Now, if you were on a mountain, there would be less air pressing down on you, so the pressure would be lower, less than 1 atmosphere. The unit millimeters of mercury goes back to the device used to measure pressure, the barometer. In this barometer, we have an inverted tube containing a column of mercury with the chemical symbol Hg, and it's sitting in a pool of mercury. As the atmosphere presses down on the mercury pool, the liquid extends up into the inverted tube, and the height is measured in millimeters, or some other length measurement. So if the weather is changing, resulting in an increase in the barometric pressure, The increase is measured by how far up the mercury extends in the column. At sea level, the mercury extends about 760 millimeters up the column. The unit millimeters of mercury can be pretty confusing because it seems as if it's a unit for length, not pressure. Sometimes you may see the unit torr used instead. A torr is equivalent to a millimeter of mercury, and it's named after Evangelista Torricelli, the first person to use a barometer to experiment with and document the pressure of the atmosphere. Mercury barometers are not used much anymore because mercury is a toxic liquid, but the unit millimeters of mercury is still used as a unit of pressure. When converting among the different units of pressure, it's important to know how they relate to each other. 1 atmosphere, the force of all of the air pushing down at you at sea level, is equal to 14.7 psi, the unit you use to measure the pressure in your car's tires. 1 atmosphere is also equal to 760 millimeters of mercury, or 760 torr. The two most common units used on Ideal Island are atmospheres and millimeters of mercury. So let's try a practice conversion. Say you're hiking up a mountain on Ideal Island and the pressure changes from 1 atmosphere at sea level to 0.89 atmospheres at the top of the mountain. How many millimeters of mercury would this be equivalent to? Now you may be able to easily figure out the answer to this question using a calculator, but I'm going to set it up using dimensional analysis. First, I start out with my given, 0.89 atmospheres. I will then multiply by a conversion factor, which is just a fraction equivalent to 1. My conversion factor is 760 millimeters of mercury over 1 atmosphere, because the numerator and the denominator are equivalent pressures. I will then multiply the two fractions, canceling out atmospheres, giving me 676 millimeters of mercury as an answer. Pressure is defined as the force per unit area, and when a gas fills a container, the particles sometimes collide with the inside walls of the container, which causes the container to have a certain amount of pressure. You may measure pressure in psi, but the two units that are most commonly used when measuring pressure of an ideal gas are atmospheres and millimeters of mercury. An atmosphere is the amount of pressure you feel at sea level on a normal day. It is equivalent to 14.7 psi and 760 millimeters of mercury, or 760 torr. It was a hot and humid day on Ideal Island, the place where all gases behave ideally. Remember, ideal gases move rapidly and randomly, they're not attracted to each other, and they have elastic collisions, meaning when they collide, there is no loss in energy. Johnny Dalton and his family are vacationing on the island, and it happens to be one of the most humid days Johnny has experienced. This gets him thinking about humidity and the particles in the air. As you may know, air is a mixture of several different gases. About 78% of it is nitrogen, 20% is oxygen, 1% is argon, and the remaining is a combination of water vapor, carbon dioxide, and other gases. On more humid days, like today on the island, the amount of water vapor would exceed 1% and may even reach as high as 4%. Johnny Dalton decided to spend his day experimenting with different mixtures of gases, and while he was experimenting, he observed many different interesting features of gas mixtures. One of his most important observations was that in a mixture of gases, each gas behaved independently of the other gases, meaning that if he had a container of 5 nitrogen molecules, causing the pressure of the container to be 5 millimeters of mercury, and he added 4 oxygen molecules to this same container, the pressure would increase to 9 millimeters of mercury. Now, if he removed the original nitrogen molecules, the pressure would decrease down to 4 millimeters of mercury. This showed him that each gas particle is going to fly around and hit the walls of the container, causing the pressure on its own. It wasn't going to interfere with the other gas particles flying around. So, the more gas particles you have in a container, the higher the pressure in that container, and the less particles you have in a container, the lower the pressure. If these two gases are mixed, each gas is going to exert its own pressure, or partial pressure, combining to create a total pressure in the container. This phenomenon was so significant that it was named after Dalton. It became known as Dalton's law of partial pressures, and it simply states that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of each individual gas. We can also look at this law in equation form. So, going back to the previous mixture example, the partial pressure of the nitrogen was 5 millimeters of mercury, and the partial pressure of the oxygen was 4 millimeters of mercury. The total pressure of the mixture was 9 millimeters of mercury. So this law can be used with any number of gas components, but it assumes that each gas behaves ideally and independently. Remember that ideal gases have no intermolecular forces, so they don't affect each other, which means that each individual gas particle has an equal chance of hitting the wall and causing pressure. And the total pressure is a result of all of the collisions the particles have with the walls of the container. This law also assumes that the gases in the mixture won't react with each other. We can use this equation to find the pressure of each separate gas in the atmosphere. Say the total atmospheric pressure on the island is 760 millimeters of mercury. This is the likely pressure of the atmosphere at sea level. The pressure of each individual gas in the atmosphere would need to total 760 millimeters of mercury. If 78% of the atmosphere is nitrogen, then around 593 millimeters of mercury, or 78% of 760, would be pressure exerted due to the nitrogen. 152 millimeters of mercury of pressure would be due to the oxygen. That's 20% of 760. And the rest of the pressure, 15 millimeters of mercury, would come from the other gases in the atmosphere. Johnny decided to put his new knowledge of the additive properties of partial pressure in one final experiment. One of Johnny's favorite chemical reactions is the one between baking soda and vinegar. The combination produces a lot of carbon dioxide gas, which causes it to make bubbles and foam up. Johnny decided that this time he wants to keep the carbon dioxide that's produced. Often in a chemistry lab, the gas is collected over water, using water displacement. Johnny started by combining the baking soda and vinegar in a test tube. It instantly began producing carbon dioxide. If he were to put a cork on this test tube, it would produce so much carbon dioxide that it would cause so much pressure that the test tube may explode. He didn't want that, so he used a stopper with a hole at the top for a hose to fit in. On the other end of the hose, the carbon dioxide started coming out. He put the hose in an inverted test tube filled with water, and eventually the carbon dioxide that was being created bubbled up and took the place of the water. And all he had left in the gas collection test tube was carbon dioxide. Or did he? One aspect of this situation that takes place is the evaporation of water into the gas collection test tube. Some of it evaporates and goes off into the environment, and some of it evaporates into the test tube that is now filled with the newly created carbon dioxide. So what you have in the test tube is your newly created carbon dioxide and some evaporated water. Both of them are gases. But how much water vapor is in there? Well, that depends on the temperature of the water. Cold water doesn't evaporate very quickly because the particles are moving so slow, and warm water does evaporate quickly because the particles are moving faster. So the warmer the water, the faster the particles are moving, the more water vapor will be in the test tube, and the less carbon dioxide you will have collected. Where Dalton's law enters the picture is when you add the two gases in the test tube, the carbon dioxide and the water vapor, provided that the water level is even on the inside and the outside of the test tube, the total pressure in the test tube, which consists of the carbon dioxide and the water vapor, should be equal to the atmospheric pressure on the outside of the test tube. Suppose you are collecting some oxygen using water displacement. The atmospheric pressure that day in the laboratory is 745 millimeters of mercury. The water you are using is 25 degrees Celsius, which means that the pressure of the water vapor would be 24 millimeters of mercury. This water temperature and water vapor pressure relationship can be found using a reference table. So given all of this information, what is the pressure of the oxygen you collected? To solve this problem, we would need to set up an equation like this. The pressure of the atmosphere outside of the test tube is equal to the partial pressure of the oxygen plus the partial pressure of the water vapor. So, solving for the partial pressure of the oxygen, we would get 721 millimeters of mercury. What this means is that you didn't really just collect oxygen. In fact, about 3.2% of the gas particles were water vapor. That was found out by taking 24 millimeters of mercury, which is your water vapor pressure, and dividing that by the total pressure of 745 millimeters of mercury. Now this hot and humid day on the island should make a little more sense. The warmer the water surrounding the island, the faster the water particles are moving, and the more of that water will evaporate. This will increase the partial pressure of the water vapor in the air surrounding the island, because there will be more water vapor hitting things, causing the pressure. Because most gases behave independently, each gas in a container is going to contribute to its own pressure in that container, and the sum of all of the individual pressures of each gas will equal the total pressure in that container. This is called Dalton's law of partial pressures, and it applies to all mixtures of ideal gases.
It can be odd to think of air as having weight. After all, it doesn't feel like it. But the air is full of molecules, and though extremely light, they do have weight. The more air you have above a thing, the more weight that thing will feel. Atmospheric pressure is the weight of the atmosphere on a surface. The units for atmospheric pressure are conveniently known as atmospheres, ATM, and the average pressure at sea level is set at 1 atmosphere. On average, the weight of the atmosphere on a square inch is 14.7 pounds at sea level. This means if you were to extend a 1-inch column from sea level to the edge of our atmosphere, all the gases inside would weigh 14.7 pounds. Another way to think about it is, if you put your hand out, there is more or less 175 pounds of atmosphere weighing down on it, and a standard 8.5 by 11 piece of paper has over 1,300 pounds weighing down on it. So why doesn't it crush us? Luckily, we have evolved to deal with it and not notice it. In fact, we would have big problems if there wasn't all that pressure keeping us together. The atmospheric pressure at any given point depends on 2 factors: altitude, the height of a thing in relation to sea level, and temperature, the intensity of heat. As you increase altitude, the amount of atmosphere above you decreases. In other words, if you start to climb a mountain, you will gradually have fewer and fewer gas molecules above you. This will mean that there is less atmospheric pressure being exerted on you every step of the way. In fact, at about 3 miles up, the atmospheric pressure is only half of what it is at sea level. If you can make it up to 20 miles, there is essentially no atmospheric pressure, and you would most certainly die, but that's beside the point. Pressure is directly related to temperature. As you heat up a gas, the individual atoms begin to move around more, and with more energy. This increase in energy is an increase in pressure. If you reverse the process and cool a gas down, the pressure decreases as well. Atmospheric pressure is a large component of how weather works. As air moves around the globe, pockets of high pressure and low pressure build up. The areas of high pressure will rush into areas of low pressure, causing winds as the air moves. This is what you see when you see weather maps. They commonly show high and low pressure systems. Atmospheric pressure is the weight of the atmosphere on a surface. An atmosphere is the unit for atmospheric pressure, and at sea level is set at 1 atmosphere, ATM. The atmospheric pressure at any given point depends on 2 factors: altitude, the height of a thing in relation to sea level, and temperature, the intensity of heat. This affects weather patterns across the world, as well as a person taking a mountain hike.
If you've ever rode a plane, you've heard a flight attendant give a pre-flight safety announcement, including instructions on what to do if cabin pressure is lost. Why are airplanes pressurized to begin with? Modern passenger jets spend the majority of the trip at an altitude of 39,000 feet. Our bodies are accustomed to life at sea level. At 39,000 feet, the air pressure is much lower and contains fewer oxygen molecules. At this lower air pressure with such low oxygen concentrations, there is definitely not enough for humans to survive. So in order to fly at such high altitudes, the planes must keep an artificially high cabin pressure so that we have enough oxygen to breathe. So why does air pressure decrease with altitude? Turns out there are two main causes for this phenomenon. One, the effect of gravity lessens the further away you get from the center of the Earth. 2, in the outer atmosphere, there are fewer overlying air molecules pressing down from above, so they're not increasing the pressure as much. Let's delve a little deeper into these two ideas, starting with gravity. The force of gravity is what keeps the Earth's atmosphere in place. However, the further you get away from the Earth, the less you experience the force of the Earth's gravity. This is modeled by the gravity equation. In this equation, F is the force of gravity, G is the gravitational constant, M1 and 2 are the masses of the two objects, and R is the distance between their two centers. Obviously, the mass of the Earth is very large, and the largest gravitational force nearby. As you increase R, which here represents the distance between the center of the Earth and an air molecule, the force of gravity decreases. Gravity is a force acting against the air molecule, causing it to be pulled towards the Earth and the other air molecules. So the greater the gravity, the higher the pressure on the air molecule, and the lower the gravity, like at high altitudes, the lower the pressure. The other force acting on air molecules to increase their pressure is the weight of the overlying air. Imagine just a vertical slice of the Earth's atmosphere. Air near the Earth's surface has all of the overlying air pressing down on it, while air at the top has less air pressing down. This is similar to why pressure increases as you go into the ocean, where you experience the weight of a larger and larger overhead water column the deeper you go. This pressure is known as hydrostatic pressure and is due to the weight of overlying fluid, either water or air. Hydrostatic pressure is governed by this equation. Here, P is pressure, G is gravity, the Greek letter rho is density, and H is the height of water above the point of interest. To incorporate all of the changes that occur with changes in altitude, the barometric pressure formula models the changes in air pressure with altitude. Barometric pressure is another term for atmospheric pressure, thusly named because it is measured with a barometer. The equation is as follows. Here, P sub h is the pressure at elevation, P sub 0 is the pressure at sea level, M is the mass of one air molecule, G is gravity, H is the height at elevation, K is the Boltzmann constant, and T is temperature. What this equation shows you is that pressure decreases exponentially with altitude. As we learned in this lesson, atmospheric pressure decreases with distance away from the surface of the Earth. There are two main phenomena responsible for this decrease in pressure. First, the effect of gravity decreases the further you are from the center of the Earth. Therefore, air molecules in the outer atmosphere do not feel as great a force from gravity as air molecules closer to the Earth. Second, air molecules near the Earth experience more downward force from the overlying atmosphere, which is known as hydrostatic pressure. Higher in the atmosphere, there is less overlying air and thus less hydrostatic pressure. Less overall force acting on the air molecules in the outer atmosphere means they are at a lower pressure than lower air molecules that experience stronger gravity and hydrostatic pressure. We can be thankful for these combined forces because they concentrate enough oxygen for us to safely breathe at the Earth's surface.
Johnny is riding his bicycle and enjoying his vacation here on Ideal Island, where all gases behave ideally, meaning they move rapidly and randomly, and the gas particles have no volume and no intermolecular forces. Keep in mind, real gases, like the ones you and I are familiar with, behave like ideal gases at normal temperatures and normal pressures. So, often when we are describing real gases, we will use the ideal gas characteristics to make approximations of our real gases. Now back to Johnny on Ideal Island. One thing Johnny really loves about this place is that all gases here are predictable and follow one law. Just like different states and countries have different laws, Ideal Island has its law of the land, the ideal gas law. All gas particles follow this law all of the time. The ideal gas law relates the temperature, pressure, number of moles, and volume of any gas. So let's take the air in the tires in Johnny's bicycle as an example. The air particles are all flying around inside of the tires, hitting the inner walls of the tires and applying pressure to the inside of the tire with each collision between the particle and the wall of the tire. These particles all have a certain velocity based upon the temperature of the gas. The hotter they are, the faster they will move. Also, these tires have a certain number of particles, and as a group, they have a certain volume, meaning they take up a defined amount of space. These four variables are all related, meaning that if one increases or decreases, one or more of the others will change. They can be related mathematically by the ideal gas equation, or PV equals nRT. In this equation, P stands for the pressure inside the container, the bicycle tires. V stands for the volume of the container. N represents the quantity of particles in the container. R is the ideal gas constant, equal to 0.0821 liter atmospheres per mole K, which we'll go into later, and T is the temperature of the gas in the container. Now any number of units can be used for pressure, volume, number of particles, and temperature, but the most commonly used ones are atmospheres, liters, moles, and kelvins, and we must use these units if we want to use 0.0821 as our R constant. So what does this equation mean? Well, let's start by comparing the pressure and temperature. Remember that pressure is caused by the collision between a gas particle and the walls of its container. Say we have two containers, each is holding particles. If they are both at the same temperature, the pressure inside each container will be the same. Now, if we increase the temperature of one container, the velocity of particles will increase and there will be more collisions with the inside walls of the container. According to Gay-Lussac's law, this will result in a higher pressure. So pressure and temperature are directly related to each other. We can represent this as P is proportional to T. And we can see this relationship in our car tires. As we drive, the temperature in our tires increases, which causes an increase in tire pressure. We also know that if two containers have the same volume and the same temperature, the more particles that are in that container, the more collisions there will be with the inside walls of that container, and the higher the pressure will be. This means that the pressure and the number of particles, or the number of moles of particles, is directly related. We see this every time we fill our tires with air. The more air we put in, the higher the tire pressure. We can represent this as P is proportional to N, or combine the two relationships to make P is proportional to N times T. Next, we will examine the relationship between the number of particles and the volume. According to Avogadro's law, if we increase the number of particles in a balloon, or a container that can expand, the volume of that container will also increase. So the volume and the number of particles are also directly related, giving us V is proportional to N. Now if we combine this with our previous statements, we get PV is proportional to NT. So this P times V is proportional to N times T also shows Boyle's law, which states that the pressure and the volume are inversely proportional to each other. And it also shows Charles' law, which states that volume and temperature are directly related to each other. All of these separate combinations of gas laws fuse together to form the ideal gas law. So where does this R come from? I'm going to start by taking the ideal gas law and rearranging it for R. So if we do that, we need to divide both sides by N times T, giving us R is equal to P times V divided by N times T. Now we can find the R for any gas situation, each time getting the same number, of course. So let's solve it for a gas situation we have previously been introduced to, Avogadro's law, which states that 1 mole of an ideal gas at standard temperature and pressure, or 1 atmosphere and 273 kelvins, takes up 22.4 liters of space. So if we fill in the values we know, pressure equals 1 atmosphere, volume equals 22.4 liters, N equals 1 mole, and T equals 273 kelvins, we multiply across the top and bottom and then divide, round to 3 significant figures, we will get 0.0821 liter atmosphere per mole K. So you never really have to memorize R if you know Avogadro's law. One thing that's really tricky about this number is all the units attached to it. When we solved for R, none of these units canceled out. So whenever you use this R, you need to make sure you keep all 4 of those units on it. Also, if you do this when using the ideal gas law, you will always end up with the correct unit you are solving for. Another thing to mention about this constant is the number, 0.0821, is different depending on which units of pressure and volume you use. So if you always use liters, atmospheres, moles, and kelvins, the 0.0821 will always work. This means that there may be many situations you need to convert units like Celsius to kelvins, or torr to atmospheres, and so on. If we combine everything we already know about gases into one central governing principle, it would be the ideal gas law, which shows the relationship between pressure, volume, temperature, and the number of moles of an ideal gas. It is represented using the ideal gas equation, or PV equals nRT, where P is the pressure in atmospheres, V is the volume in liters, N represents the quantity of particles in the container, T represents the temperature in kelvins, and R is the ideal gas constant, equal to 0.0821 liter atmosphere per mole kelvins. Johnny uses this equation in his gas experiments to calculate any one of these variables as long as the other 3 are known.
In another lesson, you learned about ideal gases and the ideal gas equation. Ideal gases are just what they sound like, ideal. But since real gases behave similarly to ideal gases at normal temperatures and pressures, we can use the ideal gas equation to predict the behavior of real gases under these conditions. First, let's review the ideal gas law, PV equals nRT. In this equation, P is the pressure in atmospheres, V is the volume in liters, N is the number of particles in moles, T is the temperature in Kelvin, and R is the ideal gas constant, 0.0821 liter atmospheres per moles Kelvin. Just like any equation, if we know 3 of those 4 variables, other than R, which we already know because it's a constant, we can rearrange the equation to calculate the unknown. Let's start with a very simple example to see how this works. Say we want to calculate the volume of 1 mole of gas at 273 Kelvin, which is the same as 0 degrees Celsius, and 1 atmosphere of pressure. Here's what our equation looks like when we fill in the variables we do know. If we want to find the volume V, we simply rearrange the equation to get this variable by itself. We do this by dividing by the pressure 1 atmosphere. So now our equation looks like this. The moles cancel out, as do atmospheres and Kelvin. All we're left with in terms of units is liters, and then to get our volume, we simply do the math. Our final answer is 22.4 liters. Make sense? Let's try another example, this time solving a real-life example. Suppose you want to calculate the temperature of the gas in your bike tire. As long as you know the other variables, you can do this quite easily. In this case, the pressure is 1.14 atmospheres, the volume of the tire is 5.00 liters, and we have 0.225 moles of gas. So our original equation looks like this. To get temperature alone, we simply divide by N and R to get. Once we do the math, we end up with 310 degrees Kelvin because all of our other units cancel out. And what exactly is 310 degrees Kelvin? Well, that's about 37 degrees Celsius, or about 98.6 degrees Fahrenheit, and that's pretty warm. The best part about this equation is that you can find any variable as long as you have the other 3. So if you know the temperature, pressure, and number of moles, you can easily find the volume. Likewise, if you know the volume and also know the temperature and pressure, you can solve the equation to calculate how many moles there are. This makes the ideal gas law ideal to work with. We know that ideal gases are just that, ideal. But since real gases can behave like ideal gases under the right conditions, this allows us to use the ideal gas law to predict their behavior. The ideal gas law states that PV equals nRT, or in plain English, that pressure times volume equals moles times the gas law constant R times temperature. As long as you know 3 of the 4 variables, you can easily rearrange and calculate the missing one, no matter which one that may be.
Barometric pressure, more commonly called atmospheric pressure, is the pressure exerted by the surrounding air in the atmosphere. It gets the name barometric pressure because it is measured with a barometer. Barometric pressure is commonly measured at all weather stations. Why is this such an important feature of understanding our climate and weather? As it turns out, minor variations in atmospheric pressure are tied to changing weather conditions. In this lesson, we're going to examine the science behind barometric pressure. First, we need to understand what barometric pressure is and why it changes. In another lesson in this series, we learned that altitude and barometric pressure are closely interrelated. Atmospheric pressure decreases exponentially with higher altitude due to decreasing gravity with elevation and less overlying air pressing down. To incorporate all of the changes that occur with changes in altitude, the barometric pressure equation models the changes in air pressure with altitude. The barometric pressure equation is as follows, where P sub h is the pressure at elevation, P sub 0 is the pressure at sea level, M is the mass of one air molecule, G is gravity, H is the height at elevation, K is the Boltzmann constant, and T is temperature. What this equation shows you is that pressure decreases exponentially with altitude. As we see in this equation, barometric pressure is dependent on altitude, pressure at sea level, gravity, and temperature. However, I mentioned at the beginning of this lesson that barometric pressure can also tell us about changes in weather. You've likely seen local weather reports talking about high pressure and low pressure systems. Low pressure systems are associated with storms because air rises at areas of low pressure and condenses to form clouds. So these low and high pressure systems form and move around the globe with changing weather and climatic patterns. By measuring slight changes in barometric pressure at a weather station, we can then predict if a stormy low pressure system is approaching due to dropping atmospheric pressure. If the pressure begins to rise again and stays stable, we know that we're in a high-pressure system, which is associated with clear weather and stagnant air. So now that we know a little bit about barometric pressure, let's cover how it is measured. Barometers are instruments that measure atmospheric pressure. There are 3 common types of barometers: mercury, aneroid, and digital. Mercury barometers contain a glass tube that is open to a small pool of mercury at the bottom. As outside air pressure increases, the mercury is pushed higher in the glass tube in an attempt to equalize the internal pressure in the glass with the outside pressure. When the outside air pressure drops, the mercury level drops as well to lessen the internal glass pressure. Think of the small space above the mercury as a mini atmosphere. To increase the air pressure, you need to condense the air in the space. To decrease, you need to give the internal air more space. Created in the 17th century, mercury barometers are the earliest type of barometer. They are still used today due to their high accuracy, simplicity, and low cost. Despite their advantages, the size, glass, and poisonous mercury make this an unideal technology for some applications. The other type of barometer is the aneroid barometer, which uses a small sealed metal cell. Increases in atmospheric pressure cause the walls of the cell to come closer together, while decreases cause the air inside the cell to expand and the walls push further apart. Traditional aneroid barometers have a cell attached to the base of the instrument, while the other side is attached to either a spring or a series of levers and pulleys to spin a rotating pointer on a dial. Modern digital barometers use pressure transducers to quickly and easily measure changing pressure by using one of the many electrical pressure sensors. Because of their very small size, they can be installed on the control boards of many electronics, including smartphones. Note that there are many units of pressure that are used in recording barometric pressure. Standard atmosphere, or ATM, is meant to be approximately the average pressure at sea level. The other common units are hectopascals, millibar, torr, and inches of mercury, or PSI. The relationship between these units are displayed. Now, you won't need to memorize these conversions, as you can commonly look them up if you need to convert between units. However, it is good to know some of the common units of pressure so you can recognize their use. In this lesson, we learned that barometric pressure varies by altitude and also changing weather conditions. Measuring barometric pressure can tell us if storms are coming by dropping pressure, or if we can expect fairer weather by rising and then stable pressure. The first barometer was the mercury barometer that had an open end with mercury that can rise or fall with varying atmospheric pressure. Aneroid barometers use a small sealed metal cell that expands or contracts with exterior atmospheric pressure. Finally, the more modern digital barometers use electrical pressure sensors installed on control boards.
If you've ever taken a trip to the tropics, you likely went to enjoy the warm climate. The climate near the equator is so warm because this area receives the highest amount of solar radiation, or energy from the sun, throughout the year. Likewise, the polar regions are colder because they receive a much smaller and less consistent amount of annual solar radiation. Since the tropic region does not get progressively hotter with more solar radiation, and the polar regions do not get progressively colder, there must be some force to balance out all of this energy to keep these areas at a semi-consistent temperature. This force is atmospheric circulation. Solar radiation at the top of the equator causes the air to rise high into the atmosphere. The air will rise until the tropopause, which is the boundary between the troposphere, the lowest layer of the atmosphere, and the stratosphere, the next layer up of the Earth's atmosphere. Continuously rising air will push the air towards the north. Additionally, the Coriolis force diverts this wind to the right in the northern hemisphere and to the left in the southern hemisphere. The Coriolis force is the force that diverts wind due to the rotation of the Earth. As the air rises and travels away from the equator, it cools down and becomes more dense. The denser air falls back closer to the Earth and is pushed back towards the equator. Eventually, this air will become heated due to solar radiation again, completing the circulation cell. Air does not circulate in a single cell from the equator to the poles. Instead, each hemisphere is broken into 3 circulation cells. The Hadley cell is the circulation cell nearest to the equator and has air rising at the equator and sinking near 30 degrees. The Ferrel cell is a circulation cell in the mid-latitudes where the air rises near 60 degrees and sinks near 30 degrees. The Polar cell is a circulation cell in the polar regions. Let's look a little deeper into each of these air circulation cells. The Hadley cell creates some of the most important weather patterns on Earth. As air rises and travels northward to the east, it eventually falls around 30 degrees. Where this air descends, it creates a ring of high atmospheric pressure. High pressure zones are associated with calm, dry weather. Therefore, a majority of the world's deserts are located at 30 degrees from the equator. After the air in the Hadley cells falls back to Earth, it travels close to the surface of the Earth in a northeasterly direction or from northeast to southwest. These northeasterly winds generated by the Hadley cell are called the trade winds. It is important to note at this point that I have been discussing air circulation in the northern hemisphere. In the southern hemisphere, the circulation patterns are opposite because the Coriolis force pushes air in the opposite direction. The Hadley cell in the southern hemisphere rises at the equator and sinks at 30 degrees south. The wind at the top of the cell is pushed by the Coriolis force to the left. The air along the surface of the Earth travels back to the equator in a southeasterly direction or towards the northwest. The northeasterly and southeasterly trade winds converge near the equator in an area called the Intertropic Convergence Zone, or ITCZ. The ITCZ is always near the equator, but migrates throughout the year. It can sometimes be seen on satellite images as a string of clouds near the equator. The convergence of the trade winds from the northern and southern hemispheres creates some of the most consistent and widespread thunderstorms on Earth. At the ends of the Earth, the polar cells move in the same direction as the Hadley cells. Air rises near 60 degrees, creating a low-pressure zone, and falls near the poles, creating a high-pressure zone. Just as with the Hadley cells, the air is deflected by the Coriolis force. The surface winds blowing from the north and south poles to the west are called the polar easterlies. We are discussing the Ferrel cell last because it is driven by circulation in the Hadley and polar cells. Also, the Ferrel cell operates in the opposite direction than the other two cells. Here the air rises near 60 degrees where it is cold and sinks at 30 degrees where it is relatively warm. Why is this behavior opposite in the mid-latitudes? Instead of dissipating energy from solar radiation, the Ferrel cell is actually balancing thermal energy between the Hadley and polar cells. Cold air travels down to cool the subtropics, and warmer air then travels near the surface to warm the polar region. Interestingly, these solar cells are also responsible for the largest global wind patterns, the jet streams. The jet streams are high-altitude strong winds associated with the downwelling of the Hadley cell near 30 degrees and the upwelling of the Ferrel cell at 60 degrees. These winds are heavily influenced by the Coriolis effect and the rotation of the Earth, so they flow from west to east. You've likely heard the jet streams discussed in the context of plane flights. If you fly from the west coast of the U.S. to Asia, you'll notice that it takes a lot longer to fly to Asia than it takes to fly back to the U.S. That is because when you are flying from Asia back east to the U.S., you can catch the jet stream, which can cut down your flight time by a couple of hours. Let's review. Air circulates in the Earth due to energy variations from incoming solar radiation. At the equator, air heats up and rises. This air is pushed away from the equator and falls back to the Earth once it cools and becomes more dense. There are 3 circulation cells in each hemisphere. The circulation cell closest to the equator is known as the Hadley cell. Surface winds in the Hadley cell, where the air is traveling back toward the equator, are known as the trade winds. The stormy region where the trade winds converge is the Intertropical Convergence Zone, or ITCZ. The circulation cells near the poles are the polar cells and occur where air rises near 60 degrees and sink near the poles. The mid-latitude circulation cell is the Ferrel cell. The Ferrel cell has the opposite motion to the other 2 cells because it is equalizing the uneven temperatures between the equator and the poles. Cooler air rises near 60 degrees and falls down near the subtropics. The warmer air then travels along the surface towards the poles.
Let's do a quick activity. Hold your hand out a few inches from your mouth with your palm toward your face. Now open your mouth wide and blow onto your palm. The air that hits your palm is fairly warm. Now make your mouth into a tight O and blow again. Were you surprised by the result? This time, the very same air that came from your mouth was cool. This happens because air cools as it expands. When you closed your mouth in the second part of the activity, you restricted the space where the air could leave your mouth, and so it expanded outward as it made its way to your palm. It cools because as the space becomes larger, the particles in the air run into each other less and therefore give off less heat. The same thing happens with air in the atmosphere. As warm air rises, it expands and cools. It then sinks back down to fill the space the warm air left behind. This convection current, or circulation of warm air rising and cool air sinking, has some interesting effects on wind. Wind is horizontally moving air, so any air that moves left to right instead of up and down. Wind ultimately comes from temperature differences because, as we learned in another lesson, temperature differences lead to air pressure differences, and air pressure creates convection currents, which, as we just learned, create wind. Let's back up and see how this works. Say we have a warm location like the equator and a cold region like the North Pole. Air at the equator is warmed with more solar energy than air at the North Pole, so it rises and then moves horizontally toward the North Pole. As it cools, it sinks back down toward the warmer equatorial region. The air pressure difference between the two locations is called the pressure gradient, and the force that actually drives the air from high pressure area to low pressure area is called the pressure gradient force. If Earth didn't rotate, which we know it does because we have cycles of day and night, this pressure gradient force would create two single-cell circulations of wind, one for the northern hemisphere and one for the southern hemisphere. But since Earth does spin on its axis, we get multiple circulations of wind on Earth. What's especially interesting is that this rotation of Earth affects the path of wind so that it appears to deflect to the right in the northern hemisphere and the left in the southern hemisphere if you're looking down from one of the poles. This deflection of wind from Earth's rotation is called the Coriolis effect. The Coriolis effect is like being on a merry-go-round. Imagine that you're on one side and your friend is directly across from you on the other. If you were to throw a ball to your friend while the merry-go-round was not spinning, it would go straight to them. This is our one-cell circulation pattern on a non-rotating Earth. But now let's get the merry-go-round spinning counterclockwise. Throw the ball to your friend again, and the ball misses them this time. You may not realize it, but the ball is still traveling in the same straight line path as before, and you would see this if you looked straight down from above. However, from your perspective on the merry-go-round, it looks as if the ball is deflecting to the right as it misses your friend. This is what happens to wind on Earth. As Earth rotates, all free-moving objects like air, water, airplanes, and even snowballs appear to leave their straight-line paths. Nothing is free from the Coriolis effect. The Coriolis effect also differs depending on wind speed and latitude. When wind travels faster, it gets deflected more. Objects that are higher in latitude, so closer to the polar regions, deflect more than those at the equator. When we talk about wind, we certainly can't forget friction. Friction is a force that restricts motion, and any time an object comes in contact with the surface, it experiences friction. You can feel this when you slide down a slide. You definitely feel the friction on the back of your legs if you slide down in shorts instead of long pants. Wind encounters friction all over Earth because it's constantly coming in contact with Earth's surface. And the rougher the surface, the more friction it will experience. So a sandy desert will allow wind to move over it more easily, but a rough mountain range is likely to slow that wind down considerably. Friction also reduces the effect of the Coriolis effect because, as we learned before, slower wind deflects less than faster moving wind. Just like the air that comes out of your mouth, air in the atmosphere cools as it expands. As warm air in the atmosphere expands and cools, it sinks to fill the space that the warm air left behind, and this circulation of warm air rising and cool air sinking is called a convection current. Convection currents create wind, which is horizontally moving air, but convection currents are ultimately at the mercy of temperature differences because these are what create pressure differences in the first place. The pressure difference between two locations is called a pressure gradient, and the force that actually moves air as wind is called the pressure gradient force. Earth's rotation means that air does not circulate in a single cell convection current for each hemisphere. Instead, we get multiple air cells and the Coriolis effect, which is the apparent deflection of wind due to Earth's rotation. Like throwing the ball to your friend on the merry-go-round as it spins, wind actually travels in its same straight line path, but when observed from above appears to deflect to the right in the northern hemisphere and the left in the southern hemisphere. Wind deflection is greater with higher speeds as well as with higher latitudes. Friction also plays an important role in wind behavior on Earth because this is a force that restricts motion. When wind encounters rougher surfaces on Earth, it slows considerably. When wind travels more slowly, the impact of the Coriolis effect is also lessened because slower wind deflects less than wind traveling at faster speeds.
There are a number of forces that can either change the force or direction of wind. Two of the biggest forces of wind vectors are the pressure gradient force and the Coriolis force. When these two major forces are combined and are equal to each other, we get a type of wind called a geostrophic wind. In this lesson, we'll study how pressure gradient force and Coriolis force are created and the formation of geostrophic winds. One of the largest such drivers is the pressure gradient force. The pressure gradient force is the force that drives air from high to low pressure. Systems in nature are always trying to stay at the lowest energy state possible. High pressure systems are high energy states. If there is a nearby lower pressure area, air will freely move from the high pressure to low pressure area in an attempt to equalize this energy gradient. You may have been introduced to the idea of isobars, which are imaginary lines of equal pressure. Because the air is wanting to move as quickly and efficiently from high to low pressure, it will move the shortest distance between these areas, which is always perpendicular to the isobars. This is described in the following equation for the horizontal portion of the pressure gradient force. The pressure gradient force, here shown as capital P, is equal to the inverse of the density times the pressure gradient. The inverse sign is the upside-down triangle. The negative at the beginning of the equation designates that we move from high to low across the pressure gradient. Now, if this was the only force acting on the atmosphere, we could easily predict wind direction. Wind should move from high to low pressure perpendicular to the isobars. However, we observe that higher in the atmosphere, wind is actually moving parallel to the isobars. How can that happen? We must look at some other forces that act on wind. Another dominant force on wind direction is the Coriolis effect. The Coriolis effect is the diversion of the path of air due to the rotation of the Earth. The Earth is spinning from west to east. The Earth is a sphere, and therefore all points on Earth are traveling at the same angular velocity. However, because a point at the equator must travel a much further distance than a point near the pole for a full rotation, areas near the pole are actually traveling at a much higher linear velocity. When an object moves either closer or further from the equator, its original momentum is preserved, giving the path a diversion off its original course. Paths in the northern hemisphere are drugged to the right, and paths in the southern hemisphere are drugged to the left. So if we have a wind that is originally blowing according to the pressure gradient force, this wind will be deflected by the Coriolis force. Now the Coriolis force is not present at the equator, but it increases in intensity the further you approach the poles. The increase in force is due to the greater divergence from linear speed observed at the equator. Coriolis force is described by this equation. In this equation, the Coriolis force is F sub c. Omega is the rotational rate in radians per second, and phi is the latitude. Thus, the higher the latitude, the higher the Coriolis force. Also, the Coriolis force only acts on air that is already set into motion. The Coriolis force will not set wind into motion, but will only deflect the direction of wind that is already moving. Thus it follows that the faster that air is moving, the stronger it is affected by the Coriolis force. Combining these two major forces in the atmosphere gives us the geostrophic winds that are the topic of this lesson. Geostrophic winds are winds that are moving parallel to the isobars under the effect of the pressure gradient force and the Coriolis effect. As winds begin to move with the pressure gradient force from areas of high pressure to low, the Coriolis force will cause the winds to deflect. The higher the wind speed, the greater the deflection. Eventually these forces will balance each other out, which produces winds that are parallel to the isobars. This is only possible in areas of low friction, over a kilometer above the Earth. Frictional forces are a drag force resulting from interaction with the Earth's topography or ocean surface. When a geostrophic wind encounters a frictional force, this will cause it to move from its original direction of parallel to the isobars to oblique to the isobars. In review, the pressure gradient force causes air to move from high pressure to low pressure areas across the shortest distance possible, which is perpendicular to the isobars. Isobars are lines of equal pressure in the atmosphere. The other major driver of wind vectors is the Coriolis effect, which causes moving wind to deflect from their original path due to the rotation of the Earth. This force deflects wind to the right in the northern hemisphere and to the left in the southern hemisphere. In areas high in the atmosphere above the surface of the Earth, these two forces will balance each other to produce geostrophic wind flows. Geostrophic winds are parallel to the isobars because they are winds resulting from the Coriolis effect equaling the pressure gradient force. Winds are a common feature of all storms, ranging from thunderstorms to hurricanes. However, winds are also common at certain locations, such as by the ocean or in the mountains. So why are winds associated with certain events and locations? At their very basic, winds are moving air masses in response to differential pressure and temperature gradients in the atmosphere. In an attempt to lower the overall energy of the system, air molecules will move from areas of high pressure to those of lower pressure. Think of pressure as a pushing force. The high pressure pushes the air away into lower pressure areas. The pressure gradient force, or PGF, is the force that pushes air from high to low pressure in an attempt to equalize the pressure. These differences in pressure create winds throughout the atmosphere. This lesson will be focused on surface winds. Surface winds are winds near the Earth's surface that are normally measured at 10 meters above the surface. We'll look at unique features of surface winds and how they are formed. So we just learned that winds are created by pressure variations in the atmosphere. These pressure fields are shown on weather charts by a series of isobars, or lines of constant pressure. Just like how contours on a topographic map mark areas of equal elevation, isobars on a pressure chart allow the user to follow areas of equal pressure. In these maps, local maxima are referred to as high-pressure systems, labeled H in red, and minima are low-pressure systems, labeled L in blue. You've likely seen these maps and labels if you've watched the local news on TV. We care about the pressure systems across the U.S. because they drive the larger weather patterns across the country. However, these differences between higher and lower pressure create winds on a more local scale as well. The space between isobars on the map will determine how fast the winds blow. Stronger pressure gradients exist in locations where there are larger changes in pressure across a shorter area. On our pressure map, these are locations where the isobars are closely spaced. The winds have a higher speed at these locations of larger pressure gradients than lower. There are two types of surface winds based on the distance over which they occur. Synoptic winds are winds that occur due to pressure differences over thousands of miles. Local winds are winds that occur on the scale of 1 to 30 miles. Synoptic winds are ones that would blow across the entire country due to pressure differences seen on the country scale pressure map. Local winds are what you would experience on the beach, where cool air blows from the ocean to the land. You may be familiar with some of the common local wind patterns, such as winds at the beach. When the sun rises, the land heats up quicker than the water. The hot air near the land rises, and cooler air from the ocean rushes in to fill the space. The opposite happens in the evening when the sun begins to set. The ocean takes longer to cool, so the wind rushes back out to the ocean. As we've learned, the direction of the wind is from areas of high pressure to low pressure. However, winds over long distances won't move in a straight line. This is because the rotation of the Earth actually causes the winds to move. Imagine trying to draw a straight line on a rotating tray or turntable. You start drawing from the center out to the edge, however the tray starts to rotate counterclockwise. Your line would start to veer off to the right. In the same way, if you tried to draw a straight line on the bottom of the tray while it was spinning, you would find your line was veering to the left. In the northern hemisphere, air path is deflected to the right. In the southern hemisphere, air path is deflected to the left. This deflection of wind is known as the Coriolis effect. The Coriolis effect is not noticeable across short distances, but is more noticeable across longer synoptic wind patterns. Winds are created by air molecules moving from areas of high pressure to low pressure. Surface winds are the ones that exist close to the Earth's surface and are measured at a height of 10 meters above the Earth's surface. Pressure gradients are mapped on weather charts with isobars that mark locations of equal pressure. These are the maps you see on local weather forecasts showing high and low pressure systems across the U.S. Winds will move in the direction of high to low pressure, but over longer distances can be deflected by the Coriolis effect. Across shorter distances, like across the beach, winds are much more affected by local pressure variations caused by things such as temperature variations.
You've likely seen dramatic satellite photos of hurricanes in the Atlantic Ocean off the coast of the U.S. These storms mean strong winds, flooding, and damage if they struck land. You also may have heard local weather reporters discussing the storms losing strength as they impacted the land. What you likely did not hear the reporters discussing is that all of these storms are rotating in the same direction, or that they are associated with strong low-pressure systems. In this lesson, we're going to learn how cyclone systems develop in the atmosphere and how different types of cyclonic storms are produced. Next time you see coverage of hurricanes on the national news, you'll be able to understand a little more about where the storm came from. Before storm systems become fully developed cyclones or anticyclones, they first form as ridges and troughs. To understand these terms, let's review air pressure isobars. Isobars are lines marking areas of equal pressure, just like contours mark areas of equal elevation on a map. In ridges, the isobars are elongated towards the north. In troughs, the isobars are elongated towards the south. You can think of them as pressure topography of the atmosphere, with the ridges being high-pressure mountains and the troughs being low-pressure valleys. While these low-pressure troughs can start as elongated features, they can also develop into closed cells through the spinning of the winds via the Coriolis force and pick up enough energy to become cyclones. The same is true of high-pressure ridge systems, which will form into closed anticyclone cells. This is the formation of closed high and low-pressure isobars that you've likely seen in the local weather reports across the country. So in review, cyclones are closed cells with a low-pressure center, and anticyclones are closed cells with a high-pressure center. So you can think of ridges and troughs as beginner cyclones. These ridges and troughs would not develop into fully formed cyclones or anticyclones without the Coriolis force. The Coriolis force directs winds away from their original path due to the rotation of the Earth. Because the Earth is a sphere and is rotating to the east, moving winds in the northern hemisphere are deflected to the right, and winds in the southern hemisphere are deflected to the left. Now, if there were no Coriolis force, air would choose to move along the pressure force gradient, which is the shortest distance between high pressure and low pressure zones. Therefore, air would want to rush directly into a low pressure trough or directly away from a high pressure ridge. But because of the Coriolis effect, these winds will not travel directly along their intended path. Remember that winds in the northern hemisphere are directed to the right, and winds in the southern hemisphere are directed to the left. So in the northern hemisphere, as winds are rushing to the center of the storm's eye in low-pressure systems, they are deflected to the right. This produces the counterclockwise spinning of some storms that we witness in the northern hemisphere. The opposite happens in the southern hemisphere, where the deflection of winds to the left creates a clockwise spinning. These counterclockwise spinning cells in the northern hemisphere and clockwise spinning cells in the southern hemisphere are also called cyclones. Cyclone is the general term for rotation around a low-pressure system, and thus eliminates the confusion over the direction of the rotation due to the hemispheric difference. In fact, here in the U.S., we call low-pressure storms in the Atlantic hurricanes, but they call the same storms cyclones in the southern Pacific. According to the definition of cyclone, though, all of these storms are cyclones, despite where they occur or what the locals choose to name them. So that covers low-pressure systems. What about high-pressure systems? Although high-pressure systems are generally associated with calmer weather patterns, there are still some associated winds due to the pressure gradient force from the center of the pattern to the outside. However, in this case, the higher pressure is in the center. Thus, air is moving from the center outwards. Just as in low-pressure systems, the air is deflected to the right in the northern hemisphere and to the left in the southern hemisphere. Therefore, high-pressure systems in the northern hemisphere will spin clockwise and counterclockwise in the southern hemisphere. These spinning storms around high-pressure systems are called anticyclones because they have the opposite rotation to low-pressure systems. Anticyclones spin clockwise in the northern hemisphere and counterclockwise in the southern. In review, cyclones are rotation around a low-pressure system that spin to the counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. This is because the Coriolis effect directs winds away from their original path due to the rotation of the Earth, and deflects winds to the right in the northern hemisphere and to the left in the southern hemisphere. Anticyclones are spinning storms around high-pressure systems. Therefore, anticyclones have the opposite spin than cyclones. We also learned that before storms are fully fledged cyclones or anticyclones, they start out as either ridges or troughs. Ridges occur when isobars are elongated towards the north. Troughs are when isobars are elongated towards the south. These ridges and troughs can develop further into fully closed cells according to the Coriolis force.
While most winds are benign, winds associated with destructive storms have the ability to cause property damage and other problems. Therefore, being able to measure and predict wind is important to our society in understanding possible wind damages and weather patterns. In this lesson, we're going to briefly cover the history of wind measurement and then delve into the technology we use to measure wind today. There are two different devices for measuring the wind: wind vanes and anemometers. Wind vanes are an instrument for showing the direction of the wind. Wind vanes are a much older technology than anemometers. The oldest known wind vane was on top of the Tower of the Winds in Athens, dating back to 48 BC. Although the wind vane did not survive, the Tower of the Winds is still in present-day Athens. There are writings that suggest that wind vanes may have existed in ancient Mesopotamia and ancient China at even earlier periods. Wind vanes became common in the 9th century AD when the Catholic Church decreed that all churches should have a rooster as a symbol of a passage in the Bible. Since these churches already had wind vanes, the rooster was combined with the wind vane to create the extremely common rooster wind vanes still seen today. An anemometer is a device used to measure wind speed. It is derived from anemos, which is the Greek word for wind. Even though the word is derived from ancient Greek, we were not able to measure wind speed until 1450, when Leon Battista Alberti invented the first anemometer, which used a flat disc that would swing back and momentarily show the force of the wind perpendicular to that disc. A more familiar anemometer is the cup anemometer, which was invented in 1846 by Irish scientist Thomas Romney Robinson. The wind caused the cups to rotate horizontally, which moved a series of wheels to record the rotations. The most recent anemometer technology is the sonic anemometer, which was invented in 1994. We'll delve further into both of these anemometers in this lesson because they're methods that are still commonly used. Modern anemometers can be classified as either a velocity anemometer or pressure anemometer, based on the technology used to measure wind speed and direction. We're going to examine some of the common anemometers in both of these categories, starting with velocity anemometers. Cup anemometers are still the most common wind measurement device at weather stations. They consist of 3 arms ending in hemispheric cups, all at equal angles to each other. As the cups rotate in the wind, a copper wire in the vertical shaft causes a minor electrical field. The output voltage from the electrical field is directly correlated to wind speed. Cup anemometers are preferred because they are cheap, easy to operate, and simple. However, the moving parts mean that they need to be replaced. Also, the cup anemometer won't tell you wind direction. Hot wire anemometers are another style of anemometer that give you wind speed but very little directional information. In these instruments, a very thin wire is heated to a set temperature. The wind across the wire drops the temperature. The relationship between the temperature drop and wind speed is dependent on the type of wire and the starting temperature. These anemometers are preferred when you are measuring wind speed in a very tight space. Users must be wary to keep these clean at all times because they will become inefficient when the wire becomes dirty. Sonic anemometers use ultrasonic sound wave to measure wind speed and direction. They work by measuring the speed at which sonic pulses travel between pairs of transducers. Depending on the configuration, these anemometers can measure either 2 or 3 dimensions. The 2D sonic anemometers can provide 2-dimensional direction, and the 3D versions can provide 3D direction. Finally, the propeller-style anemometer combines both anemometer and wind vane technology with a propeller in front and a wind vane in the rear. They are mounted on a movable vertical axis that allows the wind vane to rotate and record dominant wind direction, while the speed of the propeller marks the speed of the wind. All of these anemometers mentioned thus far are velocity anemometers. The other type of anemometer are pressure anemometers, which use pressure as a proxy for wind speed and direction. These pressure anemometers are similar in theory to the original plate-style anemometer developed by Leon Battista Alberti. There is still a modern plate anemometer that has a plate attached to a spring. The compression of the spring directly relates to the force of the wind. The more advanced tube anemometer determines wind speed using a glass tube closed at one end and pressure transducers both inside and outside the tube. The pressure differential between the inside and outside of the tube is directly related to wind speed. A special type of tube anemometer is the pitot tube. These instruments contain 2 separate tubes running alongside each other. One is open to the wind, and one is closed at the upstream end with small holes somewhere downstream. Pressure will increase in the open tube proportionally to the wind speed, while pressure in the closed tube will remain relatively undisturbed. Pressure sensors in the bottom of each tube monitor the pressure in the tube, and the differences between the 2 measurements is used to calculate wind speed. Next time you are on an airplane, see if you can identify a pitot tube on the body, as they're commonly used to measure airspeed on aircraft. Any of these modern anemometers may be used at weather stations to monitor wind speed and possibly direction, depending on the technology. The choice of anemometer is dependent on the situation, cost, and accuracy. Many scientists and meteorologists will choose velocity anemometers such as the cup and sonic anemometers. Sonic anemometers are the newest technology and are popular among users who want to collect both wind speed and direction in one instrument. However, they are costly. Propeller-style anemometers are also quite popular due to their combination of velocity and wind vane type technologies to provide wind speed and 2-dimensional direction in one instrument. Next time you are outside, see if you can notice one of these anemometer types near your home.
When you hear the word circulation, a beating heart, arteries, and veins probably comes to mind. But what about atmospheric circulation? Does the atmosphere have a giant heart with blood vessels that pumps air through the atmosphere? Of course not. But you know what? Atmospheric circulation is kind of similar to your beating heart and blood vessels with a few differences. Instead of blood, there's air, and instead of a heart that pumps blood, unequal heating of the Earth and the Earth's rotation drives atmospheric circulation. So, in a nutshell, atmospheric circulation means air traveling around the Earth due to unequal heating and the Earth's rotation. Let's take a moment to delve a little deeper into that definition, starting with unequal heating. As the sun's energy reaches the Earth, more heat energy reaches the equator compared to the poles, thus creating unequal heating. The warm equatorial air rises and heads towards the poles. As it heads north and south, however, it starts to cool, sink, and then return to the equator. This creates a cell, or a cycle of air. And because the Earth is rotating, the air gets deflected in what is known as the Coriolis effect. In the northern hemisphere, winds are deflected to the right as they blow from high to low pressure systems, and the opposite is true in the southern hemisphere, where winds are deflected to the left as they blow from high to low pressure systems. Now that you have a general idea of how atmospheric circulation works, let's scale down a bit so you can get a clearer picture. The atmospheric circulation we just went over is a little more complicated than equatorial air heading to the poles and polar air heading to the equator. There are actually several cells that occur on the Earth. For example, there is the polar cell that occurs near the poles, the Hadley cell that occurs near the equator, and the mid-latitude cell that occurs, you guessed it, at mid-latitudes. And in reality, it's even more complicated than that. But let's scale down even further and see what weather someone would observe if she were living on the east coast of the United States. We'll focus on the polar cell in the northern hemisphere, but there's one in the southern hemisphere too. Remember, due to unequal heating by the sun, the North Pole has cold, dense air, whereas the equator has warm, less dense air. The cold, dense air flows from the high-pressure system in the North Pole towards the equator in what is known as polar easterly winds. And remember, the Earth is rotating, so these winds get deflected to the west. They get their name because of where they originate, at the poles and from the east. Let's scale down a little more and take a look at these winds. They tend to be dry, cold, and weak, and blow from the poles to about 60 degrees latitude. The polar easterlies meet up with warm, wet wind that is blowing towards the poles, or the prevailing westerlies, at about 60 degrees north and south latitude. The warm, wet wind from the prevailing westerlies and the dry, cold wind from the polar easterlies create the polar front. A front, in case you're wondering, is just a transition between two different types of air. In this case, the dry, cold air and the wet, warm air. Now let's scale down even further to see how these winds and the polar front impact weather. On the east coast of the United States, the polar front is responsible for mid-latitude cyclones, which create blizzards and storms. In fact, in 1993, a storm occurred that was so severe it's been called the storm of the century. This storm was one of the most expensive natural disasters during the 20th century in the United States, with snow piling up from Maine to Alabama and Florida experiencing flooding, all followed by extreme temperatures. Let's take a moment to zoom in on another cell and see how it impacts the weather. This time, let's head closer to the equator to look at the Hadley cell. Here, the warm equatorial air rises and heads towards the poles. At about 30 degrees north and south latitude, the air cools, sinks, and returns to the equator. Let's scale down further and check out the winds that are created by the Hadley cell, or the trade winds. Like the polar easterlies, the trade winds are deflected due to the Coriolis effect, so they blow from the northeast in the northern hemisphere. Let's scale down a little more to see how someone living in Hawaii would observe the trade winds. The trade winds come into contact with Hawaii as they blow towards the equator, and they tend to bring cooler temperatures and precipitation to the windward side of the islands. When the trade winds die down, many find it feels muggy and humid. In addition to bringing increased precipitation to the windward side of the Hawaiian Islands, they help steer storms that form over bodies of water, including the Pacific Ocean, Atlantic Ocean, and parts of the Indian Ocean. These storms eventually reach North America and parts of Asia and Africa. Atmospheric circulation is similar to the circulation that occurs in your body, but here we aren't dealing with a heart and blood vessels. Instead, it's the movement of air in the atmosphere due to unequal heating of the Earth and the Earth's rotation. The sun heats the equator more than the poles, so warm equatorial air rises, heads to the poles where it sinks and heads back to the equator. This causes a cell or cycling of air. Of course, this is large scale, and it's actually more complicated. We zoomed in on two cells, the polar cell and the Hadley cell. The polar cell creates the polar easterly winds, which are caused by cold, dense polar air heading towards the equator. The polar cell occurs from about 90 degrees latitude to 60 degrees latitude. These winds create a polar front when they meet the prevailing westerlies. And if you were to scale down even further, you might observe the weather patterns that are created by the polar front, such as mid-latitude cyclones, which can bring increased storms to the United States, especially the East Coast. Next, we zoomed in on the Hadley cell, which is caused when warm equatorial air heads towards the poles but cools and sinks at about 30 degrees latitude. The Hadley cell causes the trade winds near the equator throughout the world, but we zoomed in on the Hawaiian Islands, where we saw trade winds bringing precipitation to the windward side of the islands. So, just like your heart and blood vessels circulate blood through your body, these cells and winds circulate air and weather throughout the atmosphere.
Welcome to the fashion runway. Fancy shoes, bright lights, celebrities, and beautiful models. Wait, what? You mean another type of model? Oh, you mean something developed by scientists that helps explain how things occur in nature. Okay, sure, I can work with that, and I can even think of some scientific models I've heard of, like the atomic model or a model of the solar system. And I know that models change as scientists learn more. For example, models of the solar system and of the atom have changed substantially over time. So just like the solar system and the atom, there are models about how air circulates through the atmosphere. And these models have changed over time too. Let's talk a little about one of these models, the single-cell model. And no, this isn't a single-celled organism that's a model. In fact, here, cell refers to the cycling of air. Back in 1735, a physicist and meteorologist from England named George Hadley developed the single-cell model in order to explain trade winds. This model says cold air sinks at the poles and warm air rises at the equator, resulting in a cell. Sometimes this cell is referred to as a Hadley cell. Wow! Lucky George Hadley! To have a cell named after him? Wouldn't that be great? Let's look a little closer at Hadley's model. As the sun shines on the Earth, more heat energy hits the equator versus the poles. So the air at the equator is warmer than the air at the poles. Makes sense, right? So George, or Mr. Hadley, was definitely onto something. The warm air is less dense, so it rises until it reaches the tropopause, which is the area in the atmosphere between the troposphere and stratosphere, both of which are layers in the atmosphere. A really quick note about air before we go on. The molecules in warmer air are further apart compared to colder air, so this is why warmer air is less dense. From the tropopause, some of the warm air heads towards the North Pole and some heads towards the South Pole. Now, as it heads to the North and South Poles, the warm air cools, thus becoming more dense and sinking. Once it sinks, it cycles back to the equator where it gets warmed again, rises to the tropopause, and heads back to the poles. This creates one giant cell above each hemisphere. The warm air that went to the North Pole would be over the northern hemisphere, and the warm air that went to the South Pole would be over the southern hemisphere. And yeah, I realize that's a little confusing since the name is single-cell model, and there are actually two cells. So now you can see why the single-cell model has nothing to do with the single-celled organism or a fashion model. Instead, it's how air circulates through the atmosphere. George Hadley's single-cell model helps explain how air moves. However, he failed to consider several factors. Does that mean the model is garbage? Of course not. Remember, models are always being revised and updated, so the single-cell model explains some aspects of air circulation and was used to develop more complex models. But let's check out what Hadley neglected to take into account. First, in the single-cell model, the sun must be directly over the equator. Now, we know the equator gets a lot of sun, but the sun isn't constantly over the equator, which results in seasonal winds that aren't represented by the model. Second, the Earth cannot rotate, but we know it does. As the Earth rotates, it deflects wind. In the northern hemisphere, wind is deflected to the right, and in the southern hemisphere, wind is deflected to the left. So you can see the single-cell model doesn't account for that, and if you consider rotation, you get the 3-cell model, which actually has 6 cells, but that's another lesson. And finally, water must cover the Earth uniformly. Now, if you take a look at the Earth, you can see there are chunks of land breaking up the water, and since there is a difference between how land and water are heated, this affects how the air is heated, which isn't addressed by the single-cell model. So I realized that if the single-cell model were to be true, there would be an apocalypse. The Earth quits rotating, not to mention the sun and the water issues. But remember, it's a model, so its purpose is to explain natural phenomenon as well as be a building block in the development of more complex air circulation models. So maybe I was initially confused and this lesson wasn't about models on the runway, but instead a different type of model. And, unlike models on the runway, scientific models help scientists explain how the world works around them, as well as help them build and expand on current scientific ideas. Models are constantly changing and being modified. Remember, the atomic model or the model of the solar system? They are completely different today than they were in the past. The same holds true for models of air circulation in the atmosphere. The single-cell model helps explain how air moves, but it fails to take several things into consideration, including the Earth rotating, how water covers the Earth, and the sun's location above the equator. Nonetheless, this model gives a simple understanding of air circulation, so let's review the main points of the model. Because of the uneven heating of the Earth, the equator gets more heat energy compared to the poles. The warm equatorial air is less dense, so it rises and heads toward the poles, where it cools, sinks, and floats back to the equator. This movement of warm air to the poles where it cools and returns to the equator where it rewarms creates a Hadley cell above each hemisphere. This is the basis for the single-cell model. So, while this model may not wear fancy shoes or hang out with movie stars, it's still helpful in determining how the world works.
When you look up into the sky, you probably aren't thinking about weather patterns or pressure cells. Maybe you notice a nice blue sky or puffy clouds or even a bird flying, but semi-permanent pressure cells? No, that's probably not what pops into your mind. But it should. So, why don't you climb into your hot air balloon and we will check out everything you've ever wanted to know about pressure systems. As you ascend in your hot air balloon, you may notice the pressure decreases. Before we get too high, let me quickly go over some things you should know about pressure. Air is made up of particles that are bouncing around. The more particles, the greater the pressure they exert on their surroundings. So as you ascend, you'll notice there are fewer particles, so less pressure. Temperature also affects air pressure. If air is warm, the particles are further apart, so they exert less pressure compared to cold, dense air. Your hot air balloon, believe it or not, floats because of temperature. The hot air inside your balloon is less dense than the surrounding cold air, so the balloon rises. While you're floating around up there, let me briefly fill you in on semi-permanent pressure cells, which are areas where high or low pressure systems exist for much of the year. In the northern hemisphere, high pressure systems are typically associated with air that moves in a clockwise direction. High pressure systems usually create dry, clear weather. Contrast this with low pressure systems, which are associated with air that moves in a counterclockwise direction and create increased precipitation and storms. Why don't you head out to the cold ocean in your hot air balloon? You're going to be inside a parcel of air, which just means a clump of air that shares similar properties. Because of your proximity to the cold ocean, you may notice the parcel of air is getting colder and colder. This takes longer than seconds, but it's a short lesson, so you'll have to use your imagination again. Now think back to what I said before. As air cools, the molecules that make up the air slow down and get closer together. As a result, the parcel of air takes up less room than it did before it cooled. This can happen in your balloon too. If the air inside your balloon cools, the particles get closer together and take up less space. Your balloon might even seem to have deflated a little. Since the parcel of air takes up less room, other parcels of air rush in to take up the space once held by your parcel of air. Now you have more air in the same volume than you did before the parcel cooled. And since there is more air, you have more pressure being exerted, or a high-pressure system. The opposite happens in a low-pressure system. Let's use the same parcel of air as before. In this scenario, why don't you travel to a warm place where the heat radiates from the land and warms the air parcel? Since the parcel is warm, the molecules move faster and get further apart, thus taking up more space and pushing out other parcels of air. This can happen to your balloon too. As air heats up inside of your balloon, the air takes up more space and your balloon may seem to inflate. But back to the parcel of air. If the parcel takes up a lot of room and pushes out other parcels of air, there is less air in the given volume, so less pressure is exerted. Hence the low-pressure system. In reality, the formation of high and low-pressure systems is slightly more complicated, but this explanation allows you to get your foot in the door. Semi-permanent pressure systems are these highs and lows that last a really long time. So now that you have some background, let's check out some semi-permanent pressure systems and see how they impact weather patterns. Why don't you head towards the Azores, which are a group of islands located in the North Atlantic Ocean? This semi-permanent pressure system is called the Azores High. Can you guess how it got that name? Yep, because it's near the Azores. In fact, you'll notice the semi-permanent highs and lows get their names based on where they are located. I guess that makes things easier to remember. Okay, back to high-pressure systems. Remember, they are often associated with clear and dry conditions, and the Azores High is no exception. High-pressure systems bring dry conditions to the Sahara Desert, droughts to the Mediterranean, and warm and dry weather to parts of Europe and the eastern United States. Let's check out one more semi-permanent high system. You'll need to travel to the northeastern part of Siberia this time, where you'll observe the Siberian High. This high forms during the winter months when Siberia becomes bitterly cold. The Siberian High impacts weather throughout the world and can cause extremely cold and dry conditions in Siberia, China, and Mongolia. Now, let's take a moment to investigate two semi-permanent lows, starting with the Aleutian Low, which is located in the Gulf of Alaska near the Aleutian Islands. So, why don't I give you a moment to get your hot air balloon over there? Wow, that was fast. Okay, remember, low-pressure systems bring precipitation and storms, so the Aleutian Low brings storms to the Gulf of Alaska and the Pacific Northwest during the winter. In the summer, the Aleutian Low weakens. Although there are more semi-permanent highs and lows, we only have time to check out one more, the Icelandic Low. Hurry up, I'll meet you there. The Icelandic Low is located, you guessed it, near Iceland. In the winter months, this pressure system brings winds to the North Atlantic Ocean. In addition, it, along with the Azores High from before, is part of the North Atlantic Oscillation, which is a weather phenomenon that causes fluctuation in pressure over the North Atlantic Ocean. This causes weather patterns to vary throughout the Earth. Why don't you land your hot air balloon and I'll go over some things to remember from this lesson. Semi-permanent pressure cells are areas of high or low pressure that exist much of the year and can be found all over the globe. High-pressure systems are associated with dry, clear weather, whereas low-pressure systems are associated with precipitation and storms. High-pressure systems occur when air gets cold and the air parcel shrinks. Low-pressure systems occur when air gets warm and the parcel expands. We examined 4 semi-permanent pressure systems, and each was named based on where it originates. The Azores High brought dry conditions to the Sahara, Mediterranean, parts of Europe, and the eastern United States. The Siberian High brought dry, cold conditions to much of Asia. For the low-pressure systems, we examined the Aleutian Low and the Icelandic Low. The Aleutian Low brought storms to the Gulf of Alaska and Pacific Northwest. Finally, the Icelandic Low brought winds to the North Atlantic Ocean, and it was also involved, along with the Azores High, in the North Atlantic Oscillation. So the next time you see a weather forecast in the news, pay close attention to the highs and lows, since now you know how they are created and how they can impact weather.
A long time ago, armies didn't have guns, grenades, or fighter jets. They fought on the ground, face to face. An army ready to fight would consist of lines of men, each line with a specific job. In general, the front line was a strong line of shielded soldiers forging ahead, protecting those behind it. Weather fronts act just like the front line of an army. Fronts are contact zones between two different air masses, and you can think of the air masses as the advancing armies, just with different pressure, density, temperature, and moisture. And just like there's conflict between the battling armies, air masses battle along fronts, creating changes in weather conditions. There are 4 types of fronts, and the type of front we get depends on which type of air mass, or army, is advancing over the other. A cold front is the contact boundary of an advancing cold air mass over a stationary warm air mass. Conversely, a warm front is the contact boundary of an advancing warm air mass over a stationary cold air mass. This makes sense. The front is described by the type of air mass winning the fight. On a weather map, you'll see these symbols for a cold or warm front. The color helps you identify which type of front is moving in, blue for cold, red for warm, and the arrows tell you which direction the advancing air mass is coming from. A stationary front is just what it sounds like, when neither air mass is advancing over the other. They are both stationary, and so is the front. The armies are at a stalemate. Finally, an occluded front is when a cold front overtakes a warm front. This happens because cold fronts move faster than warm fronts, so it's like one army is sneaking up from behind and taking over in a surprise attack. On a weather map, you will see these symbols for a stationary or occluded front. As you can see with the stationary front, neither air mass is advancing. With an occluded front, the cold air mass is advancing over the warm air mass from behind. Just because they didn't have machine guns or grenades doesn't mean that battles weren't bloody. When 2 opposing armies fight, things can get very violent and dangerous because each side believes very strongly in what they're fighting for. Weather fronts do the same thing. They advance forward, creating weather changes and sometimes even violent storms along the front. This is like the front line of battle on both sides, the initial point of battle contact. Thunderstorms are common along cold fronts. This is because when a cold front occurs from a cold air mass moving into a warm air mass, the warm air is forced upward. When warm air rises, it cools, and since cool air can't hold as much moisture as warm air, the water in the air gets forced out, which is what creates clouds. Since the air is moving straight up, it forms a vertical cloud, which leads to thunderstorms along the front. However, behind the front, the skies are clear and the weather is calm. Along warm fronts, storms are less intense and more drawn out. This is because the warm air moving in over the cold air rises gradually instead of quickly. Along the front, expect overcast skies and drizzle or light rain. Behind the front, the air will be warm and clouds will be pretty scattered. Think about it like this. Thunderstorms generally develop quickly and are very dramatic storms. This comes from the quick, dramatic rise of the warm air when a cold air mass moves in. You know how it feels when you jump into a cold pool? It's a shocking feeling, and you're likely to jump right back out. When you step into a warm hot tub, though, it's a little less dramatic, and your body reacts much more gradually. The same thing happens with a warm front when the warm air slowly moves up over the cold air mass it's taking over. Because stationary fronts are like stalemates, they can last for many days. Both armies are winning or losing equally in the battle, and neither is willing to give in. Eventually, the stalemate will end because one side will take over, creating a cold or warm front, or the front will simply dissipate because the two sides just don't feel like fighting any longer. Long days of rain and clouds accompany stationary fronts. Because an occluded front is when a cold front overtakes a warm front, this can lead to some really rainy weather. The cold front comes in from behind and literally wedges itself under the warm front, lifting it up. This means that the zone of contact between the two fronts is up in the air, not on the ground. This also pushes any warm air up that was between the two fronts, which as we now know creates rain and thunderstorms depending on how quickly that warm air rises. Each front still retains its army though. The weather behind the occluded front is similar to that of a cold front, and the weather ahead of the occluded front is similar to that of a warm front. Like two armies at battle, air masses also battle with weather. When two air masses meet, we get weather fronts, and the type of front depends on the type of air mass advancing. The differences in the air masses come from differences in air pressure, temperature, moisture, and density. A cold front is when a cold air mass moves into the area of a stationary warm air mass. Like jumping into a cold pool, a cold front shocks the warm air upward very quickly. This sharp rising of warm air creates thunderstorms along the front, while behind the front skies are clear. A warm front is when a warm air mass moves into the area of a stationary cold air mass. You wouldn't dive into a hot tub, would you? You're more likely to slowly step in and let your body adjust. Warm fronts are the same way. The warm air rises slowly and gradually over the cold air mass, creating gray skies and drizzle. A stationary front is a stalemate. This is when neither air mass is advancing over the other, and you can expect rain and clouds to accompany this type of front. Like two armies in battle that are equally winning or losing, these fronts can last for long periods of time. When a cold front overtakes a warm front, we get an occluded front. This is like one army sneaking up and attacking the other army from behind. The fronts do not overlap. The cold front literally pushes the warm front up off the ground. When these two fronts come together, we get a wide area of rainy weather along the front, but weather similar to cold fronts behind and similar to warm fronts ahead.
You've surely heard of the Three Little Pigs fairy tale, right? But you probably didn't hear about the Three Little Pigs and the wind belts. Don't worry, though. I'll tell you the story. But before I start, I should fill you in on wind belts, or wind generated by the Earth's rotation and unequal heating from the sun. We'll get into the details of that definition when we examine the three main wind belts: the polar easterlies, the tropical easterlies, and the prevailing westerlies. Oh yeah, all of our piggies inhabit the northern hemisphere, so even though we'll mention the southern hemisphere, the focus will be on the northern hemisphere. Before we get into the details, there are some things you should know about wind that'll help you on this fairy tale. Wind blows from high pressure areas to low pressure areas. Cold, dense air causes high pressure, and warm, less dense air causes low pressure. This is because cold air has more molecules packed into a certain volume, and the more molecules that are present, the greater the pressure exerted. Okay, on to our story. Once upon a time, there were 3 little pigs. Each one lived in a different part of the world. Let's start with pig number 1, who lived in an igloo at the North Pole. Technically, he lived in the 60 to 90 degree north latitude part of the world. Now, this little piggy had to deal with the polar easterlies because of where he lived. The polar easterlies are winds that are found between 60 and 90 degrees north and south latitude that blow from the poles and are deflected towards the west. Although our little piggy lives near the North Pole, you may have gathered from that definition that the polar easterlies can be found near both poles. Before the polar easterlies try to blow our little piggy's igloo down, let's look at how they form. The air at the poles is cold and dense, creating high pressure. This high pressure air heads to the equator towards lower pressure air, but since the Earth is rotating, these winds are deflected in what is called the Coriolis effect, or the deflection of wind due to the rotation of the Earth. It can get a little tricky to remember which way the winds are deflected, so let me give you some rules. Remember, wind travels from high to low pressures, so, as they do, here is the deflection. Wind is deflected to the right in the northern hemisphere and to the left in the southern hemisphere. So, based on our rules, and since the polar easterlies are blowing away from the poles, we can assume that the winds are blowing towards the right or west in the northern hemisphere. You may be wondering why they're called polar easterlies then, right? Well, winds are named based on where they start. So, since they start in the poles, and due to the Coriolis effect, blow from the east, they are called polar easterlies. Uh-oh, and here comes those polar easterlies. The little piggy is taking shelter but can't help but notice the winds are cold and dry, and, thankfully for our polar piggy, not very strong. So, all is well in the north. Now to our second little pig who lives near the equator in a house made from palm trees and is worried about the tropical easterlies, or winds that blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere and are located between 0 and 30 degrees north and south latitude. Their more familiar name is the trade winds. Before these winds flow over the palm hut, let's see how they're formed. Remember, the sun heats the equatorial region more than the polar regions, so warm air from the equator rises and flows north and south. This air eventually cools and sinks at a latitude of about 30 degrees, again, north and south of the equator, and some of it returns to the equator. This air moving back to the equator is the tropical easterly. And remember our rules from before, as wind blows from high pressure to low pressure, it will be deflected to the right, or west, in the northern hemisphere, so as the air heads back to the equator, it's going to be deflected westward. So, like the polar easterlies, this wind originated from the east, so it's called an easterly. And here it comes! Look out, piggy number 2! Although the tropical piggy has taken shelter, he notices these winds are steady and warm, and actually more like a breeze, so they don't knock down his hut. Now the third little piggy lived in between polar pig and tropical pig at latitudes between 30 and 60 degrees, so he was worried about the prevailing westerlies, which are winds located 30 to 60 degrees north and south of the equator that blow eastward towards the poles. You might notice these are a change from our first two winds as they blow eastward, so they're called westerlies, since they blow from the west. Remember, they're blowing towards the poles, so they're deflected to the right, which causes them to blow eastward. Now, before our mid-latitude piggy has to deal with this wind, let's see how the prevailing westerlies form. Hot air from the equator rises and heads towards the poles, but as it gets further away from the equator, it cools and sinks around 30 degrees north and south latitude. Now remember, some of this air goes back to the equator and some of it continues on to the poles. The air that continues towards the poles causes the prevailing westerlies. Now, the prevailing westerlies can be quite strong, so let's hope mid-latitude piggy can make it. Here comes the wind! Oh no, it's blowing his house down! The prevailing westerlies are powerful and strong, so run, little piggy, run! It looks like he's made it. Wow, that was close. Thankfully, our little piggies survived the 3 wind belts. Before we wish them a happily ever after, let's take a moment to review our story. Wind belts are formed due to unequal heating of the Earth and the Earth's rotation. The first wind belt in our story, the polar easterlies, lies between 60 and 90 degrees north and south latitude and blows from the poles. And don't forget our rules regarding the Coriolis effect. Winds are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. And this is as they blow from high to low pressure. Next, we looked at the tropical easterlies, which are winds that are located between 0 and 30 degrees and blow towards the equator. Finally, we looked at the prevailing westerlies, which are winds that are located between 30 and 60 degrees and blow towards the poles. And now we're ready. The first 2 little piggies lived happily ever after, and the third pig built a stronger house to withstand the prevailing westerlies. So, they all lived happily ever after.